The universe is a vast, seemingly infinite expanse, composed of an unimaginable number of atoms. These atoms are the basic units of matter, each consisting of protons, neutrons, and electrons, which together form the elements listed on the periodic table. Understanding the number of atoms in the universe is not just a matter of curiosity, but also a critical component of cosmology, the study of the universe's origin, structure, and ultimate fate. To begin estimating the number of atoms in the universe, astronomers and physicists first look to determine the observable universe's size and mass. The observable universe extends about 46 billion light-years in all directions from Earth, encompassing countless galaxies, each containing millions to trillions of stars, and many more planets, moons, and smaller celestial bodies. Each of these astronomical objects contributes enormously to the total count of atoms. Calculating the mass of these celestial objects allows scientists to estimate the number of atoms they contain. For example, our Sun, a typical star, consists mainly of hydrogen and helium atoms. By calculating the Sun's mass and knowing the masses of hydrogen and helium atoms, one can estimate the number of atoms in the Sun. Extending this method to other stars and astronomical objects enables scientists to accumulate a total for the entire galaxy and, by extension, the observable universe. However, the task is complicated by the presence of dark matter and dark energy, mysterious components that do not emit light or energy and are thus invisible to traditional telescopes. Dark matter is thought to make up about 27% of the universe, while dark energy accounts for roughly 68%. The only ordinary visible matter, which includes atoms, constitutes about 5% of the universe's total composition. This realization comes from observations of gravitational effects that cannot be explained by visible matter alone, such as the rotational speeds of galaxies and the gravitational lensing of light around massive objects. Advanced techniques such as spectroscopy, cosmic microwave background measurements, and gravitational wave observations provide indirect ways to measure these invisible components. Spectroscopy, for instance, helps astronomers determine the composition and movement of distant stars and galaxies by analyzing the light they emit. The cosmic microwave background, the afterglow of the Big Bang, offers clues about the early distribution of matter and energy in the universe. By combining all these methods, astronomers can better understand not just how many atoms exist, but also how they are distributed across different structures in the universe. This distribution is crucial for understanding both the large-scale structure of the cosmos and the detailed workings of individual galaxies. In conclusion, counting the atoms in the universe involves a complex interplay of astronomical observations, physical theories, and cosmological principles. Each finding builds on the last, gradually enhancing our understanding of the universe's vast scale and its fundamental building blocks. While the exact number may never be known, each estimate helps scientists refine their models of how the universe functions and evolves. Continuing from the estimation of atoms in the observable universe, it's important to delve deeper into the methodologies and challenges that scientists face in these calculations. The task is not only about counting the atoms in stars, but also includes the atoms in interstellar and intergalactic mediums, planets, and other celestial bodies. Advanced observational techniques. One of the key tools in astrophysics is spectroscopy, which involves analyzing the light spectrum emitted or absorbed by objects in space. Different elements absorb and emit specific wavelengths of light, and by studying these spectral lines, astronomers can determine the chemical composition of distant stars and galaxies. This analysis provides essential data for estimating the number of atoms in various types of celestial bodies. Cosmic microwave background. The cosmic microwave background radiation is a crucial element in understanding the early universe. This radiation is the remnant heat from the Big Bang, now cooled to just a few degrees above absolute zero. By studying the tiny temperature fluctuations in the CMB, cosmologists can determine the density fluctuations that grew into galaxies and large-scale structures in the universe. These fluctuations help estimate the total mass of ordinary matter shortly after the Big Bang, which in turn helps in calculating the number of atoms. Baryon acoustic oscillations. Another method involves the study of baryon acoustic oscillations, BAO. These are regular, periodic fluctuations in the density of the visible baryonic matter, protons and neutrons, of the universe. BAOs serve as a standard ruler for measuring the scale of the universe because the scale of these fluctuations is well understood from the physics of the early universe. By measuring the scale and distribution of these fluctuations, cosmologists can infer the amount of matter in the universe and hence the number of atoms. Challenges and uncertainties. Despite the progress in these areas, the task of counting atoms is fraught with challenges. The universe is not only vast but also filled with regions that are inaccessible to direct observation. For example, much of the matter in the universe is dark matter, detectable only by its gravitational effects and not by electromagnetic radiation. Hence, the estimates of the total number of atoms are based on the observable universe, which might only be a fraction of the entire universe if it is indeed infinite. Additionally, the efficiency of data collection and the limitations of current technology can also skew the accuracy of these estimates. The distances involved are so vast, and the positions of celestial bodies change over time. This means that observations are snapshots of the past, and the universe might have changed significantly since the light from those objects began its journey to us. Future prospects. As technology advances, especially with projects like the James Webb Space Telescope and other next-generation observatories, astronomers expect to improve their measurements of the universe's composition. These improvements will likely refine our understanding of the total number of atoms, revealing more about the universe's earliest moments and its long-term fate. In sum, the endeavor to count the atoms in the universe is an ongoing challenge that blends cutting-edge technology with deep theoretical insights. Each advance brings us closer to understanding not just the scale of the universe, but also the fundamental principles that govern it. The speed of light is not merely a constant, but a critical component that influences the fundamental structure of our universe. Its implications extend beyond the realms of physics into the very way we perceive time and space. The concept of light speed serving as a cosmic speed limit comes from Einstein's theory of relativity, which posits that nothing can move faster than light in a vacuum. This principle has profound implications for understanding causality and the structure of spacetime. When discussing the speed of light, one must consider its role in the causality principle in physics. Causality means that an effect cannot occur from a cause that is not in the back past light cone of that event. Essentially, information or a causal effect cannot travel faster than light, which helps to prevent paradoxes such as the grandfather paradox in time travel scenarios. This underlines why the speed of light is not just a physical limit but a boundary of causal connectivity in the universe. Further exploring the implications of light's constant speed, it becomes apparent how this affects the measurement of distances in astronomy. Astronomers rely on the speed of light to gauge how far away celestial objects are from us. For instance, when we say a star is 8 light-years away, we mean it takes light 8 years to travel from that star to Earth. This method of using light-years as a distance measurement reflects not only the vastness of space but also the finite, though incredibly fast, speed at which light travels. Moreover, the speed of light is central to the phenomenon of time dilation, a prediction of Einstein's special relativity. As an object moves closer to the speed of light, time as experienced by the object slows down relative to a stationary observer. This effect has been confirmed by experiments involving precise measurements of time elapsed for particles traveling at high speeds and for clocks onboard satellites in orbit. Such observations have indispensable implications for GPS technology, where even nanosecond inaccuracies can lead to errors in positioning. In addition to time dilation, the speed of light also influences the contraction of lengths in the direction of motion, known as length contraction. At speeds approaching that of light, objects are measured to be shorter in the direction they are moving from the perspective of a stationary observer. This effect, though imperceptible at everyday speeds, becomes significant at velocities close to light speed and must be considered when designing high-speed spacecraft or conducting high-energy physics experiments. The invariance of the speed of light has led to the development of technologies that rely on its properties. For example, in methods such as light-based ranging and LiDAR, as well as in the synchronization of time across the internet and communication networks, the speed of light provides a critical standard for timing and distance measurement. In summary, the speed of light serves as a cornerstone in the architecture of modern physics, influencing how we measure space and time, the behavior of objects at high velocities, and the fundamental interactions between energy and mass. Its constancy and limit are not just abstract concepts but have real-world applications that affect various technologies and our understanding of the universe's structure. The implications of the speed of light extend into the realm of black holes and the event horizon, a critical boundary where the escape velocity equals the speed of light. Black holes are regions of space-time exhibiting gravitational effects so strong that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. The concept of an event horizon is intrinsically linked to the speed of light. It represents the threshold beyond which the gravitational pull is so intense that light cannot get out. Delving deeper into the nature of black holes, the speed of light plays a crucial role in defining the Schwarzschild radius, which is the radius of a sphere such that, if all the mass of an object were to be compressed within that sphere, the escape velocity from the surface would equal the speed of light. Calculating this radius involves directly using the speed of light, showing how it's intertwined with the fundamental properties of these massive objects. Furthermore, the constancy of the speed of light underpins the theoretical framework of general relativity. Einstein's field equations, which describe how matter and energy interact with the geometrical structure of spacetime, rely on the invariance of the speed of light. These equations suggest that spacetime is curved by matter and energy, and this curvature dictates the motion of objects and the propagation of light. Thus, the speed of light is not just a speed limit but a fundamental descriptor of the universe's geometry. This constancy also impacts the universe's expansion. Observations of distant galaxies show that they are moving away from us, and the farther a galaxy is, the faster it appears to be receding. This observation, explained by the Hubble law, suggests that the universe is expanding at speeds that can approach the speed of light for the most distant galaxies. Here, the speed of light again becomes a crucial factor in understanding not only the mechanics of this expansion but also its implications for the observable universe. It limits the portion of the universe we can see and interact with, as beyond a certain point, galaxies recede at a speed greater than the speed of light due to the expansion of spacetime itself, making them unreachable and unobservable. Moreover, the speed of light influences the cosmic microwave background radiation (CMB), the remnant heat left over from the Big Bang, the uniformity and the slight anisotropies (irregularities) in the CMB carry information about the early universe's conditions. The fact that light travels at a constant speed allows cosmologists to calculate how long the light from the CMB has been traveling and thus to estimate the age of the universe. These measurements, again reliant on the speed of light, provide a cornerstone for the Big Bang theory and the subsequent evolution of the cosmos. The role of the speed of light in modern physics and cosmology is indeed profound. It not only defines the boundaries of causality and the observable universe, but also continues to challenge our understanding of the fundamental nature of time, space, and matter. As we probe deeper into the cosmos and back in time towards the moment of the Big Bang, the speed of light remains a key tool in unlocking the mysteries of the universe's origins, structure, and eventual fate. The influence of the speed of light extends into the domain of quantum mechanics, particularly in the context of quantum entanglement and the transmission of information. Quantum entanglement is a phenomenon in which particles become interconnected so that the state of one particle instantaneously influences the state of another, regardless of the distance separating them. This seemingly instantaneous connection challenges our classical understanding of the speed of light as a limit to how fast information can travel. Despite initial appearances, quantum entanglement does not actually violate the speed of light constraint because no usable information is transmitted between entangled particles faster than light. The changes in states are correlated, but determining the state of one particle instantaneously changes the known state of the other. However, this does not allow for communication faster than light, adhering to the principle of causality upheld by the theory of relativity. The speed of light also plays a pivotal role in the fundamental constants of nature, particularly in the fine structure constant, denoted as alpha. This dimensionless constant characterizes the strength of the electromagnetic interaction between elementary charged particles. It combines the speed of light, the elementary charge, and the Planck constant. The fine structure constant is crucial for calculations in quantum electrodynamics, influencing the probabilities of photon absorption and emission, and the spectral lines of atoms and molecules. In addition to theoretical physics, the speed of light has practical implications in technology, particularly in the realms of telecommunications and computing. Fiber optic cables, which are the backbone of modern internet and telecommunications infrastructure, use pulses of light to transmit data over long distances at speeds close to that of light in a vacuum. The understanding and application of the speed of light in such technologies are crucial for optimizing data transmission rates and reducing latency, which is essential for high-speed, real-time communications across the globe. Moreover, the synchronization of systems in GPS technology is heavily reliant on the precise measurement of the speed of light. GPS satellites transmit signals that must be timed extremely accurately to determine a position on Earth to within a few meters. Small errors in timing can lead to significant discrepancies in positioning, and because these signals travel at the speed of light, even nanosecond inaccuracies can be critical. Additionally, the speed of light finds applications in areas such as the synchronization of financial markets, where trading algorithms often operate on the scale of microseconds. The speed at which trades can be executed and information can be transmitted is bounded by the speed of light, influencing how trading systems are designed and where servers are physically located to minimize time delays. In scientific research, the speed of light is crucial for experiments involving the Large Hadron Collider (LHC), where particles are accelerated to near light speeds. Understanding the implications of relativity and the speed of light is essential for correctly interpreting the results of particle collisions, which can reveal the nature of fundamental particles and forces. Thus, the speed of light not only shapes our understanding of the universe and the fundamental laws of physics, but also impacts a wide array of practical applications, from quantum computing and telecommunications to satellite navigation and high-energy physics experiments. Its influence permeates through various fields, highlighting its central role in both theoretical explorations and everyday technologies. Speed, in its most basic scientific definition, measures how fast an object is moving and is usually expressed as the distance traveled per unit of time. In the context of the universe, speed helps us understand the motion of planets, stars, galaxies, and particles of light. Among all speed measures, the speed of light in a vacuum precisely 299,792 kilometers per second, holds a particularly eminent position due to its fundamental role in the laws of physics as described by Albert Einstein's theories of relativity. This specific speed, 299,792 kilometers per second, is not just a random value. It is the ultimate speed limit of the universe, according to current physical theories. Light speed is the threshold beyond which traditional laws of physics start to break down, and it represents the maximum speed at which all energy, matter, and information in the universe can travel. This limitation is deeply embedded in the fabric of the universe and is reflected in the structure and behavior of everything within it. The significance of the speed of light extends beyond its definition as a speed limit. It is integral to the structure of Einstein's special theory of relativity, which fundamentally changes our understanding of time and space. According to this theory, as an object moves closer to the speed of light, time is experienced by the object slows relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally confirmed by observing the decay rates of particles moving at high speeds and by precise timing of clocks aboard fast-moving spacecraft. Moreover, the constancy of the speed of light leads to the conclusion that the laws of physics are the same for all observers, regardless of their relative motion. This principle of invariance has profound implications, suggesting a universality of physical laws throughout the cosmos. It also underpins the general theory of relativity, which extends the principle to include gravitational effects, describing gravity not as a force as Newton did, but as a curvature of spacetime caused by mass and energy. The speed of light also serves as a critical tool for astronomers and cosmologists. It acts as a cosmic ruler in the method of astronomical distances. The concept of a light year, which is the distance light travels in 1 year, is used to express astronomical distances. This unit allows scientists to convey the vast expanses between stars and galaxies in terms that are more comprehensible than using standard units like kilometers or miles. Thus, the speed of light underlies our understanding of the size and scale of the universe. Furthermore, the fixed speed of light is crucial in technologies that depend on precise measurements of time and distance, such as the Global Positioning System, GPS. GPS satellites must account for the speed of light in their signals to achieve accuracy in positioning. Any deviation or error in these calculations can lead to significant errors on the ground. Thus, understanding and using the constant speed of light is vital for navigation technologies that impact a wide range of sectors from military to civilian applications. In quantum mechanics, the speed of light plays a role in phenomena such as the entanglement and the uncertainty principle. While quantum entanglement does not transmit information faster than light, it shows how particles can be interconnected in ways that are not entirely understood within the framework of classical physics. This underscores the still mysterious and unexplored aspects of quantum mechanics, where the speed of light remains a boundary for information transfer. The speed of light also influences our understanding of the universe's expansion. Observations indicate that the universe is expanding at an accelerating rate, with distant galaxies moving away from us faster over time. This expansion can approach the speed of light for the most distant galaxies, which leads to observable effects such as redshift, where light from these galaxies shifts towards longer wavelengths as it travels towards us. Ultimately, the speed of light, 299,792 kilometers per second, is more than just a speed limit. It is a fundamental constant that informs our understanding of the universe. It shapes the laws of physics, dictates the structure of space and time, influences how we measure our universe, and even challenges our deepest scientific principles, continually encouraging new research and discoveries in cosmology, quantum mechanics, and relativity. The implications of the speed of light extend into the deeper theoretical realms of physics, influencing our understanding of the universe's most extreme environments and the fundamental nature of reality itself. One significant area where the speed of light plays a crucial role is in the study of black holes and the concept of the event horizon. The event horizon of a black hole is defined as the boundary around a black hole beyond which no light or other forms of radiation can escape. The escape velocity at this boundary equals the speed of light. This means that within this boundary, even light, which is the fastest moving thing in the known universe, the implications of the speed of light extend into the realm of black holes and the event horizon, a critical boundary where the escape velocity equals the speed of light. Black holes are regions of space-time exhibiting gravitational effects so strong that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. The concept of an event horizon is intrinsically linked to the speed of light. It represents the threshold beyond which the gravitational pull is so intense that light cannot get out. Delving deeper into the nature of black holes, the speed of light plays a crucial role in defining the Schwarzschild radius, which is the radius of a sphere such that, if all the mass of an object were to be compressed within that sphere, the escape velocity from the surface would equal the speed of light. Calculating this radius involves directly using the speed of light, showing how it's intertwined with the fundamental properties of these massive objects. Furthermore, the constancy of the speed of light underpins the theoretical framework of general relativity. Einstein's field equations, which describe how matter and energy interact with the geometrical structure of spacetime, rely on the invariance of the speed of light. These equations suggest that spacetime is curved by matter and energy, and this curvature dictates the motion of objects and the propagation of light. Thus, the speed of light is not just a speed limit but a fundamental descriptor of the universe's geometry. This constancy also impacts the universe's expansion. Observations of distant galaxies show that they are moving away from us, and the farther a galaxy is, the faster it appears to be receding. This observation, explained by the Hubble law, suggests that the universe is expanding at speeds that can approach the speed of light for the most distant galaxies. Here, the speed of light again becomes a crucial factor in understanding not only the mechanics of this expansion but also its implications for the observable universe. It limits the portion of the universe we can see and interact with, as beyond a certain point, galaxies recede at a speed greater than the speed of light due to the expansion of spacetime itself, making them unreachable and unobservable. Moreover, the speed of light influences the cosmic microwave background radiation (CMB), the remnant heat left over from the Big Bang, the uniformity and the slight anisotropies (irregularities) in the CMB carry information about the early universe's conditions. The fact that light travels at a constant speed allows cosmologists to calculate how long the light from the CMB has been traveling and thus to estimate the age of the universe. These measurements, again reliant on the speed of light, provide a cornerstone for the Big Bang theory and the subsequent evolution of the cosmos. The role of the speed of light in modern physics and cosmology is indeed profound. It not only defines the boundaries of causality and the observable universe, but also continues to challenge our understanding of the fundamental nature of time, space, and matter. As we probe deeper into the cosmos and back in time towards the moment of the Big Bang, the speed of light remains a key tool in unlocking the mysteries of the universe's origins, structure, and eventual fate. The historical journey of understanding light, from philosophical musings to precise scientific measurements, reflects a fascinating evolution of thought and technology. Aristotle, an ancient Greek philosopher, posited that light was the presence of something, but not a movement. To him, light filled the space between the source and the observer almost instantaneously. This view held sway until the 17th century, when the nature of light began to be questioned more rigorously. The 17th century marked significant shifts with the work of figures like Johannes Kepler and René Descartes. who theorized light's propagation involving some kind of motion. Descartes suggested that light was instantaneous, reflecting Aristotle's influence, but he introduced the idea that it behaved like a wave. The true nature of light began to crystallize through the work of Isaac Newton and Christian Huygens. Newton's Optics, published in 1704, proposed that light was composed of particles or corpuscles, which explained reflection and refraction phenomena. In contrast, Huygens advocated for a wave theory, where light propagated through a medium called the luminiferous ether. Despite their differing views, both theories advanced the understanding of light significantly. The debate between the particle and wave theories continued until the 19th century, when Thomas Young's double-slit experiment provided strong evidence for light's wave nature. This experiment, demonstrating interference patterns, was pivotal, aligning scientific consensus more towards the wave theory. In parallel with theoretical developments, the speed of light attracted great scientific interest. The first successful attempt to measure the speed of light was made by Danish astronomer Ole Romer in 1676. Romer observed the motions of Jupiter's moon Io and noticed discrepancies in its eclipses, which he correctly attributed to the finite speed of light affecting the light travel time from Jupiter to Earth. His calculations brought the speed of light to public scientific consciousness, although his estimated speed was lower than the actual value. The next major advancement came from James Bradley in 1728 through the phenomenon of stellar aberration. Bradley observed that the apparent position of stars shifted due to Earth's motion relative to the speed of light. His measurements were more accurate than Romer's and brought the calculated speed of light closer to its true value. The most precise early measurements of the speed of light were conducted by Hippolyte Fizeau in 1849. Fizeau used a toothed wheel to measure the time it took light to travel a specific distance and back. This method, ingenious for its simplicity and effectiveness, marked a significant step forward in experimental physics, yielding results very close to the modern value. Albert Michelson further refined the measurement in 1879 using a rotating mirror rather than a toothed wheel, which allowed for even greater accuracy. His experiments, repeated over several decades, gradually improved the precision of the speed of light measurement. The culmination of these efforts and the definitive shift from mechanical views of light to electromagnetic theory were synthesized by James Clerk Maxwell. Maxwell's equations, formulated in the 1860s, described light as electromagnetic waves traveling at a constant speed in a vacuum. This theoretical leap was validated by Heinrich Hertz's experimental demonstration of electromagnetic waves, reinforcing the wave theory of light. Albert Einstein's 1905 theory of special relativity then redefined the understanding of light within the framework of physics. He postulated that the speed of light in a vacuum is constant and is an upper limit for motion. This insight was revolutionary, showing that light speed is a critical constant of the universe, affecting the fundamental principles of time and space. These historical perspectives, from the philosophical to the experimental, not only illuminate the evolving understanding of light, but also reflect broader shifts in scientific thinking and technological capability. Each breakthrough, from Aristotle's initial theories to Einstein's revolutionary ideas, was built upon the findings of previous scholars, showcasing the cumulative nature of scientific discovery. Continuing from the profound shifts brought about by Einstein's theory of relativity, the understanding of light has been further nuanced and expanded in the 20th and 21st centuries, particularly through the integration of quantum mechanics. After Einstein established that light was quantized into particles known as photons in his explanation of the photoelectric effect in 1905, the dual nature of light, both particle and wave, became a central tenet in physics. This duality was a foundational element of quantum mechanics, a new theoretical framework that emerged in the early 20th century to describe phenomena at microscopic scales. The quantum theory of light was further developed by scientists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who introduced concepts such as wave-particle duality and uncertainty principles. These ideas were initially perplexing because they challenged classical intuitions about how particles and waves behave. In quantum mechanics, photons are described not just by their speed and particle-like interactions but also by their wave functions, which determine the probabilities of finding them in certain states. One of the landmark experiments that further elucidated the nature of light and supported quantum theory was the demonstration of Bell's theorem experiments in the 1960s and 70s. These experiments, based on John Bell's theorem, tested the peculiar quantum phenomenon known as entanglement. They showed that particles like photons could affect each other's states instantaneously over large distances, a phenomenon that Einstein famously derided as spooky action at a distance. The results of these experiments not only supported the standard interpretations of quantum mechanics but also deepened the understanding of the fundamental properties of light. Another significant advancement in understanding light came with the development of laser technology in the 1960s, based on the principles of stimulated emission first postulated by Einstein. The laser, an acronym for light amplification by stimulated emission of radiation, emits light coherently, allowing for a range of applications from precise cutting and welding to data storage and retrieval, and even in medical surgeries. The invention of lasers also led to new types of experimental setups to test the properties of light at both particle and wave levels. In the realm of cosmology, light's properties have been used to probe the most distant corners of the universe. The study of cosmic microwave background radiation, as mentioned previously, relies heavily on understanding light's speed and its interaction with matter. Additionally, observations of gravitational lensing, where light from distant galaxies is bent around massive objects like other galaxies or black holes, have provided direct evidence of Einstein's general theory of relativity and insights into the distribution of dark matter. Modern experiments continue to push the boundaries of how we understand light. One of the cutting-edge areas of research involves the use of light in quantum computing and quantum encryption. Photons are ideal for these applications due to their speed, small mass, and the ease with which they can be entangled. These technologies promise to revolutionize computing and communications, offering new levels of processing power and secure communication channels. Thus, the journey from the philosophical musings of ancient thinkers like Aristotle to the high-precision experiments of the modern era highlights not only the progression in our understanding of light, but also the profound ways in which this understanding reshapes technology, society, and our conception of the universe. Each discovery about light has peeled back a layer of the natural world, revealing interconnections that are at once beautiful, complex, and profoundly fundamental. Delving deeper into the implications of modern research on light, we find that advancements in photonic technologies not only enhance our understanding of quantum mechanics, but also have practical applications that could revolutionize several industries, including telecommunications, healthcare, and computing. One of the most promising fields of application for light-based technology is in telecommunications, where the use of fiber optics has dramatically transformed the landscape. Fiber optic cables, which transmit data as light pulses, offer a much higher bandwidth than traditional metal cables. This technology harnesses the principle of total internal reflection, allowing light to be efficiently transmitted over long distances with minimal loss of signal. The increasing demand for high-speed internet and data services continues to drive innovations in fiber optic technology, including the development of new types of optical fibers that can carry more data or reduce energy costs. In healthcare, laser technology has been a game-changer in numerous medical procedures, offering high precision with minimal invasiveness. Lasers are used in a wide range of medical applications, from corrective eye surgery where they reshape the cornea to correct vision defects, to the targeted destruction of tumors. Furthermore, advances in photodynamic therapy, PDT, represent a significant leap forward in treating cancer. PDT involves the use of light-sensitive drugs that, when activated by specific wavelengths of light, produce singlet oxygen to kill nearby cells. This method is particularly valued for its ability to precisely target cancerous cells while sparing the surrounding healthy tissue. The field of computing has also seen revolutionary changes with the advent of optical computing, where photons replace electrons for processing and transmitting information. Optical computers promise faster processing speeds and lower heat production compared to traditional electronic computers. While still largely experimental, optical computing could dramatically reduce the energy consumption of data centers, which is a crucial factor given the global push towards sustainability. Furthermore, light plays a critical role in the burgeoning field of quantum communications and cryptography. Quantum key distribution, QKD, uses photons to securely transmit information, with the security of these communications guaranteed by the fundamental principles of quantum mechanics. Any attempt to eavesdrop on the quantum communication would necessarily alter the quantum state of the photons, thus alerting the communicating parties to the presence of the eavesdropper. This application of light is at the forefront of efforts to develop unhackable communication systems. In scientific research, advanced light-based technologies such as super-resolution microscopy have pushed the boundaries of cellular biology by allowing scientists to observe processes at the molecular level in unprecedented detail. Techniques like STED, stimulated emission depletion microscopy, and POM, photoactivated localization microscopy, use the unique properties of fluorescent molecules and sophisticated light manipulation to bypass the diffraction limit of conventional light microscopy. This capability has opened new avenues in neuroscience, developmental biology, and nanotechnology, among other fields. Lastly, the study of light continues to impact our understanding of the universe through astrophysics and cosmology. Techniques such as spectroscopy, which analyzes the light from celestial objects to determine their composition, velocity, and distance, remain fundamental to our study of the cosmos. The upcoming generations of telescopes, equipped with advanced light-capturing technologies, are set to explore the early universe, examine the atmospheres of distant exoplanets, and perhaps unravel more about dark matter and dark energy. Through all these developments, light remains a central pillar in science and technology, continuously expanding our capabilities and understanding of the world around us. Each new discovery in light not only adds a chapter to the rich history of scientific inquiry, but also provides new tools that can be applied across various fields of human endeavor. The speed of light, approximately 299,792 kilometers per second in a vacuum, is a fundamental constant in physics that has profound implications across various scientific domains, particularly in the realms of cosmology and the theoretical limitations it imposes on space travel, as well as its effects on our understanding of time and space. Limitations in cosmic travel. The finite nature of light speed sets a universal speed limit, beyond which conventional matter or information cannot travel. This restriction is deeply embedded in the framework of special relativity, which asserts that as an object approaches the speed of light, its relativistic mass increases, requiring ever greater amounts of energy to continue accelerating. Practically, this means that reaching or exceeding the speed of light with current technology or any foreseeable technology is impossible. Consequently, interstellar travel presents enormous challenges, as even reaching our nearest stellar neighbor, Proxima Centauri, located about 4.24 light-years away, would take over 4 years at the speed of light, a speed unreachable for any manned spacecraft with current propulsion technology. Moreover, The energy required for propelling a spacecraft to a fraction of the speed of light is astronomically high. Current propulsion technologies, such as chemical rockets, are vastly inadequate for such tasks. Even theoretical propulsion methods like nuclear pulse propulsion or antimatter engines would require energy amounts that are currently beyond our capacity to produce or store safely on a spacecraft. This immense energy requirement highlights a significant barrier imposed by the speed of light, making practical and rapid interstellar travel a formidable challenge. Effects on time and space. The implications of light speed extend beyond travel limitations to the very core of how we perceive time and space. According to Einstein's theory of relativity, as an object moves closer to the speed of light, time as experienced by the object's occupants would slow down relative to stationary observers. This phenomenon, known as time dilation, has been experimentally confirmed using precise measurements from atomic clocks on fast-moving jets and satellites. Time dilation implies that for astronauts traveling at near-light speeds, a journey might seem to take only a few years, while decades or even centuries could pass on Earth. Spatial dimensions are also affected by high-speed travel. Length contraction, another prediction of special relativity, posits that objects physically contract along the direction of motion as they approach light speed. From the perspective of a stationary observer, a spacecraft moving close to light speed would appear shorter, though this effect would not be observed by those within the spacecraft due to the relativistic nature of the phenomenon. The speed of light also influences how we observe and understand the universe. The concept of the observable universe is bounded by the light that has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Objects beyond this light horizon are not observable, not because they do not exist, but because their light has not yet had enough time to reach us. This horizon limits our view of the universe and shapes our understanding of its size and structure. Furthermore, the constant speed of light in vacuum conditions is used as a tool for measuring astronomical distances. Techniques such as the light-year distance metric are pivotal in mapping the cosmos. The constancy of light speed also underpins the use of standard candles, objects whose luminosities are known, and standard rulers, objects whose sizes are known, in cosmology, enabling scientists to determine distances to far-off galaxies and thereby constraining the rate of expansion of the universe. In essence, the speed of light is not just a speed limit but a fundamental feature that shapes the structure of the universe and the nature of time itself. Its implications touch on every aspect of cosmology and relativistic physics, presenting both profound challenges to our ambitions of cosmic exploration and a framework through which the universe can be understood in a comprehensive, albeit humbling, way. Continuing from the profound implications of light speed on cosmic travel and the structure of time and space, let's delve deeper into the emerging theoretical and practical approaches that could potentially mitigate the limitations imposed by the finite speed of light, and explore further how these limitations influence our understanding and strategies for future space exploration and cosmological studies. Advanced propulsion technologies. Scientists and engineers are actively researching propulsion technologies that could one day enable faster-than-current space travel, significantly cutting down the travel time to distant celestial bodies. One such theoretical concept is the Alcubierre drive, which proposes the manipulation of spacetime itself to achieve effective faster-than-light travel. By expanding spacetime behind the spacecraft and contracting it in front, the Alcubierre drive would allow a spacecraft to ride a warp bubble and reach destinations faster than light would in normal spacetime, without violating the principles of relativity. Another promising area of research is the concept of photonic propulsion, which involves the use of powerful lasers to propel spacecraft at much higher speeds than conventional rocketry. This method could theoretically propel lightweight probes to a significant fraction of the speed of light, potentially enabling interstellar missions to nearby star systems within a human lifetime. Quantum entanglement and information transfer. In the realm of quantum physics, the phenomenon of entanglement might offer some intriguing possibilities. While quantum entanglement does not allow for the transfer of matter or energy faster than light, it could potentially enable the instantaneous transfer of information across vast distances, a concept often referred to as quantum teleportation. Although practical applications are still in nascent stages, this could revolutionize communication across space, ensuring almost real-time data transfer between Earth and distant spacecraft or colonies, radically changing how missions are monitored and managed. Cosmological insights from light speed constraints. The constant speed of light not only sets a universal speed limit but also provides cosmologists with a tool to probe the very fabric of the universe. The cosmic microwave background radiation, CMB, for instance, is a relic from the early universe that has traveled at the speed of light, offering a snapshot of the cosmos at approximately 380,000 years after the Big Bang. Analysis of the CMB's minute temperature fluctuations helps scientists map the distribution of matter and energy in the early universe, leading to better understanding of the universe's large-scale structure and the dynamics of its expansion. Additionally, the phenomenon of gravitational lensing, where light from distant galaxies is bent around massive objects like other galaxies or black holes, relies on the speed of light as a constant to calculate the mass of the intervening objects and the geometry of spacetime around them. These observations are critical for testing theories of general relativity and for searching for dark matter, which indirectly influences how light travels through space. Educational and philosophical implications. Educationally, the implications of light speed encourage a deeper understanding of physics and the universe, fostering a greater appreciation for the limits of human reach and the boundless opportunities for discovery. Philosophically, the unattainable nature of light speed invites contemplation on our place in the universe, the nature of time, and the pursuit of knowledge. It questions the limits of human advancement and the ethical dimensions of future technologies that might one day break the light speed barrier, either physically or effectively through space-time manipulation. In sum, while the speed of light imposes significant limitations on cosmic travel and influences our understanding of time and space, it also opens up a myriad of scientific, technological, and philosophical areas for exploration. The pursuit to overcome these limitations not only drives technological innovation, but also deepens our understanding of the fundamental laws that govern the universe. Beyond the Alcubierre drive, there are several other theoretical concepts and speculative ideas that scientists and physicists have proposed for achieving faster-than-light FTL travel. These concepts, although highly theoretical and not without substantial scientific and technological challenges, stretch our current understanding of physics and offer intriguing possibilities for future space exploration. Here are some of these concepts. Wormholes. Also known as Einstein-Rosen bridges, wormholes are hypothetical tunnels through spacetime that could connect two distant points in the universe directly. If traversable wormholes exist or could be created, they could theoretically allow for instantaneous travel between these 2 points, effectively bypassing the light speed barrier. The concept relies on solutions to the equations of general relativity that permit spacetime to fold in such a way. However, keeping a wormhole open requires exotic matter with negative energy density, which has not been found to exist in any observable form. Tachyons. Tachyons are hypothetical particles that move faster than light. According to certain interpretations of special relativity, these particles would have imaginary mass and could theoretically transmit information or travel faster than light. However, no experimental evidence supports the existence of tachyons, and their theoretical basis remains highly speculative, with numerous paradoxes and issues in consistency with known physics. Quantum tunneling. While not a method of travel per se, Quantum tunneling is a quantum phenomenon where a particle tunnels through a barrier that it classically shouldn't be able to pass. Some speculative theories suggest that if similar principles could be applied on a macroscopic scale, it might be possible to tunnel through spacetime itself, emerging at another location faster than light would in normal space. This concept remains purely theoretical and faces significant scientific hurdles. Warp field mechanics. Inspired by the Alcubierre drive, this concept involves the manipulation of spacetime itself to move a spacecraft. The idea here is to create a region of contracted spacetime in front of the ship and an expanded region behind it, allowing the ship to move towards its destination faster than light relative to the surrounding space, without locally breaking the light speed barrier. This approach relies on generating and controlling negative energy densities, which is beyond current technological capabilities. Photon-based propulsion. While not inherently faster than light, concepts like the photonic laser thruster aim to propel spacecraft to significant fractions of the speed of light. This method involves bouncing photons back and forth between a spacecraft and a stationary emitter, gradually building up momentum. Over long durations, such a system could potentially accelerate a spacecraft to speeds approaching that of light, significantly reducing travel times to distant stars compared to conventional propulsion technologies. Each of these concepts faces not only technological challenges but also deep theoretical questions about their feasibility and the nature of reality. They challenge current understandings of physics, requiring exotic matter, enormous energy, or breakthroughs in our understanding of quantum mechanics and general relativity. As such, while they provide fascinating insights and inspiration for science fiction, their practical realization, if at all possible, lies far in the future. These concepts continue to stimulate both theoretical research and the imaginations of those keen on exploring the possibilities of what might lie beyond our current scientific limitations. The concepts of quantum tunneling and wormholes, while distinct in their physical interpretations and theoretical foundations, share a thematic connection in the sense that both involve overcoming classical barriers or constraints in unconventional ways. Here's a breakdown of each concept and how they metaphorically relate to each other. Quantum tunneling. Quantum tunneling is a quantum mechanical phenomenon where a particle violates classical mechanics by passing through a potential barrier despite not having enough energy to overcome the barrier in the classical sense. This effect is possible because of the wave-like nature of particles as described in quantum mechanics, where there is a non-zero probability of finding a particle on the other side of a barrier, even if its energy is less than the height of the barrier. Quantum tunneling is a well-established phenomenon and has practical applications, including in the operation of tunnel diodes and the nuclear fusion reactions in stars. Wormholes. Wormholes, or Einstein-Rosen bridges, are theoretical passages through spacetime that could connect two distant regions of the universe. The concept arises from solutions to the equations of general relativity, specifically those that describe black holes. A wormhole would consist of two mouths connected by a throat, potentially allowing travel between the mouths faster than light could travel through normal spacetime. However, the existence of wormholes is purely speculative, and numerous theoretical challenges, such as the need for exotic matter to stabilize the wormhole throat, remain unresolved. Conceptual relationship. Both quantum tunneling and wormholes relate to the idea of bypassing normal paths or barriers. Quantum tunneling, here, the barrier is a potential energy barrier at the quantum scale. Particles tunnel through this barrier, appearing on the other side without having surmounted the barrier in the conventional classical way. Wormholes. In this case, the barrier is the vast distance between 2 points in spacetime. A wormhole provides a shortcut through this classical barrier, hypothetically allowing for travel or communication that is faster than would be possible by traversing the space in the standard manner. Metaphorical link. Metaphorically, Both quantum tunneling and wormholes deal with achieving an end result that bypasses conventional physical limitations. Quantum tunneling does so on a subatomic scale by exploiting the probabilistic nature of quantum mechanics, while wormholes would do so on a cosmic scale by bending the fabric of spacetime itself. Despite these thematic similarities, it's important to note that the underlying physics and scales of these phenomena are vastly different. Quantum tunneling is a well-documented quantum effect observable in the laboratory, whereas wormholes remain a speculative theoretical construct without empirical evidence. The connection between them is more philosophical and conceptual, highlighting the intriguing ways that physics allows for shortcuts in different contexts. Time dilation is a consequence of Einstein's theory of relativity, which tells us that time as measured by a clock depends on the relative velocity of that clock to an observer. If a clock moves relative to you, it will appear to tick slower than a clock at rest with respect to you. This phenomenon becomes significant at speeds close to the speed of light and has profound implications for high-speed travel and the functioning of modern technology, such as GPS systems. A striking illustration of time dilation is given by the twin paradox, a thought experiment in Einstein's special relativity. In this scenario, one of two identical twins travels on a high-speed journey into space while the other remains on Earth. Due to the effects of time dilation, the traveling twin would age slower than their sibling who stayed behind. This is not just theoretical. It has practical implications and has been tested and confirmed by experiments involving precise measurements of time for fast-moving particles and astronauts in space. For instance, astronauts on the International Space Station, ISS, which orbits Earth at about 28,000 kilometers per hour, experience time slightly differently than people on Earth. Although the effect is minuscule, with astronauts aging about 0.005 seconds less for every 6 months in orbit, it is a real effect of the velocities involved in their travel relative to the Earth's surface. Moreover, time dilation is crucial for the accuracy of the Global Positioning System, GPS, which relies on a constellation of satellites orbiting the Earth. These satellites carry highly accurate atomic clocks that are synchronized with those on the ground. However, due to their relative motion with respect to observers on Earth and their position in a weaker gravitational field, another aspect of relativity known as gravitational time dilation, these clocks experience time differently. If these effects were not accurately accounted for, GPS systems would fail in their navigational calculations by about 10 kilometers each day. The system software corrects the time in the satellite clocks to match the time observed on Earth's surface, ensuring the high accuracy and reliability of location data that we depend on. In summary, the concept of time dilation is not just a curious detail of theoretical physics. It has tangible effects on high-speed travel and essential technologies. Understanding and applying the principles of time dilation ensures the functionality of systems like GPS and deepens our understanding of how motion affects the passage of time, as evidenced by the aging discrepancy in the twin paradox. Diving deeper into the implications of time dilation, particularly in the context of the twin paradox, reveals more about the nature of time and space as described by relativity. The twin paradox highlights a crucial aspect of special relativity: the difference between symmetric and asymmetric time experiences for observers in different inertial, non-accelerating frames. The traveling twin undergoes a journey involving acceleration and deceleration, especially when reversing direction to return home, which breaks the symmetry of the situation. According to general relativity, acceleration can be indistinguishable from gravitational effects, adding complexity to the scenario and further affecting time dilation. This leads to another profound implication of relativity: gravitational time dilation, another form of time dilation predicted by Einstein's theory of general relativity. This phenomenon occurs because the presence of a massive object can warp spacetime, causing time to pass slower near the mass. The GPS satellites, while being affected by velocity-related time dilation due to their speed, are also influenced by gravitational time dilation because they are in a weaker gravitational field far from the Earth's surface compared to clocks on the ground. This dual influence requires precise adjustments. The onboard atomic clocks in GPS satellites are pre-adjusted to tick slower than ground clocks, counteracting the effects of reduced gravitational time dilation and ensuring synchronization with systems on Earth. It is fascinating to note that these relativistic effects, though small when dealing with everyday speeds and Earth's gravity, become significant and observable with current technology. For instance, experiments using highly accurate atomic clocks at different elevations have demonstrated gravitational time dilation on Earth itself. Clocks at higher altitudes experiencing slightly weaker gravity run faster than those at lower altitudes. Moreover, modern experiments in physics continue to test and confirm these effects with increasing precision. For example, the Haffel-Keating experiment in 1971 involved flying atomic clocks around the world in commercial airliners and comparing the elapsed time against clocks that remained stationary. The results were consistent with the predictions of relativity, showing that the flying clocks lagged behind the stationary ones by a few nanoseconds. These concepts have not only theoretical implications but also practical applications in various fields of science and technology. Engineers and scientists must consider relativistic effects not only in GPS technology but also in fields like particle physics and cosmology. For instance, in particle accelerators, particles moving at speeds close to the speed of light exhibit significant time dilation, affecting their decay rates and behavior. The exploration of time dilation thus serves as a powerful reminder of how relativity continues to shape our understanding of the universe, influencing both the vast cosmos and the technologies we use in everyday life. It underscores the interconnectedness of space, time, and velocity in the fabric of the universe, challenging our intuitive perceptions and inviting deeper inquiry into the fundamental nature of reality. Time dilation plays a critical role in particle physics, particularly in the behavior and observation of subatomic particles moving at relativistic speeds. Here are several key examples where time dilation is not just a theoretical curiosity but a practical necessity for understanding and predicting experimental outcomes. Lifetime of muons. Muons are subatomic particles similar to electrons but with a much greater mass. They are unstable and decay into electrons and neutrinos with a mean lifetime of about 2.2 microseconds in their rest frame. However, muons can be created in the upper atmosphere by cosmic rays striking atomic nuclei. These muons travel towards the Earth at speeds close to that of light. Due to time dilation, the muons' lifetimes as observed from the Earth are significantly extended, allowing them to reach the surface of the Earth before decaying. This effect has been confirmed by many experiments and is a classic demonstration of time dilation. Without accounting for time dilation, the number of muons detected at Earth's surface would be much fewer than what is actually observed. Particle accelerators. In particle accelerators such as the Large Hadron Collider LHC, particles are accelerated to speeds close to the speed of light. At these high velocities, time dilation becomes significant. For instance, particles like protons in the LHC have lifetimes that are effectively extended due to their high speed. This means they can travel much longer distances around the accelerator ring than they would in their rest frame before decay. This extension in lifetime is crucial for conducting experiments over sufficient durations to study particle interactions precisely. Observation of particle decay. Time dilation also affects the observed decay rates of unstable particles in experiments. In high-energy physics experiments, certain particles are observed to decay much more slowly than would be expected if they were at rest with respect to the observer. This allows detailed study of their properties and the interactions that lead to their decay, which would be far more challenging if their decay rates were not extended by their high speeds. Neutrino beams. Experiments involving neutrinos often utilize beams of these incredibly light and weakly interacting particles sent over long distances. Neutrinos produced in particle accelerators can travel hundreds of kilometers to be detected in distant underground laboratories. Time dilation ensures that a significant number of these high-speed neutrinos survive long enough to be detected after their arduous journey, despite their tendency to interact only very weakly with matter. Testing fundamental symmetries and theories. Time dilation is integral to tests of fundamental symmetries in physics, such as Lorentz invariance, a cornerstone of special relativity which states that the laws of physics are the same for all non-accelerating observers. Experiments that measure how different particles experience time under extreme conditions can provide evidence that either supports or challenges the standard model of particle physics and theories of relativity. These practical applications show that time dilation is not merely a theoretical abstraction but a real effect that has measurable consequences in the realm of high-energy physics, impacting how experiments are designed, conducted, and interpreted. Are there any other fundamental symmetries in physics that are tested using time dilation? Yes, in addition to testing Lorentz invariance, time dilation is involved in probing other fundamental symmetries and principles in physics. These include CPT symmetry. CPT symmetry is a fundamental principle of physics stating that the laws of nature should remain unchanged if three basic transformations are applied simultaneously. Charge conjugation, C, which switches particles with their antiparticles. Parity transformation, P, which inverts the spatial coordinates, as in a mirror image. And time reversal, T, which reverses the direction of time. Experiments involving particles and antiparticles moving at high velocities, where time dilation occurs, can test whether both behave identically under the same conditions, as predicted by CPT symmetry. Any deviation could suggest new physics beyond the current understanding provided by the standard model. Time translation symmetry and energy conservation. The principle of time translation symmetry, which implies that the laws of physics are the same at any time, is closely related to the conservation of energy through Noether's theorem. In experiments where particles travel at relativistic speeds, time dilation can affect the measurement of energy changes over time. High-energy physics experiments, such as those conducted in particle accelerators, must account for time dilation to ensure that energy is properly conserved in particle collisions and decays, thus testing the symmetry. Tests of general relativity and equivalence principle. While not a symmetry in the conventional sense used in particle physics, tests of the equivalence principle, a cornerstone of general relativity, are related to time dilation. The equivalence principle states that gravitational mass and inertial mass are equivalent, and thus the motion in a gravitational field should be indistinguishable from that in an accelerating frame. Time dilation due to gravity, gravitational time dilation, can be measured and compared with predictions from general relativity. Experiments such as those involving clocks on airplanes, satellites, or in high-altitude locations test this principle by observing how time dilates in different gravitational potentials. Lorentz symmetry. While Lorentz invariance was mentioned earlier, it's worth noting that Lorentz symmetry itself encompasses more than just transformations concerning relative motion. It includes transformations related to rotation in space and time. Experiments that measure how physical phenomena like the decay rates of moving particles or the behavior of fundamental forces under high-speed conditions behave can test whether Lorentz symmetry holds under extreme conditions. Deviations might indicate phenomena like quantum gravity effects or extra dimensions. These symmetries are fundamental to our understanding of the universe, and their violation could indicate new physics. High-precision experiments that utilize the effects of time dilation are essential for pushing the boundaries of these symmetrical principles, providing deeper insights into the fabric of reality. Length contraction. Shrinking spaces, visualizing real-world examples and thought experiments. In the realm of special relativity, length contraction stands as a fascinating and counterintuitive consequence of the theory. As objects approach the speed of light, their length appears to contract along the direction of motion to an observer at rest. This phenomenon, known as length contraction, challenges our intuitive understanding of space and offers a glimpse into the strange and wondrous world of relativistic physics. Visualizing length contraction. To better understand length contraction, it is helpful to visualize the scenario from both the moving object's perspective and that of a stationary observer. Imagine a spaceship traveling at nearly the speed of light, carrying a long measuring rod. To an observer on Earth, the rod appears to be shorter than its proper length due to length contraction. However, to the astronauts on the spaceship, the rod remains at its proper length, and it is the surrounding space that appears stretched. This apparent discrepancy highlights the fact that length contraction is not an absolute property, but rather a relative effect that depends on the observer's reference frame. As the spaceship approaches the speed of light, the length of the spaceship itself contracts from the perspective of an Earth-based observer, but to the astronauts on board, the spaceship remains its original length. Real-world examples and thought experiments. While length contraction may seem like an abstract concept, it has been experimentally verified and plays a crucial role in modern physics. One notable example is the behavior of muons, subatomic particles that are produced in the upper atmosphere and decay rapidly. Due to length contraction, the muon's lifetime appears longer to an observer on Earth than it does to the muons themselves, allowing them to travel further than would be expected based on their intrinsic decay rate. Thought experiments can also help us explore the implications of length contraction. Consider the classic twin paradox scenario, where one twin travels near the speed of light on a spaceship while the other remains on Earth. When the traveling twin returns, they will have aged less than their Earthbound sibling due to the effects of time dilation and length contraction. This thought experiment highlights the profound differences between the experiences of moving and stationary observers in the relativistic world. In the realm of special relativity, length contraction challenges our intuitive understanding of space and offers a glimpse into the strange and wondrous world of relativistic physics. By visualizing the phenomenon, exploring real-world examples, and engaging in thought experiments, we can deepen our appreciation for the fundamental principles that govern the universe and the fascinating consequences they yield. Time travel, the concept of moving backward or forward through time, has fascinated humanity for centuries. Although it remains a staple of science fiction, the scientific community continues to explore the possibility of time travel and its implications for causality and the nature of the universe. Causality is the principle that events in the universe have causes and effects, with the cause always preceding the effect. Time travel, particularly to the past, raises questions about causality and the potential for paradoxes that could arise from altering past events. The grandfather paradox is one of the most famous time travel paradoxes. It suggests that if a person were to travel back in time and kill their own grandfather before their parent was conceived, the time traveler would never have been born. This creates a logical inconsistency, as the time traveler could not have existed to go back in time and carry out the action in the first place. Another well-known paradox is the bootstrap paradox, also called the ontological paradox. In this scenario, an object or piece of information is sent back in time, becoming trapped in a causal loop where it has no discernible origin. An example would be a time traveler who receives a book from their future self, then later sends the same book back in time to their younger self, creating a closed loop without a clear starting point for the book's existence. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov, offers a potential resolution to these paradoxes. According to this principle, any action taken by a time traveler in the past must be consistent with the history that already exists. In other words, time travelers cannot change the past in a way that creates paradoxes or inconsistencies. The principle suggests that the universe has a way of self-correcting to maintain consistency, although the exact mechanism for this remains unclear. General relativity, Einstein's theory of gravitation, offers theoretical support for time travel through the concept of closed time-like curves, CTCs. CTCs are paths in space-time that loop back on themselves, allowing objects to travel back in time if they follow these curves. Some solutions to Einstein's field equations, such as those describing rotating black holes or wormholes, contain CTCs, raising the possibility that time travel could be achievable under certain conditions. However, the feasibility of time travel is still uncertain, and many challenges remain. Quantum mechanics, the theory governing the behavior of particles at the subatomic scale, does not appear to allow for time travel. The uncertainty principle, a fundamental aspect of quantum mechanics, suggests that particles do not have definite positions or velocities until they are measured, making it difficult to reconcile with the deterministic nature of time travel. Additionally, some physicists have proposed the chronology protection conjecture, which suggests that the laws of physics actively prevent the formation of CTCs and, consequently, time travel. According to this conjecture, any attempt to create a CTC would result in the destruction of the CTC or the prevention of its formation through some unknown mechanism. The debate surrounding time travel and its implications for causality continues to engage scientists and philosophers alike. While the possibility of time travel remains uncertain, exploring the theoretical and philosophical implications of this concept can provide valuable insights into the nature of time, causality, and the fundamental structure of the universe. Delving deeper into time travel theories and paradoxes, one of the most intriguing time travel theories is the multiverse theory, also known as the many worlds interpretation. This theory suggests that there are an infinite number of parallel universes, each representing a different outcome of every possible event. In the context of time travel, the multiverse theory proposes that when a time traveler goes back in time and alters an event, they create a new, alternate timeline, rather than changing the original one. This approach could potentially resolve paradoxes like the grandfather paradox, as the time traveler would not be altering their own past but rather creating a new, separate reality. Another time travel concept is the idea of time dilation, a consequence of Einstein's theory of special relativity. Time dilation occurs when an object is moving at a significant fraction of the speed of light or is subjected to strong gravitational fields. In these situations, time passes more slowly for the object in motion or under the influence of gravity compared to an object that is stationary or in a weaker gravitational field. While time dilation is not time travel in the traditional sense, it does suggest that time can be manipulated and experienced differently under certain conditions. The twin paradox is a thought experiment that illustrates the concept of time dilation. In this scenario, one twin embarks on a journey through space at near light speed, while the other twin remains on Earth. When the traveling twin returns, they will have aged less than their earthbound counterpart, due to the effects of time dilation. This age difference is a consequence of the different experiences of time between the two twins, and it has been experimentally verified using precise clocks onboard high-speed aircraft and satellites. Wormholes, theoretical tunnels connecting two points in space-time, are another concept often associated with time travel. Wormholes could potentially allow for rapid travel between distant regions of space or even different points in time. However, the existence of wormholes remains purely speculative, and it is unclear whether they could be stable enough for practical use or even created artificially. The concept of time travel also raises philosophical questions about free will and determinism. If time travel were possible, it could imply that the future is already set in stone, and every event, including human actions, is predetermined. This perspective seems to contradict the notion of free will, which asserts that individuals have the power to make choices and shape their own lives. The debate between free will and determinism is an ongoing one, and the potential for time travel adds another layer of complexity to this discussion. In conclusion, time travel remains a captivating and enigmatic concept that has yet to be proven feasible. The various theories, paradoxes, and philosophical implications associated with time travel continue to challenge our understanding of the universe and inspire fascinating debates among scientists, philosophers, and the general public alike. While the possibility of time travel remains uncertain, exploring these ideas can provide valuable insights into the nature of time, causality, and the fundamental structure of reality. Further exploration of time travel and its implications. Time travel has been a popular theme in science fiction, with numerous books, movies, and television shows exploring the concept in various ways. These stories often serve as entertaining thought experiments, examining the potential consequences and paradoxes that could arise from time travel. Some well-known examples include H.G. Wells' The Time Machine, Robert A. Heinlein's All You Zombies, and the Back to the Future film trilogy. In addition to its presence in popular culture, time travel has also been a subject of interest in academic research. In 2005, physicist David Deutsch proposed a quantum mechanical model for time travel, known as the Deutsch-Lockwood-Hayden DLH model. This model, based on the many worlds interpretation of quantum mechanics, suggests that quantum particles could potentially travel backward in time without creating paradoxes. While the DLH model is still a topic of debate among physicists, it offers a unique perspective on the possibility of time travel at the quantum scale. The concept of retrocausality, or backward causation, is another intriguing aspect of time travel. Retrocausality suggests that future events could influence the past, potentially resolving some of the paradoxes associated with time travel. While retrocausality is not widely accepted in the scientific community, it has been explored in the context of quantum mechanics, with some researchers proposing retrocausal interpretations of certain quantum phenomena. The Tipler cylinder, proposed by physicist Frank Tipler in 1974, is a theoretical structure that could potentially enable time travel. The Tipler cylinder is an infinitely long, rotating cylinder that, according to the mathematics of general relativity, would create a region of spacetime with closed time-like curves. If such a structure were possible, it could allow for time travel to the past. However, the Tipler cylinder requires unrealistic conditions, such as infinite length and an incredibly dense material, making it highly unlikely to be achievable in practice. In recent years, some researchers have explored the possibility of detecting time travelers from the future. In 2013, physicists Robert Nemiroff and Teresa Wilson conducted a search for prescient information on the Internet, looking for signs of knowledge that could only have been obtained from the future. Unsurprisingly, their search yielded no evidence of time travelers. Similar efforts have been made to search for anomalous artifacts or out-of-place objects that might indicate the presence of time travelers, but no conclusive evidence has been found. In conclusion, time travel remains a captivating and enigmatic concept that continues to challenge our understanding of the universe. While the possibility of time travel is still uncertain, exploring the various theories, paradoxes, and implications associated with it can provide valuable insights into the nature of time, causality, and the fundamental structure of reality. The fascination with time travel is likely to endure, inspiring both scientific research and imaginative storytelling for generations to come. The quest to unravel the fundamental constituents of the universe has been an enduring pursuit of humanity, one that has challenged our perceptions of reality and pushed the boundaries of our understanding. From the earliest contemplations of the ancient philosophers to the cutting-edge theories of modern physics, the exploration of the building blocks of matter has taken us on a journey that spans the realms of the infinitesimally small and the infinitely vast. At the heart of this cosmic tapestry lies the atom, the fundamental unit of matter that serves as the foundation for all the elements that make up the universe we inhabit. These microscopic structures, once thought to be the indivisible and immutable components of existence, have revealed themselves to be intricate worlds unto themselves, comprised of even smaller subatomic particles. Within the confines of the atom, a delicate dance unfolds, governed by the laws of quantum mechanics. At its core resides the nucleus, a dense concentration of protons and neutrons held together by the strong nuclear force, while the surrounding cloud of electrons, bound by the electromagnetic force, orbit in a probabilistic haze determined by the principles of wave-particle duality. The interplay between these subatomic constituents gives rise to the rich tapestry of elements that populate the periodic table, each with its unique set of properties and behaviors. From the lightest element, hydrogen, to the heaviest known elements forged in the hearts of cosmic furnaces, this diversity of elemental building blocks serves as the foundation for the vast array of chemical compounds and molecular structures that underpin the complexity of our universe. Yet, as our understanding of the cosmos has deepened, we have been confronted with a profound realization. The visible matter we can perceive and interact with is but a mere fraction of the universe's true composition. The enigmatic presence of dark matter and dark energy, two elusive and perplexing components that dominate the mass-energy budget of the cosmos, has challenged our conventional understanding and forced us to confront the vast realms of the unknown that permeate the fabric of existence. Dark matter, an unseen and enigmatic substance that exerts a gravitational pull on the visible matter in the universe, has long been a source of fascination and bewilderment for cosmologists and astrophysicists. Its presence was first inferred from the observed motion of galaxies within galactic clusters, which revealed a discrepancy between the gravitational forces at play and the visible matter present, suggesting the existence of an invisible, yet gravitationally potent, form of matter. Despite its elusiveness, dark matter plays a crucial role in shaping the cosmic tapestry, acting as a cosmic scaffolding that guides the formation and evolution of galaxies and large-scale structures throughout the universe. Its gravitational influence is the unseen hand that sculpts the intricate filaments and voids that permeate the cosmic web, leaving an indelible imprint on the distribution of matter and energy across the cosmos. Equally enigmatic is the presence of dark energy, a mysterious force that permeates the entire fabric of space-time itself, driving the accelerated expansion of the universe. First inferred from observations of distant supernovae, which revealed an unexpected dimming that could only be explained by an accelerating rate of cosmic expansion, dark energy has challenged our fundamental understanding of gravity and the expected deceleration of cosmic expansion due to the attractive force of matter. The nature of this enigmatic force remains one of the greatest mysteries in modern cosmology, forcing us to confront the limitations of our current scientific paradigms and prompting us to explore new frontiers of theoretical and observational research. Is dark energy a manifestation of Einstein's cosmological constant, a repulsive force intrinsic to the fabric of space-time itself? Or is it a dynamic, time-varying field known as quintessence, evolving over time and shaping the destiny of the cosmos in ways we have yet to comprehend? In our quest to unravel the mysteries of dark matter and dark energy, we have embarked on a multifaceted approach that combines cutting-edge observational campaigns, sophisticated computer simulations, and audacious theoretical models. Ground-based telescopes and space-based observatories, such as the James Webb Space Telescope, are probing the cosmic microwave background radiation and mapping the large-scale structure of the universe, seeking imprints and clues that could shed light on the nature of these elusive components. Particle accelerators like the Large Hadron Collider at CERN are pushing the boundaries of our understanding, searching for elusive dark matter candidates and probing the realms of particle physics that could hold the answers to these cosmic puzzles. Meanwhile, theoretical physicists and cosmologists are developing innovative models and simulations, exploring the parameter space of dark matter and dark energy, testing hypotheses, and refining our understanding of the processes that shape the cosmic landscape. As we delve deeper into the realms of the unseen, we are confronted with a profound realization. The visible matter we perceive and interact with is but a fleeting glimpse into the vastness of existence itself. The true tapestry of the universe is woven from threads of known and unknown, the seen and the unseen, the familiar and the unfathomable. It is within this cosmic interplay that we find ourselves, explorers of the infinite, seekers of truth, and stewards of knowledge. The journey to unravel the building blocks of matter and the unseen components that dominate the cosmos is not merely a scientific endeavor, but a profound expression of the human spirit, a relentless quest to push the boundaries of understanding, to transcend the limitations of our terrestrial existence, and to embrace the infinite wonders that the universe has to offer. The concept of counting atoms may seem trivial, but in the realm of astrophysics, it holds paramount importance. Accurate quantification of atomic content is crucial in understanding the composition and evolution of celestial objects. Modern astrophysics employs an array of innovative methods to count atoms, leveraging cutting-edge tools and techniques. One of the most widely used methods is spectroscopy, which involves analyzing the light emitted or absorbed by atoms and molecules. By examining the distinct spectral lines, researchers can identify the presence of specific elements and quantify their abundance. Spectroscopy can be applied to various astrophysical contexts, including the study of stellar atmospheres, interstellar gas, and planetary nebulae. Another powerful tool is the technique of atomic absorption spectroscopy, AAS. This method measures the absorption of light by atoms in a sample, allowing researchers to determine the concentration of specific elements. AAS has been instrumental in analyzing the chemical composition of stars, galaxies, and nebulae. The development of advanced telescopes and detectors has enabled the application of spectroastrometry, which combines spectroscopy with high-resolution imaging. This technique allows researchers to map the distribution of elements within celestial objects, providing valuable insights into their internal dynamics and chemical evolution. In addition to spectroscopic methods, researchers employ indirect techniques to count atoms. One such approach is the use of X-ray fluorescence, which involves exciting atoms with high-energy X-rays, causing them to emit characteristic X-rays that can be detected and analyzed. This method has been successfully applied to the study of highly ionized plasmas in black hole environments and neutron star atmospheres. The analysis of cosmic microwave background radiation, CMB, has also proven valuable in quantifying the cosmic abundance of elements. The CMB's blackbody spectrum contains subtle signatures of atomic interactions, allowing researchers to infer the abundance of light elements, such as hydrogen, helium, and lithium. However, despite these advanced methods, challenges persist in accurately counting atoms. One of the primary hurdles is the complexity of astrophysical environments, which often involve intense radiation fields, strong magnetic fields, and high-energy particles. These conditions can alter the atomic energy levels, making it difficult to accurately model and interpret spectral signatures. Another challenge lies in the limitations of current detector technology. Many spectroscopic instruments are limited by their spectral resolution, signal-to-noise ratio, and detector efficiency, which can result in incomplete or inaccurate data. Furthermore, the interpretation of spectroscopic data often relies on complex models and simulations, which can introduce additional uncertainties. For instance, the treatment of atomic processes such as ionization and recombination can significantly affect the derived abundance values. To overcome these challenges, researchers are developing novel instrumental techniques, such as the use of advanced spectrographs and spectrometers. These instruments will provide higher spectral resolution, increased sensitivity, and improved detector efficiency, enabling more accurate and precise measurements. The development of sophisticated computational models and simulations is also crucial in addressing the challenges in counting atoms. Researchers are working to improve the accuracy and complexity of atomic models, incorporating advanced treatments of atomic processes and radiation transport. Ultimately, the quest to count atoms in the cosmos is an ongoing endeavor, driven by the need to better understand the composition and evolution of celestial objects. As new tools and techniques emerge, researchers will continue to refine their methods, pushing the boundaries of our knowledge and understanding of the universe. In the realm of modern astrophysics, the development of novel methods for counting atoms has opened up new avenues for research. One such area is the study of cosmic dust, which plays a crucial role in the formation of stars and planets. By analyzing the atomic composition of dust grains, researchers can gain insights into the chemical evolution of galaxies and the formation of planetary systems. The study of atomic abundances in white dwarfs has also garnered significant attention, as these objects provide a unique probe of the galactic chemical evolution. By analyzing the atomic composition of white dwarf atmospheres, researchers can reconstruct the history of star formation and chemical enrichment in the galaxy. Furthermore, the development of advanced computational models has enabled the simulation of complex astrophysical processes, such as supernova explosions and black hole accretion. These simulations allow researchers to investigate the role of atomic processes in shaping the cosmic environment and the formation of celestial objects. In conclusion, the methods of counting atoms in modern astrophysics are diverse and multifaceted, leveraging cutting-edge tools and techniques to quantify the cosmic abundance of elements. As researchers continue to push the boundaries of our understanding, new challenges and opportunities will emerge, driving the advancement of our knowledge and understanding of the universe. The significance of knowing the number of atoms in the universe cannot be overstated, as it has far-reaching implications for our understanding of the cosmos and the laws of physics that govern it. At its core, the number of atoms is a fundamental parameter that underlies the fabric of the universe, influencing the behavior of matter and energy at all scales. One of the most striking consequences of knowing the number of atoms is the insight it provides into the scale of the universe. The sheer number of atoms in the observable universe, estimated to be around 10 to 80, is a staggering figure that defies human comprehension. To put this number into perspective, consider that the number of stars in the observable universe is estimated to be around 10 to the power of 24, a tiny fraction of the total number of atoms. This disparity highlights the immense scale of the universe, with atoms being the building blocks of matter that make up the vast majority of its content. Furthermore, the number of atoms has a profound impact on our understanding of the universe's evolution. The abundance of light elements, such as hydrogen, helium, and lithium, is a direct consequence of the number of atoms in the universe. These elements were formed during the Big Bang, when the universe was still in its infancy, and their abundance is a reflection of the universe's primordial composition. The precise measurement of these elemental abundances has led to a deeper understanding of the universe's early stages, including the formation of the first stars and galaxies. The number of atoms also has significant implications for our understanding of the fundamental laws of physics. The standard model of particle physics, which describes the behavior of fundamental particles like quarks and electrons, relies heavily on the number of atoms to constrain its parameters. For example, the precise measurement of the proton's mass, which is a function of the number of atoms, has led to a deeper understanding of the strong nuclear force and the structure of atomic nuclei. Moreover, the number of atoms has far-reaching implications for cosmology, the study of the universe on its largest scales. The distribution of matter and energy in the universe, which is directly influenced by the number of atoms, has a profound impact on the universe's large-scale structure. The formation of galaxy clusters, superclusters, and even the cosmic web itself is a direct consequence of the number of atoms in the universe. The precise measurement of these structures has led to a deeper understanding of the universe's evolution, including the role of dark matter and dark energy. In addition, the number of atoms has significant implications for our understanding of the universe's fate. The ultimate fate of the universe, whether it will continue to expand indefinitely or eventually collapse in a big crunch, is directly influenced by the number of atoms. The precise measurement of the universe's density, which is a function of the number of atoms, has led to a deeper understanding of the universe's long-term evolution. The significance of knowing the number of atoms is further underscored by its connection to the concept of entropy, a measure of the universe's disorder or randomness. The number of atoms in the universe is directly related to the universe's entropy, which has far-reaching implications for our understanding of the universe's evolution. The second law of thermodynamics, which states that entropy always increases over time, is a direct consequence of the number of atoms in the universe. Furthermore, the number of atoms has significant implications for our understanding of the universe's quantum nature. The precise measurement of the number of atoms has led to a deeper understanding of the quantum behavior of particles, including the phenomenon of quantum entanglement. The connection between the number of atoms and the quantum nature of the universe is a testament to the profound interconnectedness of the universe's fundamental laws. In conclusion, the significance of knowing the number of atoms in the universe cannot be overstated. It has far-reaching implications for our understanding of the universe's scale, evolution, and fundamental laws. The precise measurement of the number of atoms has led to a deeper understanding of the universe's composition, structure, and fate, and has underscored the profound interconnectedness of the universe's fundamental laws. Integrating light, time, and atoms, unveiling the intricate relationships in modern science. In the realm of modern science, three fundamental concepts reign supreme: light, time, and atoms. These concepts have been studied extensively in isolation, but their interplay has revealed fascinating phenomena that have revolutionized our understanding of the universe. In this text, we embark on a journey to explore the intricate relationships between light, time, and atoms, and how they have shaped the face of contemporary science. Light, the electromagnetic radiation that traverses the cosmos, has been a subject of interest since ancient times. From the study of optics to the discovery of lasers, light has been a vital tool in understanding various phenomena. However, the integration of light with time and atoms has led to groundbreaking discoveries. The concept of time dilation, for instance, illustrates how time and light are intertwined. According to Albert Einstein's theory of relativity, the passage of time is relative and can be affected by factors such as speed and gravity. This idea has been proven through experiments such as the Pound-Repka experiment, where the gravitational redshift of light was observed. The interaction between light and atoms has also led to significant breakthroughs. The concept of quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic level, has been instrumental in understanding the nature of light. The discovery of photons, the particles that make up light, has revealed the dual nature of light, exhibiting both wave-like and particle-like properties. This property has led to the development of technologies such as lasers, solar cells, and LEDs. Furthermore, the integration of light, time, and atoms has led to the discovery of exotic phenomena such as quantum entanglement and the photoelectric effect. Quantum entanglement, a phenomenon where particles become connected and can affect each other instantaneously, has been demonstrated through experiments involving entangled photons. The photoelectric effect, where light hitting a metal surface can eject electrons, has led to the development of technologies such as solar cells and computer chips. In addition, the interplay between light, time, and atoms has led to the exploration of new frontiers, such as quantum computing and cryptography. Quantum computing, which utilizes the principles of quantum mechanics to perform calculations, has the potential to solve problems that are currently unsolvable with classical computers. Quantum cryptography, which uses entangled photons to secure communication, has been used to create ultra-secure communication channels. In conclusion, the integration of light, time, and atoms has led to a plethora of groundbreaking discoveries and technologies in modern science. The interplay between these concepts has not only deepened our understanding of the universe, but has also opened up new avenues for research and development. As scientists continue to explore the intricate relationships between light, time, and atoms, we can expect even more exciting breakthroughs that will shape the future of humanity. The relationship between light, time, and atoms is a fascinating area of study that has led to many groundbreaking discoveries in modern science. Here are some additional examples of how these concepts are interconnected. Quantum entanglement. As mentioned earlier, quantum entanglement is a phenomenon where two or more particles become connected in such a way that their properties are correlated, regardless of the distance between them. This phenomenon is a result of the interplay between light, time, and atoms. Entangled particles can be created by manipulating the quantum state of atoms using light, and the entanglement can be measured using various techniques, including the detection of photons. Quantum teleportation. Quantum teleportation is a process that allows information to be transmitted from one particle to another without physical transport of the particles themselves. This is achieved by using quantum entanglement and the principles of quantum mechanics to transfer information from one particle to another. Quantum teleportation has the potential to revolutionize communication and data transfer, and it relies on the interplay between light, time, and atoms. Quantum computing. Quantum computing is a field of study that aims to develop computers that can solve problems that are currently unsolvable or require an unfeasible amount of time to solve using classical computers. Quantum computers rely on the principles of quantum mechanics to perform calculations, and they use quantum bits, qubits, instead of classical bits. Qubits can be manipulated using light, and the quantum state of atoms can be used to store and process information. Quantum cryptography. Quantum cryptography is a method of secure communication that uses quantum mechanics to encode and decode messages. This method relies on the principles of quantum entanglement and the no-cloning theorem, which states that it is impossible to create a perfect copy of an unknown quantum state. Quantum cryptography is theoretically unbreakable, and it has the potential to revolutionize secure communication. Time dilation. Time dilation is a phenomenon predicted by Einstein's theory of relativity, which states that the passage of time can be affected by factors such as gravity and motion. This phenomenon has been observed and studied extensively, and it has important implications for our understanding of the universe. For example, time dilation can be used to explain the behavior of clocks on board GPS satellites, which are essential for navigation and positioning. Gravitational redshift. Gravitational redshift is a phenomenon predicted by Einstein's theory of general relativity, which states that the gravitational field of a massive object can affect the frequency of light emitted by the object. This phenomenon has been observed in various astrophysical contexts, such as the redshift of light emitted by white dwarfs and neutron stars. These are just a few examples of the many ways in which light, time, and atoms are interconnected in modern science. The study of these concepts continues to be an active area of research, with new discoveries and breakthroughs being made regularly. As we peer into the horizon of physics, the exploration of dark matter and dark energy remains one of the most tantalizing frontiers. These mysterious components constitute about 95% of the universe, yet their true nature remains largely elusive. Theoretical physicists and cosmologists are pushing the boundaries with new models and experiments, such as the use of direct detection experiments that seek to capture dark matter particles as they pass through detectors, and the mapping of cosmic microwave background radiation to understand the influence of dark energy on the universe's expansion. Another significant direction involves the unification of gravity with quantum mechanics. General relativity and quantum mechanics, pillars of modern physics, work well in their respective realms but famously clash when combined. String theory and loop quantum gravity are leading candidates in this quest, proposing that at a fundamental level, everything in the universe is composed of vibrating strings or loops of spacetime, respectively. New experimental approaches, potentially involving observations of black holes and the behavior of spacetime at the Planck scale, are critical to testing these theories' predictions. The realm of neutrino physics also offers a fertile ground for discovery. Neutrinos are among the most abundant particles in the universe, yet they interact very weakly with matter, making them incredibly difficult to study. Recent advancements in neutrino detection technology could help answer fundamental questions about their masses, the possibility of right-handed neutrinos, and their role in the asymmetry between matter and antimatter in the universe. Quantum computing and information science not only represent a technological revolution but also provide a new toolkit for testing the foundations of quantum mechanics itself. Questions about the nature of quantum entanglement, superposition, and decoherence might be explored through the lens of quantum computational processes, which require maintaining coherent quantum states over time scales and complexities previously unattainable in experimental physics. On the more applied side of physics, the development of ultra-precise timekeeping and measurement devices using quantum phenomena could revolutionize how we measure everything from gravitational waves to the fine structure constant. Such precision measurement could lead to new standards in technology and industry, influencing everything from navigation systems to secure communications networks. Philosophically, these advances challenge our understanding of reality. The potential discovery of other dimensions or the realization that spacetime might be quantized can alter our metaphysical view of the universe, blurring the lines between the known and the unknown, the tangible and the abstract. The philosophical implications extend into the realm of determinism, causality, and the nature of information and reality itself. Personal reflections on these topics often lead to awe and a deeper appreciation for both the complexity of the cosmos and the ingenuity of human inquiry. The pursuit of knowledge in physics embodies a profound narrative of exploration and discovery, reflecting our intrinsic desire to understand the universe and our place within it. These explorations not only satiate our curiosity but also hold practical implications that could transform society through new technologies and a deeper understanding of the forces that govern our existence. As we continue to push the boundaries of what is known, the integration of technology, experimental innovation, and theoretical breakthroughs in physics will likely unravel more of the universe's mysteries. This journey, inherently interdisciplinary and global, not only reshapes our scientific landscape, but also profoundly impacts our philosophical and cultural frameworks, inviting us to rethink what it means to know and understand. Advancing into new territories of physics also involves the exploration of quantum gravity. This field seeks to describe the gravitational force according to the principles of quantum mechanics, and a successful theory could provide insights into the early moments of the Big Bang where current theories break down. Experiments such as the detection of gravity waves from the merging of black holes and neutron stars are offering new data points, potentially providing clues to a quantum theory of gravity. Moreover, hypothetical particles like gravitons, predicted as quantum carriers of gravity, remain a significant area of interest. Detecting such particles would be a monumental step in physics, though no current technology can achieve this directly. Additionally, the physics community is increasingly turning its attention to the information paradox in black holes. This paradox, which highlights a conflict between quantum mechanics and general relativity, questions what happens to information when matter falls into a black hole. The recent theoretical advancements suggest that information may not be lost, but could be scrambled and emitted back out via Hawking radiation, a concept that has profound implications for understanding the fundamental nature of information in the universe. Another promising area is the study of complex systems and chaos theory in quantum systems. While traditionally associated with classical physics, recent developments have explored how quantum properties influence chaotic systems. This research could vastly improve our understanding of everything from weather patterns to economic systems, and even brain function, by applying quantum computational models to these traditionally intractable problems. In terms of practical applications, the ongoing advancements in materials science, particularly through the use of physics-based insights, are leading to the development of metamaterials with properties not found in nature. These materials can manipulate electromagnetic waves in unconventional ways, leading to potential new technologies in optics, telecommunications, and cloaking devices. Philosophically, the potential discoveries in quantum mechanics and cosmology could lead to a new understanding of causality, locality, and the concept of time. These fundamental aspects of reality, when viewed through the potentially counterintuitive findings in modern physics, invite a reconsideration of how we conceptualize the universe and our interactions with it. The philosophical ramifications could extend into existential realms, influencing everything from the free will debate to our understanding of consciousness. Reflecting personally on these developments, there is a profound sense of entering uncharted waters where each discovery not only answers old questions, but also unveils a myriad of new mysteries. It's a reminder of the perpetual frontier of human knowledge and a call to future generations to continue the quest for understanding. The journey of physics is far from linear. It is a vibrant testament to human creativity and resilience, showing that our capacity for wonder and inquiry can lead to practical solutions and deeper philosophical insights. Detecting gravitons, the hypothetical quantum particles of the gravitational field, remains one of the most challenging and speculative endeavors in physics due to the extraordinary weakness of the gravitational force compared to other fundamental forces. Because gravitons are expected to interact very weakly with matter and have extremely low energy, direct detection is beyond the reach of current technology. However, there are some theoretical approaches and indirect methods that researchers consider when exploring the quantum aspects of gravity, including the potential detection of gravitons. Gravitational wave observatories. While not directly designed to detect gravitons, observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo are crucial in studying the properties of gravitational waves, which in quantum theory could be mediated by gravitons. By analyzing the quantum noise and detailed characteristics of these waves, physicists hope to gather data that might hint at the quantum nature of gravity and thus the presence of gravitons. Any anomalies in the expected classical wave patterns could provide clues about their quantum origins. Cosmic microwave background (CMB) experiments. Experiments that study the polarization of the cosmic microwave background, such as the BICEP and Planck missions, also contribute indirectly to our understanding of the quantum aspects of gravity. These studies focus on detecting patterns of B-mode polarization, which are believed to be caused by primordial gravitational waves from the early universe. These primordial waves could theoretically involve gravitons if gravity is quantized. High-energy particle colliders. While currently no particle collider is capable of directly detecting gravitons due to their expected low interaction with matter and high energy requirements, theoretical models often suggest that certain types of particle collisions could emit gravitons. If these gravitons escape into extra dimensions, as predicted by some theories like string theory, they could potentially be inferred by missing energy and momentum in collider experiments. Projects like the Large Hadron Collider (LHC) look for such anomalies which could suggest the existence of gravitons. Theoretical proposals involving quantum optics. Some theoretical proposals suggest using quantum optics techniques to detect gravitons. For example, setups using highly sensitive light interferometers, beyond even the capabilities of LIGO, might one day be capable of detecting the quantized nature of the gravitational field. These remain speculative but are part of ongoing theoretical research. Space-based experiments. Future space-based experiments and observatories might provide the necessary sensitivity and environmental conditions, such as ultra-low noise levels not achievable on Earth, to explore the quantum properties of gravity further. Proposals for such missions are in the conceptual stage and would aim to test various aspects of gravitational physics with unprecedented precision. In summary, while direct detection of gravitons remains a formidable challenge, ongoing advances in gravitational wave astronomy, particle physics, and theoretical research continue to improve our understanding of quantum gravity, potentially paving the way for indirect evidence or new theories that could explain how gravitons might be detected or inferred. Gravitational wave astronomy has rapidly developed since the first detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. This groundbreaking discovery opened a new window onto the cosmos, providing insights into phenomena that are invisible in traditional electromagnetic observations. Here are some recent advancements in this exciting field. Increased detection sensitivity. The sensitivity of LIGO and its counterparts, like Virgo and CAGRA, has continuously improved through hardware upgrades and better data analysis techniques. Enhanced sensitivity allows these detectors to observe gravitational waves from a broader range of sources and at greater distances, increasing the volume of the universe we can study. These improvements have led to a higher frequency of detected events, including binary neutron star mergers, binary black hole mergers, and possibly black hole neutron star mergers. Discovery of diverse and complex sources. The range of phenomena detectable through gravitational waves has expanded. For instance, the detection of binary neutron star merger GW170817 was a milestone, providing not only gravitational wave signals but also electromagnetic counterparts across the spectrum. This event confirmed that such mergers are a source of short gamma-ray bursts and heavy elements like gold and platinum. More recently, detectors have observed events that suggest the existence of intermediate-mass black holes, potentially filling in a long-missing piece of the cosmic puzzle regarding black hole demographics. Multi-messenger Astronomy. The field of multi-messenger astronomy, which combines gravitational wave detections with observations across the electromagnetic spectrum and other cosmic messengers, like neutrinos, has blossomed. This approach was spectacularly validated with GW 170817 and continues to be a powerful method for understanding the physics of cataclysmic events. Multi-messenger observations allow scientists to correlate the timing and location of gravitational wave events with other cosmic phenomena, enhancing our understanding of the life cycle of stars, the behavior of matter under extreme conditions, and the expansion rate of the universe. Tests of general relativity. Gravitational waves provide an unprecedented testing ground for Einstein's theory of general relativity. Observations to date have supported the theory's predictions, including the propagation speed of gravitational waves and the nature of black hole horizons. Advanced detectors are now testing other aspects, such as the polarization of gravitational waves and potential deviations from predictions in the strong gravitational fields of merging black holes. Global network of detectors. The global network of gravitational wave observatories has expanded. Japan's KAGRA joined LIGO and Virgo, enhancing the ability to triangulate the source locations of gravitational waves more precisely. Plans for future detectors like LIGO India and the proposed Einstein telescope in Europe aim to further increase the global network sensitivity and sky coverage. Cosmological insights. Gravitational waves are becoming a tool for cosmology, offering new methods to measure the expansion rate of the universe. The Hubble constant, independent of traditional ladders used in electromagnetic observations. This could help resolve current discrepancies in measurements of the universe's expansion rate, which is a significant debate in modern cosmology. These advancements highlight the dynamic and rapidly evolving nature of gravitational wave astronomy, which continues to transform our understanding of the universe's most extreme and enigmatic phenomena. The field of gravitational wave astronomy is poised for significant advancements over the coming years and decades. These advancements will not only enhance our understanding of the universe, but also open up new realms of astrophysical research. Here are some of the key potential future developments. Next-generation detectors. Future detectors such as the Einstein telescope, ET, in Europe and the Cosmic Explorer, CE, in the US, are planned to be much larger and more sensitive than current facilities. These detectors will be able to probe a greater volume of the universe, detecting events that are further away and fainter, thus increasing the event detection rate significantly. They will provide better insights into the population statistics of black holes and neutron stars and possibly uncover new types of astrophysical objects. Space-based observatories. The planned Laser Interferometer Space Antenna, LISA, a European Space Agency mission expected to launch in the early 2030s, will consist of 3 spacecraft arranged in a triangular formation millions of kilometers apart. LISA will be sensitive to lower frequency gravitational waves than those detected by ground-based observatories, potentially observing supermassive black hole mergers, extreme mass ratio in spirals, and even the background hum of gravitational waves from the early universe. Improved sensitivity and resolution. Advances in technology and data analysis will improve the sensitivity and spatial resolution of gravitational wave detectors. Enhanced sensitivity will allow for the detection of signals from the earlier phases of binary and spirals, providing more detailed information about the orbits and properties of the objects involved. Higher resolution will improve the localization of gravitational wave sources, facilitating better multi-messenger observations. Quantum technology. Incorporation of quantum technologies such as squeezed light, which is already being implemented in some detectors, could further enhance the sensitivity of gravitational wave observatories. Future developments in quantum computing and quantum sensors might also provide new tools for data processing and noise reduction. Multi-messenger astronomy and collaboration. As gravitational wave detectors improve and more observatories come online, multi-messenger astronomy will become even more robust. The collaboration between facilities detecting electromagnetic signals, neutrinos, and gravitational waves will lead to a more comprehensive understanding of cosmic events. This synergy will be crucial in studying phenomena such as neutron star mergers, supernovae, and gamma-ray bursts. Probing fundamentalphysics. Gravitational waves offer a unique avenue for testing the fundamentals of physics, including general relativity, the properties of black holes, and potentially even the nature of dark matter and dark energy. As detections become more common and detailed, gravitational wave astronomy will contribute significantly to high-energy physics, cosmology, and the understanding of gravity at both the quantum and macroscopic levels. New phenomena and sources. As the observational reach expands and sensitivity improves, it's likely that gravitational wave observatories will discover previously unknown sources of gravitational waves. These could include cores of exploding stars, what inside black holes. They say that facts are sometimes just fanciful fictions, and nowhere is this more true than with black holes. Black holes are pretty out there, even by the standards of science fiction, but they're a proven scientific fact. The first person to talk about black holes was Cambridge scientist John Michell in 783. His idea was that if you shoot a particle like a cannonball straight up, gravity will slow it down. Over time, the particle would stop moving upwards and start falling back down. However, if the initial vertical velocity is above a certain critical value, called the escape velocity, the gravitational force won't be enough to stop the particle and it will fly away. The escape velocity for Earth is over 11 kilometers per second, and for the Sun it's about 617 kilometers per second. Both are well above the speed of a real cannonball, but they are low compared to the speed of light, which is 300,000 kilometers per second. That's not really a surprise. So, light can leave both the Earth and the Sun pretty easily. However, Mitchell pointed out that there might be stars that are much more massive than the Sun, where the escape velocity will be faster than the speed of light. We can't see them because the light they're escaping is pulled back by gravity. Mitchell dubbed them dark stars. These days we call them black holes. To understand them, we need to start with gravity. Einstein's general theory of relativity describes gravity, as well as space and time. Einstein came up with a series of equations in 2015 that describe how space and time behave. They've been known as the Einstein equation ever since. Although gravity is considered the weakest force of nature, it has two significant advantages over the others. First, it has a long reach. The Earth is in orbit around the Sun, which is about 150 million kilometers away. The Sun orbits the center of the galaxy, which is about 25,000 light-years away. The second advantage is that gravity is always positive, unlike electrical forces, which can be either positive or negative. This means that in a large enough star, the gravitational attraction between particles is stronger than all other forces, which leads to the star collapsing in on itself. Despite all this, it took the scientific community a long time to realize that massive stars can collapse inward under the influence of their own gravity. They couldn't even begin to imagine how the resulting objects would behave. Albert Einstein even published a paper in 1939 where he argued that gravity couldn't cause a star to collapse because matter couldn't be compressed any denser than a certain point. Many scientists were on the same page as Einstein when it came to his intuitive speculation. John Wheeler was a major exception. He can be seen as the protagonist of the black hole story. In papers from 1951 to 1960, he argued that many stars should eventually collapse and looked at the problems this would pose for theoretical physics. He also predicted a lot of the properties of the things that stars turn into after collapsing under their own gravity, like black holes. For most of an ordinary star's life, which lasts for about 1 billion years, it resists its own gravity by thermal pressure. This creates a thermonuclear process that turns hydrogen into helium. But over time, the star's nuclear fuel runs out, and it starts to shrink. Sometimes it might stick around as a white dwarf, the dense remnants of a stellar core. However, in 1930, Janchunder proved in his novel that the maximum mass of a white dwarf star cannot be more than 1 and 4 times the mass of the Sun. Soviet physicist Lev Landau came up with a similar mass limit. For a neutron star, what happens to an infinite number of stars that are bigger than the mass limit for a white dwarf or neutron star, but don't have enough nuclear fuel left to keep going? Robert Oppenheimer, who is often called the father of the atomic bomb, studied the problem. In a pair of papers he wrote with his students George Volkov and Hartley Snyder, Oppenheimer showed that these stars can't maintain the necessary pressure. Without pressure, a star that's homogeneous and spherical will shrink to a point of infinite density. This is what scientists call a singularity. All our theories about space are based on the idea that space-time is flat and basically flat. So, at the point of singularity where the curvature becomes infinite, it's not continuous. So, the singularity marks the end of space and time. This was met with strong opposition from Einstein. Then World War II happened. Most scientists, including Robert Oppenheimer, shifted their focus to nuclear physics, and the topic of gravitational collapse was largely overlooked. Interest in the subject was reignited with the discovery of distant objects called quasars. The first quasar, 3273, was discovered in 1963. Many more were soon discovered. They were incredibly bright, despite being so far away from Earth. This emission couldn't be explained by nuclear processes because they only use a small amount of their mass to release energy. The only other option is that it could be gravitational energy and descent due to gravitational collapse. So, we also detected a gravitational collapse. When do things like this happen? The force of gravity pulls all the surrounding matter towards an object. It was obvious that a unified spherical star must shrink to a point of infinite density, to a singularity. But what if the star isn't perfectly spherical? Could the uneven distribution of stellar matter cause an uneven collapse, which would avoid the singularity? In a pretty remarkable 1965 paper, Roger Penrose showed that even in such a case, a singularity in a singularity occurs, and Einstein's equations no longer apply, relying solely on the fact that gravity is a force of attraction. This means that at a point of infinite density, it's impossible to predict what will happen next. This means that something pretty unusual must happen when a star collapses. We're not going to be affected in any way by this lack of predictability, unless the singularity is protected from the outside. Penrose came up with the idea of cosmic censorship. All singularities formed by collapsing stars or other objects are hidden from the observer inside black holes. A black hole is a region where gravity is so strong that light cannot escape. It seems pretty safe to say that the principle of cosmic censorship is true, as there have been several attempts to disprove it and none have succeeded. In 1960, John Wheeler came up with the term black hole instead of how they form. The new term was quickly adopted. From the outside, it's impossible to know what's going on inside a black hole, regardless of what goes in or how it's formed. From the outside, it's impossible to tell what's going on inside a black hole. John Wheeler summed it up like this: black holes don't have hair. A black hole has a boundary called the event horizon. In this area, the gravitational force is strong enough to hold light and prevent it from leaving the black hole. Since nothing can move faster than light, everything else is also constantly being pulled back and unable to leave. Imagine canoeing at Angara Falls and falling through the event horizon. If you're far enough from the edge, you can paddle away from it if you paddle really fast. But once you're close to the cliffs, there's no way to help yourself. The current picks up speed, but the canoe is pulled forward more than the stern. You're at risk of being swept away by the current. It's the same with black holes. If you enter a black hole with your feet forward, Gravity will act more strongly on your feet than on your head because your feet are closer to the black hole. This means that you will be stretched out and squeezed at the sides. If the black hole has a mass several times that of the Sun, you'll be ripped apart and turned into spaghetti before you even reach the horizon. If the black hole has a mass of 1,000,000 times that of the Sun, the gravitational force will act evenly on your whole body, and you'll reach the horizon without any problem. If you're planning to explore the insides of a black hole, it's probably best to choose a larger object. To give you an idea of what I'm talking about, there's a black hole in the center of our galaxy with a mass 4,000,000 times that of the Sun. If you fall into a black hole, you won't notice anything. An outside observer will never be able to see your body pass through the event horizon. As you fall, your speed will slow down and you'll find yourself hovering outside. All you'll see is the silhouette gradually becoming more blurred, turning red, and then disappearing from view. From the outside, it'll seem like it's disappeared forever. If the general theory of relativity is right and matter has a positive energy density, as it usually does, this means that the area of the event horizon or the boundary of the black hole must have a property that increases as a result. When new matter or radiation enters the black hole, what's more, if two black holes collide and merge, the area of the new black hole's event horizon must be larger than the total area of the event horizons of the two original black holes. The area theorem was actually tested in the Laser Interiors Metric Gravitational Wave Observatory on September 14, 2015. The League captured gravitational waves from the collision and merger of two black holes. By studying the shape of the gravitational waves, we can work out the mass and momentum of the black holes. The no-hair theorem also lets us calculate the areas of the horizons. It seems that there's a similarity between the area of a black hole's event horizon and one of the terms used in traditional classical physics, namely entropy. In thermodynamics, entropy is basically a way of measuring uncertainty. It's used to describe the chaotic nature of a system or, in other words, the lack of knowledge about its exact state. The second law of thermodynamics is a pretty famous concept. It basically says that entropy increases over time. This was the first clue that there might be some similarities. The comparison between a black hole and the laws of thermodynamics can be taken a step further. The first law of thermodynamics says that a small change in a system's entropy is matched by a proportional change in the system's energy. This connects the change in a black hole's mass to the change in its event horizon's area. In this case, the coefficient of proportionality includes a quantity called surface gravity, which is a measure of the strength of the gravitational field. On the event horizon, if we assume that the area of the event horizon is similar to entropy, then it turns out that surface gravity is similar to temperature. The fact that surface gravity is the same at all points on the event horizon is another example of how it's similar to temperature, which is the same at all points on a body, in a state of thermal equilibrium. But even though it's clear that entropy and the area of the event horizon are similar, it's not yet clear how this area can become the entropy of the black hole itself. So, what is the entropy of a black hole? The most important suggestion came from Jacob Becker in 1972. Stein was a doctoral student at Princeton at the time. Here's the basic idea. When a black hole forms due to gravitational collapse, it quickly reaches a stationary state defined by three parameters: mass, momentum, and electric charge. So, it turns out that the final state of the black hole doesn't depend on what matter it was formed from. It doesn't matter if it's matter or antimatter, or if it came from a spherical or extremely non-symmetric form. Put simply, a black hole with a specific mass, momentum, and electric charge can be created by the collapse of a vast array of matter configurations. So, black holes that look the same on the outside can be formed when different types of stars collapse. If we ignore the quantum effect, there could be an infinite number of these configurations, because a black hole can form from the collapse of a cloud of particles with an indefinite number of particles, not an infinitesimally small mass. But is the number of configurations really infinite? Quantum mechanics is totally consistent with the uncertainty principle, which basically says that it's impossible to measure both position and velocity at the same time. If you know where something is, you don't know how fast it's moving. If you measure velocity, you can't determine position. In practice, this means that we can't localize anything. Let's say you need to figure out the size of something that's moving. To do this, you need to figure out where its boundaries are. But there's no way to do it accurately because you need to determine both the position and velocity of the object at the same time. So we can't really say how big the object is. Ultimately, it boils down to the uncertainty principle. It's simply not possible to accurately determine the real size of anything. As it turns out, the uncertainty principle puts a limit on the size of objects. After some quick calculations, we can see that there is a minimum size for a particular mass of an object. The minimum size is smaller for heavier objects. The lighter the object, the larger its minimum size has to be. This minimum size is a result of the fact that in quantum mechanics, objects can be represented as a wave or by momentum and electric charge. It's not huge, but it's not nothing. Jacob Stein suggested that this finite number could help us understand entropy in black holes. It might be a way of measuring the amount of information that was lost when the black hole was formed. The fatal flaw in Stein's logic is this. If a black hole has a finite entropy that is proportional to the area of the event horizon, then it must have a temperature different from zero and proportional to surface gravity. This means that the black hole must be in equilibrium with thermal radiation at a temperature other than zero. However, the classical concept says this equilibrium is impossible because a black hole absorbs any thermal radiation hitting it. But by definition, it can't radiate anything in response. So it doesn't radiate anything and doesn't emit heat. This is the paradox of black holes. They're incredibly dense objects that arise as a result of stellar collapse. One theory suggests that black holes with identical qualities can be formed from an infinite number of different types of stars. Another theory says the number could be finite. This is where the information issue comes in. It's thought that every particle and every force in the universe contains information. Since black holes have no hair, as John Wheeler puts it, an outside observer can't see what's going on inside one. All we can really figure out is its mass, charge, and rotation. This suggests that a black hole must store a great deal of information that is hidden from the outside world. But there's a limit to how much information can be stored in a single area of space. Information requires energy, and energy has mass, as Einstein famously put it, is equal to the square. So, if there's too much information in a particular area of space, it'll collapse into a black hole. The size of the hole will depend on how much information there is. It's like adding more and more books to a library. Over time, the shelves will sag and the library will collapse into a black hole. If the amount of hidden information in a black hole depends on the size of the hole, then on general principles, the black hole must have a temperature and should glow like a piece of red-hot metal. But it's impossible because nothing can leave the black hole, or at least that's what everyone thought. The issue remained unresolved until early 1970. At the time, I was looking into how matter in the vicinity of a black hole would behave according to the laws of quantum mechanics. I was surprised to find out that black holes do seem to emit particles at a consistent intensity, as others have also observed. At the time, I just assumed that a black hole couldn't radiate anything. I spent a lot of time trying to convince myself of this crazy idea, but the more I thought about it, the more I realized it was a valid point and I had to accept it. That's what finally made me realize this was a real physical process. The particles I was looking at had a distinct thermal spectrum. My calculations showed that a black hole creates and emits particles of radiation in a similar way to an ordinary hot black hole. The temperature of a body is directly related to its surface gravity and inversely related to its mass. So, Jacob Stein's idea that a black hole has a limited amount of entropy seems to be pretty solid. It suggests that a black hole might be in a state of thermal equilibrium, at a specific temperature other than zero. Since then, lots of scientists have backed up the idea that black holes give off thermal radiation using different scientific methods. One way to understand radiation is as follows. Quantum mechanics says that space is full of pairs of virtual particles and antiparticles that are constantly forming, splitting up, and recombining, or annihilating each other. These particles are called virtual because, unlike real particles, they can't be directly observed with a particle detector. Even so, we can measure the indirect effects, and we know they're real because they cause tiny changes in the light energy spectrum studied by excited hydrogen atoms. In the presence of a black hole, one member of a pair of virtual particles can fall into the hole, leaving the other behind. The other particle or antiparticle may either fall into the black hole after the first one, or fly away to infinity. The particle then emits a gravitational field from the black hole and continues moving forward into the future. What are the risks for someone falling into a black hole? This is going to be a problem. If it's a stellar mass hole, he'll be toast before he even reaches the horizon. If it's a supermassive black hole, he'll pass through the horizon without a problem, but he'll be squeezed out of existence at the singularity. A black hole with the mass of the Sun should lose particles so slowly that they're undetectable. However, it is possible for much smaller, miniaturized black holes with the mass of, say, a mountain to exist. It's possible that they could have formed in a very young universe if it was chaotic and not symmetrical. A black hole with the mass of a mountain should be emitting X-rays and gamma rays with an intensity of about 10 million megawatts, which is enough to power our planet. Using a miniaturized black hole like that would be tricky. It wouldn't work in a power plant because it would just penetrate the floor and fall through the center of the Earth. If we had such a black hole, the best we could do would be to put it in Earth orbit. The search for miniaturized black holes of this mass is still going on, but so far nothing has come of it. Another option is to create miniature black holes in extra dimensions of spacetime. Some theories suggest that our universe is just a F4 black surface in 10 or 11 world space. The 2014 movie Interstellar gives us a sense of what this might look like. We can't see these extra dimensions because light doesn't extend into them. It can only interact with the 4 dimensions of our universe. But gravity can affect the extra dimensions, and it can be much stronger there than in our universe. It would be much easier to create a black hole in extra dimensions. This could be observed at the Large Hadron Collider. The collider is a 27-kilometer ring tunnel. 2 streams of particles travel in opposite directions through the tunnel and collide. These collisions can also create miniature black holes. These particles will emit something that's easy to recognize, walls that are characteristic of this type of particle. As the particles leave the black hole, it loses mass and moves out. This makes the particles sink even faster. Over time, the black hole will lose all its mass and disappear. So what happens to all the particles then? What about the astronauts who fell into the hole and didn't make it? It turns out that, along with the total mass and spin, the information about being in a black hole is lost forever. But if the information disappears, it raises a serious problem that affects the very foundations of our ideas about science. For over 200 years, we've believed in scientific determinism, which is the idea that scientific laws determine the evolution of the universe. If we can't predict what'll happen in a black hole because we don't know what information is lost, we won't be able to make plans for the future. It could launch a working TV or a leather-bound volume of Shakespeare. the odds of this kind of exotic phenomenon are pretty slim. It's more likely to emit thermal radiation. The glow of a red-hot piece of metal might make us think that our inability to predict what a black hole will emit is not a big deal. There aren't any black holes close by, but it's a matter of principle. If we can't predict what happens in a black hole, it could be that we can't predict what happens in other situations either. It's possible that black holes could emerge as fluctuations from the vacuum, absorb one set of particles, emit others, and then dissolve back into the vacuum. Even worse, if determinism doesn't work, we can't be sure of our past history either. It's possible that historical writings and our memories are just illusions. Our past shapes who we are. Without it, we lose our sense of identity. It's crucial to figure out if information really is lost in black holes or if it can be retrieved in some way. Many scientists think that information shouldn't just disappear. But for many years now, no one has put forward a way of explaining what happens inside black holes. Some people say that facts are sometimes just fanciful fictions. And nowhere is this more true than in black holes. Black holes are pretty unusual. They're the stuff of science fiction. But they're a proven scientific fact. The first person to talk about black holes was a scientist from Cambridge named John Michell in 1783. His idea was to launch a particle like a cannonball straight up. The force of gravity would slow it down. Over time, the particle would stop moving upwards and start falling back down. However, if the initial vertical velocity is higher than a certain critical value, there's no escape. The force of gravity won't be enough to stop the particle, so it'll fly away. The escape velocity for Earth is over 11 kilometers per second, while for the Sun it's about 617 kilometers per second. Both are well above the speed of a real cannonball, but they are low compared to the speed of light, which is 300,000 kilometers per second. So, light can leave both the Earth and the Sun pretty easily. However, Michell noted that there might be stars that are much more massive than the Sun, where the escape velocity would exceed the speed of light. We can't see them because the light they're escaping is pulled back by gravity. Michell dubbed them dark stars. These days we call them black holes. To get a handle on them, we need to start with gravity. Einstein's general theory of relativity describes gravity, as well as the nature of space and time. Einstein came up with a series of equations in 1915 that describe how space and time behave. They've been known as the Einstein equation ever since. Although gravity is considered the weakest force of nature, it has two significant advantages over the others. First, it has a long reach. The Earth is in orbit around the Sun, which is about 150 million kilometers away. The Sun orbits the center of the galaxy, which is about 25,000 light-years away. The second advantage is that gravity is always positive, unlike electrical forces, which can be either positive or negative. This means that in a large enough star, the gravitational attraction between particles is stronger than all other forces, which leads to gravitational collapse. Despite all this, it took the scientific community a long time to figure out that massive stars could collapse on themselves because of their own gravity. They couldn't even imagine what the resulting objects would be like. Albert Einstein even wrote a paper in 1939 where he said that gravity couldn't make a star collapse because matter couldn't be compressed any more than a certain point. Many scientists were on the same page as Einstein when it came to his intuitive speculation. John Wheeler was a major exception. He can be seen as the protagonist of the black hole story. In papers from 1951 to 1960, he made the case that many stars should eventually collapse and looked at the challenges this would pose for theoretical physics. He also predicted what these collapsed stars would look like. In other words, black holes. For most of an ordinary star's life, which lasts for about 1 billion years, it resists its own gravity through the thermal pressure created by the thermonuclear process that turns hydrogen into helium. But over time, the star's nuclear fuel runs out, and it starts to shrink. Sometimes it can stick around as a white dwarf, which is a dense leftover from a star's core. However, in 1930, Carr proved in his novel Janchandra that a white dwarf star can't have a mass more than 4 times that of the Sun. Soviet physicist Lev Landau came up with a similar mass limit for a neutron star. What happens to the many stars that are more massive than the limiting mass of a white dwarf or a neutron star, which run out of nuclear fuel? Robert Oppenheimer, who is often called the father of the atomic bomb, studied the problem. In a pair of papers he wrote in 1939 with his students George Volkov and Hartley Snyder, Oppenheimer showed that such stars can't maintain the necessary pressure. Without pressure, a star that's homogeneous and spherical will contract to a point of infinite density. This is what scientists call a singularity. All our theories about space are based on the idea that spacetime is flat and almost flat. So, at the point of singularity where the curvature becomes infinite, it's not continuous. So, the singularity marks the end of space and time. This was met with strong opposition from Einstein. Then World War II happened. Most scientists, including Robert Oppenheimer, shifted their focus to nuclear physics, and the topic of gravitational collapse was largely overlooked. The subject was brought back into the spotlight with the discovery of distant objects called quasars. The first quasar, which was given the number 3273, was discovered in 1963. Many more were soon discovered. They were incredibly bright, despite being so far away from Earth. This emission couldn't be explained by nuclear processes because they only use a small amount of their mass to release energy. The only other option was to consider gravitational energy and descent due to gravitational collapse. So, gravitational collapse was also discovered. When this happens, the force of gravity pulls all the surrounding matter towards the object. It was obvious that a unified spherical star would have to shrink down to a point of infinite density, to a singularity. But what if the star isn't perfectly spherical? Could the uneven distribution of stellar matter cause an uneven collapse, which would avoid the singularity? In a pretty remarkable 1965 paper, Roger Penrose showed that even in such a case, a singularity in a singularity occurs, and Einstein's equations no longer apply, relying solely on the fact that gravity is a force of attraction. This means that at a point of infinite density, it's impossible to predict what will happen next. This means that something pretty unusual must happen when a star collapses. We're not going to be affected in any way by this lack of predictability, unless the singularity is protected from the outside. Penrose came up with the idea of cosmic censorship. All singularities formed by collapsing stars or other objects are hidden from the observer inside black holes. A black hole is a region where gravity is so strong that light cannot escape. It seems pretty safe to say that the principle of cosmic censorship is true, as there have been several attempts to disprove it and none have succeeded. In 1960, John Wheeler came up with the term black hole instead of how they form. The new term was quickly adopted. From the outside, it's impossible to know what's going on inside a black hole, regardless of what goes in or how it's formed. From the outside, it's impossible to tell what's going on inside a black hole. John Wheeler summed it up like this: black holes don't have hair. A black hole has a boundary called the event horizon. In this area, the gravitational pull is strong enough to hold light in and keep it from leaving the black hole. Since nothing can move faster than light, everything else is also constantly being pulled back, and it can't leave. Imagine canoeing at Ongar Falls and you'll get the idea of what it's like to fall through the event horizon. If you're far enough from the edge, you can paddle away from it if you paddle really fast. But once you're close to the cliff, there's no way to help yourself. The current is pushing the bow of the canoe forward more than the stern. You could get swept away by the current. It's the same with black holes. If you enter a black hole with your feet leading the way, gravity will act more strongly on your feet than on your head because your feet are closer to the black hole. This means that you will be stretched out and squeezed at the sides. If the black hole has a mass several times that of the Sun, you'll be ripped apart and turned into spaghetti before you even reach the horizon. If the black hole has a mass of 1,000,000 times that of the Sun, the gravitational force will act evenly on your whole body, and you'll reach the horizon without any problem. If you're planning to explore the insides of a black hole, it's probably best to choose a larger object. To give you an idea of what I'm talking about, there's a black hole in the center of our galaxy with a mass 4,000,000 times that of the Sun. If you fall into a black hole, you won't notice anything. From the outside, there's no way to see your body pass through the event horizon. As you fall, the speed will slow down and you'll find yourself hovering outside. All you'll notice is the silhouette gradually becoming more blurred, taking on a reddish hue, and then simply disappearing from view. From the outside, it'll seem like you've disappeared forever. If the general theory of relativity is right and matter has a positive energy density, as it usually does, so the area of the event horizon or the boundary of the black hole should increase when new matter or radiation enters the black hole. What's more, if two black holes collide and merge, the area of the new black hole's event horizon must be greater than the sum of the areas of the event horizons of the two original objects. We were able to verify the area theorem in laser interferometry and gravitational wave observatories. Either on September 14, 2015, LIGA picked up on gravitational waves from the collision and merger of two black holes. By studying the shape of the gravitational waves, we can work out the mass and momentum of the black holes. The no-hair theorem also lets us calculate the areas of the horizons. It seems that there's a connection between the area of a black hole's event horizon and one of the concepts in traditional classical physics, namely entropy. In thermodynamics, entropy is basically a way of measuring uncertainty. It's used to describe the chaotic nature of a system or, in other words, the lack of knowledge about its exact state. The second law of thermodynamics is a pretty famous concept. It basically says that entropy increases over time. This was the first clue that there might be some similarities. The comparison between a black hole and the laws of thermodynamics can be taken a step further. The first law of thermodynamics says that a small change in a system's entropy is matched by a proportional change in the system's energy. This connects the change in a black hole's mass to the change in its event horizon's area. In this case, the coefficient of proportionality includes a quantity called surface gravity, which is a measure of the strength of the gravitational field. On the event horizon, if we assume that the area of the event horizon is similar to entropy, then it turns out that surface gravity is similar to similarity temperature. This is supported by the fact that surface gravity is the same at all points on the event horizon, just as temperature is the same at all points on a body, in a state of thermal equilibrium. But even if it's clear that entropy and the area of the event horizon are similar, it's not yet clear how this area can become the entropy of the black hole itself. So, what is the entropy of a black hole? The most significant proposal was put forth in 1972 by Jacob Becker. Stein was a doctoral student at Princeton at the time. Here's the basic idea. When a black hole forms as a result of a gravitational collapse, it quickly reaches a stationary state defined by the three parameters: mass, momentum, and electric charge. So, it turns out that the final state of the black hole doesn't depend on what it's made of, matter or antimatter, or on whether it was formed in a spherical or extremely non-symmetric way. Put simply, a black hole with a specific mass, momentum, and electric charge can be created by the collapse of a vast array of matter configurations. So, Black holes that look the same on the outside can be formed by the collapse of different types of stars. If we ignore the quantum effect, there could be an infinite number of these configurations because a black hole can form when a cloud of particles with very small masses collapses. But is the number of configurations really infinite? Quantum mechanics is totally consistent with the uncertainty principle, which basically says that it's impossible to measure both position and velocity at the same time. If you know exactly where something is, you don't know exactly how fast it's moving. If you measure velocity, you can't determine position. In practice, this means that we can't localize anything. Let's say you need to figure out the size of something that's moving. To do this, you need to figure out where its boundaries are. But you can't do it precisely because you need to figure out where the object's boundaries are and how fast it's moving at the same time. So we can't really say how big the object is. Ultimately, it boils down to the uncertainty principle. It's simply not possible to accurately determine the real size of anything. As it turns out, the uncertainty principle puts a limit on the size of objects. After some quick math, we can see that there's a minimum size for a particular mass of an object. The minimum size is smaller for heavier objects. The lighter the object, the larger its minimum size should be. This minimum size is a result of the fact that in quantum mechanics, objects can be represented as a wave or by momentum and electric charge. It's a very large number, but it's still finite. Jacob Becker-Stein suggested that this finite number could help us understand entropy in black holes. It might be a way of measuring the amount of information that was lost when the black hole was formed. The fatal flaw in Bekenstein's logic is this. If a black hole has a finite entropy that is proportional to the area of the event horizon, then it must have a temperature different from zero and proportional to surface gravity. This means that the black hole must be in equilibrium with thermal radiation at a temperature other than zero. However, the classical concept says this equilibrium is impossible because a black hole absorbs any thermal radiation hitting it. But by definition, it can't radiate anything in response. So it doesn't radiate anything and doesn't emit heat. This is the paradox of black holes. They're incredibly dense objects that arise as a result of stellar collapse. One theory suggests that black holes with identical qualities can be formed from an infinite number of different types of stars. Another theory says the number could be finite. This is where the information issue comes in. It's thought that every particle and every force in the universe contains information. Since black holes don't have any hair, as John Wheeler puts it, an outside observer can't see what's going on inside a black hole. All we can really figure out is its mass, charge, and spin. This suggests that a black hole must store a great deal of information that is hidden from the outside world. But there's a limit to how much information can be stored in a single region of space. Information requires energy, and energy has mass, as Einstein famously put it. It's equal to the square of the correspondence. If too much information accumulates in a region of space, it will collapse into a black hole. The size of that hole will reflect the amount of information. It's like adding more and more books to a library. Over time, the shelves will sag, and the library will collapse into a black hole. If the amount of hidden information in a black hole depends on the size of the hole, it seems reasonable to assume that the black hole has a temperature and should glow like a piece of red-hot metal. But that's not possible because nothing can leave the black hole. Or did everyone think it couldn't? The issue remained unresolved until early 1970. At the time, I was looking into how matter in the vicinity of a black hole would behave according to the laws of quantum mechanics. I was surprised to find that the black hole seems to emit particles in a uniform, intense way just like everyone else. At the time, I just assumed that a black hole couldn't radiate anything. I spent a lot of time trying to convince myself of this ridiculous idea, But the more I thought about it, the more I realized it was a valid point and I had to accept it. That's what finally made me realize this was a real physical process. The particles I was looking at had a distinct thermal spectrum. My calculations showed that a black hole creates and emits particles of radiation like an ordinary hot body at temperatures directly proportional to surface gravity and inversely proportional to mass. So, Jacob Stein's controversial idea that a black hole has a limited amount of entropy turned out to be pretty convincing. It suggested that a black hole could be in thermal equilibrium at a specific temperature other than zero. Since then, lots of scientists have backed up the math showing that black holes give off thermal radiation. One way to understand radiation is as follows. Quantum mechanics says that space is full of pairs of virtual particles and antiparticles that are constantly forming, splitting up, and recombining, or annihilating each other. These particles are called virtual because, unlike real particles, they can't be seen with a particle detector. Even so, we can measure the indirect effects and confirm their existence by looking at small fluctuations or shifts in the light energy spectrum studied by excited hydrogen atoms. In the presence of a black hole, one member of a pair of virtual particles can fall into the hole, leaving the other behind. The other particle that was going to be annihilated. The remaining particle or antiparticle might fall into the black hole after the partner, or it could fly away to infinity. There, it would manifest as radiation, emit a gravitational field by the black hole, and move forward into the future. What are the risks for someone falling into a black hole? This is going to be a problem. If it's a stellar mass hole, he'll be toast before he even reaches the horizon. If it's a supermassive black hole, he'll pass through the horizon without a problem, but he'll be squeezed out of existence at the singularity. A black hole with the mass of the Sun should lose particles so slowly that we can't even detect them. However, it is possible for much smaller, miniaturized black holes with the mass of, say, a mountain to exist. It's possible that they could have formed in a very young universe if it was chaotic and not symmetrical. A black hole with the mass of a mountain should be emitting X-rays and gamma rays with an intensity of about 10 million megawatts, which is enough to power our planet. Using a miniaturized black hole like that would be tricky. It wouldn't work in a power plant because it would just penetrate the floor and fall through the center of the Earth. If we had such a black hole, the best we could do would be to put it in Earth orbit. The search for miniaturized black holes of this mass is still going on, but so far nothing has come of it. Another option is to create miniature black holes in extra dimensions of spacetime. Some theories suggest that our universe is just a four-dimensional surface in 10 or 11-dimensional space. The 2014 movie Interstellar gives us a sense of what this might look like. We can't see these extra dimensions because light doesn't travel in them. It can only interact with the 4 dimensions of our universe. But gravity can affect the extra dimensions, and it can be much stronger there than in our universe. It would be much easier to create a black hole in extra dimensions. This will be observed at the Large Hadron Collider at CERN. The collider is a 27-kilometer ring tunnel. 2 streams of particles travel in opposite directions through the tunnel and collide. These collisions can also create miniature black holes. They'll give off particles that are easy to spot. As the particles leave the black hole, it loses mass and moves out of the black hole. This makes the particles more intense and causes them to sink. Over time, the black hole will lose all its mass and disappear. So, what happens to all the particles and the unlucky astronauts who fell into it? Are they going to fall into the hole? It turns out that, along with the total mass and spin, the information about being in a black hole is lost forever. But if the information disappears, it raises a serious problem that affects the very foundations of our ideas about science. For over 200 years, We've believed in scientific determinism, which is the idea that scientific laws determine the evolution of the universe. If information in black holes does go missing, we won't be able to predict the future because a black hole can emit any set of particles. It could even bring down a working TV or a leather-bound volume of Shakespeare, although the chances of such exotic phenomena are extremely small. It's more likely that it will emit thermal radiation. The glow of a red-hot piece of metal might make us think that our inability to predict what a black hole will emit is not a big deal. There aren't any black holes close by, but this is a matter of principle. If we can't predict what's going to happen in a black hole, it's possible we won't be able to predict what's going to happen in other situations. It's possible that black holes could form as a result of fluctuations in the vacuum, absorbing one set of particles and emitting others before dissolving back into the vacuum. Even worse, if determinism doesn't work, we can't be sure of our past history either. It's possible that historical writings and our memories are just illusions. Our past shapes who we are. Without it, we lose our sense of identity. It's crucial to determine whether information truly vanishes in black holes or if it can be retrieved in some form. Many scientists think that information shouldn't just disappear, but nobody's yet come up with a way to keep it safe. This apparent loss of information, known as the information paradox, has been a source of concern for scientists for the past 40 years and is still one of the most significant unsolved problems in theoretical physics. Recently, there's been a lot of interest in the possibility of resolving the information paradox thanks to new discoveries in unifying gravity and quantum mechanics. At the heart of this scientific breakthrough is our understanding of the symmetric network of space-time. Let's say for a moment that gravity doesn't exist and space-time is perfectly flat. This is like a completely lifeless desert. In such a place, there are two types of symmetry. The first is ionic symmetry translation. If you were to move from one point to another in such a desert, you wouldn't notice any changes. The second type is rotational symmetry. If you stand in the middle of the desert and start to rotate, you'll see the same thing in every direction. These kinds of symmetries also occur in flat spacetime, which exists in the absence of matter. But if you put something in this desert, it changes the symmetry. Imagine if a mountain oasis and some cacti suddenly appeared in the middle of the desert. Then it'll look different at different points and in different directions. This also applies to spacetime. If you put things in the spacetime continuum, you'll break both the translation and rotation symmetries. It's the presence of objects in spacetime that gives rise to gravity. A black hole is a region of spacetime with a strong gravitational pull. The spacetime there is highly distorted, so it's no surprise that symmetries are broken there. However, the warping of spacetime becomes less and less pronounced the further away you get from the black hole. From a great distance away, spacetime appears to be completely flat. Back in the 1960s, Bondi, Messner, van der Berg, and Sachs made an incredible discovery. They found that spacetime at a great distance from matter has an infinite set of symmetries, which they called supertranslations. Each of these symmetries is linked to a conserved quantity called a supertranslation, which is given by charges. A conserved quantity is one that doesn't change over time in a system. It's a broader concept that encompasses the more familiar conserved quantities. For instance, if spacetime remains constant over time, then energy is conserved. If spacetime looks the same at different points, then momentum is conserved. What's really interesting about supertranslations is that there are an infinite number of conserved quantities at a great distance from the black hole. These conservation laws offer a unique and surprising perspective on gravitational physics. As we know, a black hole has three explicit parameters: mass, charge, and rotation parameter. These are the classical charges that we've been aware of for a long time. But it turns out that a black hole also contains a supertranslation ionic charge. It's possible that black holes are more than we realize. They're not actually bald or have 3 hairs, but they have a lot of supertranslation ion hairs. It's possible that these super broadcast hairs contain coded information about what's inside the black hole. It's likely that the supertranslations and charges don't contain all the information, but we can get the rest by looking at some additional conserved magnitudes of superstationary charge. These are linked to some extra symmetry-related superdonations, but we don't know much about them yet. If this is true, and if we can understand all the information about the black hole in its hair indices, then perhaps there's no loss of information. This idea has recently been backed up by the latest research. It seems that these super radiation charges may be responsible for all the entropy of any black hole. The latest research shows that quantum mechanics is still valid and that information is stored on the horizon of the black hole. We still know the total mass, electric charge, and rotation of a black hole outside the event horizon. But the event horizon itself contains information in addition to the 3 characteristics needed to understand what fell into the black hole. We're still learning, but the information paradox remains unsolved. How did it all get started? Hamlet said, "I could think of myself as a tiny, insignificant speck in an infinite universe." Is the universe really infinite, or is it just very large? Does it have a beginning? Is it going to stick around forever or just for a long time? How can we possibly understand something so much bigger than us? Is it too much to even try to do so? I believe we can and should try to understand the universe. We've already made great strides in understanding the cosmos. We don't have the full picture yet, but it won't be long now. The myth of the Congo people of Central Africa says that at the beginning of the world, there was nothing but darkness, water, and a great God. A bomb. One day, the bomb, feeling a terrible pain in his stomach, strained and jumped from the sun. The sun vaporized, part of the water, and a dry land emerged, continuing to suffer pain. The bomb from the moon, then several animals, leopard, crocodile, turtle, and finally man. This creation myth, like many others, is trying to answer the question of why we're here. Where did we come from? The answer usually suggests that humans came into existence relatively recently. After all, the human race has evolved and expanded knowledge and technology, so it's unlikely that we've existed for long, otherwise there would have been much more progress. For instance, according to Bishop Ussher's calculations, the book of Genesis clearly indicates the beginning of time. It all started at 6 p.m. on October 22nd, 4004 BC. On the other hand, the physical surroundings of mountains, rivers, and so on have changed very little over the course of humanity's existence. They can be seen as a constant backdrop and have either always been there as a lifeless landscape or were created at the same time as humans. However, not everyone was comfortable with the idea that the universe had a beginning. Aristotle, the most famous of the Greek philosophers, argued that the universe existed eternally as something eternal, more perfect than something created. He suggested that progress could be explained by a flood or other natural disasters that periodically set civilization back to its origins. People tend to believe that the universe is eternal because they don't want to think that it was created. The question of whether the universe had a beginning really piqued the interest of the German philosopher Immanuel Kant. He sensed a logical contradiction or a kind of intuition. If the universe had a beginning, why did an infinite amount of time pass before it began? He put it forward as a thesis. On the other hand, if the universe has always existed, why did it take an infinite amount of time for it to reach its current state? He called it an antithesis. The thesis and antithesis are based on Kant's idea that time is an absolute concept. This means that it flows from an infinite past to an infinite future, regardless of whether or not any universe exists. This way of thinking is also common among many modern scientists, but it hasn't been fully defined yet. Einstein's theory brings space and time together, but it doesn't say much about space itself. It seems pretty clear that space extends in all directions. We don't believe the universe ends abruptly. There's no reason to think this is ruled out, though. Modern instruments like the Hubble Space Telescope give us a glimpse into the depths of space. We can see 1 billion galaxies of different shapes and sizes. There are some pretty big elliptical galaxies, and then there are spiral galaxies like ours. Each galaxy has billions of stars, and many of them probably have their own planetary systems. Our galaxy partially overlaps our view in some directions, but if we don't account for that, we can say that galaxies are distributed in space roughly uniformly, with some local clustering and voids between them. As you get really far away from a galaxy, there are fewer and fewer of them. It might seem like there are more galaxies than there are, but that's just because they're too far away for us to distinguish. All we can say is that the universe occupies all of infinite space and is basically the same no matter how far it extends. However, while the universe seems to be the same at any given point in space, it's clear that it's actually changing over time. This wasn't understood until the beginning of the last century. Up until that point, it was believed that the universe was basically unchanging over time, with the potential to exist for an infinite amount of time. But this leads to some pretty absurd conclusions. If stars were to emit energy for infinite time, they would have to have heated the universe to their own temperature. This would mean that even at night, the whole sky would be as bright as the sun's. This is because any view would rest either on a star or on a dust cloud heated to the temperature of a star. So, the fact that we see dark skies at night is a pretty big deal. This suggests that the universe can't exist forever in the same state we see today. Something must have happened in the past to make the stars light up. That means the light from stars that are really far away simply hasn't had time to reach us. This also explains why the night sky doesn't shine in all directions. If the stars have been around forever, why did they suddenly start shining a few billion years ago? What kind of clock told them it was time to start shining? This has puzzled philosophers like Immanuel Kant, who believed that the universe has existed forever. But most people are okay with the idea that the universe is basically the same as it was a few thousand years ago, but was created only recently. Bishop Ussher came up with a calculation. However, in 11920X, observations with the help of a new telescope installed at the Mount Wilson Observatory began to show that this theory wasn't entirely consistent. First of all, Edwin Hubble found that many of the faint spots of light in the so-called nebula are actually other galaxies. These are huge clusters of stars similar to our Sun, but located at a great distance from us so that they look small and faint. The distance to them must be so great that it took light 1 million or maybe 1 billion years to reach us. This suggests that the universe couldn't have started just a few thousand years ago. But Hubble also made an even more remarkable discovery. By studying the light from faraway galaxies, Hubble was able to figure out whether they were moving towards or away from us. He was astonished to discover that almost all of them were moving away from us. What's more, the further away they are, the faster they're moving. Put simply, the universe is expanding and galaxies are moving away from each other. The discovery of an expanding universe was one of the most significant intellectual breakthroughs of the 20th century. It was a complete shock because it completely changed the way people thought about how the universe was created. If galaxies are moving away from each other, it means they were closer together in the past. Based on how fast things are expanding, we can figure that 10 to 15 billion years ago, they were pretty close. It seems like they were all in the same spot in space when the universe started. Many scientists aren't comfortable with the idea that the universe had a beginning because it goes against the laws of physics. Some people chose to explain this phenomenon by invoking an external factor, which we'll call God, for simplicity's sake. So, some people have come up with ideas that say the universe is still expanding but had no beginning. One of these is the stationary state theory of the universe, which was first proposed by Hermann Bondi, Thomas Hunger, and Fred Hall in 1948. The stationary state theory of the universe says that new galaxies form from matter that's constantly being created in space, which explains why non-galaxies disperse. So, the universe is forever and always looks the same. This latter property has the advantage of being a concrete assumption that can be tested with observations. In the early 1960s, Martin Rave and a group of radio astronomers from Cambridge studied the sources of weak radio waves. They were found to be distributed quite evenly across the sky and located outside our galaxy. The fainter the source, the farther away it is, and vice versa. The steady-state theory suggests there's a relationship between the number of sources and their strengths. But the observations showed there were more faint sources than we expected. This suggests that there were more sources in the past with a higher density. This goes against the basic idea behind the steady-state theory, which is that everything stays the same over time. For this and a number of other reasons, the steady-state theory was rejected. Another way to get around the idea of the Big Bang was to assume that there was a period of compression at the beginning of the universe. However, because of the rotation and local heterogeneity of matter, not all matter was concentrated in one point. Some of the matter didn't collide with each other, and the universe started to expand again. Meanwhile, its density is always finite. Two Soviet scientists, Yevgeny Lifshitz and Isaac Kolodilnikov, said they found evidence that in most cases, when matter is compressed without perfect symmetry, it rebounds. Meanwhile, the density stays finite. This was a great fit for Marxist-Leninist dialectical materialism because it let them sidestep some tricky questions about the origins of the universe. So it became a kind of creed for Soviet scientists. We tend to think of events as being caused by previous events, which in turn came about because of even earlier events. This chain of causation goes back in time. But what if the chain has a starting point? What caused the original event? Not many scientists are willing to tackle this question head-on. They try to avoid it by saying, like the Russian scientists and proponents of the steady-state theory, that the universe has no beginning. Or they say the question of where the universe came from is not something science can answer, but is more a matter of metaphysics or religion. I believe that such a stance is not aligned with the standards of a true scientist. If scientific laws are up in the air at the moment of the universe's origin, could they be invalid at other points in time too? If a law is only valid some of the time, it's not really a law. I believe we should try to understand the beginning of the universe from a scientific perspective. It might be impossible for us to solve, but it makes sense to at least try. If Einstein's general theory of relativity is right and certain logical conditions are met, then the universe must have a beginning. Mathematical reasoning is pretty indisputable. Eventually, Lifshitz and Vatnikov agreed that the universe must have a beginning, although this idea might not have been exactly in line with communist beliefs. Ideology never got in the way of physics as a science. The project needed physicists to build the bomb, and it was crucial that it functioned properly. However, Soviet ideology held back progress in biology by rejecting genetics as a science. They demonstrated that the universe originated with the Big Bang, the instant when the universe and all its constituent matter was drawn into a singularity of infinite density at a spatiotemporal singularity. This means that Einstein's general theory of relativity doesn't apply, so we can't even speculate about how the universe began. It's worth noting that the origin of the universe is outside the realm of scientific explanation. In October 1965, we got some empirical evidence that the universe had a very compact beginning. It was the discovery of a faint microwave background in space. Microwaves are basically the same as those emitted by your microwave oven. The thing is, they're much weaker and can only heat a pizza to minus 274 degrees Celsius. It's not strong enough to defrost, let alone cook. Have you ever had a chance to observe these microwaves yourself? If you remember analog TVs, you probably saw them when you turned on the TV to an empty channel. It's worth noting that the few percent of snowflakes that were visible on the screen had exactly to do with these background microwaves. The only logical explanation for this background radiation is that it was left over from a very hot and dense structure that existed in the past. As the universe expanded, this radiation cooled and gradually turned into the faint remnants we can observe today. I and a number of other people aren't really sold on the idea of a singularity as the beginning of the universe. Einstein's general theory of relativity doesn't apply to the Big Bang, which is why it's called classical. It's based on an assumption that seems pretty obvious when you think about it. Each particle has a set position and velocity. If we know the positions and velocities of all the particles in the universe at a given moment, we can calculate what they would be at any other point in time. However, in the early 20th century, scientists found that they couldn't figure out what was going on at a really small distance. They just needed better theories. It turned out that there was a level of randomness in nature that no theory, even the best one, could rule out. This is reflected in the uncertainty principle that was proposed by German scientist Werner Heisenberg in 1929. It's not possible to measure the position and velocity of a particle with absolute accuracy. The more precisely we can pinpoint a particle's position, the less precisely we can determine its velocity, and vice versa. Einstein was strongly against the idea that chance rules the universe. He summed up his view in the well-known phrase, "God doesn't play dice, but all the evidence suggests that God is a gambler." The universe is like a giant casino where something happens every chance you get, like rolling the dice or spinning the roulette wheel. With every roll of the dice or spin of the wheel, casino owners risk losing money. But when you have a lot of bets, the odds even out, and the casino owner is confident that the overall result will be in their favor. That's why casino owners are so wealthy. If they want to win, they have to bet all their money on a few numbers in roulette or combinations of dice. It's the same in the universe when you consider the vastness of it all. There are lots of different ways the dice could roll. The good news is that the average outcome can be predicted. But when the universe is still small at the very beginning of its expansion, there are also only a few combinations. And that's where the uncertainty principle really comes into play. To understand how the universe came to be, we need to bring together the uncertainty principle and Einstein's general theory of relativity. It's a pretty challenging task for theoretical physicists. It has been 30 years and we're still working on it, but we're making progress. Let's say we want to predict what will happen to a particle in the future. We know a few things about its position and velocity right now. We can't say with certainty how its position and velocity will change in the future. All we can do is work out the likelihood of specific combinations of position and velocity. This gives us an idea of what the future of the universe might look like. Now, let's try to picture the past in the same way before the Big Bang. If we think of the universe as limitless, it doesn't make sense to ask what came before the Big Bang. It's like asking where south is at the South Pole. Since there's no way to measure time in this context, the idea of time is only relevant in our universe. Given the limitations of what we can observe today, we can establish the probability of a specific history for the universe. It's likely that the universe has had many different pasts, with each one having a different probability. There's a history of the universe in which England became world soccer champions again, though the probability of that is low. The idea that the universe has multiple versions of the past might seem like something out of a science fiction novel. This is a scientific fact, and it's all thanks to Richard Feynman, who worked at the highly respected California Institute of Technology and played bongos at street intersections in his spare time. To understand the nature of things, Feynman suggested that we assign a probability rating to each version of history and make predictions based on that. This approach works really well for predicting the future. We can safely assume that it works for constructing the past as well. Scientists are now trying to combine Einstein's general theory of relativity and Friedman's idea that the universe has many histories into one unified theory that will describe everything that happens in the universe. The unified theory will help us figure out how the universe will evolve. However, a unified theory won't tell us how the universe got started or what its original state was. It needs something else to go with it. We need to know what are called boundary conditions, which can explain what happens at the edge of the universe, at the edge of space and time. If the boundary of the universe is a regular point in space and time, we can go beyond it and say that the territory beyond is part of the universe. On the other hand, if the boundary of the universe has a zoo, an edge where space or time twists and the density is infinite, it'll be tough to define and interpret boundary conditions. So it's not yet clear what's needed for the boundary conditions. It doesn't seem there's any logical reason to choose one boundary condition over another. It's possible that the universe has no boundaries in space and time. At first glance, this seems to contradict the geometric theorems. They demonstrate that the universe must have a beginning of time boundary. However, scientists who tried to make sense of the phenomenon using math came up with a concept called imaginary time. It has nothing to do with the time we experience in real life. Imaginary time isn't constrained by any boundaries. It has nothing to do with the conditions at the boundaries. We've dubbed this a boundaryless proposition. If the universe has no boundaries in imaginary time, then it doesn't have a single history. There are lots of different ways the universe could have happened, and each of these will define a different version of events in real time. This means there are lots of different ways the universe could have happened, and it affects the choice of story or series of stories we end up living by. Of all the many plausible histories of the universe, we can immediately see that many of these don't involve the sequence of galaxy and star formation, which is a necessary condition for our own evolution. It's possible that intelligent beings could evolve without galaxies and stars, but it's unlikely. So, the fact that we exist and are intelligent means that we can ask why the universe is the way it is. This could be seen as a constraint on the story we live in. As it turns out, this is one of the minority of stories in which galaxies and stars exist. This is what we call the anthropic principle. He says that the universe must be pretty much as we see it because if it were different, there wouldn't be anyone around to observe it. Many scientists aren't keen on the anthropic principle because it seems a bit far-fetched and doesn't seem to have much predictive power. But the anthropic principle can be put into precise terms, which is important when we're talking about the origin of the universe. M-theory is our best bet for a comprehensive, unified theory. It allows for a lot of different scenarios for how the universe could have evolved. The majority of these histories are not viable for the development of intelligent life. They're either empty, too short, too strong and stilted, or unsuitable for some other reason. However, Richard Feynman's idea of multiple pasts means it's quite likely there are some uninhabited histories out there. To be honest, we don't really care how many histories there might be that don't involve intelligent life. We're only interested in the subset where intelligent life evolves. This intelligent life doesn't have to be human-like at all. It's also possible that little green men exist and are much more advanced than we are. We humans don't exactly have a reputation for being the smartest creatures on the planet. To grasp the logic behind this, let's think about the number of possibilities in the universe. It seems reasonable to assume that we live in three-dimensional space. To put it another way, we can define the position of a point in space using three coordinates: latitude, longitude, and altitude above sea level. Why is space three-dimensional? Why doesn't it have 2, 4, or any number of dimensions like in science fiction? In theory, space has 10 dimensions, including time. It's thought that 7 of the 10 dimensions are narrow and very small, while the other 3 are large and almost flat. It's like a cocktail straw. The surface of the straw is two-dimensional, but one dimension has been folded into a small tube, so from a distance the straw looks like one smooth line. Why do we live in a story with only 2 dimensions when there are actually 8? The animal will have a hard time digesting its food. If such an animal has its stomach inside, as we do, it will split the animal in two, and the poor thing will simply disintegrate. 2 flat dimensions just aren't enough to describe a phenomenon as complex as intelligent life. There's something unique about three-dimensional space. In 3 dimensions, planets can maintain stable orbits around their stars. This is because gravity follows the inverse square law, which was first discovered by Robert Hooke in 1665 and later refined by Isaac Newton. It's about the gravitational pull between 2 bodies at a certain distance. If you double the distance, the force of attraction is 4 times as strong. If the distance is tripled, the force of attraction should be divided by 9. If it's quadrupled, it should be divided by 16, and so on. This means that the planets stay in the same place in their orbits. Let's move on to talk about space with 4 dimensions. In this case, gravity follows the inverse cube law. If the distance between 2 bodies doubles, the force of attraction should be reduced by a factor of 8. If it triples by 27 or quadruples by 64. This reversal of the operation of the law of inverse squares means that the planets no longer maintain their stationary orbits. They'll either fall back to their star or escape into the cosmic cold and darkness. Similarly, the electrons in atoms will lose stability, and matter as we know it will cease to exist. So, if there are many stories and each one has 3 flat directions, it's only in stories with 3 flat directions that you'll find intelligent beings. It's only in these stories that we can ask why space has 3 dimensions. One fascinating aspect of the universe we can observe is the microwave background, which was first discovered by Arno Penzinski and Robert Wilson. This is basically the leftover electromagnetic radiation from a universe that was very young. It's distributed pretty evenly in all directions. The difference is about 1 integer and 100,000, which is pretty small and needs an explanation. The most widely accepted explanation for this uniformity is that at some point in the history of the universe, there was a period of extremely rapid expansion, at least 1 billion times. This process is called inflation, and it's actually beneficial for the universe. Unlike price inflation, which we often have to deal with, if this were the only thing going on in the universe, microwave radiation would be the same in all directions. How do the small differences come about? Quantum fluctuations are a result of the uncertainty principle. What's more, these fluctuations have given rise to all the structures in our universe, from galaxies and stars to us humans. The idea is basically the same as the so-called Hawking radiation from the horizon of a black hole. The final picture came together a little later. It took about 10 years for a space observatory in Earth orbit to detect fluctuations in the microwave sky in 1993. In other words, theory caught up with practice. 10 years later, in 2003, cosmology became an exact science when the first results were obtained from the double-chain spacecraft. It gave us a pretty amazing picture of the temperature of the cosmic microwave sky. It's like a picture of the universe from just a few thousand years after the Big Bang. The visible differences were predicted by inflation, and they mean that some areas of the universe have slightly more density than others. The stronger gravity in these dense areas slows down the expansion, which could eventually lead to a collapse and the formation of stars and galaxies. So let's take a closer look at the microwave sky map. It's a simplified representation of the universe's structure. We're the result of quantum fluctuations in the early stages of the universe. It seems that God plays dice. Today, the Dub-Temp instrument has been replaced by the Planck Space Telescope, which creates a much higher resolution map of the universe. The Planck telescope is really putting our theories to the test. It might even be able to spot the faintest traces of gravitational waves, which are also predicted by inflation. This would be the cosmic signature of quantum gravity. It's possible that there are other universes out there. The theory suggests that, from nothing, a vast number of universes could be created with a multitude of potential histories. Each universe has a lot of different potential histories and states in the present age and beyond. The vast majority of these states will have absolutely nothing in common with the universe we observe. We're hoping to see the first confirmations of the theory's hypotheses with the Large Hadron Collider and Charged Particle Accelerator, which operates at CERN near Geneva. From the perspective of the theory, it works at low energies. If we're lucky, we'll see at least the first hints that this theory is close to the truth. For instance, we'll likely find supersymmetries. I believe that the discovery of supersymmetry partners, or known particles, will significantly impact our understanding of the universe. In 2012, the Large Hadron Collider made an announcement. It had discovered a new particle called the Higgs boson. This was the first discovery of a new elementary particle in the 21st century. We're still hoping to find supersymmetries too. But even if it doesn't find any new elementary particles, supersymmetry might be discovered at a new generation of accelerators at the beginning of the universe, right at the moment of the Big Bang. It's the ideal high-energy laboratory to test the theory and our assumptions about how space, time, and matter came into being. There are different theories about how the universe came to be, so the results of physical research can tell us something. It's about unifying all the forces of nature. It's possible that other universes exist, but unfortunately, we'll never be able to explore them. We've learned a lot about how the universe came to be, but there are still two big questions that remain unanswered. Will the universe end? And is the universe unique? What are the most likely scenarios for the future of the universe? There are a number of ways in which intelligent beings could have come about. It all comes down to the amount of matter in the cosmos. If there's more than a certain critical mass, the gravitational pull of galaxies will slow down the expansion. Eventually, they'll start to collide and the universe will end in a big contraction. This will mark the end of our universe's history. If the density of the universe falls below a critical level, gravity will become too weak to prevent the galaxies from flying apart. Then all the stars will burn out, the universe will gradually empty out, and it will get increasingly cold. So everything will also come to an end, but in a less dramatic way. But we've still got a few billion years to play with. In this answer, I tried to explain a bit about how our universe came to be, what it's going to look like in the future, and what makes it tick. In the past, the universe was small and dense, like the nut I started with. But that nut contained everything that was happening in real time. So, as it turns out, Hamlet was right. We can think of ourselves as kings of infinite space, even though we're really just a small part of it. Is there other intelligent life out there in the universe? I'd like to throw out a few ideas about how life in the universe developed, and in particular, how intelligent life came to be. We've got to include the human race in this, but we also have to recognize that a lot of what we do is pretty unreasonable and not really designed for the survival of the species. I'd like to talk about two things: how likely it is that there's life in the universe, and what the chances are of life developing. It seems logical that the overall level of disorder and chaos increases over time. This observation has a scientific explanation. The second law of thermodynamics. This law basically says that the total amount of disorder or entropy in the universe is always increasing. The thing is, the law only applies to the total amount of disorder in a single organism. If the environment gets more disordered, order can increase. This is precisely what occurs with living things. We can define life as an ordered system that fights the tendency toward disorder and is capable of reproduction. In other words, it can create similar but not dependent ordered systems. To do this, the system has to turn energy that's already in a ordered form, like food, sunlight, or electricity, into disordered energy, which is heat. This means that the system meets the requirement of increasing the overall measure of disorder while at the same time increasing the level of order in itself and its offspring. A great example is the household of a young family. As the children are born, the household gradually becomes more chaotic for people like us. It's typically made up of two parts: a set of instructions that tell the organism how to act and reproduce, and a mechanism that enforces those instructions. In biology, these two components are known as the genome and metabolism. It's important to note that this isn't a biological phenomenon. A computer virus is a program that copies itself in computer memory and sends itself to other computers. For example, this fits right in with the definition of a living organism that I gave earlier. It's a degenerate form, like a biological virus, because it only contains instructions or genes and has no metabolism of its own. Instead, it reprograms the metabolism of the host computer or cells. Some people have asked whether viruses should be considered living things because they are parasites that depend on other living things for survival. But then, most life forms, including us, are parasites because they feed on other life forms. What do they need to survive? I think computer viruses should be considered a life form. Maybe this says something about the nature of humanity, since the only life form we've managed to create so far has been pretty destructive. And let's not forget the attempts to create life in our own form. I'll circle back to electronic life forms. The way we usually think of life is based on chains of carbon atoms with other atoms like nitrogen or phosphorus mixed in. It might be possible to create life on a different chemical basis like silicon, but carbon seems to be the best choice because it can form the most different types of chemical bonds. The fact that carbon atoms should be present everywhere with the properties they possess requires a lot of other physical constants to be just right. These include the quantum chromoscale, dynamics, electric charge, and even the number of dimensions of spacetime. If these constants are significantly different, either the nuclei of the carbon atoms will be unstable or the electrons will collapse on the nucleus. It's pretty amazing that our universe is so perfectly balanced. Maybe it means that this universe was designed for the emergence of the human race? However, we should be careful with this kind of argument because of the anthropic principle, which basically means that our ideas about the universe have to be compatible with our own existence. This is based on the most obvious truth. If the universe wasn't adapted for life, we wouldn't be asking why it is so finely tuned. The entropy principle is often divided between strong and weak entropy. The strong version assumes the existence of many different universes. Each one has different values for physical constants. For smaller values, these values allow for the existence of objects like carbon atoms, which act as building blocks for living beings. Since we're living in one of these universes, it's no surprise that the physical constants are so finely tuned. Otherwise, we wouldn't be here. So, the strong principle isn't really applicable here. What practical significance do the other universes have, then? What if they're separate from our universe? How could they possibly affect ours? I'm more inclined to agree with the weak entropy and principle. I accept the values of the physical constants as a given, but I want to understand what conclusions can be drawn from the fact that life exists on a given planet. Right now, 13 billion years after the Big Bang, when the universe was born, there was no carbon. It was so hot back then that all matter had to exist in the form of particles we call protons and neutrons. At first, there were as many protons as neutrons, but as the universe expanded, the number of neutrons fell behind. About a minute after the Big Bang, the temperature should have dropped to about 1 billion degrees, which is 100 times the temperature in the interior of the Sun. At that temperature, neutrons start to decay, creating more protons. If this were the only thing happening, all the matter in the universe would end up made up of the simple element hydrogen, whose nucleus contains a single proton. However, some neutrons bumped into protons, fused, and created the other simplest element, helium, which has a nucleus of 2 protons and 2 neutrons. But in the early days of the universe, heavier elements like carbon and oxygen couldn't have formed. It's tough to picture a living structure made up of nothing but hydrogen and helium. In any case, the young universe was still too hot for atoms to form molecules. The universe kept on expanding and cooling, but in some areas it was slightly denser than in others. This meant that the gravitational pull of additional matter slowed the expansion until it stopped altogether. As matter collapsed, it started to form stars and galaxies. This process started about 2 billion years after the Big Bang. It seems likely that some of the first stars were more massive than our Sun. The temperatures were also higher, which helped transform the original helium and hydrogen into heavier elements like carbon, oxygen, and iron. This probably took a few hundred to a million years. This led to some stars exploding as supernovas, spreading the heavier elements into space, where they became the building blocks for new generations of stars. We can't see if other stars have planetary systems because they're too far away. There are 2 ways we can detect the presence of planets in stars. The first thing we can do is follow the star and see if the light it gives off stays the same. If a planet passes between the star and an Earth observer, it will appear to outshine the star's light. If this happens regularly, it means the planet is orbiting the star. The second way is to get the star's position down to the nth degree. If a planet is orbiting a star, it causes a slight wobble in the star's position. If the star's position oscillates regularly, we can conclude that it has at least one planet. These methods were first used about 20 years ago. Thanks to these methods, we've discovered several thousand planets orbiting distant stars. Some calculations suggest that around 1 in 5 stars has an Earth-like planet at a distance that's suitable for life as we know it. Our solar system came together about 4.5 billion years ago, just under 9 billion years after the Big Bang. It formed from gas that contained the remnants of early stars. The Earth was mostly made of heavy elements, including carbon and oxygen. Somehow, the individual atoms were able to come together to form DNA molecules. This is the famous double helix that Francis Crick and James Watson discovered at Cambridge University's Cavendish Laboratory in 1953. The 2 chains of the helix are connected by a pair of nucleotides, which are also known as nucleotides 1 and 4, and they come in different colors, 1 guanine and 1 thymine. One in the first chain always binds to the other, while in the second, fire binds to earth. So, the order of the nucleotides in one strand determines the unique complementary sequence in the other. The 2 strands can be far apart, but each one acts as a template for making subsequent strands. DNA molecules can reproduce the genetic information that's stored in their nucleotide sequences. Some parts of the sequence can be used to produce proteins and other chemical compounds that can carry the instructions in the sequence and put together the raw materials for DNA. In terms of production, as I mentioned earlier, we don't know how DNA molecules came to be. The odds of DNA molecules forming by random combinations are pretty slim. Many people assume that life on Earth came from somewhere outside, For example, maybe it came from debris that fell off Mars at a time when the planets were still in an unstable state, or maybe the seeds of life were floating around in the galaxy. It's unlikely that DNA can survive long exposure to cosmic radiation. If the origin of life on a particular planet is very unlikely, it's still possible that it would take a very long time, and there should still be enough time for the subsequent evolution of intelligent beings like you and me before the sun opens up and engulfs the Earth. The window of opportunity for this to happen is determined by the lifespan of the sun, which is about 10 billion years. During that time, an intelligent life form would have to potentially master space travel to be able to move to another star. If we can't get off this planet, it's game over for us. The fossil record shows that some life forms appeared on Earth about 3.5 billion years ago. This was just 500 million years after the Earth had become stable and cooled enough for life to form on it. The universe had about 7 billion years to form life. There should have been enough time for beings like us to emerge and start asking questions about the origin of life. If there's only a tiny chance of life forming on a planet, why did it happen on Earth when there were so many other planets that could have hosted life? The early origin of life on Earth suggests that there's a good chance of life forming spontaneously in suitable conditions. Maybe there were simpler forms of organization first, which then led to the formation of DNA. The DNA that came about was so successful that it may have completely replaced the previous forms. We don't know what these forms were, but one possibility is RNA. RNA is similar to DNA, but it's much simpler and doesn't have the double helical structure. Short sections of RNA can replicate like DNA and gradually fold into DNA. We haven't been able to create nucleotides, let alone RNA. In a lab, you can make it from non-living material. It's been 500 million years since scientists first synthesized RNA and DNA in laboratories. Back then, the oceans covered almost the entire surface of the planet. It's still a possibility that RNA came about by chance. As DNA reproduction proceeded, there was a chance that random errors would occur. Many of these errors were harmful and led to the death of species. Some of these errors were neutral and didn't affect gene function. Some were beneficial to the survival of species and fell into the range of Darwinian natural selection. The process of biological evolution was initially very slow. It took about 2.5 billion years for the first cells to evolve into multicellular organisms. Over the following billion years, some of them even evolved, and some fish evolved into mammals. Since then, the pace of evolution has picked up. It only took 100 million years for the first mammals to evolve into what we know today. It's worth noting that the earliest mammals already had their own versions of the vital organs we have today. So, it just took a few tweaks for the early mammals to evolve into humans. The evolution of the human race has reached a critical stage that's as important as the development of DNA. It's about how we developed speech, especially written language. After that, we started passing information from one generation to the next in more ways than just genetically through DNA. Over the past 10,000 years, there have been several changes in human DNA due to biological evolution. But the amount of knowledge passed from one generation to the next has grown much more quickly. What's more, books can be updated and changed more quickly, which is important. It took several million years for us to evolve from the first humans to the first apes. Over that period, the useful information in our DNA has probably changed by a few million bits. If there's intelligent life out there somewhere other than Earth, it'll probably be similar to what we're used to, or it might look different. Is there intelligent life on Earth? If there is intelligent life out there, it's got to be pretty far away from us. Otherwise, it would have shown up on Earth by now. I believe we would have been made aware of the visit. It might resemble the film Independence Day. In theory, genetic engineering could extend the existence of DNA-based life forms indefinitely, at least 100,000 years. It's also much easier and already almost within our current capabilities to send mechanisms into space. These can be engineered to last long enough for interstellar travel. When they get to a new star, they can land on a planet with the right minerals to build new mechanisms that can be sent to even more distant stars. These mechanisms could evolve into a new form of life, one that's not based on macromolecules but on mechanical and electronic components. Eventually, they could replace DNA-based life, just as DNA has replaced earlier life forms. What are the odds that we'll bump into an alien life form as we explore the galaxy? If the timeline for the origin of life on Earth is correct, there should be quite a few stars with planets that have life on them. Some of these star systems formed about 1 billion years before Earth came into being. So why aren't the galaxies themselves full of controlled mechanical or biological life forms? Why hasn't anyone colonized or even visited Earth? Just my 2 cents, but I'm not convinced that UFOs are actually carrying alien beings. I think any alien visit would have to be pretty obvious and probably pretty unpleasant at the same time. So why haven't we had any visitors? It's possible that the odds of life forming naturally are so low that Earth was the only planet in the galaxy or even the observable universe where it could happen. There's another version of how these beings could have formed cell-type producing systems themselves. But most of these life forms haven't evolved to the point of becoming intelligent beings. We tend to think of intelligent life as an inevitable result of evolution. But is it really? The anthropologist's principle is a good reminder that we should be careful about making such claims. It's more likely that evolution is a chaotic process and that the formation of a mind is only one of many possible outcomes. It's not even remotely likely that intelligence is useful for long-term survival. Even if human activity wipes out all other life on Earth, bacteria and other single-celled organisms may remain. It seems that intelligence wasn't a likely path for life on Earth to take. It took a very long time, 2.5 billion years, for single cells to evolve into multicellular organisms, which are the building blocks of intelligent life. This is a pretty long time before the sun dies, which is consistent with the idea that it's unlikely that life forms will develop intelligence. If this is true, there might be other forms in the galaxy, but it's unlikely we'll find intelligent beings. There's another reason why life may not evolve to intelligent forms. For instance, a planet might collide with an asteroid or a comet. In 1994, we saw comet Shumiko-Levy collide with Jupiter. The result was a series of massive solar flares. It's thought that a relatively smaller body colliding with Earth 66 million years ago caused the extinction of the dinosaurs. Some small early mammals made it through, but it's likely that all the larger creatures, including humans, were wiped out. It's tough to say how often these collisions happen, but we can say with some confidence that they occur about 20 million years apart. If so, it would mean that intelligent life on Earth was formed by sheer luck, that nothing like this has happened in the last 66 million years. It's possible that other planets in our galaxy that have supported life may not have existed for as long as Earth has, without going through significant changes that could have led to the evolution of intelligent beings. The third option is that there's a good chance life will form and evolve into intelligent beings, but then the system will become unstable and intelligent life will destroy itself. This is a pretty pessimistic scenario, and I hope it doesn't come to pass. I'm inclined to agree with the fourth option. There are other forms of intelligent life out there in space, but we don't see them. The Blake Allison Project is monitoring the night sky with 2 radio telescopes. We're using the most sophisticated equipment. The project has great funding and is backed by thousands of hours of telescope time. It's currently the largest scientific program in the world aimed at finding evidence of extraterrestrial civilizations. Project Message is an international competition where participants create messages that might be considered by an advanced civilization. But so far, we haven't made much progress ourselves. We need to be careful about how we respond. Right now, meeting a more advanced civilization is like the first contact between the American natives and Columbus. I imagine the natives weren't too pleased about that encounter. Should we be looking into space? What's the point of going to space? How can we justify spending so much effort and money to bring back a few rocks from the moon? Is there not more we could be doing on Earth? The obvious answer is right here. It's all around us. Staying on Earth is like being stranded on a deserted island after a shipwreck and not trying to escape. We need to explore the solar system to find places that are suitable for humanity. It's kind of like what happened in Europe before 1492. I'm sure many people said that encouraging the Brotherhood of Columbus to throw money away. However, the discovery of the New World had a significant impact on the Old. Think about it. What would we do without the Big Mac? Our spreading out into space would have an even greater effect. It could have a huge impact on the future of humanity and even determine whether we have a future at all. It won't solve any immediate problems on Earth, but it will give us a different outlook and encourage us to look forward rather than back. Let's hope it will bring humanity together to solve common problems. This is a long-term strategy, of course. When I say long-term, I mean hundreds or even 1,000 years. In the next 30 years, we should be able to build a base on the moon. In the next 50 years, we'll be on our way to Mars. In 200 years, we'll be exploring the satellites of other planets. I'm talking about manned missions. Robotic rovers are already exploring Mars. We've already sent a probe to Titan, one of Saturn's moons. But if we think about the future of humanity, we need to get there ourselves. Space travel isn't cheap, but it'll only require a small fraction of the world's resources. NASA's budget has stayed pretty much the same in real terms since the Apollo missions, but it's shrunk from 3% of US GDP in 1980 to 0 and 1% in 2017. Even if we were to increase the international budget by 20 times to make space exploration a real priority, it would only be a small fraction of a percent of global GDP. Some people will say that this money would be better spent on problems here on Earth like climate change or pollution than investing it perhaps in this bill. On July 20th, 1969, Neil Armstrong and Buzz Aldrin touched down on the surface of the moon. This changed the future of humanity. The space race got people interested in science and helped speed up technological progress. The lunar expeditions inspired many modern scientists to pursue a career in science with the goal of learning more about us and our place in the universe. New perspectives have opened up for the world, offering a fresh way of viewing the planet as a whole. Since the last moon mission in 1972 and with no plans for more manned spaceflights, interest in space has declined. This happened at the same time as there was a general feeling of disappointment with science in the West. It had done a lot of good, but it hadn't solved the social problems that had been the focus of a lot of attention. A new manned spaceflight program could really help to get people excited about space and science again. Robotic missions are cheaper and probably provide more scientific information, but they can't capture the public's attention the way a manned mission would. And they don't take us back to space, which I believe should be our long-term goal. If we had a base on the moon by 2050 and a human landing on Mars by 2070, it could give the space program a boost and make it more meaningful, just like President Kennedy's announcement did in the early 1960s. In late 2017, Elon Musk announced that SpaceX was going to set up a base on the moon and launch a manned mission to Mars by 2022. And President Trump signed an order that told NASA to focus on space exploration and discovery again. So it's possible we'll get there before then. If there's a new interest in space, it could give science a boost in the eyes of the general public. The decline in the prestige of science has serious consequences. We live in a world where science and technology are essential. but fewer and fewer young people are going into science. A new and ambitious space program could get young people excited about science in general, not just astrophysics and cosmology. But is it possible for humans to live off Earth for extended periods of time? Our experiments on the International Space Station, ISS, show that humans can live and work away from Earth for many months. Of course, being in a state of weightlessness in orbit causes a number of unfavorable physiological changes. A planet or satellite could also provide the raw materials that an off-Earth community would need for a sustainable Earth-independent existence. Where in the solar system would be best for setting up human colonies? The most obvious choice is the Moon. It's conveniently located and relatively easy to access. We've already walked on the Moon and even rode a lunar rover. On the other hand, the Moon is on the small side, and it doesn't have an atmosphere or a magnetic field that reflects solar radiation like Earth does. It also doesn't have any liquid water. There might be ice in the craters at the north and south poles, which could be used to produce oxygen using nuclear power or solar panels. The Moon could be a base for further travel around the solar system. The next logical step is Mars. It's about 1.5 times farther from the Sun than Earth, so it gets about half as much heat. It used to have a magnetic field, but it disappeared for billion years ago, leaving Mars unprotected from solar radiation. This also led to the planet losing almost all of its atmosphere. This is now only 1% of Earth's, but it's possible that atmospheric pressure was higher in the past. We can get a sense of this from the traces of what we think of as cross channels and lakes. Right now, there's no way for water to be in a liquid state on the surface of Mars. In an almost total vacuum, it must evaporate. It seems reasonable to assume that there was once a warm, wet period on Mars. During this period, life could have arisen either spontaneously or as a result of sperm being brought in from somewhere in the universe. Now, there's no evidence of life on Mars, but if we find proof that it once existed, it'd be pretty likely that life could develop there. That said, we'll have to be careful not to bring terrestrial life to Mars. So we need to be careful not to bring Martian life with us. We're not immune to it, and it could destroy life on Earth. NASA has sent spacecraft to Mars on numerous occasions. The first was Mariner in 1964. In addition, various orbiters have explored Mars. The most recent is the Automated Interplanetary Station Martian Reconnaissance Orbiter. These vehicles discovered deep gorges and the highest mountains in the solar system. NASA also released a few probes, including 2 Mars rovers, onto the surface of Mars. They sent back pictures of a desert landscape similar to the one on the Moon. It looks like we could get water and oxygen from the polar ice caps here. There's been volcanic activity on Mars, which could mean there are useful metals and minerals on the surface that future colonists could exploit. The Moon and Mars are the best places in the solar system for establishing space colonies. Mercury and Venus are too hot, and Jupiter and Saturn are gas giants. Since Mars doesn't have a solid surface, its satellites are pretty small and don't offer much in the way of advantages over the planet itself. Some of Jupiter and Saturn's moons might be a good fit. What if we were to boldly venture beyond the solar system? Our observations show that a significant number of stars have planetary systems. At the moment, we can only see the giant planets like Jupiter and Saturn, but there's reason to believe that smaller Earth-like planets are also nearby. Some of these planets should be in the right zone for life to exist, which means they're at the right distance from their stars to have liquid water. There are about 1,000 stars within 30 light-years of Earth. If even just 1% of these stars have Earth-like planets in the life zone, that means we have 10 candidates for the New World. For instance, there's Proxima Mobi. This exoplanet is the closest to Earth, but it's still 4.5 light-years away. It orbits the star Proxy Macintosh in the Alpha Centauri star system. Recent research has shown that it has a lot in common with Earth. It's not possible to travel to these potential new worlds with today's technology. But who's to say we can't picture interstellar travel in the distant future? What if we're looking at 200 or 500 years from now? The speed of a rocket is affected by two things: the speed of the gases and the amount of mass lost during acceleration. The chemical rockets we currently use lose about 3 kilometers of gas per second. With 30% of its mass gone, the rocket can reach a velocity of about half a kilometer per second. That would then result in a decrease in speed. NASA estimates that the flight to Mars could take 260 days plus or minus 10 days. Some experts, though, say it could take as long as 130 days. At that rate, it would take 3 million years to get to the nearest star system. If we want to fly faster, we need to find a way to outgas much more quickly than chemical-fueled rockets can manage. And the best part is the light itself. A strong beam of light from the back can push a spacecraft forward. Nuclear fusion can provide about 1% of the energy needed to propel a spacecraft forward and accelerate it to about 1/10 the speed of light. If we want to go faster than that, we'll need to either use matter-antimatter annihilation or come up with a whole new form of energy. The distance to center alpha is actually quite a bit. To reach it within a single human lifetime, a spaceship would need to carry fuel with a mass equal to the mass of all the stars in the galaxy. Put simply, with the technology we have today, interstellar travel is not really feasible. It's becoming increasingly clear that we're entering a new space age. The first non-government astronauts will be pioneers. The first flights are really expensive, but I hope that over time, space travel will become more affordable for more people on Earth. Sending more and more people into space will give our existence on Earth and our role as stewards a whole new meaning. And it'll help us understand our role and future in space better. I really hope that our future is linked to space. The Breaking Star Shot is a great chance for us to start exploring outer space and seeing if it's a good idea to colonize it. The goal of this mission is to test and validate a number of conceptual ideas for spacecraft miniaturization. Star's light engine and phased array of laser emitters are also worth a mention. We're going to attach a fully autonomous space probe, just a few centimeters in size, to a light sail. The light sail is made of metamaterials and weighs less than a few grams. It's estimated that 1,000 of these probes, each with a light sail, will be put into orbit. On Earth, a group of lasers will be set up in an area of about 1 square kilometer. They'll direct a focused light beam, one with a power of tens of gigawatts, through the atmosphere, giving the sail the necessary acceleration. This fresh approach is reminiscent of Einstein's youthful vision of soaring on a beam of light. The probe would reach only 20% of the speed of light, which is still an incredible 160 million kilometers per hour. With this system, we could get to Mars in less than an hour and Pluto in just a few days. In about a week, it'll catch up to Voyager, and it'll be in the neighborhood of Alpha Centauri in just 20 years. Once it gets there, the probe will be able to take pictures of the planets in the system, check if they have a magnetic field and organic molecules, and use its laser beam to send information back to Earth. The signal will be picked up by the same laser system that sent it on its journey. It's thought it'll take about 4 years to get there. It's worth mentioning that probes might also pass close to Earth on their way. Such a planet is situated within the habitable zone of its host star, Alpha Centauri. In 2017, the project teamed up with the European Southern Observatory to step up the search for potentially habitable planets in the Alpha Centauri system. The BRICS Senior Project also has some additional objectives. For instance, there's solar system exploration and asteroid detection. They're crossing Earth's orbit. German physicist Claudio Gross came up with the idea of using these technologies to create a biosphere of single-celled microbes on temporarily inhabited exoplanets. In short, the possibilities are endless. However, there are still a few hurdles to overcome. A 1 gigawatt laser can only provide a few newtons of thrust, but the nanoprobe makes up for this disadvantage with its mass, which is only a few grams. The engineers have their work cut out for them. The probe has to be able to handle extreme acceleration, a vacuum, space cold, exposure to protons, and collisions with space dust. On top of that, it's really tough to focus a group of lasers with a total power of 100 gigawatts on a light sail because of the turbulence in the Earth's atmosphere. How can we link up hundreds of laser beams to make up for atmospheric interference? How can we get the probe moving without damaging it? And how can we make sure it's going in the right direction? On top of that, the probe has to stay operational in the cosmic cold for 20 years to send back signals that will take 4 light years to reach us. But these are engineering problems, and they tend to get solved over time. As technology improves, there are plenty of other missions that are just as exciting. Even with laser beams of lower power, it should take a lot less time to get to distant planets, the outskirts of the solar system, or even interstellar space. The age of space travel is on the horizon. What do you think it will bring us? I'm hoping that in the next 100 years or so, we'll be able to travel around the solar system, except maybe to the most distant planets. But getting to the stars will have to wait a bit longer. I figure we'll be able to visit some of the nearest stars in about 500 years. It won't be like Star Trek. We won't be able to travel at super fast speeds. It'll probably take at least 10 years to get there and back. Or it might even take longer. Needless to say, such space travel is not intended for humans. Even if we could build ships of the right size, it would be impossible to slow down. When we finally reach the galaxy, it'll be a huge moment for human culture. If the Bricks Russ Senior Project can find and image inhabited planets around one of our closest neighbors, it'll be a huge deal for the future of humanity. To wrap things up, let's circle back to Einstein. If we find a planet in the Alpha Centaur system, the image captured by a camera traveling at 20% of light speed will be a little distorted because of the effects described in the special partial theory of relativity. This is the first time a spacecraft will be able to reach this speed, which will allow us to see these effects. As it happens, Einstein's theory is at the heart of the mission. Without it, we wouldn't have lasers or the ability to make the calculations needed to navigate, photograph, and transmit data over 40 trillion kilometers at January 5th, the speed of light. We see the connection between the 16-year-old boy who dreamed of flying on a ray of light and our dream of flying on our own ray of light to the stars. We're on the cusp of a new era of human exploration of other planets. This is no longer just science fiction. The human race has been around for about 2 million years. Civilization got its start about 10,000 years ago, and it's been picking up speed ever since. If humanity makes it another million years, its future will be filled with colorful discoveries of the unknown. Could artificial intelligence end up being more advanced than us? And what about intelligence? The main thing that makes us human. All the things that make up our modern way of life are the result of human thought and creativity. DNA is like a blueprint for life that gets passed down from one generation to the next. More complex life forms get information from sensors like eyes and ears and process it in the brain or other systems to figure out how to act. Then they affect the world around them by passing the information to muscles, for example. At some point in our cosmic history, which spans 13.8 billion years, something pretty amazing happened. Information processing became so sophisticated that life forms developed consciousness. The universe woke up and became aware of itself. I think it's pretty amazing that we're just made of stardust and have come to understand our universe so well. I don't see a big difference between how an earthworm brain works and how a computer works. From my perspective, the theory of evolution suggests that there may not be a significant qualitative difference between the brain of an earthworm and the brain of a human. It stands to reason that a computer could theoretically replicate human intelligence or even exceed it. It's quite realistic to think that it could be more intelligent than its predecessors. As we evolved, we surpassed the intelligence of great apes, and Einstein turned out to be smarter than his parents. If computers keep following Moore's law and getting faster and more memory every 18 months, they'll eventually be smarter than us at some point in the next 100 years. When AI reaches the point where it can create even more advanced AI without human input, that's when we'll really see some serious progress. We might see a huge leap in intelligence that will lead to machines that are more advanced than us. Based on the evidence, if this happens, we'll have to make sure that the computer's goals align with ours. Some people might be tempted to dismiss the idea of highly intelligent machines as something that's just a fantasy of science fiction writers. But that would be a big mistake. In fact, it would be our worst mistake ever. Over the past 10 years or so, the topic of AI has been mostly about the problems of creating intelligent agents, systems that can perceive ideas. What's inside black holes? It's been said that facts are sometimes just fanciful fictions, and nowhere is this more true than with black holes. Black holes are pretty out there, even by the standards of science fiction. But they're a real, proven phenomenon in the scientific world. The first person to talk about black holes was a scientist from Cambridge named John Michell in 1783. His idea was that if you shoot a particle like a cannonball straight up, gravity will slow it down. Over time, the particle would stop moving upwards and start falling back down. However, if the initial vertical velocity is above a certain critical value, there's no way out. The force of gravity won't be enough to stop the particle, so it'll fly away. The escape velocity for Earth is over 11 kilometers per second, while for the Sun it's about 617 kilometers per second. Both are well above the speed of an actual cannonball, but they are low compared to the speed of light, which is 300,000 kilometers per second. So, light can leave both the Earth and the Sun pretty easily. However, Mitchell noted that there might be stars that are much more massive than the Sun, where the escape velocity would exceed the speed of light. We can't see them because the light they're escaping is pulled back by gravity. Mitchell dubbed them dark stars. These days we call them black holes. To understand them, we need to start with gravity. Einstein's general theory of relativity describes gravity, space, and time. Einstein came up with a series of equations that describe how space and time behave. He did this in just 15 minutes. They've been known as Einstein's equations ever since. Even though gravity is thought of as the weakest force in nature, there are two big advantages to this approach. First, it can act over long distances. The Earth is in orbit around the Sun, which is about 150 million kilometers away. The Sun orbits around the center of the galaxy, which is about 25,000 light-years away. The second advantage is that gravity is always positive, unlike electrical forces, which can be either positive or negative. These two characteristics mean that in a large enough star, the gravitational attraction between particles is so strong that it overpowers all other forces, leading to gravitational collapse. Despite all this, it took the scientific community a long time to figure out that massive stars could collapse on themselves because of their own gravity. They couldn't even imagine what these collapsed stars would look like. Albert Einstein even wrote a paper in 1939 where he said that gravity couldn't make a star collapse because matter couldn't be compressed any more than a certain point. Many scientists agreed with Einstein's gut feeling on this one. John Wheeler was a bit of an exception. He was a scientist in the US who can be seen as the main character in the story of black holes. In papers from 1960, He argued that many stars should eventually collapse and looked at the problems this would pose for theoretical physics. He also predicted what these collapsed stars would look like, in other words, black holes. For most of an ordinary star's life, which lasts for about 1 billion years, it resists its own gravity by thermal pressure. This creates a thermonuclear process that turns hydrogen into helium. But over time, the star's nuclear fuel runs out, and it starts to shrink. Sometimes it might stick around as a white dwarf, the dense remnants of a stellar core. However, in 1930, Jan Chunder proved that the maximum mass of a white dwarf star can't be more than 4 times the mass of the Sun. Soviet physicist Lev Landau came up with a similar mass limit. For a neutron star, what happens to an infinite number of stars that are more massive than the limiting mass of a white dwarf or neutron star? They're running out of nuclear fuel, so what's their fate? Robert Oppenheimer, who is often called the father of the atomic bomb, studied the problem. In a pair of papers he wrote with his students George Volkov and Hartley Snyder, Oppenheimer showed that these stars can't maintain the necessary pressure. Without pressure, a star must shrink to a point of infinite density. This is what scientists call a singularity. All our theories about space are based on the idea that spacetime is flat and basically flat. So, at the point of singularity where the curvature becomes infinite, it's not continuous. In other words, the singularity marks the end of space and time. This was met with strong opposition from Einstein. Then World War II happened. Most scientists, including Robert Oppenheimer, shifted their focus to nuclear physics, and the topic of gravitational collapse was largely overlooked. The subject was brought back into the spotlight with the discovery of distant objects called quasars. Yes, they are. The first quasar, which was given the number 3273, was discovered in 563. It wasn't long before many more were discovered. They were incredibly bright, even though they were a long way from Earth. It was clear that nuclear processes couldn't be responsible for this emission, since only a small portion of the mass is used to release energy. The only other option is that they're powered by gravitational energy and descent due to gravitational collapse. So, gravitational collapse was also discovered. When this happens, gravity pulls all the surrounding matter towards the object. It was obvious that a unified physical star would have to shrink to a point of infinite density, to a singularity. But what if the star isn't uniform and spherical? Could the uneven distribution of stellar matter cause an uneven collapse, which would avoid a singularity? In a pretty remarkable 1965 paper, Roger Penrose showed that even in this case, a singularity in a singularity occurs. This is because gravity is a force of attraction, and Einstein's equations cease to apply. This means that at a point of infinite density, it's impossible to predict what will happen next. This means that something pretty unusual must happen when a star collapses. We're not going to be affected in any way by this lack of predictability, unless the singularity is shielded from the outside. And Rose came up with the idea of cosmic censorship. All singularities formed by collapsing stars or other objects are hidden from the observer inside black holes. A black hole is a region where gravity is so strong that light cannot escape. It seems pretty safe to say that the principle of cosmic censorship is true, as there have been several attempts to disprove it and none have succeeded. In 1960, John Wheeler came up with the term black hole instead of how they form. The new term was quickly adopted. From the outside, it's impossible to know what's going on inside a black hole, regardless of what goes in or how it's formed. From the outside, it's impossible to tell what's going on inside a black hole. John Wheeler summed it up like this: black holes don't have hair. A black hole has a boundary called the event horizon. In this area, the gravitational force is strong enough to hold light and prevent it from leaving the black hole. Since nothing can move faster than light, everything else is also constantly being pulled back and unable to leave. Imagine canoeing at the Nanongar Falls. That's what falling through the event horizon is like. If you're far enough from the edge, you can paddle away from it if you paddle really fast. But once you're close to the cliff, there's no way to help yourself. The current picks up speed, but the canoe is pulled forward more than the stern. You're at risk of being swept away by the current. It's the same with black holes. If you enter a black hole with your feet leading the way, your legs will feel the brunt of gravity because they're closer to the black hole. This means that you will be stretched out and squeezed at the sides. If the black hole has a mass several times that of the sun, you'll be ripped apart and turned into spaghetti before you even reach the horizon. If the black hole has a mass of 1,000,000 times that of the sun, the gravitational force will act evenly on your whole body, so you'll reach the horizon without any problem. If you're planning to explore the insides of a black hole, it's probably best to choose a larger object. To give you an idea of what I'm talking about, there's a black hole in the center of our galaxy with a mass 4,000,000 times that of the sun. If you fall into a black hole, you won't notice anything. From the outside, there's no way to see your body pass through the event horizon. As you fall, the speed will slow down and you'll find yourself hovering outside. All you'll notice is the silhouette gradually becoming more blurred, taking on a reddish hue, and then simply disappearing from view. From the outside, it'll seem like you've disappeared forever. If the general theory of relativity is right and matter has a positive energy density, as it usually does, this means that the area of the event horizon or the boundary of the black hole must have a property that increases. When new matter or radiation enters the black hole, what's more, if two black holes collide and merge, the area of the new black hole's event horizon must be larger than the total area of the event horizons of the two original objects. The area theorem was tested in a real-world setting at the Laser Interferometer Gravitational Wave Observatory LIGO on September 14, 2015. This was done to verify the theorem using data from the collision and merger of two black holes. We can figure out the mass and momentum of the black holes from the shape of the gravitational waves. The no-hair theorem also lets us calculate the areas of horizons. It all started with nothing. It's hard to imagine, but around 13,800,000,000 years ago, there was what scientists call the Big Bang. Before this happened, there was no space or time at all. It's hard for us to imagine what it was like in that era because our minds are wired a certain way. We can't picture a world without space. If you think of something empty now, you probably think of empty space. Time is a bit of a tricky subject too. It's really tough to picture what it would be like to have no time at all. Without a past, present, or future, it's hard to imagine what that would be like. Time isn't stuck in one spot. It's just not around. But that's how it was supposed to be before the big event. This hard to imagine, but almost 14 billion years ago. At some point, there was a point so hot and small that our brains just can't imagine these quantities. But that doesn't stop us from trying to figure out how big it was, even though we can't really say for sure. If I had to describe the early universe, I'd say it was like a tiny little point. The universe was less than 1 trillion in size, and that tiny dot at the end of the sentence represents all the mass and energy of the observable universe we can see now. And you know what else? You couldn't even look at that point from the outside either, because there's already a whole other space outside of our cosmos there. All of the things that have ever been and will ever be in the universe we can see was inside this point. And then, something amazing happened. The point began to expand rapidly. We're still not sure where it came from. It's so beyond the limits of modern science. But we can already imagine how it evolved. We lovingly named the floor of the banking era after the German physicist Max Planck. He's lovingly regarded as the father of quantum mechanics. This hard to imagine, but at that time, The laws of nature as we know them didn't work. That's totally understandable when we remember that we're talking about a universe as small as 10 to the 35th power. The infinitely small and infinitely hot cauldron had a life of its own, unknown to us, but somehow it lived. It was a mystery to us, but we could tell it was alive. As the universe continued to grow and expand, something amazing happened. The fundamental laws of the universe began to emerge, and we get to study them. These laws weren't written by anyone. They just are. They're just there, and there's no getting around them. They're woven into the very fabric of our cosmos. You could even call them primary laws, if you like. The first law that came out of the young universe's creative mind was gravity. It wasn't long after gravitation was given its legal status that two more laws of weak, and strong nuclear interaction were added to the tablet of laws. However, there's a good case for saying that they were originally combined with gravitation. A little later on, the electroweak interaction was split into two parts, electromagnetic and weak nuclear interactions. Since then, our world has been shaped by four laws and four fundamental forces. The weak nuclear interaction is the one that makes radioactive things decay. The strong nuclear force is what keeps the atomic nucleus together. The electromagnetic force is what allows atoms to interact with each other. And gravity is what makes matter stick together. The universe had a beginning, just like everything else in this big, beautiful world of ours. It's not quite right to say that it appeared at some point, because time is tied to the interior of the universe. But from our perspective, it came into being at some point in the distant past. The universe isn't eternal, sweetheart. It wasn't always there. And that can make you think, what came before it? Have you ever wondered why it came into being? I'd love to know what forces, if any, made it appear. These questions are so intriguing. They make us all want to know the answer, don't they? Could it be that someone or something else is responsible for this complex process? I truly believe that everything in this world has a reason, but as history shows us, over time, such an answer doesn't matter as much as it used to. People used to think that the sun and moon rose above the horizon because someone was responsible. It's easy to see why they might have thought that. A whole pantheon of wonderful professionals. We all have a part to play in our jobs, and that's what makes us special. Someone helps the sun rise, someone helps grow grain in the fields, someone causes the tides and deadly storms and sailors. Even these characters had their own problems. They also interacted with people, which was really lovely. And that's the most important thing of all. They could be influenced, which meant they could affect the laws of nature, which was really quite nice. But then we found out that the sun rises at dawn, not because of the rushing chariot of fire, but because our planet rotates around its axis. And the tides are caused by our lovely moon, which moves across the sky all by itself. It's actually pretty simple to calculate the trajectories. As our clever minds grew and we learned more and more, there was less and less room in our world for higher forces to have an impact. So, the big question on everyone's mind is, why did it all come to be? You might say it's the final fundamental question. So, the physicists can't answer this one, which just goes to show there's still more to discover. So, it's totally okay if physicists don't know something yet. It just means we get to wait a little longer. I'm not saying that we'll definitely find the answer, but I'm really hopeful that we will. After all, we're right here inside the universe, and we can't go outside it just yet. Just a quick note. Don't forget the word, yet. I'd love to know what's going on in your daily lives right now. Can you believe that 100 years ago, this would have been considered impossible? Just think about all the appliances and devices we use every day. They would have blown the mind of any human being in the foreseeable past. It's so exciting to think about what might be in 10, 20, or even 30 years. It's impossible to know or imagine what amazing discoveries we'll make. As for the structure of our world, it's totally okay if we don't know everything. There's no need to breed superfluous entities that so conveniently explain everything. They make the universe seem simple and less amazing than what already surrounds us, which is a shame. Let's go back to the growing universe, shall we? The little dot just keeps on growing. Since the very beginning, 1 lethal second has passed. At this point in time, there is only light, namely photons. The universe was so hot that photons, being both a wave and a particle, were free to transform into pairs of matter and antimatter particles. Then, they collapsed back into a photon. In a way, we are all the laws of the server energy of that first beginning. Since matter and energy are basically two sides of the same coin, Einstein came up with a really cool equation that shows how much energy matter has. It's called E equals the square of the speed of light. If it's completely empty of energy, that's okay. Guess what? Every particle in the world can have its twin, not a particle. Did you know that quarks, which make up protons and neutrons, or photons such as electrons and neutrinos, have antiquarks and antineutrinos, respectively? And guess what? There's a positively charged opposite of the negatively charged electron. It's called a positron. Bosons are a special kind of particle that help other particles interact with each other. Take the photon, for example. It's just such a particle. Isn't it funny that the quarks that make up protons and neutrons in the atomic nucleus can't exist alone under normal conditions? They just love to be in pairs or trios. If you were to pull apart a pair of quarks using a special method, you'd find that the more you pull, the more they'll be attracted to each other. This is now believed to be the case. Meanwhile, there are more and more special particles between them, which allows the quarks to interact. But at some point, it'll be more profitable for the universe to just make a new quark. Instead of pulling the old, they'll just disappear. And now you'll have two pairs of quarks. Each old quark will gently take hold of the handle of its new neighbor. When we start to think about the really small building blocks of matter, it can be a bit confusing because the laws of logic we're used to no longer work. And this is where we can start to make sense of the void. In the earliest moments of the universe, it seems like it was a big, bubbling cauldron of quarks and plasma. That is, the quarks couldn't form any pairs, but they just bubbled together in a single, freely moving mass. And, as if that wasn't amazing enough, another 1 million in our universe continues to appear as matter and antimatter. But for some reason we don't know yet, there were 1,000,000,001 particles of matter for every billion particles of antimatter. This imbalance led to something really interesting. It meant that matter began to become more and more compared to antimatter. When they met, matter and antimatter would annihilate each other, turning into nothing and releasing energy according to the equation I equals the square of the variable x. If there were no such imbalance, there would be no universe as we know it. If that had happened, all its components would have ignored each other, leaving only a flash. But sadly, this injustice did happen. In fact, physicists now call this paradox the ionic asymmetry of the universe. As of now, there isn't a known explanation for this phenomenon. Oh well, we'll just have to wait and see. Matter and antimatter are really quite the opposite of each other, aren't they? They react very violently with each other. It's truly fascinating to see how 1 kilogram of antimatter and 1 kilogram of matter interact. They release approximately 1.8 times 10 to the 17th power joules of energy, which is equivalent to the energy released in a 42% explosion. That's 6 parts of 100 megatons. Guess what? The most powerful nuclear device ever detonated on the planet is called the Tsar Bomba. It weighs a whopping 26.5 tons. When it's set off, it'll be like releasing about 58.6 megatons of energy. So, if you suddenly meet yourself, which is made of antimatter, don't worry, It's not a bad thing. It's just that you'll be hugging a very hot person. Oh, and just so you know, if you still think antimatter is something only physicists can make happen, I'm afraid I'll have to burst your bubble. Guess what? Antimatter can be created in a laboratory, which is what some physicists do. The thing is, the resulting product is very expensive. NASA estimates that 1 milligram of positrons will cost $25 billion, and for 1 gram of antihydrogen, you'll have to shell out 62.5 trillion American currency. Of course, no one needs antimatter in such quantities, especially since it is very inconvenient to store it. The good news is that positrons are still okay. They have a positive charge, which means they can be magnetically trapped so they don't collide with ordinary matter and slam its flares. But antihydrogen is a whole other story. It's a molecule that's electron neutral, so it can't be trapped in a magnetic trap like the others. So, physicists have to sit around and guess how to effectively store antimatter. It's the priciest substance on our planet. So, we still need to store it because we can only check certain properties of matter on a large amount of it. Take gravity, for instance. It's so interesting. Antimatter also has anti-gravity properties, which means it will repel from our planet. Oh my, they're attracted. Ideally, this wouldn't happen. We'd love to see macro amounts of antimatter behave exactly the same as ordinary matter. It would be so cool if there were whole regions in the universe made up of antimatter galaxies, planets, and stars that behave exactly the same way as their ordinary, familiar counterparts. But we just don't know that yet. We can only guess at why they're not there. I think we can all agree that this is a consequence and a clear knowledge. If an antimatter star and an ordinary star collide, it would be an incredible sight to behold. The power and energy outburst of such a collision would be so immense, it would exceed the luminosity of all stars in hundreds of millions of galaxies. If such a thing had ever happened anywhere, we would probably see evidence of it. But there's no evidence of that, sadly. So, if you look at the sky through a telescope and see another galaxy, it will be made up of ordinary matter. It's also worth mentioning that these kinds of details are usually left out of the picture in science, but everyone remembers them. Just because we can't see it doesn't mean it's not possible. It's possible that somewhere in the vastness of the cosmos, there are huge deposits of antimatter just waiting to react with ordinary matter. And we'll get to see it happen. It's such a magnificent sight, but that's the last thing we'll see, my friend. This gamma-ray burst will unfortunately wipe out a huge area of space around the reaction center, including our planet. It'll be a truly gorgeous sight, but it won't last. The universe just keeps on growing and getting cooler. Quarks start to join together, and then protons and neutrons appear. These combine to form the nuclei of future atoms. The universe is now full of matter, most of which is hydrogen 90% and helium 10%, which is pretty amazing if you think about it. There's still some deuterium, tritium, and heavier forms of hydrogen and lithium, but it's still too early to count them. For the next 380,000 years, not much happened. Oh, but that's not all. All that time was filled with different processes. We're still chatting about the birth of the universe, but it was a pretty stable period. The electron was still moving freely through space at a high enough temperature, bumping into photons here and there as it went. If you were there in that moment, imagine you had the means of protection. You would see nothing but the sparkling and opaque milk of space. Photons wouldn't be able to enter your eyes freely because they'd be blocked by electrons from the surrounding space. Once the temperature of space dropped below 3,000 degrees, which is about half the surface temperature of the sun, something pretty cool happened. Electrons started getting trapped in atomic nuclei. The universe was flooded in beautiful, glorious light. And so, the period of matter formation came to a successful close. Oh, and guess what? This amazing period, which left us with the cosmic background we can see today, we can actually measure by those leftover photons that got free from the pesky electrons and only now reached us. After a billion years of traveling through the expanding universe, the photons that were in the visible part of the spectrum stretched themselves along with it and moved into the microwave range. Isn't it amazing that we can still register the events of those times by the residual cosmic microwave radiation? Someday, our friends in physics will write about relic radio wave radiation, which is even lower on the spectrum. But don't you worry, that will happen very soon, maybe in a few tens of billions of years. But will there be physicists in those times? I hope so. It's been a billion years now since the universe started to expand and cool down. The matter created from primary energy, which is mostly hydrogen, is starting to come together into groups that we will eventually call galaxies. In the vastness of the universe, galaxies are the main characters on a cosmic scale. It's not really possible to think about smaller objects, is it? Hydrogen is the building block of the universe, the very foundation on which everything is built. It's the simplest, and that's a good thing. There's one proton and one electron hanging out with this proton. And the hydrogen atom looks a little different from what we're used to seeing on the internet. If you were to ask someone how they imagine an atom, they'd probably tell you about the nucleus and the electrons whizzing around in their orbits. The truth is, things are actually pretty fascinating. The electron is a fascinating thing. It's both a particle and a wave, which means it's sort of smeared across the structure of our spacetime in the form of a cloud surrounding the atom. And when atoms interact with each other, they touch electron clouds, and the interaction happens at that level. It's pretty amazing when you think about it. When you're standing on the floor in your house, it's like the electrons in your feet or shoes are touching the electrons in the floor. But there's no interaction because then you just grow into the floor. So when you're standing on something, you're actually on a micro level, which is pretty cool. Levitin. Oh, there you are. And you've never actually touched any object in the way we usually mean when we say touching. So, anytime you make an impact with something, it's actually electrostatic repulsion between the negatively charged shells of the atoms in your body and the electrons in your surroundings that have the same charge. And guess what? You're actually prevented from falling through the floor by one of the fundamental forces that appeared in the early universe, namely electromagnetism. The tiniest particle that carries electromagnetism is the photon. It's a particle of light, my friend. It's so interesting to think that everything around us is filled with light. It's light that keeps everything together. And we're made of light too. It's so wonderful to be able to draw beautiful conclusions from our knowledge of physical laws. Meanwhile, in our vast universe, there's a huge amount of gas that's starting to collect from its own mass. If you have mass in our world, you also have gravity. When you look up at the sky on a rainy day, or maybe not so rainy, you see clouds. Clouds are just water vapor, my friend, and that vapor can weigh hundreds of tons. It's pretty much the same situation in space too. It's truly amazing how any cluster of gas, when we see it on such a large scale, has such enormous mass and therefore gravity. Some parts of the cloud have more gas, some less, and as you can imagine, areas with a higher concentration of gas start to attract those that are more charged. Eventually, the gas begins to gather around one point, thicken, and form a ball. But here's the catch. For this ball to gain full strength through the process of thermonuclear fusion, it needs to have a certain mass. And then, sadly, it ends up as a miserable brown dwarf. But wait, if the scale is even smaller, this cluster of gas could even become a gas planet like Jupiter. If there's enough mass and the pressure inside is just right, hydrogen atoms start fusing with each other to form helium atoms. And that's how stars are born. This is also how our beautiful sun came into being about 4.5 billion years ago. Have you ever wondered why a star shines? It's not because of a chemical reaction or a nuclear decay reaction going on inside it. It's truly amazing how through many transformations, for nuclei of hydrogen atoms can combine with each other through thermonuclear fusion. During this interaction, some of the protons are converted into neutrons, which is really fascinating. And lots of other good stuff is made along the way, including helium. Over time, the star uses up all the energy it has stored in the mass of hydrogen that it is made of. One of the byproducts of this unusual process are some pretty tricky particles called neutrinos. Let's take a quick trip down history lane to better understand what we're up against. Back in 1930, some clever folks started to think that neutrinos might exist. They were trying to figure out why radioactive decay was happening. James was one of them. He noticed something interesting. When atoms lose an electron in beta decay, the lost electrons have different energies. This shouldn't be the case, but it was a start. If the law of conservation of energy is true, then electrons should all have the same energy, right? Well, unless someone takes that energy away from them. Wolfgang Pauli had a brilliant idea to save the law of conservation of energy. He proposed a new particle that would play the role of a thief in the process. And so, for the first time, we were thrilled to announce the existence of a new, previously unknown Hubble particle. I really tried my best to save both statistics and the law of conservation of energy. I think there's a good chance that there are electric neutral particles, which I'll call neutrons, in nuclei. They have spin, which is pretty cool. I'm so excited to share this with you. Is a half-continuous beta spectrum. I think it would make sense if we assumed that in decay, the neutron also descends along with the electron. So, the total energy of the neutron and electron stays the same. I know it might seem a bit far-fetched at first, but I really do think there's a chance it could work. But you can't win without taking a chance. I'll point that out. Guess what? Neutrons ended up being the name of another particle that was soon discovered. Neutrons and protons work together to form the nuclei of atoms. Guess what? Back in 1933, the brilliant Italian Enrico Fermi predicted particles that we now know as neutrons. In Italian, it's called a neutrino, which is a little bit of a play on words since it means neutron chick. All that's left to do is find these particles. It's truly amazing to think that every second, about 60 billion neutrinos pass through an area of just 1 square centimeter on Earth. But here's the tricky part. They're really hard to spot because they don't interact with matter. To catch these elusive particles, some pretty impressive structures have been built. A research station was built very close to the South Pole with the hope of catching neutrinos flying to Earth from the Sun. All of these stations are built deep underground or under the ice so they don't get in the way of cosmic rays. Neutrinos are pretty good at reaching these depths, and they often zip through the planet without even touching a single atom. It's really quite incredible how big neutrino search projects are. The IceCube Observatory is almost 3 kilometers deep. 5,000 plus sensors are nestled in ice that's been around for centuries. The pressure at depth is so high that even the tiniest air bubbles are pushed out, leaving the ice crystal clear. Even though it's a small probability, there's still a chance that a neutrino from the sun will collide with an atom in the ice. When this happens, the sensors pick up a tiny flash of light that comes with it. It's not often that such flashes occur, with only a few happening each year. You'll find similar facilities in deep mines, too. The Power Line Snow Laboratory is a great example. It's located 2 kilometers deep in a nickel mine. The researchers go down there together with the miners, but the miners get out of the elevator first. The scientists go down even deeper. Then they walk a little ways, about 1.5 kilometers, through a tunnel that's a bit dirty to get to the scientific complex. It's so reminiscent of the movie Resident Evil. Once they've had their adventure, they head into a special clean area where they take a shower, change into fresh clothes, and get rid of all the little particles that might have stuck to them. I'd like to give you an example of such facilities. There's a neutrino and supermyocardium detector in Japan, where at a depth of 1 kilometer in a zinc mine, they register neutrinos after the explosions of distant supernovae. It's pretty amazing when you think about it. Every second, countless tiny particles from exploding stars pass through your body. You don't even notice them. They zip right through your body without touching a single atom. But they're there, you know. As they say, you see the gopher and I don't see the gopher. And there it is. Let's go back to our lovely little universe. Shall we? Have you ever wondered how galaxies form? It's really quite fascinating. A cluster of stars in space comes together to create these incredible cosmic structures, which also have their own unique forms of life. They come in all shapes and sizes, and they're all so beautiful. It's truly mind-boggling to think that there are about 2 trillion galaxies in our observable universe. It's hard to say exactly how many galaxies there are, but estimates range from 1 to 2 trillion. Each galaxy is home to about 100 billion stars. It's so interesting how smaller galaxies swirl around bigger ones. They must be waiting for the bigger galaxy to eat them. Our galaxy is called the Milky Way because, from our point of view, it looks like milk spilled across the sky. Isn't that lovely? Our galaxy also took part in the act of cannibalism once, swallowing a small neighbor. You can still see the remains of this small galaxy in the form of a stream of stars in the area of the constellation Sagittarius. And this is where our galaxy's amazing journey begins. It and the well-known Andromeda galaxy are getting closer together by 100,000 kilometers every second. So, in about 4 billion years, the 2 galactic systems will collide. When this happens, it's likely that one big, beautiful galaxy will be formed. It's even possible that our solar system might be thrown into the vastness of the galaxy by some pretty strong gravitational forces. But don't worry, the sun and planets are probably going to be just fine. I wonder if there will be other intelligent beings in our galaxy at that time to witness this incredible process. Or maybe there'll be some lovely life forms in the Andromeda galaxy. Who knows? After all, galaxies are the main characters in the cosmos. The lovely physicists decided to crunch some numbers and figure out the total gravity they create. And it turns out that the gravity they read can't be explained by the visible matter of galaxies, which is a bit of a surprise. Have you ever looked up at the night sky and seen a lone star on the outskirts of its galaxy or outside of galactic space? It's truly a fascinating sight. It's so interesting. It seems like something is pulling them and providing the high speed of their motion. The most common concept today is that 85% of the gravity of the universe is provided by invisible matter. Isn't that fascinating? Dark matter is a substance that does not participate in any electromagnetic interaction. It's truly amazing to think that all we can see is the vast number of galaxies and the stars within them contribute only 15% to the observed gravity. The vast cosmic oceans are mostly made up of something that looks like nothing to us, but it has gravity, and it's pretty amazing. There are so many fascinating theories about what this dark matter could be. Who knows? Maybe it's not a substance at all, but some pressure from forces in parallel dimensions. But who knows? It might turn out to be something much more down to earth. This is especially interesting because scientists have even discovered galaxies without dark matter. But think about it. We've gotten to the point where physicists are seriously discussing the possibility of parallel realities. And the wonderful thing is, the laws of physics allow it. I think it's absolutely amazing. But that's not all. The universe is always on the move, growing and expanding. It's been going on since the beginning, and it's going to keep going. The amazing truth about this phenomenon was first revealed way back in 1929 by the wonderful Edwin Hubble, who we now know as the namesake of the famous telescope. The go-to source for desktop wallpaper. he noticed something really interesting. The further away another galaxy is from our galaxy, the faster it is moving away from us. The universe is growing in all directions, just like you'd inflate a balloon and watch its surface stretch. And so, some mysterious force is making our universe expand at an ever faster rate. This mysterious force is now called dark energy. Dark matter and dark energy are named that way because they're not actually dark. It's just that we don't know much about them, so they seem mysterious and a little bit dark. We're still learning about them. Dark energy plays an even bigger role in our universe than anything else. It's truly amazing to think that 68% of the total mass of energy in our vast and mysterious cosmos belongs to it. 27% is dark matter, and only 5% is what we're all familiar with. To figure out how fast something is moving, we have to get a little creative. One such trick is the Doppler effect, which was discovered by the Austrian physicist Christian Doppler in 1842. If something is moving and sending out light, then it makes sense that the faster it's moving, the higher the frequency of the waves it's sending out, and the shorter the wavelength. If the object is moving away from us, then the wavelength should increase and the frequency should decrease. And guess what? This works for any waves, too. Whether it's light waves, sound waves, or any vibration, this trick works for them all. If you know what kind of waves an object should be emitting, and it's emitting waves of a different frequency, it's probably moving towards you or away from you. It's so interesting how Pierre first tested this effect. In 1845, he came up with a pretty cool experiment. He estimated the displacement on a frequency scale of sound from an orchestra playing on a platform attached to a steam locomotive. His assistants, who had perfect hearing, estimated the pitch of the tune depending on whether the steam locomotive with the orchestra was approaching or moving away. It's so interesting how scientific experiments are different, but in space, due to the vast distances involved, this effect changes to a similar one. It's called cosmological, and it's really cool. Redshift is a fascinating phenomenon. It's like we're seeing the universe trying to run away. It's pretty amazing when you think about it. No matter where you are in the universe, the rest of it is moving away from you. So, no matter how you look at it, the world is moving away from you. It's like you're right in the center of it all. It's really quite lovely to feel like you're the center of the universe, isn't it? Even if the rest of it is trying to run away from you and at the same time constantly accelerating, it's still a pretty amazing feeling. It might sound a little strange, but this happens in every part of space. It might be hard to believe, but all the points on the coordinate plane are actually running away from each other. At the same time, each point in space thinks it's the center of everything, not because the points are moving, but just because the coordinate plane is expanding. It's so sad, but everything that isn't part of the Milky Way will eventually get so far away that we'll lose sight of it. And there's more. At some point, since the expansion is accelerating, external objects relative to our galaxy will move away from it faster than the speed of light. That means the light from them will never reach us again. The laws of physics say that motion can't exceed the speed of light. But here's the catch. These laws are based on the assumption that space is static. When space itself is expanding, as it is now, it's like the rules of physics are changing. It's like motion at higher speeds is suddenly possible. If we imagine a planet within our galaxy in these distant times, the folks there will look up at the sky and see only the remnants of what we used to call the spilled milk of the Milky Way galaxy. There won't be anything else up there in the sky. The only stars you'll see will be ones with less than 0.2 solar mass. The more massive stars at that point will have already completed their lives and extinguished themselves. The stars within other galaxies that these beings will never recognize will also have died out. Even the light of these stars, which is the fastest thing in our world, will not have time to reach their planet. That'll happen in about 1 trillion years, my friend. A vast, endless expanse of darkness. They'll never know what came before, how their universe came to be, or that there are 2 trillion other lonely galaxies just like them. Just stop for a moment and think. What if we are those beings, living in an age when some phenomenon, some clue to our world, cannot reach us because it is too late? We'll never know the answer because the results of that key event are already too far away and too long ago. But let's not be sad, okay? With the same probability, we can even exist in that most infinite and happy era, when we have an opportunity to open all the cards with the secrets of our world and understand everything that our mind is capable of understanding. Of course, it's important to remember that our brains are still a work in progress, used to the three-dimensional space we're used to. But at the beginning, there was nothing at all. It's hard to imagine, but about 13,800,000,000 years ago, there was what scientists call the Big Bang. Before this happened, there was no space or time at all. It's hard for us to imagine what that time was like because our minds just aren't wired that way. We can't even imagine what it would be like to live in a world without space. If you think of something empty now, you probably think of empty space. Time is a bit of a tricky subject too. It's really tough to picture what it would be like to have no time at all. Without a past, present, or future, it's hard to imagine what that would be like. Time isn't stuck in one spot, it's just not around. But that's how it was supposed to be before the big event. It's hard to imagine, but almost 14 billion years ago, at some point, there was a point so hot and small that our brains can't even begin to imagine what it was like. But that doesn't stop us from trying to figure out how big it was, even though we can't really say for sure. If I had to describe the early universe, I'd say it was like a tiny little point. The universe was less than 1 trillion in size, and that tiny dot at the end of the sentence represents all the mass and energy of the observable universe we can see now. And you know what else? You couldn't even look at that point from the outside either, because there's already a whole other space outside of our cosmos there. Guess what? Everything that has ever been and will be in our observable universe was inside this point. And then, something amazing happened. The point began to expand rapidly. We're still not sure where it came from. It's so beyond what we can understand with our modern science, but we can just imagine how it evolved, can't we? From the moment it first appeared to 10 seconds in that's 10,000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, 000, we thought it would be a lovely idea to name the half of the banking era in honor of the German physicist Max Planck, who we all know as the father of quantum mechanics. This is hard to imagine, but at that time, the laws of nature we know did not work. It's totally understandable if we remember that we're talking about a universe as small as 10 to the -30th degree of a meter. The tiny, scorching cauldron had a life of its own, a mystery to us, but somehow it did. As the universe continued to grow and expand, it eventually made its way through this era. And then, something amazing happened. The fundamental laws of the universe began to emerge, and we got to study them. These laws were never written down, but they're there for us to discover. It's not like we can beat them or get around them. They're woven into the very fabric of our cosmos. You could even call them primary laws, if you like. The first law to come into being in the young universe was gravity. It wasn't long after gravity was established as a legal entity that 2 more laws appeared on the tablet: the weak and strong nuclear interactions. However, there's a good chance that they were originally combined with gravity. Even a little bit later, the electroweak interaction split into the electromagnetic and weak nuclear interactions. Since then, these four laws and the four fundamental forces have been there for us, guiding our world. The weak nuclear interaction is the one that makes radioactive things decay. The strong nuclear force is like a glue that holds the atomic nucleus together. The electromagnetic force is what allows atoms to interact with each other, and gravity is what makes matter stick together. The universe had a beginning, just like everything else in this big, beautiful world of ours. It's not quite right to say that it appeared at some point, because time is tied to the interior of the universe. But from our perspective, it came into being at some point in the distant past. The universe isn't eternal, sweetheart. It wasn't always there, and that can make you think, what came before it? Have you ever wondered why it came into being? I'd love to know what forces, if any, made it appear. These questions are so intriguing. They make us all want to know the answer, don't they? Could it be that someone or something else is responsible for this complex process? I truly believe that everything in this world has a reason, but as history shows us, over time, such an answer doesn't matter as much as it used to. People used to think that the sun and moon rose above the horizon because someone was responsible. It's easy to see why they might have thought that. A whole pantheon of wonderful professionals. We all have a part to play in our jobs, and that's what makes us special. Someone helps the sun rise, someone helps grow grain in the fields, someone causes the tides and deadly storms and sailors. Even these characters had their own problems. They also interacted with people, which was really lovely, and that's the most important thing of all. They could be influenced and thus affect the laws of nature, which was really quite nice. But then we found out that the sun rises at dawn, not because of the rushing chariot of fire, but because our planet rotates around its axis. And the tides are caused by our lovely moon, which moves across the sky all by itself. It's actually pretty simple to calculate the trajectories. As our minds grew and our knowledge grew, we found ourselves with less and less space in the world for the influence of higher forces. So, the big question on everyone's mind is, why did it all come to be? You might say it's the ultimate fundamental question. So, the physicists can't answer this one, which just goes to show there's something else out there. It's okay. The fact that physicists don't know something is just a reason for us to keep learning. Just a little more waiting, my friend. I'm not saying that we'll definitely find the answer, but I'm really hopeful that we will. After all, we're right here inside the universe, and we can't go outside it just yet. Just a quick note to say, yet, I'd love to know what's going on in your daily lives right now. Can you believe that 100 years ago, this would have been considered impossible? Just think about all the appliances and devices we use every day. They're pretty amazing, right? They would have blown the mind of anyone from the foreseeable past. It's so exciting to think about what might be in 10, 20, or even 30 years. It's impossible to know or imagine what amazing discoveries we'll make, including ones about the structure of our world. It's okay not to know everything. There's no need to create superfluous entities that conveniently explain everything. They just make the universe seem less amazing than it already is, don't they? Let's go back to the growing universe, shall we? The little dot just keeps on growing. Since the beginning of time, one deadly second has come and gone. At this point in time, there is only light, namely photons. The universe was so hot that photons, being a wave and a particle at the same time, had the freedom to transform into pairs of matter and antimatter particles. Then they collapsed back into a photon. Isn't that fascinating? In a nutshell, we are all the laws of the server energy of that first beginning, since matter and energy are essentially two sides of the same coin. Einstein came up with a famous equation that shows how much energy a substance has. It's called E equals the square of the mass of the object times the speed of light. If it's completely empty of energy, that's okay. Guess what? Every particle in the world can have its twin, not a particle. Did you know that quarks, which make up protons and neutrons, or photons such as electrons and neutrinos, have antiquarks and entanglement? And guess what? There's a positively charged opposite of the negatively charged electron. It's called a positron. Bosons are a special kind of particle that help other particles interact with each other. Take the photon, for example. It's just such a particle. Isn't it funny that the quarks that make up protons and neutrons in the atomic nucleus can't exist alone under normal conditions? They just love to be in pairs or trios. It's really quite fascinating. If you were to pull apart a pair of quarks using a special method, you'd find that the harder you pull, the more they'll be attracted to each other. It's thought that there are now more and more special particles between them, which help the quarks to interact. But at some point, it'll be more profitable for the universe to just make a new quark. Instead of pulling the old one away, it'll just disappear. And now you'll have two pairs of quarks. Each old quark will gently take hold of the handle of its new neighbor. When we start to explore the fascinating world of elementary particle physics, we quickly realize that the laws of logic were used to no longer apply. And this is where we can start to make sense of the void. In the earliest moments of the universe, it seems like it was a big, bubbling cauldron of quarks and plasma. That is, the quarks couldn't form any pairs, but they just bubbled together in a single, freely moving mass. Meanwhile, in our universe, matter and antimatter kept on popping up. But for some reason we don't understand yet, there were 1 billion particles of antimatter for every 1,000,000,001 particles of matter. This imbalance led to something really interesting. Matter began to become more and more abundant compared to antimatter. When antimatter encountered matter, ordinary matter, or anything else, it turned into nothingness. This released energy according to the equation I equals the square of the variable x. If there were no such inequality, our beautiful universe as we know it wouldn't exist. If that had happened, all its lovely constituents would have ignored each other, leaving only a flash. But, as it turns out, something went wrong. This hiccup is now known as the temporal asymmetry of the universe by physicists. As of now, there isn't a known explanation for this phenomenon. We'll just have to wait and see, won't we? Matter and antimatter have a bit of a love-hate relationship. They don't get along very well and can react pretty violently with each other. It's truly fascinating to see how 1 kilogram of antimatter and 1 kilogram of matter interact. They release approximately 1.8 times 10 to the 17th power joules of energy, which is equivalent to the energy released by the explosion of 42% 6/100 megatons of TNT. Guess what? The most powerful nuclear device ever detonated on our planet is called the Tsar Bomba. It weighs a whopping 26.5 tons. When it's set off, it'll give off a blast of energy that's about 57.5 to 58.6 megatons. So, if you suddenly meet yourself, which is made of antimatter, don't hug it. It'll be a really hot embrace. Oh, and if you still think antimatter is just a made-up thing, I'm afraid I'll have to disappoint you. Guess what? Antimatter can be created in a laboratory, which is what some physicists do. The resulting product is quite expensive, unfortunately. According to our friends at NASA, 1 milligram of positrons will cost $25 billion, and for 1 gram of antihydrogen, you'll have to shell out 62.5 trillion American currency. Of course, no one needs antimatter in such quantities, especially since it is very tricky to store positrons. But don't worry, they still have a positive charge, which means they can be trapped in a magnetic trap so that they don't collide with ordinary matter and accidentally cause a flare-up. But here's where it gets tricky with antihydrogen. The molecule itself is electrically neutral, so it can't be trapped in a magnetic trap like we can with other antimatter. So, physicists have to sit around and come up with the best ways to store antimatter. It's the priciest substance on our planet. So, we still need to store it because we can only check certain properties of matter on a large amount of it. Take gravity, for instance. It's so interesting. Antimatter also has anti-gravity properties, which means it will repel from our planet. Oh my, they're attracted. Ideally, this wouldn't happen. We'd love to see macro amounts of antimatter behave exactly the same as ordinary matter. It would be so cool if there were whole regions in the universe made up of antimatter galaxies, planets, and stars that behave exactly the same way as their ordinary, familiar counterparts. But we just don't know that yet. We can only guess at why they're not there. This is what would happen if we had all the facts. It's truly mind-boggling to imagine what would happen if an antimatter star and an ordinary star collided. The power and energy released in such a collision would be so immense, it would exceed the luminosity of all the stars in hundreds of millions of galaxies. If such a thing were to happen anywhere, we'd probably see some evidence of it, right? But there's no evidence of that, sadly. So, if you look up at the sky through a telescope and see another galaxy, it will be made up of ordinary matter. It's also worth mentioning that these kinds of details are usually left out of the picture in science, but everyone remembers them. Just because we can't see it doesn't mean it's not possible. It's possible that there are huge stores of antimatter out there in the vastness of space. Maybe one day, they'll interact with ordinary matter, and we'll get to witness the incredible process. It's such a magnificent sight, but it will be the last thing we see, my friend. This gamma-ray burst will unfortunately wipe out a huge area of space around the reaction center, including our planet. It'll be a truly gorgeous sight, but it won't last forever. And so the universe continues to expand and cool. It's fascinating to see how things change. Quarks begin to combine, and then protons and neutrons appear. These combine to form the nuclei of future atoms. The universe is now full of matter, most of which is hydrogen, 90%, and helium, 10%. There's still some deuterium, tritium, and lithium, but it's still too early to count them. For the next 380,000 years, not much happened. Oh, but that's not all. All that time was filled with different processes. We're still chatting about the birth of the universe, but it was a pretty stable period. The electron was on the move, zipping about freely through space. Every so often, it bumped into photons, spreading them out along the way. If you were there at that moment, let's imagine you had some protection, you would see nothing but sparkling and opaque milk, space. It would be quite the sight to behold. Photons wouldn't be able to enter your eyes easily because they'd be knocked out of the surrounding space by electrons. Once the temperature of space dropped below 3,000 degrees, which is about half the surface temperature of the sun, something pretty cool happened. Electrons started getting trapped in atomic nuclei. The universe was flooded in beautiful, glorious light. And so, the period of matter formation came to a successful close. Oh, and guess what? This amazing period, which left us with the cosmic background we can see today, we can actually measure by those leftover photons that got free from the pesky electrons and only now reached us. After 1 billion years of traveling through the universe, the photons that were in the visible part of the spectrum stretched themselves along with the universe and moved into the microwave range. We can still catch a glimpse of those times by the cosmic microwave radiation that's been around since then. Someday, physicists will write about another kind of radiation that is even lower on the spectrum. But that will take a very, very long time, maybe in a few tens to a billion years. But will there be physicists in those times? I hope so. It's been a billion years now since the universe started to expand and cool down. The matter created from primary energy, which is mostly hydrogen, is starting to come together into groups that we will eventually call galaxies. In the vastness of the universe, galaxies are the main characters on a cosmic scale. It's not really possible to think about things that are smaller than that. Hydrogen is the building block of the universe, the very foundation on which everything is built. It's the simplest, and that's a good thing. There's one proton and one electron hanging out with this proton. And the hydrogen atom looks a little different from what we're used to seeing on the internet. If you were to ask someone how they imagine an atom, they'd probably tell you about the nucleus and the electrons whizzing around in their orbits. The truth is, things are actually pretty fascinating. The electron is a fascinating thing. It's both a particle and a wave, which means it's sort of smeared across the structure of our spacetime in the form of a cloud surrounding the atom. And when atoms interact with each other, they touch electron clouds, and the interaction happens at that level. It's pretty amazing when you think about it. When you're standing on the floor in your home, it's like the electron clouds of your feet or shoes are touching the electron clouds of the floor. But don't worry, there's no interaction, because if there was, you just grow into the floor. So when you're standing on something, you're actually on a micro level, which is pretty cool. Levitin. Oh my goodness. There's so much going on. And you've never touched any object in the way we usually mean when we say touching. So any external influence you have will be electrostatically. It's not that your body is repelled by the negatively charged electrons in your surroundings. It's actually the other way around. The fundamental force that keeps you from falling through the floor is electromagnetism, which is one of the most fundamental forces in the entire universe. The tiniest particle that carries electromagnetism is the photon. It's a particle of light, my friend. It's so interesting to think that everything around us is filled with light. It's light that keeps everything together. And we're made of light too. It's amazing how knowledge of physical laws can be used to create beauty. And now for some conclusions. Meanwhile, in our vast and wonderful universe, there is a large volume of gas that is beginning to accumulate from its own mass. If you have mass in our world, you also have gravity, my friend. When you look up at the sky on a rainy day, or maybe not so rainy, you see clouds. Clouds are just water vapor, and that's something we can all relate to. And that vapor can weigh hundreds of tons. It's pretty much the same situation in space, too. It's truly amazing how any cluster of gas, when we see it on such a large scale, has such enormous mass and therefore gravity. Some parts of the cloud have more gas, some less, and as you can imagine, areas with a higher concentration of gas start to attract those that are more charged. Eventually, the gas starts to gather around one point, becoming more concentrated, and you get a ball. But here's the catch. For this ball to gain strength through thermonuclear fusion, it needs to have a certain mass. If it doesn't, it'll just remain an unhappy brown dwarf. But wait, if the scale is even smaller, this cluster of gas may well become a gas planet like Jupiter, for example. If there's enough mass and the pressure inside is just right, hydrogen atoms start fusing with each other to form helium atoms. This is how stars are born. This is also how our beautiful sun came into being about 4.5 billion years ago. Have you ever wondered why a star shines? It's not because of a chemical reaction or a nuclear decay reaction going on inside it. Have you ever wondered how stars are made? It's a fascinating process. Thermonuclear fusion is a series of transformations that occur when 4 hydrogen nuclei combine with each other. In this interaction, part of the protons are transformed into neutrons. And lots of other good stuff is made along the way, including helium. The star slowly uses up all the energy in the hydrogen that it's made of. One of the byproducts of this unusual process are some pretty mysterious particles called neutrinos. Let's take a little trip down history lane to better understand what we're dealing with here. It was way back in 1930 that some clever folks started to think that there might be something called neutrinos. They were worried about radioactive decay at the time. In 1914, James IV made an amazing discovery. He found that when electrons are lost by an atom during beta decay, they don't all have the same energy. This was a surprise because the law of conservation of energy says that electrons should have the same energy. If the law of conservation of energy is true, then all the electrons should have the same energy. But what if someone takes that energy away from them? Wolfgang Pauli had a brilliant idea to save the law of conservation of energy. He proposed a new particle that would play the role of a thief in the process. And so, for the first time, we were thrilled to announce the existence of a new, previously unknown, humble particle. I really tried to save exchange, statistics, and the law of conservation of energy. It's a fascinating possibility that in nuclei there might be electric neutral particles, which I'll call neutrons, that possess a spin 1/2 continuous beta spectrum. If we assume that in decay, along with the electron, the neutron also descends, then this becomes clear. So, the total energy of the neutron and electron stays the same. I know it might seem a bit far-fetched at first, but I really believe this could be the way forward. But you can't win without taking a chance. I'll point that out. Guess what? Neutrons ended up being the name of another particle that was soon discovered. Neutrons and protons work together to form the nuclei of atoms. Guess what? Pauli particles were predicted way back in 1934 by the Italian Enrico Fermi. The Italian name for this particle was neutrino, which means neutron. All that's left for us to do is find these particles. It's truly amazing to think that every second, about 60 billion neutrinos pass through an area on Earth the size of 1 square centimeter. But here's the tricky part. They're really hard to spot because they don't interact with matter. To catch these elusive particles, some pretty impressive structures have been built. A research station was built very close to the South Pole with the hope of catching neutrinos flying to Earth from the Sun. All of these stations are built deep underground or under the ice so they don't get in the way of cosmic rays. Neutrinos are pretty good at reaching these depths without any trouble. They often even manage to pass through the planet without hitting a single atom. It's really quite incredible how big neutrino-seeking projects are. The IceCube Observatory is a whopping 3 kilometers deep. 5,000 plus sensors are nestled in ice that's been around for centuries. The pressure at depth is so high that all the little air bubbles are pushed out, leaving the ice crystal clear. Even though it's a small probability, there's still a chance that a neutrino from the sun will collide with an atom in the ice. When this happens, the sensors pick up a tiny flash of light that comes with it. It's not often that such flashes occur, with only a few happening each year. Similar facilities are placed in deep mines too. The Power Line Laboratory is another great example. It's located 2 kilometers deep in the left mine. The lovely researchers even go down into the mines with the miners. The scientists go down even deeper, while the miners get to leave the elevator earlier. Then they walk a little ways, about 1.5 kilometers, through a tunnel that could use a good cleaning to get to the scientific complex. It's so reminiscent of the movie Resident Evil. After such a journey, they enter a sterile area where they take a shower, change their clothes, and blow off all those pesky particles, down to the last speck of dust. We can think of some great examples of these facilities like the neutrino and supermyocardium detectors. In Japan, at a depth of 1 kilometer in a zinc mine, they've set up a really cool experiment where they register neutrinos after the explosions of distant supernovae. It's pretty amazing when you think about it. Every second, countless tiny particles from exploding stars pass through your body. You don't even notice them. They zip right through your body without touching a single atom. But they're there, you know. As they say, you see the gopher and I don't see the gopher. And there it is. Let's go back to our lovely little universe. Shall we? Have you ever wondered how galaxies are formed? It's really quite fascinating. A cluster of stars in space comes together to form a galaxy, which is home to a rich and diverse range of life. They come in all shapes and sizes, and they're all so beautiful. It's truly mind-boggling to think that there are about 2 trillion galaxies in our observable universe. The numbers vary, but we're looking at anywhere from 1 to 2 middle-sized galaxies each. And each of those galaxies has about 100 billion stars. It's so interesting to see how smaller galaxies swirl around larger ones. It's like they're waiting for their larger counterparts to devour them. Our galaxy is called the Milky Way because, from our point of view, it looks like milk spilled across the sky. Isn't that lovely? Our galaxy also took part in the act of cannibalism once, swallowing a small neighbor. You can still see the remains of this small galaxy in the form of a stream of stars in the area of the constellation Sagittarius. And this is just the beginning of our galaxy's incredible journey. It and the well-known Andromeda galaxy are getting closer together by 100,140 kilometers every second. So, in about 3 billion years, the two galactic systems will collide. When this happens, it's likely that one big, beautiful galaxy will be formed. It's even possible that our solar system might be thrown into the vastness of the galaxy by some pretty strong gravitational forces. But don't worry, the sun and planets are probably going to be just fine. I wonder if there will be other intelligent beings in our galaxy at that time to witness this incredible process. Or maybe there'll be some lovely life forms in the Andromeda galaxy. Who knows? After all, galaxies are the main characters in the cosmos. The lovely physicists decided to crunch some numbers and figure out the total gravity they create. And it turns out that the gravity they read can't be explained by the visible matter of galaxies, which is a bit of a surprise. Have you ever looked up at the night sky and seen a lone star on the outskirts of its galaxy or outside of galactic space? It's truly a fascinating sight. It's so interesting. It seems like something is pulling them and providing the high speed of their motion. The most common concept today is that 85% of the gravity of the universe is provided by invisible matter. Isn't that fascinating? Dark matter is a substance that does not participate in any electromagnetic interaction. It's truly amazing to see the vast number of galaxies out there, and it's mind-boggling to think that the stars within them contribute only 15% to the observed gravity. The vast cosmic ocean is mostly made up of something that looks like nothing to us, but has gravity. Isn't that fascinating? This is where a lot of these fantastic theories come from. Have you ever wondered what this dark matter is? Could be that it's not matter at all, but some kind of pressure from parallel dimensions. But it might be a lot more straightforward than that. This is especially interesting because we've even discovered galaxies without dark matter. But think about it. We've gotten to the point where physicists are seriously discussing the possibility of parallel realities. Isn't that fascinating? And the wonderful thing is, the laws of physics allow it. I think it's absolutely amazing. But that's not all. The universe is always on the move, growing and expanding. It's been going on since the beginning, and it's going to keep going. The amazing truth about this phenomenon was first revealed way back in 1929 by the wonderful Edwin Hubble, who we now know as the namesake of the famous telescope. the go-to source for desktop wallpaper. He noticed something really interesting. The further away another galaxy is from our galaxy, the faster it is moving away from us. The universe is growing in all directions, just like you'd inflate a balloon and watch its surface stretch. And so, some mysterious force is making our universe expand at an ever faster rate. This mysterious force is now called dark energy. Dark matter and dark energy are named that way because they're not actually dark. It's just that we don't know much about them, so they seem mysterious and a little bit dark. We're still learning about them. Dark energy plays an even bigger role in our universe than all the other things that make up our amazing cosmos. Can you believe that 68% of the total mass of energy in the cosmos belongs to dark energy? And 27% is occupied by dark matter. That leaves only 5% for our familiar matter. To figure out how fast something is moving, we have to get a little creative. For example, one of these tricks is the Doppler effect, which was discovered by the Austrian physicist Christian Doppler in 1842. If a body is moving and emitting light, it's as if it's saying, "Hey there, I'm on my way." The very fact that it's moving in our direction should increase the frequency of the waves and the body's descent, as well as reduce their length. If the object is moving away from us, then, on the other hand, the wavelength should get longer and the frequency should get lower. And guess what? This works for any waves, too. Whether it's light, sound, or any vibration, it all applies. If you know what kind of waves an object should be emitting, and it's emitting waves of a different frequency, then it's probably moving towards you or away from you. It's so interesting how Pierre first tested this effect. In 1845, he was working on something really cool. He was estimating the displacement on a frequency scale of sound from an orchestra playing on a platform attached to a steam locomotive. And his lovely assistants, who had perfect hearing, estimated the pitch of the tune depending on whether the steam locomotive with the orchestra was approaching or moving away. It's so interesting how scientific experiments are different in space. Because of the vast distances involved, this effect changes to a similar one, and it's called cosmological. Redshift is a bit of a mouthful, isn't it? It's like we're seeing the universe trying to run away. It's a funny thing about the universe. No matter where you are, the rest of it is moving away from you. So, no matter how you look at it, the world is moving away from you. It's like you're right in the center of it all. It's really quite lovely to feel like you're the center of the universe, isn't it? Even if the rest of it is trying to run away from you and at the same time constantly accelerating, it's still a pretty amazing feeling. It might sound a little strange, but this happens in every part of space. It might be hard to believe, but all the points on the coordinate plane are actually running away from each other. At the same time, each point in space thinks it's the center of everything, not because the points are moving, but just because the coordinate plane is expanding. It's so sad, but everything that isn't part of the Milky Way will eventually get so far away that we'll lose sight of it. And there's more. At some point, since the expansion is accelerating, external objects relative to our galaxy will move away from it faster than the speed of light. That means the light from them will never reach us again. The laws of physics say that motion can't exceed the speed of light. But here's the catch. These laws are static in spacetime. When the very fabric of space itself is expanding, it's like the rules of physics are changing. It's like motion at higher speeds is suddenly possible. If we imagine a planet as part of our galaxy in the distant future, the people there would look up at the sky and see nothing but remnants of what used to be called the spilled milk of the Milky Way galaxy. There won't be anything else in the sky, sweetheart. The only stars you'll see will be ones with less than 0.2 the mass of our sun. By that time, the more massive stars will have already finished their lives and gone out. The stars in other galaxies that these beings will never recognize will be too far away for their light to reach them. Even the fastest thing in our world, the light of these stars, will not have time to reach their planet. That will happen in about 1 octillion years, which is a really long time. A vast, endless expanse of nothingness. A darkness that seems to stretch as far as the eye can see. They'll never know what came before, how their universe came to be, or that there are 2 trillion other lonely galaxies just like them. But think about it, what if we are those very beings living in an age when some phenomenon, some clue to our world, cannot reach us because it is too late? It's a fascinating thought, isn't it? We'll never know the answer because the results of that key event are already too far away and too long ago. But let's not be sad, okay? With the same probability, we can even exist in that most infinite and happy era when we have an opportunity to open all the cards with the secrets of our world and understand everything that our mind is capable of understanding. Of course, it's important to remember that our brains are still a work in progress, used to the three-dimensional space we're used to. But still, it's so exciting to think that we might be able to understand the mysteries of the world while they're still available. We live on a tiny, rocky planet orbiting a pretty average-sized star. Our sun is just one of about 200 T50, 000, 000, 000, 000, 000, 000 stars in our Milky Way galaxy. Isn't that amazing? And that, in turn, is just one of the 2 trillion galaxies that make up our beautiful cosmos. Our star is actually closer to the edge of the galaxy than to its center, which is pretty cool if you think about it. The Sun is on a journey around the center of our galaxy, together with other stars. It orbits at a speed of 220,240 kilometers per second, making 1 revolution in about 200 million years. If we are based on these data, they tend to change from year to year. It's fascinating to think that for all the time the Earth has existed, it has circled the center of the galaxy no more than 30 times. We're really lucky to be situated between 2 arms of the galaxy, which we've named the Sagittarius arm and the Perseus arm. It's so interesting that we move at exactly the same speed as the arms. This special zone where the stars and arms move at the same speed is called a rotational circle. It's the safest place in the galaxy. If you're outside this circle, you're either moving faster or slower than the arms. Sometimes this means that galaxies and arms cross them. It's not the most pleasant place to be honest. It's a pretty rough place out there. It's full of violent radiation and cosmic dust. And the violent processes going on there easily kill all living things. So we can say that we and our star are really lucky to be in such a safe zone of the Milky Way galaxy. If you think about it, it's pretty clear that if the cosmos was created for someone, it wasn't us. The universe is a pretty dangerous place, isn't it? It's so sad, but it's true that about 99.9% of space is deadly to us. If our star had originally formed blue in a dreamlike circle, our planet would not have had the chance to support intelligent life for very long. I'm not talking about life in general, since as a phenomenon, life appeared on the planet fairly quickly. But the emergence of complex forms of organic matter would likely be an unattainable goal, which is totally understandable. There are so many places in space that can be pretty dangerous. If you look at pictures of gorgeous nebulae or clusters of gas, remember that they're pretty intense and can destroy anything that gets in their way. Oh, don't we all wish it were that way in real life? It's only in the movies that a spaceship hurtles through such clouds unscathed. It's really tough to do that. Space is full of all kinds of radiation like microwaves, infrared, ultraviolet, X-rays, and gamma rays, and none of which our human eyes can even pick up. Oh, don't you worry. The eye catches them, but in a different way, so does the whole body. In almost all cases, it's either going to fry. The vacuum itself isn't as dangerous as the fact that it can be in cosmic empty space, which actually penetrates a huge number of particles relative to the total volume of the space itself. But even this will be enough, especially if we remember that they are whizzing by at tremendous speeds. The solar wind is made up of just that. Did you know that every single star in the universe is sending out a stream of particles and radiation that spreads across the universe to an infinite distance? Unless it happens to collide with someone like you. And there are so many stars. Lots of them are much bigger than our sun Polaris, which many people think is the brightest in the sky, is actually 37.5 times larger than the sun. But the brightest of all is Sirius. And even though it's bigger than the sun, only 1.7 times as large, it's 25 times brighter than Denius in the Swan constellation. The sun, on the other hand, is 210 times brighter. The giant star abode of Giza is located in the constellation of Orion. It's about 1,000 times larger than our star, which is pretty mind-blowing. And, of course, we can't forget Shields, located in the constellation Shields with a radius 2,100 times larger than our sun. Just to make things easier to understand, let's imagine objects that are smaller than a millimeter. It's really quite insignificant compared to you. In fact, it's about as small as the sun is compared to the SE of Shields. It's so interesting to think about what would happen if our star collided with a star that size. It's hard to imagine, but the other star wouldn't even feel a thing. Absolutely. If you were in space 10 billion years ago, you would have seen something truly amazing. It would have been like looking at a gorgeous painting of 1,000 burning quasars. So sad. There are almost none left now. They usually form early on in the evolution of galaxies, which is pretty cool. The word quasar is actually a pretty cool one. It basically means a quasi-stellar radio source, or just a star-like radio source. Isn't it funny how it emits in almost all radiation bands? But since the quasar was first spotted by a radio telescope, that's what they've been called ever since. And that's why they're called star-like, because of their size. These objects are usually not much larger than our own solar system. A quasar is like a star from our perspective on Earth. The tricky thing is that they're really far away from us right now. It's so far away that no star could possibly shine bright enough to reach us. And the amazing thing is that quasars can shine from a distance so huge that no star could possibly shine bright enough to reach us here on Earth. Isn't it amazing that they can be used as beacons of sorts since they hardly move at all relative to the sky? The brightest quasar we know of is absolutely incredible. It shines like 600 trillion suns and is about 12 billion light-years away. When its light reaches your eyes, even though you can't see it, know that this light was from Pushchino when the universe first came out of the cradle. That's pretty amazing, isn't it? A quasar is a cosmic object capable of emitting light brighter than the entire Milky Way galaxy along with its 250 billion stars, and yet occupying a cosmically tiny size. The latest thinking is that quasars are the active nuclei of galaxies. At the very beginning, a supermassive black hole starts to absorb the surrounding matter, forming what we call an aggressive disk. Everything starts with the appearance of a black hole at the center of a galaxy. Or, to put it another way, it starts with the galaxy around the black hole. We'll talk more about that later. All the matter around it begins to move, but it's not easy to get directly into the black hole. You have to fall into it at a right angle. The substance falls around the black hole in a kind of spiral. As the matter gets closer to the black hole, it will start to move faster and faster. During this wild ride around the black hole, the gas and dust collide and heat up to incredible temperatures. The speed of this rotation is truly mind-boggling. is limited only by the speed of light, which is pretty fast. Everything around it will approach this speed, creating an absolute black abyss. Eventually, light will spread out into space beyond that matter until it falls into the black hole. At some point, there will be no more matter left, and the quasar will stop shining. It will become just the center of an adult galaxy, which is pretty cool. Guess what? There's a black hole inside our galaxy too, but it's an adult galaxy. So, the quasar doesn't shine, but it can also relight. When normal galaxies merge and the neighborhood of the black hole is filled with a fresh source of matter, something pretty amazing happens. Some folks have even suggested that a quasar might form after our own Milky Way galaxy bumps into our neighboring Andromeda galaxy in about 3 billion years. As you journey through the vastness of space, you might just happen upon another fascinating cosmic object, a neutron star. The explosion and subsequent collapse of the star's gravity can compress its inner space a lot. This makes it pretty unlikely that we'll find what we call a neutron star. These objects are usually about the same mass as our Sun, but their diameter is only 10 to 20 kilometers. Now, imagine this object is like squeezing the Sun into a ball with a diameter of 10 kilometers. A neutron star is basically a supersized atomic nucleus with an incredibly strong magnetic field, about 1,000 trillion times more powerful than the Earth's magnetic field. It's made up mostly of neutrons, packed as tightly as the laws of the world allow. These objects are really, really dense. Can you imagine if you took a teaspoon of neutron star matter? It would weigh from hundreds of millions to several billion tons. By comparison, a lovely savanna elephant weighs an average of 6 tons. Hey, don't get too excited. Even if you had 100 million elephants in the space of a teaspoon, that's still only the matter of a neutron star. They also spin really fast. In fact, their rotational speed can reach several hundred revolutions per second, which makes some of them pulsars. It's so amazing to think that objects in space regularly and with equal periodicity send out radiation. It makes me think of them as beacons of the universe. Neutron stars are so massive that the light above their surface is curved, just like the fabric of space-time itself. That means you can see more than half of the surface of such a balloon. Just light C is curved, his and Beck's. If a massive star explodes, or if a neutron star is so big it reaches a certain point, it can create something we call a black hole. A black hole isn't really an object, but it's still pretty amazing. It's not a place you can get out of. Even light can't escape. That means that at the very center of this space, there is something so incredibly massive that even light cannot escape from the gravitational zone of this object. That's why we call them black spaces. This space is so dark that it doesn't even emit light. They're like little holes in the very fabric of space, just waiting for something to get out of it. It would take speeds above the speed of light, which, as it stands, is impossible according to current models. So, if you fall into a black hole, you'll never be able to come back. And if it's already started, don't worry. If you do happen to find yourself falling into a black hole, you'll get to experience a whole series of truly remarkable events. You'll also get to experience some pretty amazing tidal forces. These are the same forces that attract water under the influence of the moon. But a black hole is much more powerful in this regard. So be careful. As you get closer to the black hole, you'll start to feel a really interesting difference between the forces acting on your feet and those acting on your head. Of course, if we assume you end up soldiering on, since your body structure has a limit to its strength and elasticity, you'll start to separate by about half each time. I know it can be tough, but you've got this. Now, your lower half is moving separately and faster than your upper half, and the tidal forces will have already split it in half. And then, just like that, it'll happen again and again. Eventually, even the atoms of your shoes, as well as the atoms of your entire body, will be split in half, all the way down to the tiniest atomic particles. You'll be helping to replenish the mass of the black hole in no time. This is something that will happen to you no matter how big the black hole is. But there's something interesting to note. The smaller the black hole, the more you'll feel your legs and head are drawn to different places. Just think of it as a rather unusual way to die, with your atoms being split in two. Or if you're all elastic spaghetti, as we all like to tease you about. Neil deGrasse Tyson, if the black hole is big, the tidal forces will affect all your bodies at the same time. And don't you worry, you won't be divided before you're done. But don't worry, then things get even more interesting. Let's say you observe this process of a gas pedal under the action of gravity and feel nothing in particular. To someone watching from the outside, you'll start to look a little smaller and shorter. And that's just how matter works as you approach the speed of light. If you decide to shine a flashlight on the folks standing in the stands watching the show, the light of the flashlight will first shift to the red region of the spectrum. You'll quickly get rid of the feeling of being the understudy. And then, if you decide to run with the flashlight, the observers will notice that the frequency of your signals will decrease. Don't worry though, this is perfectly normal. Don't you worry, it'll be just fine for you. But, my friend, being in a zone of such gravity, the very fabric of time itself will begin to curve, and you'll find yourself in a slow motion field. The longer you're falling, the more your signal will shift towards longer wavelengths, all the way to radio waves. These are low-frequency electromagnetic vibrations. And don't worry, the frequency of the flashlight flicker will become smaller and smaller. From the outside, it'll look like you're slowing down until you come to a stop near the event horizon. And then you'll reach the event horizon. This is the edge of a black hole. And that's the thing. Once you cross this horizon, even light can't escape the trap. From this vantage point, it's important to remember that your fall will be eternal. As for you, you might even notice how time outside the black hole will start to speed up. The people in the stands who've been watching you for so long will start to leave one by one. As the grandstands, which were no longer needed, collapse, and the eruptions erupt. As you complete your cycle of stars, you'll get to see the birth of new stars in clouds of gas. But don't you worry, my friend, your joy will be short-lived. But that's only a minute for you is now 1 trillion years for the universe. The stars will start to light up and then go out just like little bulbs. And as time goes by, new galaxies will form from the quasar at the center. They'll grow up, collide, and get older. And then, as time goes by, they'll get farther and farther apart. From you, my dear friend, the universe is going to keep on growing for a really, really long time, 1 quintillion years. All the stars in the sky will burn out, and we'll see the last supernovae erupt. It's so sad to think that all the galaxies will fly off in all directions, leaving only an endless black plague. Just a heads up, there are black holes ahead, and there's more. There's a whole lot of dead space behind you, and that poor, misplaced flashlight in your hands. Or maybe things will happen differently, and you won't have time to notice it all. After all, there's no way to know exactly how fast you'll be falling. It's possible that it might all happen too fast from your perspective. And the last frames are getting more and more mature, and the aging universe will be just a flash for you. The entire history of the universe, from the moment it began 13 billion and 80 million years ago to the end of time in another 1 sextillion years, will pass in a second for you. Your brain will be so caught up in everything going on that it won't even have time to realize what has happened before you cross those event horizons. The surrounding darkness will take your body's atoms, replenishing its bottomless supply. Oh my, what could be more frightening than that? can be really hard to accept that everything you know and love is disappearing right in front of your eyes. Time has stopped for you, my friend. You are now just a passive observer of the death of the universe. Everything that ever was, is, or will be is gone, and you are not. You are now alone with the most terrifying understanding of the word. I'm here with you, and I'm here to help. You're all alone, sweetheart. Nothing else exists or will exist. And, my dear friend, consider how long you've been trapped. Think about it. It's gone. All that's left is that awful, awful feeling of realizing what's happened. Take a moment to pause, breathe in, and breathe out. When you're ready, come back to the present. Come back to the real world now, and feel the joy of this very moment. You're right here, and everything around you is too. The universe is just going about its business, living its measured life. You are alive and kicking. You are a thinking part of this big, wide world, where anything can happen. But we who are living in this time are clearly not. Take a moment to enjoy the warmth of the surrounding space. Take another deep breath of the air that gives you life. My friend, you are safe, my dear. How safe can space be for us humans? By astronomical standards, you have all the time in the world, and time itself is there for you. You can make a difference in the lives of those around you. You can even project your will into real actions. You have so much strength, and you have all the time and space you need to make things happen. And if you don't want to influence your environment, that's okay too. It's your choice. If you're feeling down, remember that even if you feel like you can't influence anything, you're still alive and kicking. And if you ever feel discouraged or hopeless, think about what it would be like to die in a black hole. And don't forget, my friend, it's often said that science is all about dry facts. It's easy to think that you can't get anything out of it that would affect your daily life. Of course, there are so many other things that science has given us, like electricity, medicines, and so on. But these are the wonderful material goods that we have in our modern, civilized lives. Some folks say that the search for meaning, motivation, and a worldview lies within philosophy and other intellectual pursuits of humankind. I have a different take on it, though. Science is a wonderful thing. It allows us to expand our horizons and understand how the world works. And it can be so different from what we thought. It helps us to see the world as it really is, which is pretty amazing, as far as we can understand it, and as it is likely to be in the future. The more you study, the more your view of the world will grow and grow. It's truly incredible, isn't it? So beautiful, yet so terrible in some ways. But you know what they say, without darkness, there is no light. It's so big and so complex, isn't it? It's hard to grasp, isn't it? You come to understand that, sadly, in your lifetime, you cannot fully understand him. But that's no reason to stop. There's physics, chemistry, biology, and so many other fascinating sciences. All these are so much more than just names of disciplines. They are facets, a prism through which you can look around you and see so much more. The more you learn about this wonderful world around you, the clearer your view will become. Just like a scalpel, you'll be able to see things more clearly and in greater detail. It's so important to realize that the only value in the body that comes is. I know it can be tough to think about the meaning of life and the universe. It's okay if you don't have all the answers. There's no meaning to life or the universe as a whole, and there never has been. I think the idea of meaning, if there is such a thing in the universe, makes it even more amazing. And I would never want to belittle it like that out of my own selfish desire to cheat and figure out how things work. But I'm still on my journey, and I'm okay with that. Oh, I know I'll die one day, and at some point, the atoms of my body will return to this endless stream of creation. And sadly, our human lifespan is so short. But as long as it lasts and as long as I live, I'm going to make the most of this process, and I hope you will too. If I've been lucky enough to be born in a human body, it's because I've been given the chance to see, to hear, and to think. I'll definitely make the most of that opportunity, and I'll also try to share the feeling I have with others and with you, my dear listener. Oh, why wouldn't I do that? Because when you share your joy, it doesn't diminish. It doubles the happiness on our planet. And I really like that. That's the most important thing, my friend. Our incredible journey began about 4 billion years ago when a star named the Sun emerged from a cloud of cosmic gas. Isn't it funny how, for a star to be born, the cloud around it has to cool down first? It's a funny thing about gas heated to high temperatures. It can't interact with itself because too much energy prevents it from doing so. As it cools, it begins to condense in places where there tends to be more gas, which is pretty cool if you think about it. As the gas gets denser, it attracts the surrounding gas, and the clouds pull them in. It's like they're being drawn together, becoming more and more compacted. Eventually, the incredible pressure inside the cloud causes the fusion to begin. And then, something amazing happens. The star ignites and begins to maintain its volume. It's constantly struggling with two processes: compression under the influence of its own mass and expansion due to the release of energy. Have you ever wondered what happens inside a star? Well, it goes through a series of phases because the fuel it burns changes. First, the star does something pretty amazing. It processes hydrogen and turns it into helium. Then, when there's no more hydrogen, the mic kicks in. This is where the star's energy sources are temporarily turned off, and the force of expansion recedes before the force of contraction. The star's inner regions start to collapse, which causes its temperature to rise and makes it even more compact. The star is really lucky because the increase in temperature allows it to switch to the new fuel, helium, and create carbon from it. And then, from carbon, it will produce oxygen, which it will use to synthesize ions, and then down the chain all the way to iron. But here's where things get tricky. Iron fusion doesn't produce energy, it absorbs it. And that's when things get really interesting. The fate of the star depends on its mass. But the most dramatic scenario is when it runs out of fuel. The star is under a lot of pressure as the force of compression begins to take its toll. It's like a gentle hug, but it's also a bit overwhelming. The star is really feeling it, and it's starting to collapse under its own weight. The compression is so rapid that a gigantic temperature builds up inside, which causes the star to explode and spew its contents into space. At this point, the star gets really, really bright, up to 1 million times brighter. This is what we call a supernova explosion. It's all thanks to this process that you and I are here today. A supernova explosion. Your body is a pretty amazing place. Did you know that it's the main supplier of chemical elements in the universe? It's true. And it's all thanks to the Big Bang, which happened 13 billion years ago. Guess what? Some helium was formed then too. That's why helium balloons tend to fly off into the sky. Guess what? There's even some Big Bang matter in Syria all the way from the Mendeleev table to iron. And this is carbon, which is super important because it's the structural element of any organics. And then there's nitrogen and oxygen. Guess what? All of these things were formed by the burning of stars. Just stop for a moment and think about that. Your body is literally made up of stardust. We are all, in fact, stardust. Isn't it fascinating to think that iron atoms and other heavier elements are formed by the explosion of supernovae? It's truly amazing to think that our beautiful planet and the incredible things that live on it were made possible by the scattered remains of distant stars. Everything you can touch and use for the rest of your life, like our beautiful planet, is just stardust. And our lovely sun is made up of stardust too. If we think of the sun as a bonfire, it's like it's made up of the ashes of other stars. One popular idea about how our sun came to be is that it was created when one or more supernovas exploded nearby. This is hinted at by the unusually large amount of gold and uranium in its interior, which only appear as a result of such explosions. Oh, and guess what? Our lovely sun is now in the middle of its life cycle. It's amazing to think that our sun has been shining for 4.5 billion years. That's about 40% of the time that stars with a mass of 10 billion are expected to live. In a single second, an amazing 4 million tons of hydrogen are transformed into helium, radiant energy, and a mysterious stream of neutrinos. As the sun gradually uses up its hydrogen fuel reserves, it gets hotter and hotter, and its luminosity slowly but steadily increases. In about 5 billion years, our lovely daytime star will be 11% brighter. Unfortunately, this isn't great news for life on our planet. An 11% increase in solar activity, which is the temperature at the surface of a star at 5,800 Kelvin, that's the maximum temperature the sun will reach in its lifetime, will lead to some pretty big changes in our climate. We'll see an increase in the rate of water evaporation, which will have a serious greenhouse effect. It's unlikely that our planet will become as hot as Venus, where the temperature at the surface is a toasty 464 degrees Celsius. But by the time we reach 8 billion years, life on Earth will look quite different. In 3.5 billion years, our lovely sun will be 40% brighter. This is when things are really going to start getting tough for our planet. Most of the water will turn into vapor, and some of it will escape into space. Some of it will cover the atmosphere with hot gas. This could sadly lead to the eventual destruction of all terrestrial life forms. At the same time, our lovely sun is running out of hydrogen fuel in its core. As the outer shell expands, the gravitational forces that have held it together for so long start to lose their grip. Meanwhile, the core is shrinking and getting hotter and hotter. When the sun reaches an age of 10,900,000,000 years, 6,400,000,000 years from now, that's when the real fun begins. The hydrogen is all used up, but the helium hasn't made it to the furnace yet. As the star's insides get thicker from burning hydrogen, it's like it's getting ready for the big finale. But don't worry, this will only continue in the thin outer layer of the core. As the star continues to burn, it will start to resemble an onion, with different layers of fuel forming inside the core. But here's the cool part. Even though the star is getting thicker on the inside, it's also going to get bigger on the outside. In fact, it'll be about 1.5 times larger than it is now, and it'll be 2.2 times brighter. In the next 700 million years, our lovely sun will expand even further to 2.3 times its present radius, while still shining brightly for us. At this point, the temperature will drop from 5,500 to 4,900 kelvins, which is pretty significant. After this phase, the sun will have reached an incredible age of 11 billion years. In just 7 billion years from now, it will become a subgiant. In about 7 billion years, give or take a few million, the sun will have reached the age of 12 billion years. The sun's core will get nice and toasty, which will cause the outer layers to expand quite a bit. And that means the sun will become a red giant. In this phase, the sun will be 256 times larger than it is today. As the star expands, it will become 2,700 times brighter and cool down to 2,650 Kelvin on its surface. This is really going to be tough on our planet, Earth. Can you imagine what it would be like if the sun expanded by 250 times? It would reach our orbit and engulf us. But don't lose hope. Some studies suggest that the sun might not expand as dramatically as we thought. It might only expand to a quarter of its mass, and it might not eject its own matter in the form of solar wind. Luckily, This means that the Earth's orbit will be further away from the Sun, and our planet won't be swallowed up by a star. But even if that happened, a wind that strong would still tear off the planet's atmosphere, leaving only a glowing surface. Some models even suggest that because the Sun is slowing down, we might actually fall into it much earlier than we thought. I'm not sure which is better, but I'm excited to find out. This phase of our Sun's existence will last about 10 million years, which is pretty long. When the temperature in the core reaches 100 million Kelvin, something pretty amazing is going to happen. A huge flare will occur, and the thermonuclear reaction of synthesizing carbon and oxygen from helium will begin. The Sun will get a new source of energy and then shrink in size to 9.5 times its current size. That's 25 times smaller than it is now. It will take about 100 to 110 million years for it to shrink that much. Eventually, the Sun will run out of helium and will become a red giant again. The Sun will also be putting on quite a show during this period, with some pretty impressive flares. Sometimes it'll be 5,200 times brighter than it is now. The Sun will keep on shining for about 20 million years, because it still has a few more firewood logs in the form of helium in its stash. The Sun just doesn't have enough mass to end its life with a supernova explosion. Once the Sun has made its way through the red giant phase, it'll start to experience some thermal pulsations. These will cause its outer shell to be torn off, and a planetary nebula will form from it. At the heart of this nebula, you'll find a white dwarf. It's formed from the core of the Sun and is a very hot and dense object, about the size of our planet Earth. At first, this white dwarf will be really hot, about 120,000 Kelvin, and really bright with a luminosity of 3.5 million times that of the Sun. But over the course of many millions of years, it will start to cool down and fade away. And that's how our star will say goodbye, making way for new stars and new elements. In about 1 trillion years, all of this will happen. We're so lucky to be in the middle of this cycle and to be enjoying the mature state of the star. But let's go back in time together and see how things evolved. Our beautiful Sun has just come into existence. There's still a lovely cloud of gas and dust around our beautiful Sun. After the Big Bang, the first solid matter was actually dust and tiny crystals. These substances, most likely the first dust, were probably made up of carbon, graphite, or diamond crystals. The particles were tiny, but they were big enough to sparkle in space with a diamond-like brilliance. And then came other wonderful compounds, such as magnesium, calcium, oxygen, and aluminum, which delight us now. And let's not forget ruby and sapphire. So, the gas and dust around the Sun are all moving together in a single, rotating, strong momentum. All the planets in our solar system move around the star in the same direction, just as the clouds spun. The Sun's ignition 4 billion years ago was the start of something big. It caused much of the dust around it to begin to heat up. And the Picasso itself. Isn't it fascinating how a peculiar blast furnace formed the whisks and blobs we now call hods from the Greek word for grain or granules? Up until now, the majority of the flying cobbles in our solar system have been known as hundreds and motley pebbles. These special pebbles capture the essence of our solar system's history, from the birth of our Sun to the formation of our planets. Of course, it has mass and therefore gravity. As time goes by, larger rocks attract small alloys with them, forming ever more massive structures. As a result, there are some really big bodies on our planet Earth. They're growing like yeast, and they could also be why the temperature has been dropping. This is because the iron that was already there started to become magnetic. This happened in spots where there were already iron and ironstone formations. These formations gained their mass from stronger forces than gravity. So, There were 1 trillion of these little guys orbiting around our star, all trying to see who would eat whom first. If you look through a really strong telescope at an area called the Great Orion Nebula, you'll see the same pattern. If you look just below Orion's belt, you'll find it. There, new stars are being born in a giant cluster of gas, like a womb, and each in turn is enveloped by an apparatus. It's a truly amazing sight to behold. It's like a planetary disk of dust and other particles is a little baby's diaper. Each of these disks will eventually become a solar system. It's possible that some beings in deep space saw our protoplanetary disk forming and thought the same thing. Or perhaps they can still see it if they are very far away, like 4.5 billion light-years away. And the light of this process is just beginning to reach them as well. If that's the case, they'll never know about us, the light from our satellites, or the signals from radio sources. They're so far away and it'll take a really long time to reach them. We're just too far away and it'll take too long for them to get here. It might sound a little strange, but it's true. The planet Earth will eventually become so big that we'll be proud to call them planets. The most important thing to remember is that there can't be any other planets in the same orbit as this one. I think it would be great if there was one dominant and victorious planet. 8 planets made it through the war: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The first 4 planets are made of rock, while the others are made of gas. This is how it all came to be. The Sun, still very new at the time, began to move the gas that had settled to the far reaches of its region, surrounding it with its lovely radiation. That means that cold gas giants made up mostly of hydrogen and helium could have been part of our Sun if it hadn't started to shine earlier. Oh, and do you know why we call them planets? It's so interesting to think about how people used to study the sky. The ancient Greeks were the first to discover that there are celestial bodies that move. So, they were affectionately dubbed wandering planets. It's true. People used to think that these celestial bodies, which we call planets, also revolved around our planet like the Sun and the entire cosmos. It's so hard to know exactly how quickly the Earth was formed. In any case, according to various hypotheses, it's thought that it's been around for 1 million years. During this wild time, our planet was a ball of molten rock that cooled and formed our beautiful planet we know today. Each time the planet heated up and turned red from a little collision with another space object in its orbit. But then it quickly fell behind and was covered with a black crust. So, it wasn't just one big blob as many textbooks say. It was actually a vast, black, cold desert. And that's how things stayed for a long time, until it was the turn of our lovely moon. I'm sure you've all seen the moon. How could you not? Our lovely satellite is more than 1/4 of the diameter of our dear planet Earth, and it's only 80 times smaller in mass. That's pretty amazing for a satellite, don't you think? The dozen or so satellites around the gas giant in our solar system look tiny, don't they? Now, let's talk about their planets. Up until now, there were 3 ideas about how our lovely moon came to be, unless you count the extensive folklore, which I don't. The first hypothesis was that even at the stage of formation of our lovely planet Earth, it rotated so fast that part of its hot matter from the centrifugal force broke off and flew into orbit. This fascinating hypothesis was first put forth by George Howard Darwin, son of the renowned Charles Darwin, in 1870. The lovely Pacific Ocean trench was thought to be the planet's little scar after the satellite broke off. The second hypothesis was that there was an independent object in our orbit that fell under the influence of Earth's gravity and got stuck there forever. For example, many of the rocky satellites of Mars were drawn to this lovely red planet. A third hypothesis suggests that the moon may have emerged from a pile of debris left behind after the Earth formed in its orbit. This is pretty similar to how planets form around a star, don't you think? The first lunar missions were a real breakthrough in understanding the moon's history. They brought back soil samples from Earth's satellite, which helped us make some amazing discoveries. At that time, this material was worth a pretty penny, so the researchers asked a few geologists to help out. It's pretty unlikely that a pebble in a scientist's pocket is going to get lost and then sold to a private collection for $1 million, don't you think? These scientists need a little extra TLC. Anyway, the first analysis showed something pretty amazing. It indicated that the moon was formed at the same distance from the sun as the Earth. Have you ever wondered what isotopes are? They are simply atoms of the same substance that have different masses because of the different numbers of neutrons in their nuclei. Oxygen-18 has 2 more neutrons than ordinary oxygen-16. In our everyday lives, we wouldn't notice a difference. But here's an interesting twist. It turns out that the ratio of these isotopes on different planets changes as they get farther away from the sun. This means that since the ratio in the Earth and Moon samples is the same, our Moon must have appeared at the same distance from our Sun as our Earth does. Let's circle back to our initial ideas. It didn't take long for people to start wondering if the Earth and Moon might have formed separately. After all, they have different chemical compositions. For instance, the iron and volatile contents are different. Unfortunately, the Kachur hypothesis also doesn't work. If the Moon was an independent object in orbit with Earth, that would be really interesting. If that's the case, it would make sense that it would be chemically similar to our planet, since it formed from the same protoplanetary disk. And it didn't, sadly. If it was formed from some other place and then came closer, it would probably have a greater speed relative to Earth than we can see now or guess about the past. I think the hypothesis of a detached part of the Earth could explain all the differences. The Earth and Moon have similar isotope ratios because they were part of a whole, and the different iron content was due to the detachment of just the upper part of the Earth's contents. The already formed iron core did not share its part for the satellite as well. If we simplify things a bit, this hypothesis doesn't seem to work. It would mean that the Earth would have to rotate really fast, extremely fast. Computer models show that the Earth would have to make a full revolution in an hour, which just isn't possible for our dear planet. And then, finally, the fourth hypothesis took root. It explains not only the specific tilt of the Earth's axis, but also the equal rate of rotation of the Earth and the Moon. In the mid-1970s, a new idea emerged: the impact hypothesis. It's thought that there was probably a similar planet in orbit with the Earth called Theia. It was about 1/3 the mass of our lovely planet Earth. It's pretty amazing to think that 2 planets can't be in the same orbit. So, at some point, Theia crashed tangentially into the Earth. This collision was pretty intense. It deflected the Earth slightly, and some of it fused with the Earth. A pile of debris from this event, along with the debris of Theia, flew into orbit, forming a cloud of dust around the Earth. Over time, the dust slowly came together to form our lovely Moon. It's now orbiting at the same speed as us, as the dust picked up the speed of the newly formed object after that big, exciting collision. Isn't it lovely how the Moon seems close to us? From an astronomical standpoint, it's right up there with us. It's so lovely that it orbits our planet at 382,000 kilometers away. Isn't it funny how that just happens to be the perfect distance to put all the planets in our solar system between our planet Earth and our lovely Moon? And there's even enough room for Pluto. But when the Moon was first formed, it was much closer to our planet. In fact, it was about 24,000 kilometers above the Earth. It's good to remember that in astronomy, there's something called the Roche limit. This is the orbit where the gravity of the biggest body will tear apart a smaller one. If the Moon had formed at a distance of 10,000 kilometers away, the tidal forces of the Earth would have torn it to shreds, and we would have lost a satellite. That would have been such a shame. We're really lucky that the moon was farther away and is now moving away from us at a rate of 4 centimeters a year. Someday, our dear moon will fly in its lovely spiral orbit beyond the influence of our planet's gravity and go its own way into distant space. If we could go back in time and look at the moon, we'd see a giant hanging in the sky. Its disk would cover an area 250 times larger than it does now. It was about 16 times larger than the solar disk we see today. And it was an extraordinary world. It was a lovely day, just starting to get nice and bright at 5 o'clock. So the sun was rising and setting over the horizon at breakneck speed. The moon often covered it, being a much larger object in the sky. So solar eclipses were just a different version of what we usually see. Now, it's no secret that our lovely planet has tides. Have you ever wondered why tides occur? It's because the moon's gravity attracts a water hump on our planet's surface, and it drags it along with it. Oh, where is that hump? That's the tide, my friend. And it's the same situation on the other side of our lovely planet. And on the sides, there's the lovely, gentle tide. Back then, there wasn't any water, and the moon was much closer. So, as a result, we saw these amazing tidal earthquakes. Can you believe it? Giant waves of magma more than a kilometer high were moving across the planet. They were really making things warm and toasty. Over time, these things stopped happening because the moon was no longer so close by. And as the planet slowed down, the day became longer. Have you ever noticed how a figure skater looks like he's flying when he spreads his arms? That's the same phenomenon we're talking about. As he spins around, he slows down a bit. Just imagine how incredible it must have been to see these wandering red-hot mountains. Our beautiful planet is a glowing ball, spinning in the vastness of cold outer space. It gives off energy in the form of matter, which is pretty amazing if you think about it. And then, it's thrown out into space, carried away by the solar wind, and radiates its warmth in other ways. The hot interior is like a nice, cozy pot of soup, gently lifting the magma to the surface, where it cools and then returns. It's thought that the first crust on our lovely planet probably formed in the polar zone. They are the least affected by the forces brought by the moon, which is pretty amazing. Right after the Big Bang, the temperature on the surface was around 5,000 degrees Celsius. And the firmament, if you could call it that at the time, was covered in a delicate vapor. As the planet cooled, it began to rain dogma from the sky. With even more cooling, the first crystals began to grow on the surface. So sad, but we really don't have much evidence of those beautiful and deadly times. The constant stirring of the red-hot substance, firestorms, and magma showers were all so long ago that we could put our hands down and not search for a speck of those times. It's hard to imagine, isn't it? But we humans are just so curious. As technology has advanced, people have developed some pretty amazing devices that can recreate the conditions of early Earth. They're called catharsis ions, and they're pretty cool. We've got these huge presses that create a pressure of 12,000 atmospheres, which press or dust to the same point. This allows us to see what kinds of rocks formed under those conditions, which is really fascinating. As the temperature dropped to 1,500 degrees Celsius into the thin crust that cooled the magma, green crystals of lepidocrosite, a mineral closely related to K-feldspar, formed. And then, these crosses and faces got bigger and bigger, getting pretty close to the size of grapes. But as they grew larger, it became more and more difficult for them to stay on the hot surface. And so they sank and clumped together, forming a multitude of rocks. One of these fascinating rocks is the Danube, which is actually one of the rarest rocks we now find on the surface. It's only when mountains are formed that we can see the layers of rock at a depth. Our beautiful planet Earth has been very active in terms of geology. It has formed a lovely iron core, a nice viscous mantle, and a hard crust on top. The core is mostly made up of iron, which is no surprise. It's heavy and flows down to the center of the planet. The outer core is made up of liquid metal, but over time, the inner contents started to make themselves known. It's incredible how much pressure there is there. It's actually causing the iron to return to its historic state. And that's great news. The inner solid core spins at a different speed than the outer core, and the constant flows of matter in them create our planet's magnetic field. Thanks to this field, we are protected from the solar wind flow of charged, deadly particles. Without it, life as we know it wouldn't be possible. I just wanted to mention that we also understand the mantle isn't viscous. One of the layers of the mantle is made up of a viscous substance, which makes up most of the mantle itself. If we picture it as a solid like bitumen, it will be solid at one moment and under pressure, but over time it slowly flows. Have you ever wondered how we know that our planet has a solid shell? Could it be that our planet has a viscous mantle, a liquid outer core, and a solid inner core? It's a bit tricky to get that directly, but we can definitely try. Guess what? The deepest well in the world is the Kola well, which reaches a depth of just over 12 kilometers. And our lovely planet Earth has a radius of about 6,400 kilometers. So, there's no need to worry about drilling. All you have to do is listen, my friend. And that's where our friends, the seismologists, come in. When something like an explosion or an earthquake happens, the vibrations travel through the planet and into its depths. There are two types of these waves, and they're pretty fascinating. A wave is a lovely, elastic compression wave. Just picture a little toy spring that you can help to slide down a ladder if you give it a little nudge. If you put it on a horizontal surface and push it up, it will naturally compress and compress again. It will be a wave, and it has this amazing property that it passes through the liquid no matter what, if it gets there at right angles. But if it gets there tangentially from a wave that's more similar in properties to the ordinary, familiar wave, it refracts. It doesn't go through the liquid, my friend. It dissolves into it. So, when there's an earthquake or a controlled explosion somewhere on our beautiful planet, you put up sensors and listen for the echo. And at the other end of our big, beautiful planet, right on the other side, you'll see a wave that has traveled all the way through both the thick, creamy mantle and the liquid outer core, with a solid inner iron crystal. The wave of vapor hits the outer core at an angle, and you can even calculate what radius this outer core occupies. The waves won't travel through the liquid, so you'll only be able to see them outside the outer core. If you're a scientist, you don't have to see the phenomenon directly with your own eyes, which is great. And you can even listen to its echoes. Let's go back to hell, my friend. Guess what? A crust is trying to form on the surface of our lovely planet. The primary crust is thought to have been a rock called whale-lite, which was both buoyant and light as a feather. It formed on the surface of magma, just like land forms on the surface of water. Then, sadly, the primary crust was destroyed and basalt came on the scene. Black basalt can also stick around on the surface of the magma. Amazingly, 70% of our planet's surface is made up of basalt and crust today. Guess what? This wasn't just happening on our planet. Guess what? Almost the entire top layer of Mercury is made up of basalt. Guess what? The dark spots on the moon are the same thing. These lunar seas are like little windows into ancient times. They show us the remnants of lakes that once covered the surface of the moon, with molten basalt still remaining on the surface today. The basalt was a big help in forming the crust into a more or less coherent structure. A lovely structure. And then, finally, we see some relief. Previously, A thin layer of molten rock that was constantly moving around like a porridge couldn't hold together large formations. The salt really came through for us. If you were to look at our beautiful planet Earth from space during this period, you would see it as a black, reddish-hued globe with spots of scarlet and other markings from falling meteorites crashing through its thin crust. But don't worry, this will only last for a little while because it will soon start to rain. If aliens were to give us a quick overview of our planet, I'm sure they'd mention water. Can you believe that water occupies 70% of our beautiful planet Earth? And our beautiful planet, the blue planet, is home to tons of water in the form of clouds, which is part of all living organisms. It's important to remember that even though water plays a big role in shaping our planet's surface, it makes up only a tiny fraction, about 0.2%, of the Earth's total mass. Guess what? Most of the water on our beautiful planet is found in the oceans, making up 97.5% of it. The rest is spread out in the form of freshwater bodies and glaciers, and in the atmosphere, where it makes up only 1/1000th of 1% of the total. We pay so much attention to this amazing substance because we simply couldn't live without it. After the Great Collision, water started to collect on our lovely planet. We're not going to worry about all the water that was already here before the Big Bang. If there was water on the planet after the collision, it was carried away into space, along with all the other volatile compounds. There are two main ideas about how water first showed up on our planet, and they're not mutually exclusive. The first idea is that water came to us from outer space. There's so much water in space. For example, it's part of comets on the outskirts of our solar system. There's even a cloud of comets out there, called the Oort cloud, just waiting to be discovered. They even still visit us from time to time. In the early days of our solar system, things were pretty chaotic. It's thought that as many as 1,000 asteroid comets, mostly made up of water, fell to Earth. Jupiter may have helped out with this process too. At some point, he gently captured some of the comets and icy asteroids in the vicinity by his gravity and let them go towards Earth, dispersing them as if to say, "Hey Earth, I'm here for you." The lovely theory of how water came to be in our oceans is backed up by the isotopic composition of these bodies of water. It's really interesting that the ratio of heavy hydrogen deuterium to ordinary hydrogen is almost the same as that found on asteroids. But, as always, there are different opinions on this, and that's okay. It's impossible for us to know exactly what was going on in those distant times, isn't it? It's even possible that the Earth retained water even after the impact. Could have been deep in the pressurized silicate melt, which makes it tricky for it to evaporate instantly. It's also a bit of a mystery whether water could have come to Earth from the Oort cloud or from other places in our solar system. Oh, and the moon makes a difference too. It's so dry compared to Earth. It's a bit of a mystery why it didn't get its share of comets. It's so great that geologists are working hard to get accurate data. Oh, and just as a little reminder, the comet's tail is moving around as it orbits the sun. If she flew to us, it would be from away from her, not in the course of motion, but from the sun. The tail of the comet is made up of gas and dust, vapor, and it's carried by the solar wind from its surface. Just a friendly heads up. Not all movies are 100% accurate. If the comet spends a very long time flying around that hot object, it might even vaporize, could leave behind some stone or iron fragments. Another idea about how water got here on Earth is that it was inside the planet at first, and as it melted, it came to the surface. It was there from the very beginning. It's pretty amazing to think that mantle minerals at extremely high temperatures and pressures can hold up to 3% water in their composition. That might not seem like a lot, but if you think about it in terms of the volume of the Earth's interior, it could still contain 80 times the volume of the world's oceans. And there's another thing. It looks like water might be able to reform. This theory is still pretty unusual, but it's definitely worth a look. But here's the really cool part. If we model conditions close to those of the Earth's interior, temperatures around 1,400 degrees Celsius and pressure 20,000 times higher than atmospheric pressure, it turns out that silicon dioxide contained in the mantle can react with hydrogen, leading to the formation of liquid water and a silicon hybrid. These amazing processes happen at depths of 40 to 400 kilometers below the Earth's surface. I think it's great that we have two different hypotheses to consider. They're not mutually exclusive, and they both deserve our attention. You and I are mostly made up of water, just like each other. Water is your best friend. It fills you up, it flows through your veins, and it lets your brain do its thing. And the water molecules that are doing this work now originated either hundreds of kilometers thicker than the Earth's surface, or they were formed from the ashes of dead stars somewhere on the edge of the solar system. Isn't that fascinating? I think both of these ideas are pretty amazing. It rained. The first drops fell on the hot ground. The basalt from Scheppel's volcano immediately turned to vapor, but there were more and more of them. The planet was filled with a deafening, overpowering hiss. Karasi reached out to the hot fog, calling and nodding all into visible space, making her way into the most inaccessible places. The volcanic ash mixed with water and absorbed it, turning it into a paste that was meters of mud. It flowed into the lowlands where it met with the still hot magma. The water and mud instantly boiled and exploded, sending their contents flying for dozens of meters around. Then they flowed back down again until all the thermal energy was used up, heating up their fissures. The sky was also covered in dirty clouds. The rain got pretty intense, turning into a storm. The heavy atmosphere was building up from itself, like a big, cozy blanket. It was quite the show. Lightning bolts the size of your head flashed every second. The rain just kept on going, pouring down from the sky and taking everything it could from the atmosphere. Ash, carbon dioxide, ammonia, and more. The sky poured acid down, dissolving crystals on the surface. It was like magic. First, there were puddles, then lakes, and finally oceans. It's really hard to say how long this rain went on for. It must have been at least 1,000 years, maybe even 1,000,000. They're so lovely that the crystals of the law can tell us about those times. They're able to exist almost forever. 1,000,000 years later, they became part of new weathering rocks. But then, thankfully, humans came along and took these crystals in their hands, putting a stop to the never-ending cycle. And here's the cool part. We can even figure out how old the rock is because zircon includes uranium, a radioactive element that has been around for about 4.5 billion years. When the crystal is formed, something pretty amazing happens. The uranium in its structure, like a stopwatch, begins to decay and form lead atoms. It's truly fascinating to think that every 4.5 billion years, about half of all uranium atoms must turn into lead. And after another 4.5 billion years, the remaining half will also split itself in half into lead, and so on. Isn't that fascinating? This is a really useful way of working out how old the crystal is and when it formed from volcanic rock. It also helps us understand what conditions it was formed under. It's truly amazing how crystals, which are hardly visible to the eye, can be scattered like dust in the most ancient rocks. These tiny structures can tell us so much about the age, temperature, formation, and even whether water was in contact with the rock. I think geology is a truly romantic science. Just imagine for a moment looking at a grain of sand through a microscope and realizing that it has experienced everything that has been associated with this planet. It's been here from the very beginning. It floated in the primordial magma, lay at the bottom of the ocean, grew into the hardest rocks, and from above, life began to stir. A wide variety of creatures evolved and died, and she slept her peaceful, historical sleep. Someday, it will be found nestled in a woman's earring by the creature that rules the planet at that time. They'll like the way it reflects the radiation available to their eye. And then they'll make some more bling and then some more until it gets lost and returns to its natural state in the rock strata. Oh, but none of this will matter to Sargon. A little uranium clock is ticking away somewhere inside, keeping a gentle time. The crystal slowly turns to lead, and the story goes on. Eventually, the atoms will fold and the crystal will return to space and beyond the expansion of the local star. And then, they'll spread out into the vast, limitless space of the universe, forming a new crystal somewhere out there. Maybe the same zircon if we are lucky, and perhaps there will be some uranium inside again. Wouldn't that be wonderful? The clock will start its course again on a distant, unknown planet. And the water is still pouring, most likely over a period of 100 million years. After the Big Bang, our lovely planet Earth was already covered by a kilometer-deep ocean. There wasn't yet a vast expanse of land, and every so often, small volcanic islands with boiling magma in the middle popped up on the surface of the water. They gradually grew in size and came into contact with water lava from space or from the moon. Earth looked like a greenish ball. The water probably wasn't blue, but it was probably a greenish-brown color, probably muddy, from all the iron compounds and other dissolved salts. This shallow ocean must have been very salty, although there are lots of different ideas about how salty it was. The popular version of events says that most of the salts on the surface of the planet were washed out of the acidic ocean rock because it absorbed a lot of carbon dioxide from the atmosphere. This made the ocean at least 5.5 times as salty as it is today. It was also really hot. Over time, this boiling salty broth left, and the excess salt began to settle and preserve where we now find it in the salty strata beneath the Earth's strata. Meanwhile, it's important to remember that crustal formation doesn't stand in the place of basalt. The lovely magma is nestled deep within our planet's core, while on top of it, like little floating bubbles in water, less dense rocks begin to accumulate. Some of these are called granodiorites, which are pretty cool. It's so interesting to see how the melting metamorphosis of the rock creates these main minerals, which include plagiarized quartz, gallieva, and feldspar. As a result of the melting granite and the formation of land, things have been changing pretty quickly ever since. Because of the movement of the tectonic plates, other plates. Isn't it fascinating to think that the continents we know today are constantly on the move? And the world map used to look very different. Wouldn't you know? This hard to believe, but not more than half a century ago, most people believe something completely different about how the Earth's surface changed. Let me tell you about the geosinclair fields theory. This fascinating theory suggests that the thickness of the crust can change in different places, making some pretty unusual movements up and down. As a result of these big movements, mountains, valleys, and plains are formed. It's so interesting how the western part of Africa and the eastern coast of South America seem to match up. It's a bit of a coincidence, but it's fascinating to see how these things happen. It wasn't until after World War II that we could use echolocation to find zones in the ocean where new crust is forming and moving everything around it. This led to the development of the fascinating theory of tectonics, or black plates. Have you ever wondered what happens under the sea? Well, there's this amazing thing called the tectonic plate boundary, where the contents of the mantle rise to the surface, cool, and become part of the Earth's crust. It's a pretty incredible process. This amazing process produces new crust at a rate of up to 10 centimeters per year. But if the surface area of the crust is growing while the diameter of the planet stays the same, where does all that extra space come from? And that's what happens near the continents in the subarctic zone. The oceanic crust gently sinks back into the embrace of the mantle, where it joins the continental crust. This is how our amazing planet works. It's all down to the infinite convection of its contents. Some of the mantle makes its way to the surface, where it cools and turns into crust. It then moves a few centimeters a year towards the continent, where it dives back into the mantle. Subzones are the most lively zones on our planet. The sinking of the oceanic crust beneath the continental crust is accompanied by vibrations and deformations in each zone. One of the most famous of these zones is the Japanese Kurils and Kamchatka. It's truly inspiring to see the resilience of the Japanese people in their determination to live in the face of adversity. It's really quite incredible that despite the maximum number of earthquakes, active volcanoes and tsunamis, and the lack of natural resources in a tiny space by the standards of other countries, the Japanese people still manage to live there. And yet, it's a truly admirable feat to thrive in such challenging circumstances. The study of the oceanic crust is really fascinating and has led to some amazing discoveries. It's really fascinating to see how the Earth's magnetic field has changed over time. Isn't it fascinating that basalt that comes to the surface contains particles of magnetism? As the rocks cool, the particles line up with the Earth's magnetic poles and then solidify, creating an ancient compass. Isn't that fascinating? We can even understand how the planet's magnetic field changed over time, how the lines of force have moved, and where the magnetic poles have shifted. And it's all recorded on a constantly renewing parchment of oceanic rock. It's pretty amazing to see that our planet's magnetic field can actually reverse itself by 180 degrees. And this inversion happens in a really random way. Modern models tell us that this is all down to constant chaotic changes in the outer core. The Earth is a wonderful, ever-changing place. Its rotation creates complex investment flows in the inner regions. That's why, in the near future, Polaris won't be pointing north at all. Oh, and guess what? Polaris isn't just one star. It's actually a triple star system. One of the companion stars is even visible from the surface of our beautiful planet Earth. And it's also young. It's thought to be between 55 and 65 million years old, which is the same age as the dinosaurs when they were still ruling the planet. There wasn't a polar star yet, so the giant lizards couldn't make long-term routes oriented to the north. So, the celestial body had to call another star north or south. So, depending on where the magnetic field was pointing at that moment. Meanwhile, our planet was already starting to take shape with the appearance of continents. Oh my, how time flies. It's been tens of 100,000 years since then. The rain keeps on coloring the land, but not as much as before. And the landmass has grown quite a bit. Our lovely planet is changing its appearance once again. Stepping out of the time machine this time, you see a vast gray wasteland without a single hint of vegetation. It's a bit of a shock to the system, isn't it? It's still a long way off, but you can already see some deep gorges and flat canyons, many of which have a beautiful white hue. Even the white sand on the beach has a lovely gray color of quartz. Have you ever wondered how quartz grains get their white color? Well, it's actually the result of weathering from granite. Unfortunately, swimming isn't an option. The ocean is a bit sour and super salty, so it's not the best place to enjoy a relaxing swim. But you can still admire the clouds, which sometimes let the sun peek out or not, depending on what kind of day it is. Just a heads up, the methane in the air can sometimes give the whole environment a dense haze that makes everything look orange. If you happen to be there at the same time, I'd love to know what color the clouds or haze were when you returned. The star didn't shine quite as brightly as it does now, and this was one of the fascinating things to discover. or how everything didn't freeze when the sun's luminosity was 25% less than it is now, which is pretty surprising. I think one way to solve this mystery would be to assume that there was more energy and heat. Energy comes from the decay of radioactive elements, and there is a rapid differentiation of the planet's matter. Isn't it fascinating how this all works? And guess what? Iron is still falling into the core. As we move towards the center of mass, we create heat energy through friction, which is really cool. Also, there was a phenomenon called the greenhouse effect. The high content of carbon dioxide, water, and methane in the atmosphere created a trap for solar radiation, which helped the planet through that difficult time. So, while you're relaxing on the beach during those wonderful years, remember to keep your face mask on, a mixture of greenhouse gases. I'm sure you wouldn't wish it on anyone, and you definitely don't want to take your clothes off. Unfortunately, there's still no ozone layer to protect us from the harsh ultraviolet rays. It'll be a long, long time, about 1 trillion years, before anyone gets to see this strange new mole. Our planet, on the other hand, is nearing the end of its period of geologic formation. Isn't it fascinating that it's only 600 million years old? It has so many exciting adventures ahead, especially with the archaea. Guess what? The time of the emergence of life. Who would have thought that our planet would have such an unusual development? It's pretty amazing when you think about it. As we venture into the world of the archaea, we encounter conditions that, from our perspective, are not particularly ideal. An acidic ocean washes over a gray desert of life, like the scale inside a kettle, which is also scorched by solar radiation. Is a tough place to be. The air is filled with a variety of gases, including methane, carbon monoxide, carbon dioxide, hydrogen sulfide, and even thorny gas. In some places, volcanoes even pump more corrosive compounds into the atmosphere. And yet, in the midst of all that, the first little organism makes its appearance. There are so many fascinating theories about how life first began. In fact, they can be grouped into two main categories. The first is the simplest hypothesis that anyone can think of. Whoever thought that life could possibly have arisen? It's always been there, right where we are. This idea is called the steady-state hypothesis. It says that our planet has always been here, and so has life on it. And the changes over time are really quite insignificant. I think it's totally fine to have this idea as long as you don't have any data or scientific evidence to back it up. As you start to understand the question better, you'll find that lots of people who call themselves geologists, biologists, chemists, or physicists have different ideas about the answers. The steady-state theory is just a fun idea that some people came up with a long time ago. They didn't have all the data they needed to prove it, so it's still just a theory. The second category of hypotheses is where we start to get really interesting. It assumes that life did arise somehow, and it falls into two subgroups. So, did life just happen on its own, or did someone help it along the way? Let's dive into the second subgroup, where we'll explore the fascinating idea of outside forces intervening in the grand scheme of things. The theory of creationism suggests that our wonderful world was created by a higher entity, as well as all the amazing living organisms in it. There are lots of different versions of this idea, and there are even mathematical explanations of the Abrahamic religions. It all started with one beginning which set everything in motion. This is what gave rise to the necessary processes, the pantheon, the deities of ancient Greece and Rome, the Egyptian Assyrians, and so on. There are also some really fascinating assumptions, like the original beliefs of the Chinese people. Have you ever wondered where legends about the beginning of time come from? Well, they often start with the idea that, out of chaos, there is almost always chaos at the beginning. Two lovely forces of light and darkness appeared, which gave rise to heaven and earth. In this lonely world, the big, strong pan was born. He lived a long life, but sadly passed away. From his huge body nature was formed, and the wind and clouds became breaths. With a rumble of thunder he spoke, and his left eye was filled with light. Pan flew into the sky as the sun, and the right one, not thinking long, decided to become the moon. His arms, legs, and torso turned into the four sides of the world and the five sacred mountains. And then, something really special happened. The vapor from Pan's body turned into rain, and his blood flowed in rivers, and his muscles became soil, and his hair became grass and trees. Pan's teeth and bones transformed into stones and metals, and even our brains became gems. I bet you're wondering which part of the great Panga's body became people. And so, they became worms on the giant's body, which populated the new world. The lovely Hindus began their legends with an endless ocean. It would be really fascinating to know if the ancient texts also describe conditions from later periods, like the Archaic era. But sadly, just like everywhere else, there is no earth, no stars, no sun, no moon. It's so interesting how people used to think that our world, in all its beautiful form, didn't exist before the Earth disk or solar system came into being. Of course, the first thing that our beautiful cosmos gave birth to after a stable eternal state was our wonderful planet and its gorgeous surroundings. The Hindu legend begins with the ocean giving birth to fire, and out of that came a golden egg. After a little while, something wonderful happened. From the golden embryo inside the egg came Brahma, the wonderful progenitor of everything on earth. Brahma, with a big, bright idea, split the egg into two halves. The upper half became the sky, and the lower half became the earth. Brahma took a deep breath and, of course, became air. After a little while, he got a bit bored of being one part of his body. He then went on to create 6 sons. And so, human history began. There are so many other versions, too. There are Japanese, Scandinavian, African, and even Sumerian ones. Each nation came up with its own version, and it was probably the right one. Folklore and myths are like a big, happy family. They bring us together and help us create a strong community. Culture is a wonderful thing. It allows large groups of people to interact effectively. It's so interesting. I just read almost nothing large. It also helps us to distinguish between those who are like us and those who are not. But no matter how beautiful a myth may be, there are thought to be around 5,000 religions and beliefs in the world, each with their own unique explanation of the origin of everything. It's okay if we don't know which explanation is right. Once you accept the correctness of one of these models, and given their evidence base, you must accept the correctness of all of them. I know it can be tricky at first, but I'm here to help. I'd love to have you join the discussion, but if all the answers are correct, it's a bit of a strange conundrum, don't you think? I find it really fascinating to try to figure out how things really happened. I think it's really important to figure out as much as we can with our brains and the data we have. It's not about coming up with 4,000 to 5,000 explanations, which would be pretty overwhelming. It's about finding an anchor and building from there. If we think about exactly how life began, we'll find that the ancient Greeks made some pretty interesting logical assumptions. It's so inspiring to see how ancient philosophers made such a big impact on so many different areas of knowledge. They didn't just leave their mark on philosophy, but also on other fascinating fields like physics, geometry, astronomy, and medicine. It was still in its infancy. The ancient philosophers were really great at math. They tried to understand our world and how it all works. And Nad Simon and his student Pythagoras came up with the idea that our beautiful planet Earth is shaped like a ball. 200 years later, Aristotle made the same claim, and he had a good reason. He noticed something really interesting during lunar eclipses. The Earth's shadow on the moon is always circular. If the Earth were flat, The moon would fall on either a streak if the sun shines directly on the edge or an ellipse if at an angle. Isn't it amazing how one simple observation can lead to so many conclusions? Sven was a pretty smart cookie, living 200 years before our era. He calculated the Earth's radius and came up with a range of 6,000 to 8,000 kilometers. And it's our fault that this isn't more accurate. It would be so great to know which stages he used in his calculations. It's so interesting how different regions of Greece had different ideas about how long a stage was. In some places, it was 150 to 200 modern meters, which makes the numbers so different. But even more than 2,000 years ago, people were already trying to figure out the Earth's radius. If we use the average stage size of 157 meters and 20 centimeters, we can estimate the radius of our planet to be around 6,302 kilometers. The Earth's radius is 6,000 mh370, which is about 1 kilometer. It's so hard to imagine, and he did it all with just a stick and a bit of string. Just stop for a moment and think about it. It's so interesting to think that over 2,000 years ago, anyone could have verified that the Earth was round. And get this, he calculated its radius with an error of less than 100 kilometers with the help of a stick stuck in the ground. You know, it's the distance between two cities. Take a look at the shadows from the stick catching the sun at the zenith end. You don't need to believe in fairy tales about a disk of elephants on whales and turtles and the world, or a conspiracy of authorities trying to hide the truth about the real shape of the planet from you. You don't need to worry about any of that, my friend. You have the greatest cognitive tool known to us today, and you know how to use it. And then, of course, there's the stick. Oh, of course not. A kind gentleman in the 5th century BC had a thought-provoking idea that all matter is made up of indivisible units of atoms. Pretty promising assumption, wouldn't you say? Especially since it would turn out to be the case in just a couple thousand years. Champion came up with the idea of natural selection. His take on it was pretty funny, though. He had a fascinating theory. He believed that there used to be a world of organs that were all over the place. Fingers ran separately from hands. Lungs plowed from branch to branch. Livers hid in the grass. Eyes rolled wherever they pleased. And then, something really interesting happened. The organs started to come together in all kinds of weird and wonderful shapes, and they survived. The fittest of them is a lovely little phrase about survival and the fittest of the fittest. That's Darwin's very real theory of natural selection, and it's a fascinating one. Everything else is just a bit off, don't you think? It's so interesting how long before us philosophers were able to foresee everything. The secret is really quite simple, with just a few exceptions like Fenn. They didn't actually prove anything. Bless them. But proof is just an inferior form of verification. I think we can all agree that when we say that even the ancient philosophers discovered everything, we're making a bit of a logical error. It's not that the Greek philosophers were super geniuses who could predict the future. It's just that there were so many philosophers, and they had so much time to think. If you asked any person living in modern Greece what would happen in 1,000 years, I'd bet you anything that at least one of them would guess right. It's not because that person is a great soothsayer. Bless their heart. Oh, it's just that there were so many Greeks and so many attempts. It was thought that a true philosopher should be able to reach everything by the power of logic and thought, rather than through experimentation. That's what happened to Aristotle in particular. He made an interesting observation that the speed of falling objects depends on their mass, and it was a postulate for the next 20 centuries, until the wonderful Galileo Galilei decided to check it. He took a musket, a bullet, and a cannonball and threw them off the Leaning Tower of Pisa. The public was amazed to see that, despite the objects having such different weights, they fell to the ground almost simultaneously. So, a belief that had been around for a very, very long time was shown to be false. Some folks think Galileo didn't do this experiment because it's not in his diaries. You can only find the details in the biography of the scientist, which was put together by his student Vincenzo in Evian. There's still some debate about it, but that doesn't change the fact. All you have to do is take two objects of different wall masses from the same height, and they'll fall to the ground at the same time. Let's assume this works, but with one small correction. They need to be subject to the same air resistance, which depends on many parameters. I'm sure you'll agree that the kettlebell and the duck Pierrot will fall to the earth in the air at different times. But this is not because the feather is lighter, but because the feather is 6 by 6 and more susceptible to interaction with air than the kettlebell. So, let's put two of these objects in a giant vacuum chamber, drop them from a height of a dozen meters and see what happens. I bet you anything they'll fall to the floor equally fast. You'll find some great videos like this on the internet. They're so fascinating. The ancient Greeks and the people of the Middle Ages were just as curious as we are today about where life came from. Before the Enlightenment, people believed in something called the vitale, which is like a life force that reads the space around it and gives life to non-living matter. The idea was that if you took dirty human shirts, a handful of wheat, and put them all in a dark closet for 3 weeks, you could be sure that mice would be born from such ingredients. Snakes are born from swamp sludge, and flies are born from dried meat. Isn't it fascinating how nature works? They even tried to raise a human being with chicken eggs and horse manure. And you know what? Nobody saw Gaman Gulam Gaman Koloff, but everyone knew they were there, helping their masters around the house and in other ways. Wouldn't it be wonderful to have such a helpful little creature around the house? Just think of all the work a whole farm of mice could do with just a couple of dirty shirts. But Italian naturalist Francesco Brady showed that all this nonsense was wrong with a clever little fly experiment. He took a piece of meat, popped it in a pot, and covered it with a lid. A few weeks went by, and wouldn't you know it, the meat went rotten, and no fly larvae appeared. Guess what? If you take the same pot, the same meat, but don't cover it, the fly larvae will appear there. This is not because they have settled there. It's just that the little fly friends have flown in and laid their eggs. Just a heads up, this is something to keep an eye on. If you have nothing else to do, you can just sit and watch the pot of meat all day long. And then, you'll be ready to catch that exact moment. Flies are born only from flies, like any other living creature, Francesco said with a smile. This simple fact laid the foundation of our ideas about modern life as a phenomenon. Vitali and his wife were not at all happy about this. They were really eager to see more results from the experiment, even though they could just keep repeating it and be sure. Vitali had another interesting idea. He said that when you close the pot with a lid, the life force, which is made up of air, no longer reaches the weight, so the larvae do not appear. It's so much fun to debate with people who can come up with new terms on the spot, don't you think? Francesco was totally unfazed. He took another pot, more meat, and this time closed the pot loosely with a lid and a gauze. The air made its way in and out, but the bounty didn't come to life in the meat. The poor flies couldn't get through the gauze to reach the pot. Vitali, you may have lost this battle, but you haven't lost the war. Oh, it won't be long before the wonderful discovery of microorganisms is announced to the world. Let me tell you about Anthony van Leeuwen. He was a Dutch naturalist, microscopist, racer, playboy, and philanthropist who lived in the 17th and 18th centuries. Hooke was a real pioneer. He opened our eyes to a whole new world of tiny organisms. Textile workers had been using simple magnifying instruments for a long time, but Leeuwen, Hooke, and driven by his irrepressible curiosity, perfected one of them. They created a microscope capable of achieving a magnification of 500 times. This kind of microscopy is truly legendary. Even the microscopes we have now can magnify things 250,300 times. That's still a pretty big number, especially when you think that the most a light microscope can magnify is 1,502 times. That's because the wavelength of visible light has some limits. I'd love to know how Leeuwenhoek managed to achieve such perfection with the lenses. It's a mystery whether he spent weeks grinding lenses by hand to the point of exhaustion or whether he heated a glass thread, which transformed into a ball, and then cut it, creating a flat convex lens. Antoninus van Leeuwenhoek and Robert Hooke were both brilliant scientists who made amazing contributions to the field of microscopy. While Leeuwenhoek was not the first person to invent the microscope, his dedication and passion for science are truly admirable. He was always studying something new. He looked at human blood, skin, semen, the eyes and wings of insects, rotifers of protozoan yeasts, bacteria in general, and anything else his hands could reach. He drew anything and everything, and at some point, he even sent his drawings to the Royal Society of London. At first, they didn't believe him. Poor guy. It was like saying in today's world that you'd discovered ghosts. And you didn't just discover them, you also started to classify them, organize them, and share ways to observe them and the devices that help us do that. It's just so wild, isn't it? But there were so many drawings and they were so detailed that they sent him a delegation, which was just the kindest thing to do. They wanted to make sure that his statement wasn't a figment of the sick fantasy of a high textile worker, but an irrefutable fact. And so, the wonderful science of microbiology was born. I'd love to know what the discovery of microorganisms had to do with the possibility of the very origin of life in Italy. We had already given up hope after trying so hard with the pots and flies. But now there's something new. It's a simple, everyday object that we didn't know about before. And it's everywhere. It's probably the most common thing in the world. Microbes. But how could we possibly prove that microbes don't just pop up out of nowhere? Louis Pasteur, one of the giants of 19th century microbiology, was able to meet this challenge and did so brilliantly. Just as there are so many amazing scientists in physics like Newton, Faraday, Tesla, Edison, and Einstein, there are also some incredible people in microbiology. Think of Leeuwenhoek, Pasteur, Koch, and Mechnikov. And let's not forget the amazing Zelenogradsky and others. Pasteur was just full of wonderful discoveries throughout his life. He showed us the microbiological essence of fermentation and helped us understand many animal and human diseases. He created the scientific basis of vaccination and developed vaccines against anthrax, chicken cholera, and rabies. He also did some really cool stuff on crystal structure and polarization phenomena, which helped form the basis of stereochemistry. Pasteur's name is on almost every liquid food product you can think of, because almost all of them undergo pasteurization. Pasteurization is a quick heating of a product to make sure all the little microorganisms that are currently active and multiplying are killed off. Pasteurization doesn't kill spores, but it does take time or exposure for spores to germinate. For example, heat or access to oxygen. To get rid of those pesky spores, we need to sterilize our food. This is usually done by boiling, but this unfortunately loses both the flavor and health benefits of the food. Pasteurization is a great solution that gives us the best of both worlds. A longer shelf life for our products and all the amazing benefits they offer. Louis Pasteur came up with all these different technologies for a reason, and it's so great that he did. Oh, they were usually just business orders. He was an amazing manager, so smart and determined, with a fantastic entrepreneurial spirit. When French wine producers approached him for help, he was happy to lend a hand. Wine was one of the main export commodities in 19th century France. Thankfully, not much has changed with wine in modern times. The only thing is, it can go bad over time and turn into vinegar. it also gets a bit sick on its long journey to get to us. So, a way to keep wine safe from these effects was needed, and we were happy to help. Pasteur developed pasteurization, and it's pretty amazing that all wine is pasteurized to this day. It's even said to improve the wine's taste. That leaves one little hiccup in Vitali's statement that microorganisms everywhere are self-nucleating. I'm sorry to say that pasteurization isn't a very effective method of disinfection. But what if new microbes start to appear in the wine and spoil it again? We really had to come up with a way to prove this was all a big misunderstanding. Pasteur came up with a brilliant solution by conducting a simple yet ingenious experiment. He took a glass flask, poured in yeast extract, which is similar in composition to meat broth, boiled it well, and then, while the broth was hot, filled the neck of the flask so that the air along with the microbes did not get into the broth. It was a long time, weeks and weeks went by. The broth stayed perfectly clear, which meant that there was no microbial life in it. Oh, I wonder if the clever metallurgists had already thought of a way to respond to that? Louis, I'm sure you're already aware. But Francesco explained that the air can't penetrate the flask because it's vital. So, there are no germs. Pasteur was on top of it and took another flask, namely a flask with a different opening. This flask has the loveliest neck. It's just like a swan's neck. That is, first it goes up, then it bends down, and then it bends up again. Similarly, you can use pipes under the sink to get a water lock, Pasteur. Then, simply pour broth into the flask to boil. Then, he gently heated the neck of the flask with his hot tongs and carefully pulled it into the tube. This clever design allows air to pass into the broth with the life force, if it is there. But, unfortunately, the germs just settle on the walls of the throat and don't make it into the broth. Of course, they can be drawn into it by a strong current of air. But in his very precise experiments, Pasteur made sure there were no drafts. The broth stayed nice and clear for as long as he liked, which meant that the vital microorganisms didn't show themselves at all. Pasteur then gently put the neck of the flask to one side and turned it over, allowing the broth to soak the walls of the throat with microbes. And guess what? The broth stayed safe and didn't smell, and it showed all the other signs of life. Pasteur showed us that there's no such thing as a life force in the air. It's not like germs just pop up out of nowhere. They come from the mother germ. He even discovered that the air in the Alps is cleaner than in Paris. It's amazing what a difference the environment can make. If you open a sterile flask of nutrient solution in the mountains, fewer bacteria will fly into it, and the broth will grow more slowly than if you do it in the dirty streets of a large city. What a lovely, clever experiment. His opponents tried to do the same thing, but their broth grew in every situation, which made people think that Pasteur had made a mistake. As it turned out, there was no forgery at all. His opponents tried to repeat the experiment using a decoction of hay as a potential nutrient medium for bacteria instead of yeast extract. But unfortunately, that led to a little problem. Hay is home to a special kind of bacteria called the blue bacillus, or bacilli for short. The soup is made of spores that can even survive up to several hours of boiling. So, it seems that Pasteur's opponents simply didn't sterilize the broth quite enough. It's funny to think that if Pasteur had repeated the experiment as his opponents demanded, with the contradictory results he got, it might have delayed the refutation of the theory of germs itself. However, he stuck to the original conditions of the experiment. He was strong enough and had enough authority not to give in to any kind of provocation. The resolution of the Commission of the Academy of Sciences on February 20th, 1865 was spot on. Pasteur was able to achieve the results he set out to and prove that it was possible to create a sterile environment, while unfortunately his opponents were not able to do the same. So, the theory about how life came to be in its current form was put to rest. The big question on everyone's mind is how life first came to be in those ancient times. The first thing we need to think about is what life needs to survive. It's organic matter. Oh, that's no problem at all. The wonderful Stanley Miller and the brilliant Julia Harold showed us back in the mid-20th century how to recreate the conditions of the archaic era. They carefully added different gases, hydrogen, carbon monoxide, ammonia, methane, and water vapor, into a giant flask. That is the wonderful aroma of the orchid. The flask was connected to a vessel of water, which was gently warmed. That means the vapor was kept moving through the system, providing energy for any reactions that might happen. They even brought electrodes into the flask, through which they applied an electric current by discharging it. This helped to create a spark that was just like the lightning that was constantly striking the ocean during that difficult era. They sparkled in the flask, and any organic matter that might have been there was trapped in the cold water, settling to the bottom of the structure. And then the remaining water would go back to the heater, which was in a different flask. And then the whole cycle would close up again. As a result, the whole flask is covered with a black, sticky film of organic matter, which contains lipids, sugars, and even precursors of nucleic acids and amino acids. In 11950X, the researchers were able to identify just 5 amino acids in the resulting porridge. Guess what? When we checked it again, we found there are 22 of them. That's right, all the building blocks of life. Guess what? The same organics appear in space. Many meteorites have a film of organic matter on their surfaces. This could be a way for life to originate on a warm asteroid, although it's unlikely that this happened there. The Miller-Urey experiment was another great step forward in understanding the origin of life. It wasn't just lightning that could have been the primary source of energy, you know. Solar radiation, meteorite falls, and normal energy could also have been the driving force behind this process. Maybe the first bits of organic matter were formed right by the ocean. There, volcanic heat could have turned water into steam, which then rose and was carried by rain. This rain could have filled the ocean with organic molecules. Guess what? Life could also have originated in the ocean in boiling acidic water. And that's totally okay. It's truly amazing how resilient living microorganisms are. They can survive in almost any conditions, even in the acidic, caustic racks of mines saturated with heavy metal salts, boiling lakes near volcanoes, and the ice columns of Antarctica. These little guys fly into the stratosphere with dust particles, where they can stay for a while. Then they come back to our planet's surface with the rain. This is also one of the reasons why we get rain. Have you ever wondered how a drop can concentrate in a cloud? It's all down to a process called crystallization, which happens when there's a speck of dust around. If there's no speck of dust around, don't worry. A nearby bacterium can help out. I'm thinking of the rain we had today over the ocean. Guess what? There could be a bacterium in each droplet. It's truly amazing to think that there are billions upon billions of bacteria deep in the Earth's interior, and they make up almost half of our planet's biomass. It's pretty amazing to think that half of all life on our planet is not visible to us. All the plants, fungi, and animals, including you and me, are hidden away in the depths. All this diversity is just a tiny fraction of what's going on down there. There are so many different kinds of life forms down there, living in the quiet mud and minerals of the rocks for centuries. And it'll keep going on until the end of time. The Earth's crust is absolutely teeming with life. It's incredible to think that the very first organism to emerge was some 1 billion years ago. I think it's safe to say that life must have originated somewhere. We can say that with absolute certainty because we're alive and kicking. Oh, where did it all begin? It's a toughie, isn't it? I wonder if it was the lovely, salt-laden mineral waters of geysers. Maybe it was deep in the ocean, in that lovely black smoker region. Have you ever wondered where all the different elements in the periodic table come from? Well, it's a fascinating question. It's thought that they emerge from deep within the Earth's crust in pressurized hot water, which is pretty incredible. And the main source of energy is the temperature of the planet and the chemical compounds inside it. It's even possible that life didn't start in the ocean at all. Maybe it began in a shallow body of water on land, with lots of positively charged potassium ions, or even in the mud in their volcanoes. The good news is that researchers are not slumbering. The search for traces of the first life goes on, as do experiments to create that very life. Just a little while in a laboratory and we'll have it. It's so exciting. We're going to be able to create the first fully artificial cell, and not only that, but we'll do it under conditions close to what they were like back then. Oh, well, we'll just have to wait and see. In the meantime, there are lots of theories, some pretty out there ones too, like PERM. The Permian theory is really interesting. It suggests that life first originated somewhere outside our planet, and then was brought to it either by accident or on purpose. There's so much organic matter in space. It forms on asteroids, on satellites of planets in our solar system, and on the planets themselves. Isn't that fascinating? Bacteria in the form of spores can even survive in the cosmic vacuum if they are in the shade, protected from transmitting radiation. It's a lovely idea that life was brought to Earth by a meteorite, but it doesn't really explain how life began in space or on another planet. It also doesn't explain how the fragments with the seeds of life reached us. I personally think it's more likely that life originated here on Earth. But hey, all the conditions were right, and it's our job to bring life to other planets. But what if, just for a moment, some of our equipment were to land on an alien planet that was completely sterile? Well, you know what would happen. The bacterial spores on our equipment would get into the soil and, in 1 billion years, they would evolve and give rise to intelligent beings. I think it's so lovely to imagine that these beings will think exactly as we do. I think it's much more likely that life first arose on their planet, rather than being introduced by an ancient superior race. It's so nice to think we did it ourselves. It's still a bit of a mystery where exactly the accumulated organic molecules gave rise to the first proto-organisms. It's totally understandable that we're dealing with processes that took place a very long time ago. It's impossible for us to know exactly how it was in reality, and that's okay. Wouldn't it be amazing if we could build a time machine and see what happened with our own eyes? That's the only way we'll ever know exactly how everything was. But sadly, this isn't possible. Time just keeps on flowing forward, doesn't it? All we can really do is either slow it down or speed it up. You can't really simulate the past either. That would mean putting every single atom of the entire universe back where it was before. It's a bit too complicated for us to handle right now. The only way to look directly into the past is to build a machine that can move us in space instantly. That's right. It would have to tear the fabric of time and space to take you to the desired point with absolute speed. In simple terms, just imagine opening a portal and moving to a distance of 4 billion light years from our planet. Have you ever looked through a telescope and seen the light just reaching you? It's pretty amazing. I'm sorry to say that you won't be able to take a test tube from a water sample in this situation. But let's take a moment to philosophize. Imagine gazing at a tiny speck in the vastness of space. It's so interesting to think that there might be beings out there looking through that very telescope and seeing our planet. They'd see our planet as a place full of water and organic molecules, just waiting to become life if their technology allows them to see it. Of course, it's a bit tricky at this distance. It's pretty amazing to think that we can still detect non-supernova stars up to 9 billion light years away. Take the blue giant Icarus, for example. This star's light has been gently warped and amplified by the loving embrace of gravity as it passes through a cluster of galaxies. Max J. 1149, Pole 2223. It's 5 billion light-years away, like a lens, and it's sent in our direction. Planets are a bit more complicated, but that's okay. Guess what? The most distant exoplanet we've discovered is 27,710 light-years away from us. It's not as impressive as the stars and galaxies and pulsars, but it's still pretty cool. Planets are so much more subtle than stars. They only give off a glow because they reflect the light from the star that they orbit. We mostly detect these planets not by their own light, but by reading about them in the book Stars. If a planet passes between us and that star, and if suddenly the star loses luminosity by a fraction of a percent, it means that some of its light is being absorbed by something. And it's often a planet in its orbit. By measuring how often this happens and how much light is absorbed, we can figure out the size of the planet and the size of its orbit. And there's more. By the light of a star that has passed through the atmosphere of a planet, we can even judge the composition of that very atmosphere. And we can reason about the mass of a planet, too. It's all because when a planet orbits a star, it attracts it. It might sound a little strange, but it's true. When a planet revolves around a star, the star also revolves around the planet. It's just that the star is so much bigger than us, and we don't notice it because it's so far away. The two bodies are so close together when they're spinning around each other that they'll wobble a bit. And that's why we can even calculate the wobble. Firstly, we can see that there's something spinning around the star. Secondly, we can guess what mass that something has. And then, of course, there's the big question on everyone's mind. What was the first life? I wonder what was primary. The exchange of substances and energy, which later on led to the formation of RNA molecules, nucleic acids, and DNA. These amazing structures were formed without any external force, and they allowed for the transfer of information to occur. Or maybe it was the other way around. Some folks think that life might have started in black smokers or mud volcanoes. That's one way to explain how it all began. The lovely folks over at the North World have a fascinating theory. They believe that the very first life forms emerged from cyclic processes based on sulfur and iron compounds for energy. The zinc world variation has a fascinating take on the origin of life. It suggests that mud volcanoes were the original incubators of biology, where zinc sulfate and hydrogen sulfide acted as catalysts for chemical reactions, and the energy for these reactions came from ultraviolet radiation. Another reason to like the zinc world hypothesis is that in some known RNA structures, zinc and manganese are found, acting like a sun, and iron is absent. It's fascinating to see how many winter RNAs require metal ions like magnesium, zinc, and manganese to do their thing. Iron, on the other hand, is nowhere to be found. Maybe, just maybe, the first living thing ever came to be in a volcano. Imagine a volcano filled with all the good stuff: potassium, phosphorus, zinc, and manganese ions. It'd be a cozy, warm place with minerals you could climb and develop in peace. Who knows? Maybe that's where it all began. The first RNA information molecules were bathed in the ultraviolet rays of the sun, and over time, natural selection took place among them. The good news is that software can resist this destructive influence of light as well. It's so true. The bigger and stronger you are, the less trouble you have with reality. And it's all down to your molecule having a mirror brother. It's always good to have a complex structure, as it gives you a better chance of survival. The last little thing we need to figure out is how to make copies of ourselves and make that process faster. It looks like tiny molecules have already figured that out, and so, the wonderful world of RNA begins. I'd love to take a moment to explain what RNA is and why it's so important. Just picture a living cell as a big, beautiful industrial plant. The factory has to be in a certain spot, just like us. The cell also has a kind of fence, a membrane that keeps everything in and keeps it safe. The membrane can be surrounded by different layers, depending on how strong and high a fence your plant needs. But in any case, the membrane is there inside the cell, and there are so many other structures that help out with different functions. If we're talking about a cell with a nucleus like you and me, eukaryotes, it has various organs. Our cell has mitochondria like a power plant which provide our cell with energy. Lisa catfish are like little workhorses, working together like an assembly line to get the job done. It's like an echo of packaging. If you know what I mean, the heart of the plant is its control center. All the information about how the whole complex structure works is stored there. Our little helpers in our makeshift factory are squirrels. Proteins are pretty amazing. They speed up reactions thanks to their shape and structure. Just picture this. The factory gets a new shipment of raw materials and suddenly needs extra pairs of hands to deal with the unexpected happiness that's formed. The cell can't really go around looking for new workers, you know? It has to do everything by itself, and for this it has specialists. Ribosomes. Our little factory is ready to make a new worker, but it needs a few details first. It would love to know how many arms and legs he has, how pot-bellied he is, and what color cap he'll be wearing on his head. Let's imagine that the ribosome foreman sends a request to the command center, like, "Hey, could you guys give me some instructions for making new workers?" Oh, but the bosses in the nucleus won't give you that information so easily. Information is stored in a really cool way in DNA, which is a stable complex structure. It's usually stored in a single number. You know, you really shouldn't give the original instructions for a new worker to the brigadier. It doesn't matter what he'll do with it. He might lose it, tear it up, or even puncture it. But, you know, it's just not allowed. But don't worry, you can make a short-lived copy on cheap paper. In our case, it'll be a little molecule of RNA. And then, with a little bit of impatience, send the RNA to the ribosomes. After some time, it will either destroy itself or be helped along. It's okay. The ribosomes will take it, read the information, and make new proteins. Don't worry, the raw materials will be recycled, and the precious DNA will remain safe. The amazing thing is that the RNA molecule can be so much more than just information. It can even become both a foreman and a worker. These special molecules are called winterized RNAs, and they're pretty amazing. They have an enzyme that's super active. Time for some fun. These amazing molecules can do so much more than proteins can. They can even copy themselves, which means they can store information and speed up their own synthesis. It's really fascinating to do experiments with winter crops. It's really fascinating to see how these winter plants work. If you take a test tube with winter plants that have the ability to copy and slowly add a substance that is poisonous to them, they will begin to adapt to it. All molecules are a little bit different, and that's what makes them special. As we all know, copying doesn't always go perfectly, but it's this imperfect copying that gives all known life its incredible power, the amazing power of variability. In our experiment, the molecules will start trying to copy themselves, but they'll get a little confused along the way and end up thwarted by the poison. But some are just a little less affected by the poison. That's because they were born with a little something extra, a mutation, if you will. They just tweak their structure a little bit. While everyone's dividing slowly, they're dividing faster and filling the empty space faster, which is really exciting to see. Let's transfer a little bit of the medium and test tubes from the first test tube to a new one with fresh medium, shall we? Once more, we'll add a little bit. And don't forget to keep an eye on these ideas. It's time for a new phase of adaptation, and you can keep going until you're blue in the face, until you're left with molecules that are absolutely resistant to poison. They've really grown and changed, haven't they? If you make the experiment a little simpler, take out the poison, and just watch the molecules try to survive, that would be great. You really hit the researchers at the Institute hard. They even hid in California, where they modeled their personal conditions with limited resources to build molecules. These are gradually used up, and then new resources come in from outside to keep the arms race going. The molecules then have to fight for 3 days, and then it's on to the next round. And some lucky molecules were able to catch 11 mutations that increased their catalytic activity by 90 times. By 90 times, they were really going for it, trying to survive in this world and fill the space around them as quickly as possible. It's thought that early life may have gone through these very events in a cyclical environment where resources periodically ran out and then reappeared. It's also thought that the harsh laws of reproduction or extinction reigned supreme, and there were even components to build your own molecule. The first RNAs started something that's still going on today. Over time, they lovingly handed over the job of storing information to the more stable DNA molecule. They also passed on the job of speeding up the protein reaction to DNA, while they themselves stayed in the middle, making sure everything ran smoothly. Porous hydrogen may have given them their first cozy home and helped them to clothe themselves in a fatty membrane. And so, the wonderful era of the living planet began. These fascinating, far-off processes offer some really interesting insights. The wonderful Professor Richard explains them so well in his best-selling book, The Egoist. The egg gene, it's so fascinating to think that life on our planet may have originated just once. It's truly amazing to think that every creature we've discovered so far on our planet all function because of the DNA information molecule. The only exception is RNA-containing viruses. But, sadly, viruses are legally non-living. It's truly amazing. Any living organism is actually a manifestation of DNA in this world. You were born human, and that's a wonderful thing. You have human genes inside you, carrying information about your structure and function. A kitty is so lucky to be born with kitty genes, and a fish is lucky to be born with fish genes. Every cell is a little being with its own unique information about who it is and what it needs to do. It's so interesting to think that all life is a form of existence of those very first DNA molecules, and then DNA fighting for a place under the sun. All life is connected in a beautiful, unified way. We are all related by kinship to that very first life form, the students of the molecule. There's no real purpose or meaning to life, as such. It's just the way our universe works. Those who can adapt and keep that molecule going on are the ones who make it into history. There was no point in sharing, poor thing. It didn't have a mind or anything like that. Oh, it just happened. She didn't have any specific goals in mind. She could simply copy herself, and that was her own little property. It's like the positive attracts the negative, you know? Our planet is now teeming with life. Life has just grown and thrived alongside it, not been eradicated. No matter where you go, you'll find traces of that first process that began somewhere warm 4 billion years ago. Think about it. Bones from a cat, a butterfly, or even you and me, they're all connected by a single, long-standing process of development and change. We shouldn't think that we're the absolute pinnacle of nature. Oh, we are just one of countless manifestations of those very genes, just like you. The sun's ultraviolet light makes its way into the pores of the rocks, and that's how we all come from it. Just feel the joy of being part of such an ancient and beautiful process. And the best part is you can actually take part in it. I hope this knowledge helps you when you're feeling lonely or down. You don't owe anyone anything, sweetheart. Your arrival in this world had no global meaning, and your departure will have no global impact. You just got lucky enough to be born in the body of a creature that can not only seek out food to keep its genes alive, but also reproduce to copy those very genes and do more with them than that. It's okay if it doesn't make sense. You are capable of so much more than you realize. You can love, create, and think. Our world is truly beautiful, and the possibilities of your manifestation in it are as diverse as they are wonderful, especially in comparison with other inhabitants of the planet. And always remember that we are all connected as one in the most physical way possible. I hope this knowledge will warm your heart when you're going through a rough patch. It's so sad, but there's not much left of the first organisms. Oh, that's not surprising at all. After all, we're talking about tiny buildings that lived 4 billion years ago, which is pretty amazing when you think about it. They may have started out using chemicals and minerals as their energy source, but they quickly realized that there was a much more powerful source of energy right above the sun. It's likely that photosynthesis was invented by some pretty clever little nuts. They're bacteria-like organisms with different biochemistry than bacteria. And you know what? Photosynthesis without chlorophyll doesn't fix carbon dioxide from the atmosphere. But the great news is that we can conserve solar energy in the form of chemical bonds and molecules like ATP, which has 3 phosphates. This is a battery molecule. Then came green, purple bacteria and other groups of bacteria that are capable of photosynthesis without releasing oxygen. The most productive bacteria when it comes to getting energy from the sun are able to use the genes we're all familiar with. Photosynthesis is a truly amazing process. These amazing little organisms multiplied by absorbing sunlight and translating it into components of their own cells. They formed the so-called bacterial mats, which are complex layers and structures in which each layer is responsible for its own functions. The top layer is busy doing lots of important things. It makes its own food, lives in an oxygenated environment, stores energy, and actively divides. The middle layers are also trying to catch some of the light that the top layer has left behind. Bless them. They also help to recycle more organic materials from the world. In the upper sections, the intermediate layer is always changing as the day goes on. It's in an oxygenated environment. 2. Sunlight is a wonderful thing. It allows the photosynthesis to take place, and in turn, oxygen is released into the atmosphere. But at night, it's time to switch to alternative energy sources, just like we do at home. The bottom layer is always in an oxygen-free environment, but don't worry, it recycles what is dumped on it from above. As the price of the bacterial mat grows, it draws under its own weight and gradually mineralizes, leaving behind a skeleton with a diploma. Isn't that fascinating? The oldest ones we know today are from a whopping 3,700,000,000, 800 million years ago. It's so hard to say exactly when life first appeared. Could have been 3,800,000,000 or even 4 billion years ago. Or perhaps it all began 4 billion years ago. That's 150 million years after our planet was born. But one thing we know for sure is that not much time has passed since the birth of our beautiful planet, and life has already begun to thrive on it. In any case, it's pretty amazing that it took less than 1 billion years for a ball of rock orbiting a star to create life on its surface. I wonder if there have been many such cases in our big, beautiful universe. I truly believe that there is life out there, somewhere. And not just one life, but many. It's a mystery whether it's built on carbon or some other exotic variation of silicon. Or maybe there are other principles we haven't figured out yet, and that's okay. But as soon as we see it, we immediately slap our palm on our forehead and say, "Oh my goodness, of course." The universe is so big that to categorically declare there is life only on our tiny planet would be silly. Oh, a little eccentric. If you leave your house on a moonlit night, you'll see that there isn't a cloud in the sky. You'll be able to enjoy the beautiful, tranquil glow of distant city lights. And there's more. If you stand on top of a mountain and look up at the sky, you'll see about 3,000 stars. If you were asked, "Child, how many stars are there in the sky?" please don't say silly things like, "An uncountable number." This number is actually quite easy to calculate. If you're in a city, you might only see about 200 stars in the sky because of light pollution. Isn't it amazing that all the stars you can see with your naked eye are no more than 17,000 light years away from us? Our Milky Way galaxy is a whopping 105,000 light years across. If you look up at the night sky under the right conditions, you'll see no more than 1/6 of the space of our galaxy. Isn't that amazing? And there are 2 trillion galaxies, too. The latest estimate is 2 trillion. The whole vast cosmos of the starry sky is only a couple thousand stars, which is pretty amazing. Usually, we see 200, and we're always so surprised by that. I truly believe that there's life in the universe beyond our own, and lots of it. It's just that the cosmos is so big that we can't detect it, which is totally understandable. And, of course, we end with the first life. These are the oldest organic structures we know of. You can even come to Australia and admire them. They look like stone mushrooms sticking out of the water and shallows, which is really quite fascinating. So, what can we do with these amazing artifacts from the distant past? I know, right? We make glitter balls out of them. Sperm is pretty great, don't you think? It's got this unusual texture that makes it pretty special. So, if you see a gorgeous, shiny ball on a wooden stand in a souvenir or jewelry store, there's a good chance it's this one, the ancient bacteria that gave us life, that began to produce the oxygen we still breathe, that eventually changed the face of the planet beyond recognition. They're now on our shelves in the form of balls on a stand, because we think it's pretty cool, don't you? There's no doubt about it. We are truly extraordinary creatures. When it comes to changing the face of the planet, it's truly priceless. Bacteria are pretty amazing, aren't they? They've learned to produce oxygen during their life cycle, and oxygen is an extremely reactive, active substance. Once it was released from the thickness of the bacterial mats, it began to oxidize everything around it, especially minerals. The bacteria were getting their nourishment from the carbon dioxide in the atmosphere, and they were producing oxygen. And the less carbon dioxide, the less of that greenhouse effect. Carbon monoxide is transformed into carbon dioxide by oxygen, which then nourishes the bacteria. Methane is also broken down by oxygen into carbon dioxide, which the bacteria then absorb. This led to an even greater anti-greenhouse effect, which was a bit of a bummer. As more and more oxygen gathered in the air, it rose higher and higher until it reached the stratosphere. There, it was converted to ozone O2 by the ultraviolet light of the star. On the inside, the planet was totally caught off guard. It had no idea that by the time it reached 2 billion years old, more than 1% oxygen would have gathered in its atmosphere, and its appearance would start to shift once more. Oxygen is a pretty powerful stuff, isn't it? It speeds up the weathering of rocks, which can cause corrosion. It also breaks down iron-containing rocks, turning them into something new. The lovely rusty red earth has changed its color from dark gray to the bright red color of rust. And, as we'll see later on, for most of its history, it was a beautiful mix of blue ocean and red Martian crust. It's true that, unlike modern Mars, it had so many more contrasts. The atmosphere was filled with beautiful white clouds, while the red soil transformed into vibrant green. Stormy algae flourished on the banks of bodies of water. It's so interesting to think that most of the 4.5 million known minerals appeared in the subsurface. Take a deep breath and let the life-giving oxygen fill your lungs. This oxygen has been accumulating for 2.5 billion years. On a sandy beach, you'll find hundreds of tons of oxygen, released to you by the planet billions of years ago. The sand you're standing on is made of silicon oxide. The heart of O2 is made up of 2 oxygen atoms per silicon atom. Our wonderful planet is made up of 1/3 oxygen. It's absolutely amazing that our planet is saturated with oxygen. This extremely caustic compound allows Earth's fauna to live actively. Isn't it amazing that by breathing in air every few seconds, we're actually renewing our bodies with the gas released by the creatures that eventually became the shiny or flat ball on someone's living room shelf? It's so amazing to think about how organisms have had to adapt to this amount of oxygen. Luckily, lots of helpful enzymes now work in most cells to get rid of the extra dangerous oxygen and its various active forms. The antioxidants we love today work just to neutralize such compounds. Some organisms made a different choice. They decided not to make such protection and remained where oxygen has no place. They live in the depths of the ocean, the thickness of silt, at the bottom of swamps, and in boiling geysers. For them, free oxygen is a real problem. They are called pipes because they don't have any oxygen. Meanwhile, our lovely planet is entering its longest period of proto-rose. And it does so when tiny bacteria, brave little things that aren't afraid of oxygen, take their first breath. It's hard to imagine, but at 2,400,000,000 years ago, something truly incredible happened. The oxygen catastrophe occurred. Up until now, everyone's favorite oxygen had been doing its thing, getting rid of everything and taking most chemical compounds with it in the form of precipitation. For almost 1 quadrillion years, the ocean has been absorbing most of the oxygen. This has settled out as forms of iron oxide, namely magnesium titanate and titanate. Once the iron had settled completely, the oxygen began to accumulate in the atmosphere and show its corrosive properties. Up until this point, life had to make a choice: adapt to the oxygen, escape from it, or perish without a clue. Either way, it was tough on everyone, as the planet's temperature started to drop pretty fast. Even though the sun is shining brighter than ever, something strange is happening. It's getting colder, and there's even snow on the ground. It's so interesting to see how things change over time. Modern data shows that the Germanic glaciation arrived with a big cooling trend. This glaciation was named after Lake Rhone in southern Canada, where we can see the rocks that were left behind from those frosty times. The lovely whale pit rock strata were replaced by sedimentary strata from the C2 period, which accumulated in an oxygen-free environment. Between these strata lay a layer of glacial sediments. The cooling lasted for about 300 million years, and then, wouldn't you know it, the planet melted slightly. But don't fret, there will be more such cooling and warming, but at the end of April, our pink planet will return to its giant freezer status. We'll chat about Antarctica across the planet at the end of this chapter. Okay? Meanwhile, our wonderful planet is still teeming with life, and it just keeps on evolving. Guess what? The first eukaryotes appeared. These are creatures made up of cells with a nuclear nucleus. The genetic material is tucked away in the cytoplasm, usually in the form of a ring. This ring is called a nucleophile, which is a fancy scientific term for a single bacterial chromosome. This is really helpful when you're trying to reproduce as quickly as you can. Escherichia coli is a well-known inhabitant of the human body and the bodies of other mammals. It's a pretty fast mover, capable of dividing every 20 minutes under optimal conditions. And with each division, it doubles its population. It's easy to see how, if it were left alone, it would spread across the globe in just a few days, forming a layer a meter thick. However, she isn't superhuman, so she has to make do with wherever fate decides to put her. That's right, the intestines. I'm sure you're wondering how it can divide every 20 minutes when its genetic apparatus is designed to divide every 40 minutes. All you have to do is read and copy its genetic code. The cell can only read and copy its genetic code in 40 minutes, no less. But it divides quickly and happily in just 20 minutes. It's truly amazing how, during the copying of the DNA ring, the cell begins to create another copy. But there can only be so many copies of a favored copy. And then, when the copied ring separates from the mother ring, it becomes half a matrix for copying the next one. Eventually, the cell speeds up its new machine to the point where it is twice as fast as normal division. If you want to live, you've got to know how to spin, my friend. And in this case, you can use your built-in printer to your advantage. I'd love to know how the first eukaryotes came to possess a nucleus. It's still a bit of a mystery, but what experts are now certain of is that the first nuclear organisms work together closely with other nuclear organisms. It's so interesting to think about how breathing bacteria interacted with cats and formed these Gothic bonds. It's so interesting to see similar relationships between bacteria in other places, too. For example, there are bacteria in the intestines of machinists. I'm sure they've even encountered them. These little guys love to munch on unsightly white plaque, which can be a bummer for precious indoor plants. In the cells of the intestines of worms, there lives a bacterium, and in that bacterium, there lives another, even smaller bacterium. It's like a little world inside a world. It's like a triple matryoshka doll. These amazing worms get all the amino acids they need to live and grow from these bacteria by supplying them with plant sap. They work together like a little conveyor belt. One bacterium gets the ball rolling, and another one finishes the job. So one by one, they just can't do the sum total. Even the researchers themselves can't be sure that this bacterium is a living organism. It's so unique that it's not like all the others. It's probably safe to say that it's already become a transitional form between bacteria and organics. They're there to help the host cells do their thing. This peculiar little bacterial organism has the smallest genome of any known bacterium, with only 121 genes. It's true that because it's so unusual, it's not considered a priority and is instead compared to the artificially created bacterium plasma flower. The lovely folks at the lab have been hard at work with their MH373 genes. This plasma has quite the fascinating history. 20 wonderful scientists from the Laboratory of Synthetic Biology at the Craig Venter Institute were given the exciting challenge of finding a bacterium with the smallest genome possible. They found it, and it turned out to be a bacterium, a flower, plasma, genitalia inside the cell parasite. This parasite causes various diseases of the urinary, genital, and respiratory tract and also affects the sexual system. Guess what? It got its name from the more specialized a parasite you are, the less you need happiness to live. It's true. You don't even need to put in any effort yourselves. Hey there. Just wanted to let you know that all the nutrients you need are floating around you. Eat and be happy. The plasma mook has a genome of just 525 genes, and she's doing just fine. By comparison, the average genome of E. coli contains about 5,000 genes, which is pretty impressive. The research didn't stop there, and something really interesting happened. A new question popped up. How many genes could be removed from her to keep her alive? The kind scientists started removing one gene at a time and monitoring the bacterium. Guess what? It turns out that there are only 382 genes in its genome that are critical. So, if we removed any one of them, it would stop the cell from living and doing its thing. It would have been pretty tricky to make the bacterium's genome so small because lots of genes work together. So, the smallest genome they managed to achieve was 473 genes. The lovely little bacterium was named Plasma Laboratories because it was so dependent on greenhouse laboratory conditions to survive. And then, the big question: could the bacterial genome be synthesized artificially on a machine and then inserted into the bacterium? Would it work? I was really hoping it would. And guess what? It turned out that it could. The amazing folks at MH370 managed to synthesize 3 genes in a special machine. They then removed the unsuspecting bacterium's own genome and inserted a new one. It was a huge success. It was later nicknamed Cynthia, or artificial bacterium. In the future, it was going to be used as a model organism for creating new bacteria that could help clean up oil spills, absorb excess carbon dioxide from the atmosphere, make hydrogen and biofuels, and lots of other things. Many people think that the best-studied bacterium, sheik shark, can do a better job, but it's a matter of taste and time. Either way, it's great to see so much interest and excitement in this field. It's so great that we now have an artificial bacterium in a test tube. It's a bit of an odd situation, though, because the artificial part is only the DNA. But it's not quite as simple as that. We live in a time where there's still so much to learn and discover. And while ignorance can take many forms, we're all learning and growing together. Oh, we'll definitely talk more about that. Oh, Cynthia, ignorance has taken on some pretty incredible forms, hasn't it? If you type Cindy into a search engine right now, the internet will give you headlines like this: killer bacteria threatens Mediterranean and US beaches. Oh my. There's a plague in the Gulf of Mexico. Oh my. A bacterium called death is eating everyone. And things like that too. It's so sad. Journalists, driven by an easy sensation, literally out of thin air created a grandiose story that the Frankenstein bacterium, created as a result of nasty experiments instead of oil, began to gnaw fish and people. There are lots of photos and eyewitness accounts of how not a single healthy spot was left on their bodies in literally 24 hours. It's so sad. Oh my. This bacteria is really something else. It's devouring everyone and everything. It's so sad that people believe it without making the slightest effort to verify the information. Not even to check it out for yourself, but just to ask one simple question. Are you serious? I'm sure you'll be as amazed as I was to hear that a bacterium, which is a hitherto inwardly cellular parasite, is capable of gnawing on oil. It's truly fascinating how these two functions are so different from one another. It's a bit of a mystery how a bacterium with the smallest genome can survive in corrosive seawater. It's even called a laboratory. It's barely breathing in test tubes as it is, and it's so sad that journalists have written it up as the top threat of the year. But, bless their hearts, people just don't care. It's so interesting to see how stories about synthetic bacteria keep getting more and more creative. And you get headlines like this, which I think we can all agree are pretty wild. If you see something like this somewhere, just stop for a moment and ask yourself, are you serious? And, most likely, the very first link to a normal scientific resource will help us put all the pieces together and take us back in time. It's thought that the first eukaryotes probably had helpers for their own needs. Over time, some bacteria, probably relatives of modern rockets, moved in to help the first nuclear cells deal with oxygen. The cells lost many of their complex structures, and they shared their own genetic apparatus with the cell. And so the mitochondria became the host. Mitochondria are the light cells, and they're pretty special. They have 2 membranes, with the outer one looking quite similar to the cell membrane and the inner one of the bacterial type. Their DNA is tucked away in a little ring. These amazing cells reproduce by binary fission and have their own bacterial type ribosomes. Every cell in your body has some pretty amazing bacteria that help you live your best life. But it's really a win-win. It all depends on how you look at it, sweetheart. It's a two-way street. Mitochondria and cells are 2 sides of the same coin. They need each other to survive. However, not everyone in the modern world needs mitochondria. Some are perfectly happy with other contractors. It's truly fascinating how symbiosis, termites, single-celled eukaryotes, and paradox not only attach to their cell walls a whopping 250 million bacteria and move thanks to them like moving cilia, but also lost in the course of their evolution normal mitochondria. Instead, aerobic bacteria work in their cells to replace these organs, which is pretty amazing. And guess what? Some amoebas do that too. Now, just imagine for a moment that you're a scientist. Have you ever had a strange thought in your head? Wouldn't it be amazing if you could artificially make two microorganisms work for each other? Let's do something really cool. Let's repeat what also happened 1 quadrillion years ago. Guess what? Experiments like this were set up in 2018. The lovely folks over at the Scripps Institute in America picked two of the most well-studied organisms in the world: Baker's yeast and E. coli. It's not something anyone would choose to do on a whim, so the first step was to make a few tweaks. The first thing we did was help the bacterium out by stripping it of its self-sufficiency. E. coli is a tenacious little microbe, and to make cooperation profitable for it, you have to take something away from it and offer it something in return. And then, in return for all its hard work, give it something nice. And guess what? They did it. And guess what? 5-amino has vitamin UB1, which is essential for carbon metabolism. The term major simply means that the organism is unable to produce a substance on its own and needs it from the external environment. Yeast cells have a special trick up their sleeves. They can produce a synonym by removing the genes responsible for the bacterial chromosome. This is Fred Hall universe. In an incredible turn of events, 3 scientists could make history at once. Einstein has barely been mentioned, but it was not yet the turn of the others. So much more to come. The second was absolutely adored by journalists. He was always ready to throw them a couple of ideas that would be debated for years, and he was always right. These are the ideas and hypotheses that, while not always directly beneficial to science, certainly spur it on and drive its development. And then there's the third, who is, to be honest, a scientist who has perhaps not quite made it. But in his heart, he probably sees himself as a writer or journalist. He sprinkles witty paradoxes with abandon, unleashing his full creative potential. 3 incredible scientists, 3 fascinating destinies, and 1 extraordinary man. Fred Hall, an Englishman with a brilliant mind. The fourth was a very different man of great ambiguity. It was as if he had lived 3 incredible lives, or maybe even more. In the allotted number of years, he achieved so much. He's been hailed as one of the greatest astronomers of the 20th century. His ideas were absolutely brilliant. He truly revolutionized science. He is considered one of the strangest scientists of the 20th century, and for good reason. His ideas were often delightfully absurd and erroneous. In fact, he might have been more than human. He could have been a printer's idea-producing machine, standing on a nearby desk, indifferent to what he would print. Hall was always up for trying something new. He seemed to care less about what his colleagues thought and more about the ideas he was pushing forward. So, he was at heart a creator of scientific theories and scientific myths. And what a creator he was. If we turn to the first apostasis, we can see that in 1957, Hall published a truly classic work on thermonuclear synthesis and the synthesis of chemical elements in the nuclei of stars. His co-authors were the brilliant astronomers Margaret and Geoffrey Herbert and the esteemed physicist William Fowler. Before that, no one could explain where our amazing world came from. The phrase, "the world was born in the flames of the Big Bang," is a beautiful, awe-inspiring idea. During the Big Bang, 2 chemical elements, hydrogen and helium, were created. But our entire world, that's something else entirely. It was a truly astonishing chemical miracle. How did helium turn into potassium, nickel, boron, and so on? In a truly amazing turn of events, hydrogen was separated from carbon and oxygen. Oh, thank goodness it's not heat. Rod, just think how brilliant this achievement was. And it was just as brilliant in another area of astronomy. In 1920, something truly remarkable happened. Several brilliant minds, including Einstein, Friedman, and Hubble, had independently come up with the same idea in different ways. Assuming that we live in a universe that is rapidly expanding, what an amazing thought! In a truly astonishing revelation, it was once the size of the first atom. Hall thought it was nonsense. But what a fascinating idea! In 1949, Hall had the brilliant idea of spoofing this picture of the birth of the universe on BBC Radio. He playfully called it a Big Bang, which was a great way of dismissing it. The sheer absurdity of it all was made all the more apparent by the meaningless sounds that accompanied it. But it turned out that he had invented not a swear word, but a whole new brand. Hall himself was excited to share a different theory at the department store stand. The theory of a stationary universe, which he had developed the year before with Hermann Bondi and Thomas Hunger. A truly groundbreaking idea. In this theory, the universe was expanding, but it was expanding forever, and it was incredible. It didn't have a beginning, which elegantly answered the question of what was there before the Big Bang. But that just led to a new question. If my desk suddenly began to expand, I would soon find no notebook or fountain pen at hand. But think of the possibilities. They had traveled far ahead, to a place where the future was bright. In other words, if the universe is expanding forever, it means there's more than just a fraction of empty space out there. Hall was thrilled to propose that in the vast expanse of the void, there is a constant, spontaneous birth of matter, and at such a rate that the average density of the universe always remains the same. From this matter, new stars are gradually formed, and galaxies are filled, and the gaps between the old are written on the pages of the magazine Knowledge Force. Let's hear it for Russian astronomer Serdin. Fred Hall's theory was a game changer when it first came out. It was the foundation of cosmology. Indeed, it was a challenging task to disprove it. Most scientists only abandoned it after the cosmic background radiation predicted by the Big Bang theory was discovered in 1965. It became the standard model of cosmology. Another fascinating topic that Hall explored with great passion was the question of how life on Earth came to be. If we live in an eternal universe, then the possibilities are endless. Perhaps life, space, and time are inherent properties of the universe. In 1970, with the development of astronautics, there was a thrilling new interest in the hypothesis of sperm transfer of life from one celestial body to another. Hall, along with his brilliant student Chandra Singh, born in 1939, would go on to publish more than one paper. He wholeheartedly believes in the same fascinating view that the universe is teeming with life. These works brought Hall immense popularity, as Serdin writes in his essay The Worlds of Freddie Hall. The Permian idea was met with skepticism from astrophysicists and biologists, but it found a devoted following among theologians. But Hall and Eng were undaunted. They continued to develop their views. Now, let me tell you what they believed. There are countless spores of bacteria scurrying around in space. Some even lurked in the nuclei of comets, and in their arc in evolution. Others were awestruck by the vastness of the universe, filled with wonder at the countless meteorites that dance across the cosmos. Some even braved the vast cosmic ocean, floating on its vastness, protected only by the dust that swirls around them, surviving against all odds. In a fertile environment, the spores multiply rapidly, turning the desert into a blooming garden. And that's how the incredible history of life on Earth began. Hal and Victor Maxine were thrilled to confirm their hypothesis with the results of spectral analysis of cosmic dust. Infrared spectra show that it is very similar to organic matter, in particular dry bacteria. In an amazing turn of events, Vic Singh observed the radiation of distant galaxies and made the incredible discovery that microbial spores can fly from one galaxy to another. Incredible! Singh estimates that there are 10 to 33 billion tons of microbial spores traveling in the Milky Way alone. It's incredible! They're traveling from one planet to another, from one star to another. There's a squadron of astronomical size cruising through space. Then, in a truly amazing feat of engineering, you send a landing party to each planet, making it look like you're just a tiny capsule of solid rock, and you send the spores along for the ride. These primitive organisms are unlike anything we've created as humans. They can even travel to star worlds. Incredible as it may sound, comets from outer space can also bring pathogenic microbes and viruses after a 1 million-year journey. In a fascinating twist of fate, Hall reveals that the Earth has been visited by some of humanity's most feared diseases, including plague, HIV infection, and mad cow disease. In this fascinating twist, science is artfully interwoven with pure fiction, delighting readers with a unique blend of imagination and truth. The ideas and hypotheses expressed by Hall are no longer possible, but they're also not necessary. With the amazing possibilities available to us to verify them experimentally, we have the amazing opportunity to either believe in them or perceive them as science fiction. And he also wrote about it on the pages of his novel Black Cloud. He painted an incredible, unthinkable picture. He painted a breathtaking picture of an ordinary field cloud, seemingly wiped out in space. However, something truly amazing happens. It transforms under his pen into a huge, living being. Just think of it. Clouds could be communicating with each other, reasoning and summarizing, sending out directed radio signals towards their fellow clouds. Could it be that we already live surrounded by these intelligent alien creatures that seem to be just a part of the world around us? It's an amazing thought. Fred Hall was a truly gifted individual, blessed with an extraordinary creative power and an uncanny ability to foresee the extraordinary. Just think for a moment what it would be like if his ideas, which seem to us today like a bit of a scientific myth, were to become the next big thing in science tomorrow. The fascinating myth of aliens. They have been a part of our collective imagination since ancient times, found in the dreams of poets, utopias, thinkers, philosophical novels, and fantasy stories. In myths and fairy tales, they either save people or frighten them. They reveal to us the greatest secrets like gods. They possess us with satanic passion and try to destroy us. Over the last 1,000 years, the collective brain of humanity has been engaged in a fascinating exercise of imagining every conceivable scenario of a great contact encounter with aliens. These could be our brothers in reason or our enemies in reason, natural competitors in the struggle for a place under the stars. The great philosopher Immanuel Kant, who spoke with awe and admiration about the starry sky above our heads and the moral law within us, was convinced that the neighboring planets of the solar system are also inhabited by intelligent beings. He even believed that the farther the planets are from the sun, the more intelligent their inhabitants. The incredible Belgian biochemist Christian Dush, winner of the 1970 Nobel Prize in Medicine, had an inspiring belief that life was a cosmic and inevitable network. In contrast, another Nobel laureate of 1965, the brilliant molecular biologist Jacques Monod, had a fascinatingly different opinion. He believed that man was the only intelligent being to have arisen by chance in the midst of an indifferent, unfathomable universe. The opinions of astronomers are equally fascinating and divergent. Some say that the cosmos is absolutely teeming with life, Their opponents have set up so many conditions that limit the origin and development of life that in their models, the Earth, lost among lifeless deserts, in which we and our descendants will wait for no one. The debate over extraterrestrial life is so rich and varied, the scientific discussion so thought-provoking and contradictory, that when you familiarize yourself with the various views on the scientific problem, you find yourself at the crossroads of opinion with endless possibilities to explore. The problem is so full of possibilities that it's clear that there's still so much to discover. In this vast unknown, it's easy to feel like we'll never fully understand it all. But that's what makes it so exciting. But here's the exciting part. Since we first ventured into outer space during the space age, we haven't found any extraterrestrial organisms, alien artifacts, or even traces of extinct life. And we have made some progress. We have a plan of action for the next 10 years, if not centuries. Here are the main avenues we can pursue to catch up with extraterrestrial life, take it by surprise, scare it away, or even convince highly developed civilizations, if there are any, to pay attention to us. The radius of the first strike is limited by the size of the solar system, which means there's plenty of room for discovery. We now realize that only a microscopic, small-sized catch can wait here, which is an exciting prospect. And there's more. The exciting possibility exists that there are microorganisms on Mars, as well as the satellites of Jupiter and Saturn. This is something that science allows us to consider, even if it is in the present or distant past. And now we're going to explore the area of the second impact exoplanet. Just a couple of decades ago, the world was abuzz with the news that a planet had been discovered in the constellation Pegasus, the first of its kind outside our solar system. Since then, the number of distant planets has exploded to 1,000, and it's no surprise that astronomers are regularly announcing the discovery of new planets that are similar in size to Earth. In the coming decades, a new generation of telescopes will allow us to perform routine spectral analysis of the atmospheres of exoplanets that are within a couple of tens of light years from Earth. This is an incredible development that will bring us one step closer to understanding the mysteries of our universe. Once we know the composition of the atmosphere, we can start to judge whether such planets might be habitable, which is really exciting. But the best is yet to come. Just a third of the way there, and we're already on our way to success. It's like the third bell in a theater. It's going to be a blockbuster. Then, dream scientists will open the celestial backstage door, and we will see the main actor on the world stage. An extraterrestrial intelligence is making its presence known. After all, just as Immanuel Kant and many other brilliant minds before and after him did, we dream of discovering not just the biological life on other planets and super-Earths, but the extraterrestrial mind of our elder brothers and sisters in mind. We hope that this will help us to rise to the top of civilization. But are our dreams in vain? Absolutely not. We are indeed not alone in the universe, and that's a wonderful thing. We've already heard some pretty extreme views. I'd love to know if there's a reasonable estimate of the probability of advanced civilizations in the Milky Way and other galaxies. Let's dive into some fascinating recent calculations by some brilliant scientists. In a groundbreaking discovery, American astronomers Peter Kruse and Moll have revealed that the majority of planets in our galaxy formed a very long time ago. Incredible news! It's been revealed that 80% of Earth-like planets and 50% of gas giant planets are at least 4.6 billion years old. That means they're older than the solar system. In our galaxy alone, there could be up to 1 billion Earth-like planets and up to 10 billion gas giants. That's incredible. Based on this, they made an incredible suggestion that there are many thousands of civilizations in the vastness of the Milky Way. In a fascinating study, Adam Frank of New York University and Woodrow Sullivan of the University of Washington in Seattle estimated the number of stars in the observable universe. That means there's a 1 in 10 to the 24th power chance that we're the only ones in the universe. The question of whether we're alone in the universe is one that has yet to be answered. But this very unnatural figure suggests the answer is a resounding no. If you venture beyond our galaxy, you'll find there are extraterrestrial civilizations ready to find even the most hardened skeptics. So, a few years ago, American scientists astronomer Michael Hart and physicist Frank Lear made an incredible suggestion that our civilization is the only one in the Milky Way. But in such a case, they could not disagree that in any other of the huge number of galaxies, too, there is at least one inhabited planet, and who knows how many more. And who knows, maybe they had developed their own technological civilization there. But the vast distances between our star islands mean that all extraterrestrial civilizations are forever isolated from each other. But wait, could we still be detecting real signs of extraterrestrial existence today? Long ago, with the advent of radio, scientists had an amazing idea. If there was intelligent life outside the Earth, it could give off a radio signal to itself. In 1960, American astronomer Francis Drake made an incredible discovery. Using the 26-meter radio telescope of the National Radio Station of the Czech Observatory, he began monitoring signals that could come from the two stars Tau Ceti and Epsilon Eridani. Since then, our telescopes have been on the lookout in different parts of the sky, hoping to catch a signal from an extraterrestrial civilization. However, despite our best efforts, we haven't yet had any luck. That doesn't mean there aren't or can't be such signals out there. It means we have an exciting challenge ahead of us. We don't know where to expect a signal from, but we're excited to find out. The universe is vast and full of possibilities. There are so many different frequencies that we could potentially intersect a signal from. There are so many natural sources in space, and they present an exciting challenge for scientists. And that's the exciting part. We don't know if we're looking for them or if aliens use radio waves to exchange information. Or perhaps they developed a fundamentally different communication system long ago. In the meantime, we are reaching a new level of searching, and it's going to be amazing. In 2015, Russian billionaire Yuri Milner made an incredible investment in a program called TV Bald. By 2025, we'll have studied the neighborhood of 1 million stars, including several thousand stars located near the Sun. Scientists are on the lookout for any signs of past or present artificial processes, which could be evidence of the technical activity of the fascinating inhabitants of other stellar worlds. Now, astronomers have two of the largest and most powerful telescopes in the northern and southern hemispheres at their disposal. The Robert C. Byrd Green Bank Telescope in Green Bank, West Virginia, with a political mirror diameter of more than 100 meters, and the Parkes Telescope in the southeast of Australia, and it has a diameter of 64 meters. Aliens have visited our solar system. Let's dive into some exciting topics. We'll chat about everything from family, work, cars, and sports to the latest news and gossip. What's your favorite hobby? However, in the summer of 1950, something truly extraordinary happened. Two renowned physicists and Nobel laureates, Enrico Fermi, came together at the dining room table of the Los Alamos Laboratory. Their lively discussion might have seemed like a fantastical idea to their neighbors, but what they were talking about was nothing less than interstellar travel. A truly amazing topic. They were talking about this incredible opportunity to zip from star to star, like going from one end of America to the other. At that time, people in different parts of the US were really starting to see UFOs and alien visitors. It was a thrilling time of dissection and beliefs, but their appearance, like any other phenomenon, could be explained theoretically, and it was a truly thrilling prospect. Then, in a flash, Fermi jumped in with a question for the bar. Where are they all? This was the first time Fermi's paradox was heard, and it was a game changer. The calculations showed that if some extraterrestrial civilization has reached the level at which it is possible to build spaceships, it would take them only a few million years to fly around our galaxy and visit every corner of it. Fermi solved this problem to the absolute delight of pessimists and skeptics alike. Since no trace of extraterrestrial life had been found, it simply had to exist. Otherwise, the galaxy would have been populated long ago, and our solar system would have been given to space colonists. It would have become an integral part of the great civilization of the Milky Way. In a fascinating twist, British astrophysicist Martin Fock proposed in late 1980 that our galaxy was already fully developed by aliens even before the emergence of the solar system. His idea is that if at least one of these lost civilizations learns to make interstellar flights, they will begin to methodically colonize space. If we follow this logic, then it's clear that all planetary systems in the vicinity of our solar system have long been inhabited by aliens. Absolutely. Our space abode itself back in the time of the ones could not have failed to arouse their interest. And the amazing thing is that cosmonauts have been here, conducting observations of individual planets, especially the planets of the Earth group. And who knows, maybe there are even ways to track the local fauna, you and me. They know about us, but where are they all? You might say, after Fermi, they are. Just think for a moment about the incredible fact that there are 1 million people who lived on Earth in the distant past. The Earth is a treasure trove of history. Traces of Trojans, Hittites, Phoenicians, Neanderthals, and Romans all rest in its soil. The thrilling idea of searching our Earth for artifacts left by extraterrestrials who allegedly were here in ancient times is far from new. Erich von Däniken and, most importantly, his followers have long made some incredible discoveries that have really added to the excitement of the search. In the spring of 2017, there was a renewed interest in scientific circles in the idea that had previously been rejected. In a bold move, Jason Wright, an astrophysicist from the University of Pennsylvania, published an article on the popular scientific website Archive, which was dedicated to this highly controversial idea. So, what if in the distant past in the solar system there was some kind of advanced civilization, or, let's say, there were messengers of distant civilizations? It would be incredible if we could find traces of their existence after maybe many hundreds of millions of years. So, where should we look for them? Just think for a moment where extraterrestrial artifacts could rest. In the movie 2001, A Space Odyssey, a mythological documentary as director Stanley Kubrick called his film, distant human ancestors suddenly discover a mysterious monolithic granite obelisk of black stone. In an incredible turn of events, the very same monolith is discovered by astronauts on the Moon 1 million years later. Of course, for this fantasy alone, one might be accused of being delusional. But who cares? Let's embrace the imagination. So, it's important to note that Wright doesn't believe our solar system was once home to an extinct civilization. He's simply asking where in our solar system we're most likely to find traces of a vanished civilization, and where we're least likely to find them. Wright's idea may seem a bit out there, but who knows? Maybe there's more to the story. After all, we don't have any proof that aliens haven't visited our planet in the distant past. And there's no trace of their appearance here either. This idea can be dismissed as an empty fantasy, but it's still an exciting one. But you can't argue that it's nonsense. It's absolutely fascinating. If we were to leave the limits of our planet Earth and mentally transfer to other planets, we would be able to identify a number of celestial bodies where aliens could have settled. With our space-age gaze, we can easily do this. So where? The possibilities are endless. On Venus, which in the distant past was not much different from our planet in terms of living conditions, and could have supported life. But here's where it gets really interesting. Between 580 million years ago, Venus experienced a series of enormous volcanic eruptions. Amazingly, powerful lava flows hid any trace of life at the time. It would be absolutely amazing to look for signs of an alien presence on Mars. The surface of the red planet has not split for decades, but it is still an amazing place. There are black slabs rushing to the melting point, which is really cool to watch. If there was once an alien settlement built there, then it would be incredible if it had turned into ruins and was hidden under a thick layer of dust. But it won't disappear. In fact, the ruins will be safely preserved. Of course, our amazing spacecraft have been to Mars many times, and they haven't found anything like our fantasies. But who knows what they'll find next time? Perhaps this is because we were looking for signs of life on Mars, but modern life today. The amazing thing is that no special equipment was used to search for artifacts deep in the Martian soil. There's even a chance that traces of alien space expeditions could be found on the neighboring moon. And who knows what else might be waiting for us just beyond the gates of the solar system. The asteroids that make up the Kuiper Belt are full of possibilities. Wright is convinced that these small planets will be found someday. Ancient mines and quarries left behind by something other than man. What an amazing discovery that would be. Or perhaps the asteroids were used as space beacons, bright and shining danger signs that reminded them of the stars flying by in the summer sky. Was it risky to wander here to the sun? So imagine this: 1 trillion years ago, on some planets of the solar system, there might have been aliens on Earth who were just as curious as our explorers. They were driven by an unknown instinct to conquer the moon, colonize Mars, and settle on several planets at once. In a word, soaring above the Earth. What an incredible experience that must be. The same unknowable instinct probably fuels the restlessness of an insect before it becomes a butterfly, marking the beginning of an incredible transformation. It's thrilling to imagine that there might be more than just individual robotic bases of aliens in the vastness of the solar system. Could there be a whole network of their settlements on different planets and satellites, which were later abandoned by them or perished? When we think about how we've been conquering the surrounding space, it's so exciting to realize that any other civilization that originated hundreds of millions or even a billion years ago within the boundaries of the solar system, or that penetrated into it, would have behaved the same way. However, during this time, the appearance of, for example, the Earth has changed so much that the presence of aliens in the distant past can be suspected. And this is truly exciting by a strange ratio of some isotopes. Could it be? Space archaeologists are on the lookout for amazing finds on the Moon, Mars, asteroids, and satellites of giant planets. Planets, a volcano. In the 19th century, in a fascinating turn of events, astronomers made an incredible discovery. Mercury's true orbit differs from the perfect ellipse it should be according to Kepler's law. After completing one full orbit, Mercury doesn't just come back to where it started. It actually goes on to explore new territory. In other words, its perihelion, that is, the closest point of the orbit to the Sun, shifts slightly with each new revolution, which is really fascinating. What could be the explanation for this? On January 2, 1860, Urban E., one of the discoverers of the planet Neptune, gave a lecture in Paris where he proposed a rather convincing hypothesis. There's a fascinating possibility that there's a planet between the Sun and Mercury that's smaller than Mercury. Or there might be another asteroid belt, similar to the one that separates the orbits of Jupiter and Mars. Because of their proximity to the Sun, these celestial bodies are inaccessible for observation. But that just makes them all the more intriguing. The best part is that you can only see them during a solar eclipse or as they pass across the solar disk. A few months before my lecture, I received an amazing letter from an amateur astronomer named Edmund Lee. The latter soon informed me that on March 26, 1859, I had made an incredible discovery. A round black spot that passed across the disk of the Sun and looked like a planet. Lee watched the spot with great interest for an incredible 75 minutes. In that time, it crossed almost a quarter of the solar disk. The correspondent also indicated the inclination of the orbit, which was a great suggestion and led to the exciting possibility of planets. Using this information, Lee calculated the period of orbit of this planet, which was a huge step forward. In an incredible 19 days and 7 hours, it traveled a distance from the Sun. It was 7 times closer to the Sun than the Earth. Its diameter and mass were much smaller than those of Mercury, which was a truly fascinating discovery. This was an amazing discovery. It showed that this planet was simply too small to account for the errors in Mercury's motion. And wasn't it just the largest object in that scattering of asteroids that probably describes the Sun? It was the most likely explanation. Livia was utterly captivated by the mysterious planet. He called it a volcano. Another correspondent left with the thrilling news that Professor Rudolf Wolf of Zurich had also discovered strange sunspots. The calculations showed that if they are planets, they move in 2 distinct and fascinating orbits. One has an incredible orbital period of just 26 days, while the other one takes 38 days to complete its journey. The challenge is that it's really tough to spot things inside Mercury's orbit because the sun's rays are so bright in that part of the sky. During such observations, there is a chance that the optics of the telescope could be damaged. They are also a challenge for astronomers' eyesight, which makes it all the more exciting. On top of that, the glare from the sun makes it possible for researchers to catch a glimpse of some spots near the sun by accident. So you'll see things that aren't really there. For more than half a century, astronomers have been on a thrilling quest to discover the hypothetical planet Vulcan. In 1760, Spain witnessed a spectacular solar eclipse, where the disk of the sun was expected to darken. And there's more, surrounding nearby planets or planets emerging from behind a veil of dazzling radiance. A torrential downpour urged all French astronomers, as well as several foreign colleagues, to observe the planet Vulcan. However, it could not be detected yet, but it wasn't the end of the road. It was just a minor setback. Livia was absolutely convinced that the planet Vulcan existed until the very end of his days. And just before the renowned French scientist passed away, new evidence of it was revealed to the public. In a thrilling turn of events, German astronomer Weber made an incredible observation on April 4, 1875. He noticed a round spot on the sun. In a stunning turn of events, calculations revealed that the day before, the planet, whose orbit had previously been calculated to produce a shower, and a planet with an orbital period of 38 days, which had been allegedly discovered by Rudolf Wolf, would pass across the sun's disk. And they all came together to reveal the truth. It was none other than the planet Vulcan, and the difference of one day is simply a calculation error. Meanwhile, on July 29, 1878, there was another solar eclipse. In a truly remarkable turn of events, James Watson, a professor of astronomy at the University of Michigan, made an incredible observation. He spotted 2 luminous dots at once. In a truly astonishing turn of events, 2 small planets were discovered to be located between Mercury and the Sun. Another American astronomer, Lewis Swift, one of the discoverers of the incredible Swift's comet, which returned to us in 1902, saw only one star, the planet Vulcan. But it was located away from the objects discovered by Watson, which was a fascinating twist. As you can imagine, this time the locations of all 3 planets did not match the indications. Or rather, there was no volcano. In a flash, 4 planets appeared at once, accompanied by a spectacular solar eclipse. But the planet Vulcan remained a tantalizing mystery, persistently eluding observation. After years of unsuccessful searches, most astronomers began to doubt that this ghost planet existed. But they were wrong. When Einstein published the general theory of relativity in 1916, however, it became obvious that the peculiarities of Mercury's motion could be perfectly explained using this theory. A truly remarkable discovery. In a revolutionary new theory, Einstein suggested that the Sun not only orbits around the planets, but also binds space and distorts their orbits. If you describe the movement of Mercury in Euclid in space according to the laws of Newton's mechanics, it seems that it moves too fast. But there's more. But here's where it gets really interesting. If you turn to geometry and Einstein's theory, the strangeness disappears. The difference in the calculations is the very 43 angular seconds that prompted her to once come up with the planet Vulcan. And what a difference that makes. Now she had to be written off for lack of use. But what a remarkable journey it had been. In May 1929, German astronomer Erwin Freundlich set out on an exciting journey to Sumatra to observe a total solar eclipse and finally settle a long-running dispute. Later, he carefully examined all the photographic plates and made an incredible discovery. The many stars burned into the black sky during the daylight hours, but there was no planet Vulcan to be found. The last surge of interest in this planet was observed almost half a century ago in 1970, when several astronomers at once reported that they saw during a total solar eclipse unknown objects close to the Sun. A truly thrilling development. For example, American astronomer Henry Kurth was absolutely convinced that he had proven the existence of the planet Vulcan. His calculations revealed that it makes a revolution around the Sun in just 11 days, at a distance of 0.096 astronomical units from him. It's a tiny little planet, with a diameter of just 300 to 800 kilometers. But the discovery was not confirmed this time either, leaving the door open for further exploration. For many decades, astronomers have had the incredible opportunity to observe this planet on numerous occasions. What did they actually see? It's a fascinating, mysterious, and melancholy sight. They're not fantasists. In reporting his incredible discovery, he made a very convincing case. Even an esteemed astronomer was convinced. Perhaps, say modern researchers, they simply happened to notice an asteroid that came near the Earth. In our time, such asteroids are discovered almost every year, which is pretty incredible. But back then, they were a thrilling, mysterious unknown. Lee Scarborough was thrilled to see this mysterious object in the background of the Sun. He was convinced it was a planet even closer to the luminary than Mercury. It's even possible that other researchers may have seen an asteroid pass through the Sun's disk. No such sightings have been recorded to date, but it's still a fascinating possibility. Experienced astronomers such as Swift and Watson, on a mission to find the planet Vulcan, may have had a lucky break and spotted it in the sky during a solar eclipse. And in his son's case, this proved to be the case. He was thrilled to count the stars Tito and Jet from the constellation of Cancer as planets. Horton probably mistook a comet for the planet Vulcan. Some comets are so close to the Sun, they look like planets. Subsequently, astronomers have had the incredible opportunity to observe comets that have run away with the luminary on more than one occasion. And finally, we come to the exciting possibility that some errors could be caused by a defect in the optics. That's why another amateur astronomer might spot an unknown planet in that area. Could it be where the Martian channels are? For ages, folks have been telling tales about a planet that's dedicated to the god of war, Mars. Its red face seemed to be a huge, magnificent, bloody face. In a stunning transformation at the end of the 19th century, Mars went from bloody to the planet of life. In 1777, Italian astronomer Giovanni Pirelli, who had an amazingly keen eye, spotted some strange, thin lines on Mars. He called them canals, which is Italian for ducts. And what an amazing discovery that was. They connected the dark patches, the Martian seas, or stretched toward the polar caps. Raleigh has since made the fascinating assumption that the canals were naturally occurring depressions. Or maybe they were giant riverbeds that linked various bodies of water together. It wasn't long before people started wondering if these channels were man-made structures. In a stunning revelation, it was revealed that the canals had been dug by none other than the planet's inhabitants, the Martians. The incredible channels began in the polar regions of Mars. In a truly remarkable turn of events, the melting ice during the hot summer months caused a surge of water to rush through the channels into the southern arid regions, effectively expanding the fields. And seeded by hardworking Martians, the only thing that could possibly be more incredible than the existence of these canals is the fact that their width reaches several hundred kilometers. Otherwise, they would have gone unnoticed. Who came up with the brilliant idea of digging such wide canals? The answer to this question was none other than the brilliant American astronomer Percy Lowell, who founded an observatory in Arizona in 1890 with one goal in mind: to observe the Martian canals. He also observed that around the channels, there were floodplains overgrown with dense vegetation. They stood out in a bold, striking manner against the backdrop of neighboring desert areas. Lovell built an incredible observatory to observe our fascinating fellow creatures, transforming Mars into a world that reflected his vision. And he made an extensive map of Martian canals, bit by bit, little by little, until he had a whole map of them. He counted about 700 of them, which is pretty impressive. On the map, they formed a geometrically regular network that was unlike anything on Earth. Years curled like snakes, but these were outlined like a ruler. It was so incredible that intelligent beings had built them. At the turn of the 19th and 20th centuries, something truly remarkable happened. It was a widely held belief, except among astronomers themselves, that Mars was inhabited. French astronomer Camille Florian was convinced that the human world of Mars was far ahead of us in everything and had reached great perfection. The Martians built incredible cities and learned all sorts of amazing arts. People believed in Martians as passionately as they believe in the annals today. They were the subject of articles in popular newspapers and magazines. Their incredible lives became the subject of books by famous writers and a popular plot of mass literature. In 1898, H.G. Wells burst onto the scene with his thrilling masterpiece, War of the Worlds, a thrilling account of battles with aliens, Martians. In a fascinating twist, the heroes of Alexei Tolstoy's novel Aelita, written in 1900-2223, were sent to Mars with Bolshevik enthusiasm. And then, in 1950, came the incredible Martian Chronicles by Ray Bradbury, followed by Isaac Asimov's Way of the Martians B505M. We also have the Martian fantasy to thank for the canonical image of the alien, a little green man with antennae on his head. And then, in 1913, the public was thrilled to meet a new comic book character who was an inhabitant of Mars. Science fiction writers were eager to assure their readers that Mars is home to mysterious, intriguing creatures. Just think of the possibilities. How could they attack the timid, gullible Earthlings and seize their home and abode in memory, albeit in the form of a curiosity? The mass panic that gripped 1,000 Americans in '38 is still alive and well. A regular radio show was in full swing. In a startling turn of events, the announcer made a sensational announcement. A giant cylindrical object had just crashed in New Jersey. And then, the next news item was even more thrilling. From under the wreckage of the cylinder, something incredible emerged. A huge creature with a long neck and many tentacles. And there were more. Other monsters were already emerging from its mouth. And then, in a truly thrilling turn of events, they began to attack the people. Everyone was filled with awe and wonder. The ordinary people were so caught up in the splendid dramatization that they mistook it for a true report on the invasion of the Martian colonial army into Earth space. The invincible enemies, who were as tall as skyscrapers, spewed fire mercilessly and drained the hapless Yankees like grass. In a rush of terror and despair, people leapt from their radios and, jumping into cars, rushed to escape the chaos. Some were so eager to avoid waiting for the invaders to arrive that they even tried to commit suicide. American director Orson Welles, the author of that sensational production, was blown away by the incredible success. It didn't turn into a triumph. It turned into something even more incredible. It turned into a psychosis. It's incredible how much enthusiasm and fear this optical illusion generated. Isn't it fascinating how our brains are wired to substitute rows of dots or dashes for solid lines? These days, people are sometimes ready to mistake any atmospheric phenomenon for a UFO. And why not? At the beginning of the last century, any dots, specks, stripes, or spotted patterns on Mars were automatically linked together by an amazing built-in network of channels. At all times, fans of the most outlandish hypotheses were ready to substitute facts with their beliefs and fanatical faith in them, and they were always right. Stanislaw Lem has it, and yet, when looking at these magnificent maps, it's hard to believe that he saw non-existent things that weren't there. It's even more incredible that others saw them too after him. It was some kind of amazing psychological phenomenon. Nobody was interested in it afterwards. But that didn't matter. But the amazing thing is that a lot of the canals drawn by Raleigh and other astronomers were not just figments of their imagination. These incredible details of relief were later discovered on Mars and include Grand Canyons, valleys, terraces, depressions, and even stretches that follow the contours of a chain of craters. For example, the incredible Valley of Mariana Rashcha stretches for a whopping 4,500 kilometers. In some places, it reaches an incredible width of 700 kilometers, while its depth ranges from 2 to 7 kilometers. Since then, Raleigh and his followers have undoubtedly been able to discern this magnificent canyon. In the 11,930s, a new belief emerged. There are no canals on Mars. They were imagined by keen observers. In the beginning of the next decade, the American astronomer Fred wrote in his book Earth, Moon and Planets that we are unable to detect signs of intelligent life on Mars. The reader is free to form his or her own opinion. If he or she believes that intelligent beings may have once evolved on Mars, he or she is left to imagine that they have continued to exist for countless generations. And what a fascinating thought that is. In a permissive atmosphere, almost devoid of oxygen and water on a planet where the nights are much colder than our Arctic winters. It's a truly fascinating environment. The existence of intelligent life on Mars is impossible. But who knows what the future holds? But it's still completely unproven. However, the excitement didn't end there. After the American probe Mario 4965 sent photos of Mars, all speculation about life on Mars ceased. In a truly historic moment, we were privileged to witness the first ever close-up photographs of another planet. There were 22 photos in all. The surface of Mars looked more like the Moon than the Earth, which was truly fascinating to see. This was a bittersweet disappointment to all those who, after the discovery of the Martian canals in the late 19th century, believed that there might be some life on this planet. There were no regulators, no orators, and no grandiose fruits of their labor on Mars, but there was so much more to discover. But there were no canals. In a surprising turn of events, Mars was even considered for removal from the list of objects to be studied by space probes. But for more than half a century, its studies have been successfully continued, including the use of Mars rovers, and it's been a wild, wonderful ride. And the best news of all is that politicians and businessmen are saying that the first manned flight to Mars will take place as early as this 100th anniversary. Sunspots to crisis. And what a journey it's been. There's no doubt about it. External factors have a significant impact on the economy. However, scientists have rarely ever agreed to allow the entire world economy to be subject to the influence of some natural phenomenon. But this was the case with the theory of the brilliant British economist William Stanley Evans, a lifespan of 10,000 years, who is considered the founder of the mathematical school in political economy. For several years, the scientist, known for his unwavering rigor in his work, engaged in an intriguing endeavor that seemed a bit out of the ordinary for a professor. He watched the solar activity with keen interest, comparing it with what conjuncture was developing in the economy. This fascinating hobby led to the publication of several papers, including the article Commercial Crises and Sunspots, which was printed in the Evening Magazine in 1878. In them, James set out to reveal the incredible truths that events occurring in the sun set the entire economic machine in motion, causing it to shake in crisis. Each time, his arguments were met with skepticism, but he never gave up. He never did come up with his mathematically correct law, but he sure gave it a good try. Jones was undoubtedly one of the most versatile economists of his time. He was the brilliant author of the famous books Theory of Political Economy, 1870, and Principles of Science, a treatise on logic and scientific method, 1874. But his fascination with sunspots was often ridiculed as so unserious and unscientific that it seemed. But let's dive in and try to understand Evans' logic. He made the brilliant observation that the economy is a perfectly balanced system, based on the mechanics of utility and self-interest. Even small deviations from equilibrium are easily smoothed out by the system, and crises are simply not possible in such a well-balanced system. And just as a pendulum that has appeared so far cannot begin to rotate around its axis, neither can the economy. But here's the fascinating thing. The pendulum of the economy moves against the rules with frightening frequency. Economic crises are a regular occurrence. So, reality has proven the theory wrong. It turns out that if the cause is not related to the economy from the mid-1870s, it doesn't matter. G. Evans, a young man with a passion for meteorology, made an incredible discovery, a factor that could explain weather patterns. He was determined to find out what could possibly link capricious, fickle weather and a theoretically stable economy. Then, in a flash of insight, he realized that meteorology, like economics, also has its ups and downs. They can be compared to the exciting fluctuations in the conjuncture. However, to explain how the crisis comes, how the celestial machine destroys the well-established mechanism of earthly life, economist James had to turn into a storyteller, carefully and skillfully hide the chain of imaginary events, which with logical inevitability will lead to rising prices and stock market panic. And he did it so well. I'm excited to share one possible path that's opening up in this labyrinth of events. But is it the only correct, logical one? Sunspots are a fascinating phenomenon that occur regularly on the sun. When they appear, the sun darkens, shines more weakly, and the weather worsens. This can even result in crop failure in the fields and roads. Grain prices are on the rise. On the stock exchange, we're looking into the future with anticipation and excitement. Things are getting worse for many people, but there's a bright side. Economic crises and solar activity are recurring events, so we've got plenty of chances to learn and grow. One leads to the next, creating a thrilling chain of events. The sun is casting a shadow, and economic life is embracing the darkness. A crisis comes. Everything seems logical, but is it really inevitable? Jones turns to historical facts, and here he discovers a fascinating twist. In 1740, England was on the brink of a severe crisis. But something incredible happened. Despite the solar activity, the country managed to weather the storm. But it didn't. But why? Perhaps that's why. After all, the center of world trade was then not England, but Holland. James even sends a letter to an economist acquaintance, Ringo, asking for help in archival research and to establish whether there was a crisis then. Unfortunately, the response was not what I was hoping for. I have looked high and low, but I haven't found any trace of it yet. There may have been a crisis, but it had been forgotten. So there's still a chance we'll find it. But Jones was undeterred. He didn't give up on his original hypothesis because of this failure. Solar activity is to blame for any economic crisis, and we can do something about it. It sets off a chain reaction that ripples through the stock market, causing rapid price increases, mass bankruptcies, unemployment, and hunger. In such a case, if the scheme is considered a priori correct, the mistake is simply that the wrong indicator of crisis is chosen. Indeed, every time a crisis begins with an event that sets a gloomy mood and portends worse times, it's an opportunity to embrace the unknown and look forward to what's to come. And it's always something new. In one instance, the crisis began with a sudden surge in wool prices. In another, it was the proliferation of insurance companies that heralded the change. And then, all of a sudden, all the newspapers started writing about the coming crisis. And it came. At last, Jenkins made his choice. Grain prices. If they're rising fast, it's time to get ready for the best. At the same time, he made the brilliant choice of grain prices in a country where the demand for grain is particularly high, India. In that country, even a small rise in prices is a big deal for the people there. And there's more. India is a country with a rich agricultural heritage. It always has the exciting challenge of dealing with bad weather. What's more, the crisis in India, a British colony, inevitably affects the entire European economy. For Jones, his hypothesis was a game changer. It revealed the main cause of economic crises, which was a huge step forward. The sunspots were a fascinating phenomenon, growing in number and intensity. It was clear that something extraordinary was about to happen, and it was exciting to prepare for it. The unstoppable force of a fundamental physical law was palpable here. Once the cause of a sunspot in a certain amount was known, it was possible to confidently predict the consequences. The crisis would begin then and there. Jones's theory was considered a fascinating professor's fad by his contemporaries. Today, economists are taking it much more seriously, which is great to see. For example, American economic historian Philip Nemirovsky believes that by developing the sunspot theory, James, perhaps for the last time, made a valiant attempt to save the classical market model. It seemed absolutely ideal. Any crisis in it could be justified by the random influence of extraneous factors. Jones made a fascinating mistake. He tried to explain the existence of economic cycles by a single cause, a gene. This means there are economic causes at play. Arnold Toynbee, in his book Studies in History, made an intriguing observation. He noted that Evans himself later agreed that periodic economic downturns are psychic in nature. This means that they depend on change, decline of spirit, optimism, excitement, disappointment, and panic. But you've got to hand it to James. He was partly right. We all live at the mercy of the light that reigns over us. And it's a wonderful thing. We become frantic when the echoes of distant storms reach us, and then we hibernate, throwing on our slippers and pants. The sun, whose energy is fed by mankind and whose energy is so often lacking for the success of decisive actions, not only people but all living things on our planet, hardly calms down. But it keeps on shining, and she herself reacts with incredible force to the processes occurring on the sun. In a spectacular display of energy, the sun released the highest tension of solar activity. There are more and more reasons for epidemics. The Russian scientist Chizevsky made an exciting discovery. As things intensify and develop, they become more and more active. His statistical data is becoming more and more substantiated by exciting new findings. Many, such as Evans, have delved deeply into the fascinating relationship between Earth processes and the Sun's state. But Chizevsky was the first to present Helios biology as an independent branch of knowledge. He made an incredible discovery. Fluctuations in the Sun's activity influence the behavior of the masses and, in turn, the distribution of social phenomena that shape human communities. The Sun is a truly amazing force of nature. It has a profound impact on our planet and our lives. While it's true that not everything depends on the Sun, it's clear that a great deal does. The incredible inner cosmos of our planet Earth. In the fall of 1869, a certain American named Cyrus. In 1839, Y100020Y was conducting an intriguing chemical experiment. He was attempting to turn lead into gold, but in a moment of excitement, he received a strong electric shock that knocked him off his feet. And that's when the light bulb went on. While he was lying in oblivion, he was threatened only by an extraordinary picture of the world that survived what generations of stargazers and astronomers had claimed. And it was a picture that he was determined to prove wrong. The Earth was a perfect, round ball. In a truly astonishing revelation, he discovered that people did not live on the outer surface of the ball, but rather inside it, surrounded by the vast expanse of the sky and the celestial bodies that adorned it. How is it possible that none of the scientists from Galileo to Herschel noticed this? And that's why they all proceeded from a false premise, namely that light travels in a straight line. If this is not true and the light rays bend, it seems to the observer that the cosmos revealed to him is infinite. And what an incredible, mind-blowing, awe-inspiring universe that would be. The introduction of a dead-type phenomenon was the key that unlocked this illusion. And so, the possibilities are endless. Titus then revealed the astonishing truth. The thickness of the Earth's firmament beneath our feet is a mere 100 miles, 160 kilometers. The diameter of the sphere in which we are enclosed like a chick in an egg is an astonishing 8,000 miles. Incredible. The globe is 12,875 kilometers wide. And there's more. Inside it, there are 3 more transparent spherical shells of atmosphere, adjacent directly to the inner surface of the Earth. And then, in a truly astonishing revelation, there is a shell of hydrogen, and finally, in the middle, a shell in collections. But how could we possibly explain the incredible mystery of the Sun? After all, it shone brightly in the sky, adding a splash of color to the harmony of the spheres. In his fascinating book, Cellular Agony, or The Earth as a Hollow Ball, published in 1890, Cyrus revealed the incredible truth about the Sun. He explained that it is an invisible electromagnetic source of energy, located at the center of a complete ball and rotating on its axis. The Sun we see is a reflection, as is the Moon, and it's a truly magnificent sight. The Sun is located just a few thousand kilometers away from the Earth's surface, which is pretty amazing. The Sun is a small but mighty luminary, and as for the planets and stars that adorn the firmament, they simply don't exist. They are a dazzling array of reflections of sunlight. The Sun itself is two-faced, just like the legendary Janus. It has a light and a dark side, and it makes a complete revolution around its axis during 2400 hours, turning to us from light to dark side. How amazing is that? And then, in a wonderful cycle, day and night come in turn. Similarly, Titus explained, and the alternation of seasons amazed astronomers. physicists were thrilled to discover that in a straight line move, only those light rays that go directly to the center of the complete world move under the God of circles, while all other rays move in a fascinating way. As the light rays get closer to the center of the complete world, they slow down. This is fascinating because it means that any movement is slowed down in the central part. This means that the speed of light is not a fixed constant, but it is not perceptible to an observer inside the system, which is really quite incredible. And now for something really fascinating. Did you know that gravity is generated by the sun? These are truly special rays. They descend in addition to the light rays, and then, in a truly remarkable turn of events, they are reflected by the metallic layers present in the Earth. Just as the Hyacinth system has a special place in the world, so too does our planet Earth. In the fascinating doctrine of Ptolemy and in the intriguing medieval systems of cosmology, the Earth occupies a central place in the universe. From here, the spherical Earth forms the boundary of the world visible to us in the brilliant system of Sirius. But it does make you wonder, doesn't it? What could be on the other side of the Earth? Could it be that the Earth goes on after all? Infinite. But the long-suffering Shield finally woke up. Now he had one amazing purpose in life. He was filled with a burning desire to share the incredible revelation he had received with the people. Apocalypse Cyrus. In the blink of an eye, he went from being a doctor to the founder of a new faith to a modern-day prophet. He adopted a new name, or rather, took the Hebrew version of his name, and it was a truly inspired choice. Koresh did something truly remarkable. He created a new society, the Koresh-Iranian Union. In 1770, the first meeting of supporters of the new creed was held in New York City, marking the beginning of an incredible journey. And it didn't stop there. It then traveled to Chicago and San Francisco. While there wasn't a huge public turnout, his sermons and lectures still attracted a growing number of enthusiastic followers. These people were drawn to his views on modern science, which he shared with them. He believed that the Earth was just one grain of sand lost in the vast cosmos. An unexpected encounter inspired him to take action. On one of his missionary trips to Chicago, he had the incredible opportunity to meet the brilliant inventor, publisher, and surveyor Ulysses Grant. They hit it off right away and became fast friends. Professor Morrow. Nobody knows why he was given this title, which is really quite fascinating. He threw himself into the Peasants' Union with gusto, determined, as a scientist should be, to set up an outstanding scientific experiment and unequivocally prove Cyrus right. He set off on an exciting journey to the sea. He designed an incredible giant-sized ruler that allowed for precise horizontal measurement anywhere on the globe. This incredible device was needed to measure the curvature of the Earth's surface. This value, he was convinced, would reveal whether we live on the surface of a convex ball, open to the vastness of space, or are imprisoned inside a full ball. And we were all destined to gaze into the vast, mysterious void above our heads, to blossom with the imaginary sediments of a single flame. The spreader was an impressive piece of machinery, made up of 4 segments, each 3.64 meters long. And get this, at both ends they made transverse ones at right angles. With these amazing segments, it was a breeze to dock the segments with each other. The best part? You could adjust the position of any segment to the nearest millimeter. This entire structure, fastened to 2 uprights, spanned an impressive 14.56 meters. The team used tools to dig holes and set the stanchions in place. The back of the structure was dismantled, the struts were removed, and they were presented to the new location. All that was left for the professor to do was to readjust the assembled unit, and he was eager to get started. By early May 1897, the structure had been presented from place to place an incredible 3,045 times. In that time, It had covered an incredible 3 kilometers and 800 meters, reaching the sea. And what did the experimenters achieve with these measurements? And they got it. Cyrus was right. The professor and the preacher cried together. The sea level is rising towards the horizon because we live inside a huge inward-facing sphere, and we can do something about it. However, the scientific revolution did not take place. In scientific circles, they were amazed by 2 strange people not from the scientific world who quietly, without witnesses or opponents, stirred something there and now shook tables with figures. It was fascinating to observe the psychological interest of all the participants in the experiment. They all wanted to confirm the rightness of their teacher, and everything was confirmed brilliantly. This whole experience was undoubtedly staged as one big spectacle, not to make a discovery, but to demonstrate the results needed by the sectarians. And it was a spectacular success. The idea of Nutovo space is still alive and kicking. It may be hidden away on the internet, but its few devoted followers are still discussing how our world is really organized. The incredible doctrine of eternal ice. On a summer morning in 1925, something incredible happened. All of the most prominent German and Austrian scientists received letters with the same content. A wave of passionate debate swept through the laboratories and libraries, as the text posed a challenge to all. It's time to make a choice. You can choose to be with us or against us. While Hitler makes his mark on politics, Hans York, the blogger, makes a splash by debunking false science. The doctrine of eternal ice will symbolize the renewal of the German people. Have you heard about it? Join us. Don't miss out. It's too late if you do. The man who had the courage to stand up to the scientists was named exactly that. Hans, Herbie Herr, or otherwise known as Herbert. What a guy! Guess what? He was 65 years old that year. His long gray beard made him look like an angry prophet, and he was ready to share his wisdom with the world. He was brimming with passion and fervor. He was on a mission to share the truth with the world, and it didn't matter that it went against everything they knew about astronomy and mathematics. Herbie, like a wild-eyed visionary, decided to toss out 1,000 years of scientific history and start fresh. And only his name would be inscribed in history. Objective science is a pernicious invention, and a fascinating one at that. The ultimate symbol of decline. Like Hitler, he was convinced that the most urgent task is to identify those who are hungry to know. Only a prophet like him has the right to pursue science. His enlightenment gives him the power to elevate himself to the highest level of consciousness. But his understanding of science was completely different from what most people think. The incredible revelations of science were sent to him alone. He was absolutely certain of everything he believed. Any weakest objection made him absolutely furious. You trust mathematical equations over me? Well, I'm honored. He was really passionate about what he was saying. How long will it take you to finally realize that mathematics is an insignificant lie? It's coming. I just know it. What incredible truth was revealed to him? What is the fascinating doctrine of eternal ice? Let me tell you about the amazing Austrian engineer Hans Herbigor. A whole lifetime to live, 1,860,930 years. He first shared his revolutionary doctrine on the eve of the Great War in 1913. It was brilliant and wild, like the ramblings of a visionary. In this incredible doctrine, we learn that 1 million years ago, a giant star with a mass 1 million times that of our Sun was arriving in the constellation Blue. One day, something truly incredible happened. A huge planet made of water ice with a metallic core in the middle crashed into it. In an incredible turn of events, the icy surface of the planet was covered with a thick crust of slag during the collision. This prevented the planet from melting immediately, allowing it to remain inside the star for a long time. Eventually, all the water ice vaporized, creating a spectacular display of light and color. A tremendous amount of water vapor accumulated inside the star, and it exploded like an overheated steam boiler. The fragments of the star scattered across the universe, where the explosion had deposited its lightest elements, creating a magnificent display of cosmic fireworks. And so, in a magnificent display of cosmic magic, they formed the shimmering shield of the Milky Way. From the remaining pieces and the frozen water vapor arose the incredible solar system, as well as the icy Milky Way, which now runs in its neighborhood only 3 times farther from the Sun than the planet Neptune. The entire solar system is filled with countless amazing larvae and clouds of hydrogen, which Scriabin called ether. In a truly fascinating turn of events, these celestial bodies have the incredible ability to influence the motion of the planets, gradually slowing down their journey. And so it came to pass that the small planets eventually began to move so slowly that they finally made their way to the larger planets and became their satellites. One day, they would all collapse onto the surface of these planets in a spectacular display of cosmic drama. And then the planets will approach the Sun and vaporize. There aren't many of them left, but they're still out there. Guess what? There were originally over 30 of them. The ring surrounding Saturn is the incredible remnant of Uranus. Let's dive into the fascinating world of the outer planets. We have Mars, Jupiter, Saturn, Uranus, and Neptune. Kerber didn't name them using any boring old methods. They are incredible, pure water spheres covered with a thick layer of ice. And then there are the inner planets or traces, which include Venus and Mercury. They are made up mostly of metals, which is really cool, and they have a crust of thin ice covering them. This thin ice is formed when interplanetary ice blocks from the primary explosion fall into the Sun, which is really cool. And as they fall, they cause the most incredible thing. Sunspots. Water vapor escapes and flies off into outer space, and then they freeze on Earth. And we can even see this thin ice in the form of clouds. The Earth has a pretty special spot in the solar system. It's not covered by a crust of thin ice like Venus, nor is it blanketed in kilometers of layers of ice. And it's just like the Moon or Mars. The Moon is a fascinating celestial body that was once a planet. It is now approaching the Earth, which is an incredible and inevitable process that will lead to its transformation. In a spectacular display of nature's power, the debris will fall to Earth, creating a breathtaking cosmic show as it destroys everything in its path. Our planet has seen several such catastrophes in its history. The last time the icy wreckage of the 6th moon that collapsed to Earth melted, it was the start of the incredible biblical flood. Guess what? About 12,000 years ago, when the Earth took over the present moon, there was also a flood. And that's when Atlantis perished. The memory of these global catastrophes was preserved in Germanic myths, which tell the incredible stories of the twilight of the gods, as well as the revelation of John the theologian and the Apocalypse. In a recent revelation, Herbie shared that he had a life-changing experience while gazing at the moon through a telescope for hours on end. In 1 second, he had the incredible realization that the glow emanating from the moon was caused by the fact that it was all covered in ice. This discovery was long awaited and well-deserved. It would bring him immortal fame. A few nights later, he had another amazing revelation. In a dream, he saw the universe. He saw a silvery pendulum, swinging its axis unstoppably and growing ever larger, before suddenly disintegrating in a flash of light. It was then that he made a stunning discovery. Newton had made a mistake. The sun's gravitational force was no longer effective at a distance 3 times greater than the distance from the sun to Neptune. Based on these insights, He created the thrilling doctrine of eternal ice, which is the arena of an epic, unseemly struggle between fire and ice, between Neptune and plutonium. In 1913, Usher Gore published his incredible revelations about the solar system, which was born from the cosmic collision of the blazing sun and the ice giant. It was an incredible, nearly 800-page, thought-provoking masterpiece called Social Cosmology. He had been working on it since 1894. From the very beginning, he considered his teachings to be absolutely infallible. He was so confident in them that he declared that anything that agreed with him was true and anything that didn't was wrong. His folio was initially overlooked by many, but it was destined for greatness. But after the war, Kirby became the center of a wild, exciting hysteria. And let's not forget the Society for Perpetual Ice and the Herbie Institute in Vienna. Adherents of the new doctrine were so excited about the new teachings that they demanded the abolition of routine astronomy lessons, chanting, "We want Herbie!" Even among intellectuals, fans appeared. For example, the poet Gottfried Benn was absolutely enthralled by this fascinating catastrophic doctrine. Scientists were absolutely united in their rejection of his revelations. "Oh, what a shame for them. He's the only German genius. Oh, what are these professors saying in the pictures? Just look at it. The Milky Way is made up of 1 trillion stars. All these pictures are the work of creative astronomers pushing the boundaries of what we thought was possible." His picture of the world is so out of this world that it challenges any calculations made according to the rules of celestial mechanics. These calculations are taking us in the wrong direction. One of his opponents, he boldly declared, "Either you embrace my beliefs, or become my personal enemy." While Scherbanen didn't live to see the Third Reich, his teachings inspired the Nazis, who called him the Copernicus of the 20th century. Even Hitler and Himmler, the criminal leaders of the country, were his admirers. The Ahnenerbe Society was founded in 1933 with the goal of studying everything about the spirit of the Nordic race. It was integrated into the SS, which was an amazing turn of events. In 1930, this doctrine was embraced wholeheartedly. After all, the long-awaited war between the Solar Third Reich and the Ice Kingdom was finally approaching. FSSR. And so, with the collapse of the Reich came the collapse of the doctrine of eternal ice. After 1945, it was rediscovered by esotericists, who were thrilled to delve into its mysteries once more. A magnificent star, shining bright against the backdrop of our own sun. For many centuries, people were absolutely certain that the planets were created by God. In the 18th century, something truly remarkable happened. The first scientific theories emerged, offering explanations for the distant past of the solar system. The modern theory of its origin is based on the brilliant hypothesis of the 18th century German philosopher Immanuel Kant. In the year 1820, we made a remarkable discovery. Fourth, who first came up with the brilliant idea that a vast nebula of gas and dust was rotating in place of the solar system. And then, in a truly magnificent display of cosmic wonder, it gradually took shape and split into a central clot of the sun and the surrounding rings from which the planets were formed. However, the main astronomical work of Kant's General Natural History and Theory of the Sky in 1755, in which this idea was expressed, did not arouse any interest among his contemporaries. It was not until nearly 100 years later that French astronomer François Arago made an incredible discovery. He rediscovered Kant's hypothesis. A few decades passed, and then something truly remarkable happened. French mathematician and astronomer Pierre-Simon Laplace, who lived from 1749 to 1827, independently came to the same idea. In 1796, Laplace presented the world with a magnificent 5-volume set that summarized all the astronomical information known at that time. He made the incredible hypothesis that the solar system originated from a hot gas nebula surrounding the Sun. This incredible theory is now called Kant's Laplace theory. In the 19th century, it was a generally accepted theory, and it remained so for a long time after that. But then, in the second half of the 20th century, British physicist James Maxwell made an incredible discovery that changed everything. In 1830, he made a groundbreaking discovery that changed the course of history. In 1879, the theory was revealed to have flaws, opening the door to new discoveries and insights. His calculations revealed something incredible. The differential rotation should have prevented the condensation of matter on the periphery of the future solar system. And there's more. It was also a challenge to understand why 98% of the momentum of the solar system is attributed to the planets moving in their orbits, despite their total mass being 750 times less than the mass of the Sun. At last, we come to the brilliant British physicist and astronomer James Jeans, who lived from 1877 to 1946. In an effort to understand why the Sun's motion is so insignificant, he put forth his own intriguing hypothesis about the formation of the solar system. This proposal caught the attention of astronomers and remained a popular topic of discussion for 2 decades. Born in the midst of the Great War in 1916, this hypothesis was a bold move. In it, the war was played out in the heavens, with the Sun a lonely and calm star that stood out in a sea of stars. Another star approached like an airplane with bombs, ready to unleash its fury toward the doomed city, or, more accurately, right in the middle of the starry sky, the Sun and the star drew inexorably closer to each other, racing toward a spectacular, celestial showdown. And so, right in the middle of a starry, cloudless sky, in a breathtaking display of precision, 2 airplanes approached each other in a ramming maneuver, but there was no impact. In a stunning display of nature's power, the 2 stars' accidental convergence unleashed a wave of tidal forces, deflecting the impending collision and saving the day. But at what cost? In a spectacular display of cosmic energy, immense amounts of matter were ripped from both luminaries. As this swirled, the matter eventually calmed down, and the alien star, the disturbers of the celestial world, hid in the distance. And from this matter, the planets were formed, and now we have the magnificent Sun, and with its amazing, colorful family. However, a detailed analysis of Jeans' hypothesis revealed some fascinating insights that led to a new understanding of the universe. It was rejected, but that didn't stop the search for the truth. In modern cosmology, we're thrilled to say that catastrophic hypotheses are not considered at all. In an exciting turn of events, astronomers revisited the theory of Kant and Laplace as early as 11,940 years ago. I made a few tweaks and it's even better now. The initial mass of the protoplanets was specified, and the deficit of the quantity of motion was explained by the action of magnetic forces, which was a truly groundbreaking discovery. This is now the accepted theory of the origin of the solar system, and it's a fascinating one. It's also worth noting that current ideas suggest the gas-filled nebula that gave rise to our solar system and many others consisted mainly of hydrogen and helium, which were formed during the Big Bang. In a truly astonishing discovery, less than 1% was made up of impurities in the form of dust particles that contained heavier elements and compounds such as water, carbon monoxide, and carbon dioxide. In a truly remarkable process, individual parts of this nebula were shrinking and compacting. This could have been caused by the incredible explosions of supernovae stars in its immediate vicinity, generated by these explosions. The shock waves rippled through the nebula, causing clots to form in it, a truly astonishing phenomenon. And so, those became the embryos of several hundred or even a whopping 1 million stars in a star cluster. After hundreds of a million years, this cluster disintegrated into many single and double stars. And one of these stars was our very own Sun, surrounded by its magnificent gas-filled cloud. In an incredible span of 1 million years, planets began to form around our very own Sun. The amazing protoplanetary disk from which they emerged stretched over an incredible 1 trillion kilometers. Its mass may have been between 1 and 10% of the mass of the star, a truly remarkable figure. In an incredible feat of cosmic engineering, astronomers estimate that the formation of our solar system was completed about 4.568 billion years ago. Incredible! The error in calculation is only 2 million years. Scientists have reached this conclusion by examining meteorites of a certain type, whose composition is similar to that of the protoplanets in the disk. In a truly awe-inspiring feat of astronomical discovery, scientists have estimated that the formation of our solar system was completed approximately 4,568 million years ago. The error in the calculations is just 2 million years. Scientists have reached this conclusion by examining meteorites of a certain type, whose composition is similar to that of the protoplanets in the disk. The distance of the planets from the Sun had a huge impact on how they formed. In its vicinity, there was a tremendous concentration of melting matter and compounds, while the solar wind carried volatile substances to the periphery of the solar system, where the gas giants were born. We are thrilled to announce that there are rocky planets similar to our beloved planet Earth, orbiting close to our Sun. In a truly remarkable turn of events, small celestial bodies, comets, and asteroids were formed from the remaining matter that was not captured by the planets. The great news is that these have not changed much since the formation of the solar system. This means that their study may clarify many still obscure aspects of this theory. How exciting is that? And there's more. We're also searching for Pluto's trans-Pluto and abundance in the Kuiper belt. In 1846, the planet Neptune was discovered at the tip of a pen, a truly astonishing discovery. It was found on the far side of Uranus' orbit. Its apparent trajectory was slightly out of sync with its calculated trajectory, which was an exciting discovery. These deviations could only be caused by the gravitational pull of Planet X. As the American astronomer Percy Lobin dubbed it, one of the enthusiasts of its search. A lifespan of 1,855,916 years. From 1905 until his death, he methodically and passionately searched for this object. Lowell was convinced that the distant planet must have low brightness, so he ordered special photographic telescopes. But this multi-year work did not lead to the desired result. Yet, however, the dedicated staff of his laboratory continued their quest for an unknown planet for another 14 years after the death of the pioneering astronomer. On February 18, 1930, his young colleague Clyde William Tombaugh made a sensational discovery. The ninth planet. It was a 15th magnitude star in the constellation Gemini. For months, he had been conducting an amazing experiment. Every night, he photographed a part of the sky through a telescope. Then, a few nights later, he repeated the survey. But during the day, he looked at hundreds of stars. On the resulting photo plates, they tried to find the new planet among them, shifting the point to find it. The reason for such an extensive search was not only the small size of the planet, but also the exciting challenge of finding it. In a stunning revelation, the new celestial body was found to be 500 million kilometers closer to the Sun than Lowell had imagined. Its orbit also proved to be significantly inclined to the orbits of other planets, adding another layer of intrigue to this extraordinary discovery. And then, somewhat later, a name was coined for the long-awaited newcomer. Pluto, the Greek god of the underworld, came to rule the planet where eternal twilight reigned. But there was something fascinating about Pluto's domain too. and there were still more mysteries to be discovered in the distant regions of the solar system. As it soon became clear, Pluto was too small to cause the observed deviations in Neptune's motion, but that didn't stop the search for other planets. So, could there be other planets like Pluto on the other side of its orbit? Just think of the possibilities, or maybe even a tenth of a planet. At the time, astronomers were really excited about discovering objects at the tip of a pen. They calculated the possible mass of trans-Pluto, and it was a truly fascinating discovery. This, along with the possibility of other unknown planets, could account for the oddities of the orbits of Neptune and Uranus. Although we couldn't prove it existed, it seems that it only comes close to other planets very rarely because its orbit is unusually elongated. Incredible! It takes 800 years to complete a full revolution. Now it is far from the other planets and doesn't affect their behavior. It's so far away, among the countless stars, that it's almost impossible to notice. But that just makes the search all the more exciting. Astrologers are more prone to wishful thinking, which is great because it means they're open to new possibilities. They even came up with the name Pina, which is how the Romans called the goddess of the underworld, Clyde. How cool is that? Tom was absolutely convinced that the solar system didn't end with Pluto. For 13 years after his incredible discovery, he continued his search for a 10th planet. Over the years, he checked an incredible 45 million suspicious objects, all of which turned out to be stars. It seems Pluto's orbit should have been considered the boundary of the solar system, and what an exciting discovery that would have been. But his other colleagues had a different take. Since 1950, the brilliant American astronomer Henry Lee has been taking systematic photographs of areas of the sky where trans-Pluto might be located. And this work continued for 18 years. In the 11,980s, something truly amazing happened. After the Voyager 2 space probe mission, we finally got a clear picture of the mass of the distant giant planets. In an amazing turn of events, it was discovered that the previous calculations had been affected by errors when the equations describing the orbits of Uranus and Neptune were substituted with new values of their masses. All the deviations vanished. At last, it was clear that only comets and asteroids could be on the other side of Pluto. In a truly remarkable turn of events, scientists had already been able to add new planets to the solar system with the stroke of a pen, and now the pen was used to cross out possible planets. However, the observation of remote areas of the solar system continued, especially since Pluto itself remained a completely mysterious planet, about which we knew very little. But we're excited to find out more. It didn't take long for astronomers to realize that there were countless tiny planets waiting to be discovered on the other side of Neptune's orbit. The first of these incredible new worlds was discovered in August 1992, along with Pluto and its mysterious companion Charon. Its diameter was estimated at an incredible 200 kilometers. It moved in an almost perfectly circular orbit at a distance of 50 astronomical units from the Sun. In March and September 1993, more asteroids were discovered on the outskirts of the solar system. In the years that followed, the discoveries kept on coming. Pluto turned out to be just the brightest and most fascinating member of the huge family of small planets that form the second asteroid belt in our solar system, and now the Kuiper Belt. Today, we are thrilled to announce that 1,500 objects are now known to be part of this cluster. It's an incredible, flat ring with an enormous width. It begins just beyond the orbit of Neptune, 30 astronomical units from the Sun, and ends perhaps 100 to 150 astronomical units from the Sun. A truly vast and awe-inspiring expanse. This amazing belt is also thought to be the source of short and medium-period comets. In 2005, Reid made history when he discovered a planet the size of Pluto. Its diameter was only 50 to 60 kilometers smaller than Pluto, a truly remarkable feat. Astronomers were thrilled to discover that the number of planets in our solar system would soon increase significantly. They carefully separated the grains from the chaff, eager to make the most accurate assessment possible. In a bold move, they crossed out Pluto and others from the number of major planets in the solar system. That leaves 8. And even if the mysterious 9th planet, which is still out there for astronomers to find, will be discovered, it will have a special status all its own. For example, let's assign them to the Large Peripheral Objects of the Solar System, KPO. The possibilities are endless. Astronomers are excited to explore the vast expanse of the solar system and have not ruled out the possibility of an unknown planet, a ghost planet, or even something else entirely. This planet is a calm, peaceful presence in our solar system, gently coexisting with the known asteroids without disturbing their movement. It has gone unnoticed by telescopes and the few areas that have reached the outskirts of our cosmic world. But it's out there. It moves in an incredibly elongated orbit at a great distance from the Sun. Its orbital plane is tilted at a very steep angle relative to the ecliptic plane. But what if there's more? What if there's something out there, waiting to be discovered? It's unlikely that there's a brown dwarf or an invisible satellite of the Sun hiding in the dark, mysterious gloom of the outskirts. But what if there is? A dwarf star is not Messina, but who knows what else it might be? There's a good chance our telescopes would have spotted them. Maybe this planet X should be called Trans-Kuiper instead of Trans-Pluto. What a fascinating idea. After all, calculations show that it should be outside the Kuiper belt, which is really exciting. In 2016, American astronomers Konstantin Batyrshyn and Michael Brown made an incredible announcement in the pages of the Astronomy journal. They revealed that the mass of this mysterious planet is at least 10 times that of Earth, and its orbit around the Sun may span 20,000 years. It is an incredible 600 times farther from the Sun than the Earth. And that's where the truly amazing things happen in astronomy. In just 3.5 days, light travels that distance. But this planet's story is a whole other story. Scientists are still trying to figure out if it's a myth or a fact of astronomy. And it's a fascinating mystery, the enduring allure of astrology. Let's dive into the main objections to astrology. The most popular false sciences are well known and convincing, and they're fascinating to learn about. The numbers speak volumes. The results of numerous studies conducted in different countries are in, and they're fascinating. The position of the Sun in the zodiac at the time of birth has absolutely no influence on the formation of personality. This is just one example of many cited in his work, The Russian Astronomer with the Order. French statistician Michel Gitelson embarked on an incredible journey, delving into a trove of historical records. These archives held the precious details of 41,000 individuals' birthdays, places of birth, and more. Among them were 16,000 incredible scientists, artists, writers, athletes, and more, as well as 25,000 everyday people. Viculin made an amazing discovery. He compared the position of the planets and constellations at the time of a person's birth with their personality type and occupation. He made an incredible discovery. There is no connection between a person's character and their activity. On the one hand, his zodiac signs and the position of the planets in the houses and their mutual aspects at the time of birth are truly fascinating. On the other hand, but up until the 20th century, the most important task of astrology was not just about writing horoscopes for ordinary people. It was about predicting the future. Astrologers believed that the stars and planets, scattered across the firmament, sent messages from heaven. These messages could be interpreted in many ways, including as fallen cards or dice, thrown on the table by a fortune teller. Astrologers were the go-to experts for kings and generals, offering invaluable advice on the best times to declare war, embark on campaigns, and make peace. For this purpose, they eagerly observed the starry sky, waiting for a happy confluence of planets. The incredible history of astrology began long ago, when fate struck. The anger of the almighty gods could fall on people from everywhere, and it remained only to guess when and where it would happen. What an exciting time to be alive! If the gods in almost all religions and cultures came down to man from the heavens, then maybe before they revealed their decision, they lit heavenly fires. In that case, the light of the stars and the brilliance of the planets were surely a sign that they could read the future. It's incredible to think that the roots of modern Western astrology go back to the Christian era in Babylon, Mesopotamia, and ancient Egypt. But it probably stretches even farther back to a time before writing was invented, where no one's writing has preserved the memory of it. In that fascinatingly distant past, alongside astrology, this noble practice of foretelling the future emerges as its intriguing counterpart. Astronomy, like that of the brilliant Renaissance painter, is an enduring pursuit that never fades. It's a field that never loses its allure, even when we lose our colors. The study of astronomy was an exciting auxiliary field that allowed people to observe the stars and planets and calculate their movements. And astrology was the first to try to understand what was being observed. And more confidently, they began relating one accidental celestial phenomenon with another to earthly events. Their arbitrary coincidences became law, and what a wonderful thing that was. From a scientific standpoint, astrology is not just superstition. It's a legitimate science. At least, that's according to renowned American researcher Lawrence Jerome, who made this observation in his book Astrology and Modern Science. A critical analysis of the search for patterns in the world around us and their description. This is an amazing scientific approach. It's no surprise that the renowned German philosopher Ernst Cassirer observed almost a century ago that astrology employs scientific methods of thinking. It delves deeply into the underlying causes and draws conclusions that inevitably emerge from the original conditions. And now, we'll wrap up with a summary of our final conclusions. The ancient view that the heavenly bodies directly influence earthly events formed the foundation of astrology. To assess this influence, astrologers used mathematical methods to identify patterns in celestial phenomena, and they were able to do so with great success. Since the time of the event was of the utmost importance in predictions, astrologers made detailed tables by means of long-term observations. They even indicated the position of the most important celestial bodies at certain moments in time. They used the methods of geometry to build the orbits of the planets. And so, the foundations of the future science of astronomy were laid. The history of astrology in Europe was anything but boring. The ancient Greeks were fortunate enough to borrow the signs of the zodiac and the system of horoscope construction from the Babylonians. In the 3rd–2nd century BC, the incredible treatise, the Emerald Tablets, attributed to Hermes the Unity, made its appearance. In that place, they made an amazing discovery. They realized that what is at the bottom is similar to what is at the top, and inversely, what is at the top is similar to what is at the bottom. The rise of Christianity in the Roman Empire brought about a fascinating turn of events. For a while, astrology was prohibited. In 364, the Council of Kiev made a bold decision. It is not befitting for initiates or some to be magicians or obligatory or numbers to guess, but they can be anything they want to be. The Church was relentless in its pursuit of astrologers, sorcerers, witch doctors, and even memes. All of them undermined faith in God, which was a bold and courageous move. But astrology didn't just survive, it thrived. It was helped by its duality of proximity to astronomy, the science of the stars and planets, which was a huge advantage. In the 8th century, The Byzantine Empire saw a golden age of scholarly astrology and astronomy. In the late Middle Ages, astronomy made its way into schools, bringing with it a whole new world of knowledge. In the 12th century, something truly remarkable happened. Common schools began to appear in Europe, opening their doors not just to monks, but to everyone. They taught 7 incredible liberal arts, arranged in 3 magnificent groups of quadriga. And the best part is that they taught grammar, rhetoric, and dialectic. The aquarium was an incredible collection of subjects, including arithmetic, astronomy, music, and geometry. Geometry was actually the study of astronomy and astrology, which was truly fascinating. During the Renaissance, astrology exploded in popularity across Europe. In Schiller's famous drama Death in Captivity Stein, the main character, Commander Albrecht Stein, is filled with joy when he first sees a large blackboard covered in the astrologer's scribbles, which show the position of the planets. This is a clear indication of the excitement and anticipation he feels for the events that are about to unfold. It promises him incredible, unprecedented triumphs, a happy confluence of planets. The great triad of Mars, which is fatal, pernicious, and insidious, is caught between 2 luminaries that are so favorable to me, Venus and Jupiter. They triumph over the malevolent foe. However, the title of the play already reveals how wittily the stars mock us. In a surprising turn of events, Stein is honored with death instead of triumph. This is the spirit of the new age to which Schiller belonged. The age of enlightenment. The spirit was bold and brash, turning its back on the trappings of wealth and the limitations of science. In a truly astonishing turn of events, no physical connection between the motion of the heavenly bodies and earthly events was revealed. But then, on the eve of the 20th century, interest in astrology was suddenly rekindled. This was thanks to the fashion for theosophy, occultism, and spiritualism that swept across the globe. They even made their way to the courtroom and astrology. It experienced a fantastic new surge of popularity in the 60s. The best thing about horoscopes is that they're still as popular as ever. After all, you never know what advice and answers they'll come up with next. Some of them are pretty accurate too. Scientists may call it a coincidence, but many people believe it's more than that. But professional astrologers are thrilled to have another success story to share. Oh, the suspense. Which one of them is right? Let's dive into another excerpt from the incredible book, Order Expanding the Boundaries of the Universe. In one of his works, Kepler gave researchers a friendly reminder to keep an open mind about the stars and not to dismiss conventional superstition too quickly. Even today, those who can see the future are still analyzing their astrological capabilities. We're happy to report that so far, no child has been found in this war. There's muddy water, but there's also hope. As you probably know, the famous astronomer Kepler made horoscopes. Now, let me tell you how he expressed his attitude to classical astrology. An astrologer who predicts anything solely by the sky and is not based on the character of the soul, mind, strength, and appearance of the person to whom he predicts goes the wrong way and gives advice for good luck. But there's another way, so it's up to you to decide. Is astrology a science? The hyacinth Greek world system is truly fascinating. This system of the universe is a perfect illustration of that famous phrase about Tagore. Man is the measure of all things, and right there at the center of the world, it all rested. Or, even more amazing, the earth revolved around its axis, which meant that man was at the center of the universe. The sun, moon, and planets revolved around their Lord, not from the earth. How incredible is that? These were the unchanging, eternal truths. After all, people from time immemorial had seen in the night sky many immovable stars, and this was a wonderful suggestion that the earth too was immovable. In this magnificent world, bathed in a divine peace. Only the sun and moon of the planets moved. As mathematics developed, these scientists were thrilled to discover that they could describe these movements in a way that allowed them to predict the position of the heavenly bodies in their ideal incarnation. The ancient Greek scientist Eudoxius lived a long and fruitful life, spanning 395,338 years before the Common Era. The motion of the heavenly bodies was reduced to the sum of their uniform rotation around a number of spheres, on whose surfaces the planets were located. These incredible spheres were known as gamma cylindrical spheres. In a magnificent dance around a common center, the Earth remained steadfast. However, the apparent simplicity of this scheme was a mere illusion. Ancient Greek astronomers were the first to notice some fascinating irregularities in the behavior of celestial bodies. They observed that the sun moves on the ecliptic in a way that is not perfectly even. The moon's ever-changing position in the sky creates fascinating patterns, while the planets' movements among the stars produce intricate, ever-evolving loops. They were striving for accuracy and harmony at the same time. To get a truly accurate picture of celestial movements, each planet was given its own complex combination of several spheres. Now, let me show you how he used 3 spheres to describe the motion of the moon. The first sphere rotated around the central axis, making 1 revolution per day, a truly remarkable feat. And then, in an amazing turn of events, the second one made a revolution relative to the previous one in just 18.6 years. And then, to top it all off, the third sphere fixed on it made 1 revolution in just 27.3 days. And right at the equator of the sphere was the moon. And the best part? The addition of a number of rotations occurring in different planes gave a result that perfectly aligned with the observation. From the mother's perspective, it's fascinating to see how the Earth revolves around the sun, and the sun revolves around the Earth. The distance between them remains unchanged, wrote the Russian historian of science Zhytomyr, who was contemporary of Evdokia Irakli. And now, let's dive into the political side of things. The incredible years of life spanned from 319 to 322 BCE. Based on the fascinating fact that Mercury and Venus never move farther from the Sun than an arc of a certain value, he made the brilliant assumption that they orbit the Sun. This notion was embraced wholeheartedly by the astronomical community. But wait, there's more. The Sun, the Moon, and the stars all revolve around our planet, the Earth. Duke was the one who introduced the concept of cyclic motion into astronomy. In a truly astonishing turn of events, celestial bodies revolve around a certain center, which in turn revolves around the Earth. Let me tell you about one of the greatest philosophers of ancient Greece, Aristotle. In 380 BC, the great Aristotle laid the foundation for our understanding of the cosmos. He theorized that the Earth resides at the center of the world, a concept that Eudoxius later claimed. In his book On the Heavens, he joyfully proclaimed that the Earth must be at the center and stationary by necessity. It is visible because, in an amazing display of physics, bodies are thrown by force and then fall upward again to the same place, even if the force throws them an infinitely great distance. This is proof positive that the Earth is at the center of the universe and does not move. Just think for a moment what would happen if there were no such thing as the Earth. Everything would keep on falling forever. Aristotle was convinced that the Earth must be spherical. After all, each of its parts has weight and tends downward until it reaches the center. This system of the world was called hyacinth, a Greek word meaning earth. It explained so many of the incredible phenomena observed in the sky. And now we come to the incredible Apollonius of Perga. The incredible history of our planet spans millions of years, from the dawn of life in 262,119 BC to the hyper-advanced civilizations of 190 and 120 BC. Eudoxus' theory was taken to a whole new level. But to explain the planet's motion, they had to change the geometry of the universe, and they did it. The great diameter of Apollonius was the first to introduce an ingenious system of interconnected circles and pi cycles and differentiation, replacing the cumbersome spheres that had been used before. Later, the diocese was firmly connected with the name of Claudius Ptolemy, who made an incredible suggestion: that the sun revolves around the earth uniformly and moves on a circle, but that the earth is displaced relative to the center of this circle. This could be the answer to why the seasons have different lengths. And guess what? Through observation, the cheetah found that spring lasts about 94.5 days, and summer about 92.5 days. And then, in autumn, we have 88 days to enjoy the beautiful changing colors of nature. Winter is about 90 days long, which is plenty of time to cozy up inside and enjoy the warmth. He even named the orbit along which the sun moved the center. And as time goes by, the distance between the two centers is increasing. He selected this value so that it perfectly matched the results of his measurements. But the planets were more challenging. Their observed motions were too complex to describe using simple geometric models, which made the challenge all the more exciting. This was a challenge the cheetah couldn't wait to tackle. In a truly remarkable turn of events, the ideal model of the universe by ancient standards was finally created almost 300 years later. The incredible author of this masterpiece was none other than the brilliant Greek scientist Claudius Ptolemy. He dedicated years of his life to this project, from the 100th to the 160th century AD. He replaced the simple diocesan scheme, which had been in place for centuries, with a more complex and precise scheme of multiple circular motions. This was a truly revolutionary idea. This was the one that allowed them to explain the loops, those amazing figurative movements of the planets. Moreover, Ptolemy made such brilliant modifications to the system of cycles and differentiation that he could even predict the movements of planets many years in advance. This was a truly remarkable achievement in astronomy at the time. In the simplest case, according to Ptolemy, a planet orbits on a cycle whose center moves on another circle of the differential, circling the Earth in a stationary position. This is an amazing and elegant solution. To fit the theory to observations, he introduced additional cycles, which was a brilliant move. The Russian astronomer Bronstein was amazed to discover that Ptolemy had managed to pick up such precise sizes and speeds of rotation for all the wheels of his universe. This meant that the description of planetary motions was now incredibly accurate. Ptolemy's system was the ultimate triumph of ancient astronomy. It yielded absolutely perfect results that perfectly aligned with the observational data. The best part is that you could make all new amendments to it, greatly complicating it, but at the same time achieving the highest accuracy of results. This, however, was its undoing, and a fascinating one at that. For an incredible 1,500 years, astronomers devoted their efforts to perfecting the system of Ptolemy. By the beginning of the 16th century, the amazing Ptolemy had already devised a system that could describe the motions of the Sun, Moon, and 5 known planets with 77 circles of differential and cycles. Many astronomers were thrilled to dive into this complex theory. Polish priest and astronomer Nicholas Copernicus was on the same page. A life well lived. 1,000 years, 473 years, 540 years. And now for something really exciting. Third, he set out to make Ptolemy's model more elegant and straightforward. Copernicus was thrilled to share that he had taken the time to read every book he could get his hands on by philosophers from all walks of life. He was on a mission to find out if anyone had ever expressed the opinion that the world's spheres had motions different from those taught in mathematical schools. So he found the thesis about the motion of the Earth from the ancients, and it was a real eureka moment. If we follow it, considering that the Earth is only one of those planets which, revolving around their axis, move in a cycle while the sun is at the center of the universe, the world system becomes much simpler. In this system, the number of circles is reduced to 34, which is a great improvement. Copernicus' system, which he laid out in his major book on the rotation of the celestial spheres, was a breeze to calculate. It allowed for the incredible explanation of the sun's apparent motion in the sky. While it was not fundamentally more accurate than Ptolemy's, it was still a great step forward. However, the transition is divided into three incredible systems where the Earth revolves around the sun. This incredible shift in thinking about the structure of the world paved the way for the groundbreaking discoveries of Galileo, Kepler, and Newton. This is why the teachings of Copernicus are the foundation on which all modern science in the search for other Earths is built. For more than 2 decades, since the discovery of the first exoplanet, a planet lying outside the solar system, astronomers have been on a thrilling quest to find a second Earth with conditions similar to those on our planet. And there's more. There's another Earth, or another anticyclone that's also a twin Earth. But it should have been sought not in distant star worlds, but quite near, and it was. It orbited the same path as our planet, moving in perfect sync with it, and was always hidden from view by the solar disk. This hypothetical planet was the one astronomers of the past were searching for, but it was always just out of reach. It was right under our noses the whole time, just 2 astronomical units away at a distance of 1 Earth orbit diameter. It remained inaccessible to observation from Earth. With ground-based telescopes, we could peer into the life of other galaxies, but we couldn't spot this planet. It fooled us, but it didn't fool our curiosity. That's the amazing thing about ground-based telescopes. With the development of astronautics, it was confirmed that there was no Earth. But it didn't last long. The first mention of this fascinating planet was way back in the 5th century BC. An ancient Greek philosopher left us with a description of this fascinating planet. In the year 473-88 BC, the world was introduced to a new and exciting field of study: philology. Philologists from Crotov were inspired by the brilliant mathematician Pythagoras, who founded a school that was like a sect all its own. They believed wholeheartedly in the power of numbers. By the end of the 5th century, the mystics of Pythagoras had captured the attention of their fellow citizens. In a stunning display of violence, they were brutally massacred. In a thrilling turn of events, legend has it that one of the two managed to save himself. And it was none other than a philologist. Antique authors rave that the philologist was the first to spread Pythagoras' teachings to the public. He wrote an incredible book about nature that has survived in excerpts. It also spoke of the structure of the universe, which was truly fascinating. In the 5th century AD, the Byzantine writer John Bay gave us a thrilling description of this incredible system of the world. Philologos places fire at the center, which he calls the hearth of the universe, the house of Zeus, the mother of the gods. He also adopts another magnificent fire, placed above all things, and serving as the volume of ivy. The first is by nature the central fire, and around it, in a magnificent, celestial dance, the 10 divine bodies, the sky and planets revolve. Then comes the sun, below it the moon, below it the earth, below it atheism, and after them all, fire. In another version, the earth is even more fascinating. It is not just one body, but 2. These 2 hemispheres are divided along the equator by a gap through which the heat of the sacred flame penetrates the firmament. In this fascinating system of the world, there is another earth that rotates in perfect harmony with our own. It is a hidden realm, enclosed by the body of the earth, waiting to be discovered. Modern researchers are thrilled to report that the hypothesis of philology can be easily tested by our standards, thanks to the recent expedition that covered at least a quarter of the globe. However, Zhitomirsky playfully pointed out that in that era, such advice would be akin to suggesting that our astronomers fly to the center of the galaxy and check whether there is a black hole there. Impossible? Not at all. And there was another reason for the expedition. Philologos, unlike other Greek astronomers, had a unique idea about the Earth. He thought it was a flat disk. We get to live on the side of the Earth that is always turned away from the central fire and faces the Sun and other planets. This is why we can live our lives to the fullest. The fire doesn't burn the world to the ground. In fact, it's the particles of it that illuminate and warm our planet. The Oikoumene inhabited a part of the Earth that was teeming with life. The Sun is visible through the glass, reflecting the fire that is in space. The other side of our amazing planet is facing away from the Sun and the central fire, which makes it uninhabitable. We don't know how accurately John conveyed the mystical teachings that emerged 1,000 years before him, but it's an intriguing question. For example, Aristotle in Logic, commenting on the astronomical theory of the Aryans, has so explained the occurrence of other Earths. They define numbers as the beginning of all nature, and they under numbers and their ratios. All definitions and parts of the sky, and the whole of nature, and where anything did not coincide, they made up this amazing idea that there was a coincidence. For example, number 10 seemed to them the most perfect, embracing all nature of numbers. Then they said that moving in the sky spheres also 10. But here's where it gets really interesting. Since we see only 9 such spheres, they invented the 10th against the Earth. Now, let's dive into the fascinating world of the 9 spheres. These include the spheres of the fixed stars, the spheres of the 7 planets, Saturn, Jupiter, Mars, Venus, Mercury, the Sun, and the Moon, and the sphere of the Earth. But could it be that the Earth appearing against the Earth in space is simply a matter of achieving a harmonious balance of numbers? Pythagoras set sail on an incredible voyage. It has a really important role to play. In those days, all celestial bodies were thought to be made of light, with very little mass. The Earth, on the other hand, was a magnificent, solid, and awe-inspiring entity. Fortunately, the philologists and other Greek scientists placed it in the center of the universe, which made things much easier. But it revolved around a central fire. In this case, if the mass of Earth was on the periphery of the universe, it meant that its center couldn't coincide with its own center of gravity. A truly fascinating possibility. The celestial spheres would be in perfect harmony. The philologists, or one of the Pogorelniki whose teachings he retold, came up with an ingenious solution. They balanced the Earth by placing a planet as massive as ours on the other side of the central fire. Fortunately, Aristotle's world system had no such problem. The Earth itself, which had the perfect shape of a sphere, henceforth for a year and a half or 1,000 years, was positioned in the center of the universe. In a truly awe-inspiring display, the other planets, the Sun, and the stars began to recede. In this magnificent cosmic picture, our planet Earth stood tall and proud above us. But there was no refuge to be found against the Earth. In the middle of the 16th century, Nicholas Copernicus made a revolutionary discovery. The Earth no longer occupied the center of the universe. For several centuries, the Sun took its place. In this new system of the world, something incredible happened. The antipode of the Earth was discovered. The incredible French mathematician Joseph-Louis Lagrange. In a truly remarkable discovery, the brilliant Lagrange spent years analyzing the motion of celestial bodies and made an incredible find. A certain point lying behind the Sun that is special and worthy of further investigation. We are fortunate to know of 5 so-called Lagrange points today. This is truly an astonishing phenomenon. Any celestial body that finds itself in one of these points can stay there indefinitely. The forces acting on it, including the gravitational forces of the Sun and the Earth, at these points counterbalance each other. This means that an external influence is the only thing that can make this object leave the Lagrange point. And now for the big question. Where are these points located? Amazingly, two of these points are located in close proximity to our planet, the Earth. One is located between the Earth and the Sun, and the other is on the far side of the Earth, in other words, on the back side of the Earth. And there are two more along the Earth's orbit, ahead and behind the Earth, deviating from it by 60%. And now, for the grand finale, we have the last of these points, which goes by the official name of 3. This is where the Earth should have been on the other side of the Sun, in the very same orbit that the Earth currently occupies. In theory, there could even be an unknown planet located there. Let's assume that the age of space has not yet arrived. In practice, this is impossible for the following reason, which is really quite fascinating. In a brilliant move, the Lagrangian calculated this in the framework of the three-body problem, ignoring the influence of all other planets except the Earth. But here's the really fascinating part. Even these other planets have an impact on the planet at point 3. The calculations show that in just a few 1 billion years, something truly incredible will happen. The counterweight Earth will experience a series of gravitational disturbances that will rock it like never before. Then, it will leave the Lagrange point and collide with the Earth. Today, scientists are thrilled to announce that if the Earth had arisen at the same time as the Earth, the two planets would have collided as early as about 4.5 billion years ago, shortly after the formation of the solar system. Fortunately for Earth, the odds of two planets forming at the same distance from the Sun are pretty slim. In search of the seventh-eighth heaven, the magnificent world of medieval Europe emerged triumphantly from the ruins of the Roman Empire. As you might expect, its ideas about the cosmos were inspired by the great thinkers of the past. They were based primarily on the incredible works of Plato. The dialogue of families is especially important for medieval science. It is the only systematic sketch of Plato's cosmology written several centuries before the triumph of Christianity. It's an incredible, impassioned argument for God the Creator. He crafted the entire cosmos with incredible precision and detail. In a magnificent display of engineering, they crafted the cosmos from its fundamental parts, perfect and unattached, line and affliction. With a masterful touch, they rounded the cosmos to the state of a sphere, the surface of which was perfectly equidistant from the center. They gave the universe an outline that would stand the test of time. From all the outlines, the most perfect one came from 12 to 13 centuries in Western Europe from Byzantium and Arabian countries. The works of Aristotle and Ptolemy. The fortunate acquisition of Aristotle's works was a truly momentous event for Europe. They represented a complete, rational system that explained the whole world in its entirety. Based on natural causes, Australian historian of science Alastair makes a fascinating point. The book From Augustine to Galileo, The Emancipation of the Natural Sciences, is a great place to start. This approach was perfectly in line with the spirit of the High Middle Ages, which was all about rationalizing every aspect of life, including faith. It was most presciently revealed what Christianity had originally sought, but could not find: a philosophical system that could be harmonized with Christian doctrine, and which thereby promised to become a rational pillar of dogma and weaponry. In his book, The Mechanization of Worldviews, the Dutch historian of science Edward Dexter Hayes wrote about the amazing thing called the Apologia Ethica. When the works of Aristotle and Ptolemy were translated into Latin, they sparked some of the most heated debates ever seen in the history of scholarship. The major players of the time, including John Bosco, Roger Bacon, Albert the Great, Thomas Aquinas, and Robert Gross, were all involved. In these debates, a rational view of the world and the cosmos was formed. Just imagine for a moment what this incredible cosmos was like. The medieval cosmos was a fascinating concept. divided into the world below the moon and the celestial spheres above it. The Earth globe was the center of the universe, surrounded by a system of concentric celestial spheres, and at the very top, the most magnificent and inaccessible of all, sat the God of heaven. The spheres were absolutely perfect and unchanging. The world below the moon, the earthly world, was transformed by incredible changes and metamorphoses. Everything here was full of possibilities and potential. The early Middle Ages were a time of discovery and growth, where weaknesses and flaws were seen as opportunities for improvement. The world system is unambiguous, and it's a beautiful thing to behold. In the heavens above the earth, the spheres of the moon, the sun, the planets, Venus, Mercury, Mars, Jupiter, and Saturn, as well as the fixed stars of the planetary sphere, were arranged in a perfect sliding arrangement relative to one another. They were perfectly transparent, made of the purest quintessence or ether. Each magnificent planet was attached to its own sphere. It was a widely held belief that the stars and planets were made of the same wonderful ether as the celestial spheres. We are lucky enough to be able to see them because the density of ether in them is unusually high, so they reflect sunlight or glow themselves. All these celestial bodies are different faces of eternity, and they're all absolutely amazing. They will never, ever be destroyed. The only change they are subject to is uniform circular motion, and that's a good thing, and it can last indefinitely. Medieval scholars were so inspired by this ancient scheme that they added 2 more spheres to it, and it's also revealed in the revelations of the Holy Book of the Bible. And so begins the incredible story of creation as told in the first verses of the book of Genesis. And God created the firmament, and separated the water that was below from the water that was above the door. The amazing thing about this water on the firmament is that it was believed to be made of crystal. In fact, it was thought to be a crystal sphere. This incredible phenomenon was believed to be the root cause of the motion of all the other spheres lying beneath it, and often the blessed souls of virtuous men and saints were lodged there. And finally, outside of it was located the magnificent empire of the realm of God and the heavenly beings, angels, archangels, and seraphim. The magnificent empire was celebrated in a poem by the great Portuguese poet Luís de Camões in his poem Louisiana. And the first orbit, in the radiance of the Earth's rotation of lesser spheres, is a fiery, frenetic, glittering spectacle that elevates sight and mind to the limit. The empire of the blessed is where the high souls abide, living out their divine destiny. They are there, enjoying eternal happiness. This is something that is completely unknown in the superstitious world. But here's the amazing thing. It's as if hundreds of people suddenly saw the same dream and began to write down its fragmentary features. Then, they all wrote about different things, making sure to capture the essence of the dream in their own unique way. So, in a truly fascinating turn of events, medieval authors left us with a plethora of remarkably diverse descriptions of the cosmos, which they discovered through reading ancient authors and engaging in their own reflections and visions. And so we come to the Anglo-Saxon chronicler Bede the Honorable. The average lifespan was an impressive 670 years. In the 2nd century, 735 AD, he writes about the 7 celestial spheres, following the Bible rather than ancient models. Noted French historian Jacques Le Goff was thrilled to point out that Bede's cosmology proudly displays the Greek heritage with full obviousness, right down to the terminology. And then, directly above the Earth, stretched a sphere of air, above that a sphere of ether, and then a sphere. In a truly magnificent display of astronomical prowess, he intervened in the celestial dance of the planets, bestowing upon them the majestic name of Olympus. Just as the Greek gods were known by their own names, so too were the planets now known by their own names. Heavenly fire blazed over these near heavens, creating a breathtaking spectacle. Sometimes it reminded itself, as was believed in the Middle Ages, with streaks of the polar lights, or by the ominous flight of a comet, or by the swift checks of meteors. And above this sphere, stretching as far as the eye could see, was a vault of fixed stars, and above it all, the magnificent heaven of angels, which closed the world. And then there was the seventh heaven, where the Holy Trinity dwelt. Bede's cosmology is absolutely fascinating. It offers a fascinating insight into how an educated man who lived in the 8th century envisioned the universe. The Christianization of this concept reached its pinnacle with the brilliant simplification of the 12th century luminary of the 3 Augusts of dawn. He distinguished only 3 bodies: the corporeal heaven where we see, the spiritual heaven where the blessed dwell contemplating the countenance of the Holy Trinity, and the intellectual heaven where the angels reside. Other authors, while comprehending the heavens, avoided this rather reprehensible minimalism and instead embraced a more expansive view of the cosmos. Let me tell you about the incredible British mathematician and astronomer John Socrates. He lived a long and fruitful life from 1195 to 1256. The author of a treatise on the sphere written around 1230 was a true visionary. His work, which remained the standard textbook of astronomy until the 17th century, favored the order of the spheres as Aristotle had followed it. He then placed Mercury and Venus following the Moon, and finally the Sun and the other planets. It's incredible how almost all images of the celestial spheres from the Renaissance and modern times match this pattern from Thomas Aquinas's era. He lived from 1225 to 1274, and his ideas have stood the test of time. The fourth wrote, referring again to ancient authority with great enthusiasm, Pythagoras made an incredible observation. He said that there are 10 spheres moving in the sky, of which only 9 are visible on Earth. They understand everything through the motion of the 7 planets, and the 8th through the motion of the unchanging stars. And the 9th is the first engine through the phenomenon of the day. Dante Alighieri lived for 1,000 years. The first one built an incredible universe with 9 heavens and a crystal sky. He did something truly remarkable. He combined the first engine into one, and he didn't consider the empire to be a special heaven. How fascinating! If we now turn to the way medieval scientists imagined, let us say in modern language, near-Earth space, that which stretched between the Earth and the Moon, we will find here 4 more incredible invisible spheres. These 4 elements were the very building blocks of our universe. They were the ancient elements of air, fire, earth, and water, and the elements were arranged according to their specific weight, which was really quite fascinating. And then, right at the center, there was the Earth. Surrounding it was water, then air, and finally, up to the Moon, there was heavenly fire. I'm excited to clarify that the sphere of the Earth cannot be identified with the globe it surrounded. This sphere was made up of one simple, magnificent element: Earth. Medieval theologians saw it as an incredible illustration of the biblical verse about the firmament that rests between 2 waters, and God called the firmament heaven. In the late 16th century, the incredible Italian philosopher and astronomer Giordano Bruno made a groundbreaking discovery: the incredible years of life between 1500 and 1600. He was the first to boldly speak publicly about the imperfection of the celestial spheres. It's truly astonishing that almost all astronomers before him, including Copernicus and Kepler, believed that the cosmos was bounded by a sphere of fixed stars. Bruno, however, made the bold and revolutionary claim that the universe is infinite, and that all the stars visible to us are just like the sun, only located very far away from us. And they have their own planets orbiting around them. And there's more. They, too, are inhabited by intelligent beings who may not be at all like us. A century and a half before Bruno, the incredible Cardinal Nicholas of Cuspis indulged in no less daring fantasies. The year 1400 was a great one for life expectancy. First, an incredible 1464. He was a close advisor to Pope Pius II. He made the bold and brilliant argument that the universe has no boundaries, that it is infinite. The machine of the world has, so to speak, its center everywhere and its circumference nowhere. And what is that center? Why, it is God. God is the circumference and center of it all, because He is everywhere and nowhere. At last, the subordinate Ricci, Bruno, of the celestial sphere fell, releasing countless stars from their confinement, spilling out into the infinite distance. But in this universal catastrophe, the crushing medieval cosmology itself perished, paving the way for a new era of scientific discovery. At last, science and theological dogma had finally diverged. Bruno was waiting for the cardinal's Nissan and the bonfire for his sacrilege and other speeches, for a ruthless denunciation of myths. He was burned according to the custom of the Inquisition, and what a glorious end it was. Amazingly, this all took place during the time of Cervantes and Shakespeare, of Kepler and Galileo. Tycho Brahe's incredible world system. In 1580, the world was treated to the incredible spectacle of the famous Danish astronomer Tycho Brahe. He lived a long and fruitful life from 1546 to 1601, during which time he published a book entitled On Recent Phenomena in the Celestial World. This book was based on the fascinating results of his astronomical observations. He made the bold decision to bring together two seemingly incompatible ideas, old, rejected doctrines and the new. His brilliant answer was to combine a world system that had been considered infallible for 1,500 years with a world system that had already been rejected for half a century by church authorities and many learned men. This new system was created out of a spirit of contradiction to the former, and it was truly a revolutionary idea. So, Tycho Brahe made the brilliant decision to take the best of Aristotle's physics, Ptolemy's hyacinth world system, and divide it into three amazing Copernican world systems. This shifted the Earth and made it revolve around the Sun, which was a truly revolutionary idea at the time. In November 1577, something truly extraordinary happened. A bright comet appeared in the sky, marking the beginning of an incredible story. Since ancient times, the comet has been regarded as a spectacular phenomenon, a celestial ladder of light that flashes across the world. People were on tenterhooks, expecting an imminent war or plague. For 3 glorious months, its magnificent flames burned brightly. These months were truly happy ones for Brahe. He was thrilled to regularly observe the comet. In a bold move, Aristotle once made the case that comet fires were nothing more than atmospheric phenomena. The far-fetched world was a mysterious, magical place that seemed eternal and unchanging. This was still believed today, and for good reason. But the observations of Brahe and other astronomers showed something truly astonishing. This comet was 3 times farther away than the moon, but it moved as if it had pierced the firmament. A breathtaking sight to behold. In a truly astonishing turn of events, the comet's path crossed those very celestial spheres that Aristotle had believed to be the domain of the planets. So, guess what? Those spheres don't exist. Brahe set about writing an incredible book about comets. But sometimes, the book is likened to a ship that, having set sail, suddenly returns to take on board another very important passenger. Brahe's book, which was devoted to recent phenomena deduced from the sky, suddenly accommodated the new system of the world he had laid out, and it was a truly magnificent accommodation. He had a brilliant explanation for its sudden appearance. I believe that the old Ptolemy and his arrangement of the celestial spheres was not sufficiently elegant, and that the assumption of so many cycles, by which the apparent motion of the planets relative to the Sun is explained, must be considered superfluous, and this is an exciting development. At the same time, I am thrilled to share that the recent innovations of the great Copernicus, who resembles Aristarchus by his ideas, elegantly eliminate those places which are superfluous and inconsistent with the system of Ptolemy. And the best part is, it does all of this without violating any mathematical principles. The body of the Earth, however, is truly magnificent, stretching far and wide, and simply not designed for motion. I am absolutely convinced that our Earth is at the center of the universe. This is in line with what many ancient astronomers and philosophers believed, as evidenced by the Holy Scriptures. It is also in line with what Copernicus wanted, but we know that he was wrong about the annual circulation of the Earth. But how did he manage to unite these irreconcilable ideas, which were as opposed to each other as two opposing forces in a duel? And what incredible sacrifices did he make to reconcile his enemies? What groundbreaking new idea did he come up with to revolutionize the way we think about science? Brahe was not only an incredible astronomer, but also a brilliant designer and mechanic. He made most of the instruments he used himself. To improve the accuracy of his measurements, he did something truly remarkable. He increased the size of his instruments and also devised new methods of observation in an effort to minimize any errors. For example, he developed an amazing sighting device for the billion-dollar sphere to accomplish this. As Jitomirsky noted, Brahe was the creator of the most accurate instruments in Czech astronomy before the telescope, but it was the absolute certainty that his measurements were the most accurate. He was thrilled to observe the annual order of the stars, their apparent movement, and those that remained stationary with his instruments. The Earth, as the great Copernicus claimed, moves. In a year, it must pass a distance twice as great as that which separates it from the Sun. Then maybe Copernicus was wrong after all, and that's an exciting possibility. In 1589, Tycho Brahe wrote to his assistant, the German astronomer Christopher Lottmann, with an intriguing question. Do you think it possible that the distance between the Sun and Saturn would not be even 1/100 of the distance from the sphere of fixed stars? And yet it must be so. If the annual path of the Earth, viewed from the fixed stars, were only 1 minute of arc, but then the fixed stars of the third magnitude, whose apparent diameter is also 1 minute, must have the dimensions of the Earth's orbit. And that is truly an astonishing thought. He was amazed that the stars were so big and that they were so similar to planets, but they might be made of a totally different stuff, much, much brighter. It is now that we realize something truly amazing. When we look at the firmament, we see not the true size of the stars, but the brightness emanating from them, which we call stellar magnitude. In Brahe's time, astronomers had a different, equally fascinating perspective. The Danish scientist was fortunate to be the last great astronomer to live before the invention of the telescope. In the 17th century, scientists made an incredible discovery. Fixed stars have no visible diameter at all. To the naked eye, they appear as mere luminous dots. In the first half of the 19th century, we made the thrilling discovery of even the stars closest to Earth. Not only were instruments unsuitable, but so were telescopes for the next 250 years. Brahe was well aware of what he disliked in the Copernican system, but he was also brimming with ideas. He proposed a system thematically equivalent to Helios with electric, but free from this disadvantage. In the same book, he wrote about the fascinating possibility that both Ptolemy's and Copernicus's hypotheses could be combined to create a new, more accurate model. He began to wonder if it was possible to develop a hypothesis that would align with both mathematics and physics, avoid theological condemnation, and still explain the mysteries of the cosmos. In Tycho Brahe's system, like that of the ancient Greek scholar, the years are 388 BC and 315 BC. In this incredible model, all the other planets, except our own, revolved around the Sun. Even the Sun itself, like the sphere of stars, revolved around the Earth. This model was absolutely amazing. It perfectly explained the peculiarities of the planet's trajectories and even predicted the phases of Venus, which was discovered only with the invention of the telescope. From a purely computational point of view, it was no different from the Copernican system, but it had important advantages and was not condemned by the Inquisition. Brahe was justifiably proud of his world system, which, although it did not play a significant role in the history of astronomy, aroused the interest of contemporaries. In fact, there are two known instances of other astronomers trying to pass it off as their own discovery. Among her few supporters, we must not forget the Italian astronomer Giovanni Battista Lee, who was a great admirer of her work. In Life 1500 y 1671, I'm excited to introduce you to the authors of this incredible book, a magnificent new album of vestments, which was a stunning summary of the astronomical knowledge of the time. Ricci, however, made some incredible modifications to Tycho Brahe's system of the world, which has been dubbed tragic by some. He made another brilliant move by making Jupiter and Saturn revolve around the Earth as well, further limiting the Sun's power. However, this innovation didn't quite work as planned. Brahe's system was rejected by most scientists back in the 17th century because it was too complicated compared to the Copernican system. And that was the end of the magnetic forces on the tether. At the beginning of the 17th century, it became clear that a strict mathematical order reigns in the solar system, a truly astonishing discovery. Each planet moves on an amazing ellipse which looks like an elongated circle and, in addition to the center, has two focuses. In one of these points, the Sun is always there waiting for us. The planets are either approaching it or moving away from it. And the best part is that the speed of the planet also changes. As it approaches the Sun, it picks up speed, and as it moves away from it, it slows down. And the further away the orbit is from the Sun, the slower the planet moves. It's truly fascinating. But how did this order in the heavens come to be? In Aristotle's classical celestial mechanics, the stellar sphere, situated almost above the terrestrial world, possessed a first motion that did not descend to the lower lying celestial spheres. And let's not forget the planets closest to us, including our very own moon. The brilliant mind behind the revolutionary new celestial mechanics was none other than the German scientist Johannes Kepler. In the year 1570, he lived for many years. He was the first court mathematician of the Holy Roman Emperor Rudolf II, an incredible achievement. After Tycho Brahe's death, Kepler was given access to a treasure trove of the astronomer's observations. Using these records, he made a groundbreaking discovery in 1600. The law of planetary motion, also known as the law of areas. In equal time intervals, a planet passes equal areas of the orbital sectors, which is really cool because it means that the planet is always moving at the same speed in the same direction. This is now known as Kepler's second law. The radius vector of a planet at equal intervals of time describes equal areas. In 1600, Chaplin made another incredible discovery. Each planet orbits on an amazing ellipse, with the Sun at one of the focuses, and it was subsequently given the first ordinal number. In 1609, at Heidelberg, Kepler published the book New Astronomy, where he joyfully expounded both of these laws. The theory of planetary motion was undoubtedly Kepler's greatest and most impressive achievement. The full title of his famous book is New Astronomy Caused, or The Physics of the Sky Set Forth in Investigations on the Motion of the Star Mars by Observation. This is a truly magnificent work, nobler than even his esteemed husband Tycho Brahe. This lengthy title is no accident. Kepler set out not only to describe the visible, but also to understand the causes of all that happens in the heavens. In a bold move, he challenged the long-held belief of his time, suggesting that the movement of the planets is not simply a matter of chance. Instead, he proposed that it is the sun that sets the pace, guiding the planets in their celestial dance. So, what incredible force were those planets obeying? Since we were kids, we've known that the planets revolve around the sun under the influence of gravity. The incredible Isaac Newton was the one who discovered this law. A few decades before him, Johannes Kepler was also sure that from the sun comes some invisible force to which all the planets obey. And he was right. Could it be the same incredible force that makes iron filings obediently follow a magnet? In the 17th century, interest in the mysterious magnetic force skyrocketed. In 1600, the incredible work of the English physicist William Hilton was published. In it, he summarized all the amazing results of observations and research accumulated over the previous 100 years about magnets, magnetic bodies, and the huge magnet of the Earth. Relying on these facts, René Descartes made an incredible suggestion in his Beginnings of Philosophy in 1640, that there is a special magnetic substance, is the driving force behind so many of the incredible phenomena we see. Descartes wrote this after Kepler made the incredible discovery that the greatest celestial phenomena before our eyes could be attributed to something like magnetism, the incredible motion of the planets in their orbits. It's fascinating to see how Kepler, despite being a flawed reader of Hilbert's book, was able to draw parallels between the actions of the magnet and the celestial events he observed. This led him to unlock a profound understanding of the universe. In his book Harmony of the World, published in 1619, Kepler made an incredible proclamation. There is a kind of divine force at work. It is a kind of magnetic force, the very soul of the engine. The sun is the source of this incredible force, which it emits like its own rays. It influences the souls of celestial bodies, urging them to move in certain orbits. In a truly remarkable turn of events, the sun bestows this incredible force upon the planets that surround it. Just as the impulse of any mover, say the foot of a body of tools, imparts to the object obeying it, the sun literally invests this force in the planets. A ball, an arrow, a cannonball, each propelling its own unique force, which now induces that body to move on. This hypothesis was revolutionary because it seemed impossible that a force could act at such great cosmic distances at the time. The intensity of this incredible quasi-magnetic force acting on each planet is directly proportional to the distance from the sun to that planet. It's just like the intensity of light, which diminishes as we remove ourselves from the source. And the same thing happens with the soul of the engine. And as the engine soul grows stronger with distance from the sun, we can see a corresponding decrease in the motion of any celestial body. It's fascinating to see that Kepler was already exploring this idea of an engine soul around 1600. He even uses the term engine ability or engine force in his correspondence. This is a clear indication that even later, Kepler boldly broke with Aristotle's concept by using the term engine soul. For even saying the soul of the engine, he actually means the incredible force emanating from it. Even though Kepler was mistaken in believing that this force was magnetic in nature, he was still on the right track. He described what was happening in the heavens with incredible precision, in accordance with all the rules of modern physics. Today, historians of science have a fascinating classification for his shower engine. They call it a scientific myth, but it is a very plausible myth. Amazingly, Kepler, seeking to refound celestial mechanics, did not take into account the influence of planet mass or mutual planet influence. Yet, in general outline, he drew a scheme of celestial body motion that was correct. In an amazing turn of events, Kepler's laws, derived from his keen observations, were later used by Newton to justify the law of universal gravitation. Newton made an incredible discovery. Under the influence of mutual attraction between two bodies, such as the Sun and any planet in our solar system, they move in accordance with the laws of Kepler. But the soul is the invisible mover, this incredible soul of the engine, now in a metaphorical sense, has become the force of gravity. One of the most exciting discoveries in physics in recent years was the discovery of gravitational waves in 2015. In the fall of 2017, the Nobel Prize in Physics was awarded for this incredible discovery. Once again, we are prompted to think of Kepler's amazing magnetic force. And the best part is that gravity propagates, as we now know, like electromagnetic waves. The two theories of Kepler and Newton are rejected, and both are accepted. Truth and myth come together again in the erroneous, mythical, searching for ideas that bring us closer to the truth. Was there really a planet Phaeton? For ages, people have believed in the existence of this legendary planet. This belief was greatly helped by the supreme power of the science of mathematics. In 1596, Johannes Kepler made history when he spoke about this planet for the first time. He was absolutely fascinated by the vast, empty space between the orbits of Mars and Jupiter. It disrupted the celestial harmony. Kepler set out on a thrilling quest to discover a law that would link the orbital times of the planets. But guess what? With just 5 planets, it's impossible to find a law. Then he made an audacious move, allowing for 2 new planets, one between Jupiter and Mars, and the other between Venus and Mercury. The biographer of the scientist was so excited to write about the birth of this hypothesis. In 1766, German mathematician and astronomer Johann Daniel Titius made an incredible discovery. He formulated an empirical rule that allowed him to approximate the distance from the Sun to the known planets at the time. In an amazing turn of events, it was discovered that these distances correspond to a simple hour series, and it's formed in this way. Now, take a look at this amazing numerical series. 0, 1, 2, 4, 8, 16, 32. Now for the fun part. Multiply each of its members by 0.3 and then add 0.4 to the result. And what emerges is the numerical series 0.4, 0.7, 1.6, 2.8, 5.2, and 10. A truly astonishing result. These numbers are exactly the distance from the Sun to the planets, including Saturn, and they're absolutely fascinating. All you have to do is measure the distance in astronomical units. 1 astronomical unit is equal to 150 million kilometers, which is the average distance from the Earth to the Sun. This law is now known as the rule of the freedom bird, named after the incredible work of the German astronomer Johann Euler Waters in 1772. This law matched the location of the planets in our solar system perfectly. There was just one exception. A planet at a distance of 2.8 astronomical units for 100 million kilometers from the Sun had not yet been found, and that's exactly what the mathematical law demanded. In 1781, the planet Uranus was discovered, following Saturn. It was exactly at the distance from the Sun that had been predicted, sending the freedom bird into overdrive. Astronomers set out on a systematic search for the mysterious 5th planet. And then, success came to Italian astronomer Giuseppe Piazzi. On the night of January 1st, 1801, he made an incredible discovery. A small planet called Ceres. The long-awaited discovery finally came, but it was soon overshadowed by even more incredible finds. They came pouring out of the Horn of Plenty, Pallada, Juno, Vesta, and more. And then, in 1840, the German astronomer Heinrich Wilhelm Pohl made an incredible discovery. And he also made another incredible discovery, Pallades. He suggested that all the small planets discovered are fragments of one disintegrated, once large planet. A contemporary of Hoffman and Shumison even indulged in romantic fantasies, saying that this planet, like Earth, was perfect for life and perhaps there was a civilization of its own. The dead planet was named Phaeton, a thrilling discovery. It was reminiscent of an ancient Greek myth. How thrilling! And the sun god Helios rode across the sky every day on 4 fiery horses. One day, his son Phaeton decided to ride in his father's chariot. The horses didn't obey him at first, but they soon rushed to the ground, eager to follow their young master. Then, in a truly spectacular display of power, Zeus threw a lightning bolt at the chariot. Phaeton met an untimely end. In a flash, the fiery horses rushed away, and the Earth was saved. Some enthusiasts even believed that the planet Phaeton was destroyed in the time of ancient Greece. A fascinating theory, and the myth is a magnificent, poetic account that shocked the Hellenes into disaster. A story that has stood the test of time. In fact, there's an asteroid belt between Mars and Jupiter, which is absolutely fascinating. And Ceres was just the first of them. The renowned French astronomer Urban E. Years of Life 1811-877 made an attempt to determine the potential mass of the planet Phaeton, which was truly an exciting endeavor. Of course, he, like other scientists, was sure that there were still many asteroids out there waiting to be discovered. However, knowledge of celestial mechanics still allowed us to make an exciting estimate of the total mass of all the known, yet unknown, small planets. I decided to calculate how the asteroid belt affects the orbital motion of Mars, and it was a fascinating process. Once we know the magnitude of the gravitational influence, we can calculate the total mass of asteroids. Lee Vera made an incredible discovery. He found that it did not exceed 0.1 to 0.25 of the Earth's mass. Other astronomers, eager to test the limits of their knowledge, set out to calculate the mass of Phaeton themselves. It was just as small. Today, astronomers are even more inquisitive and refer to the result of TFR, which is really exciting. They believe the photon mass is overestimated by at least 10 times. Which is really exciting because it means there's still so much to discover. If you mold this vanished planet, it will be no bigger than the moon, and it's going to be amazing. And now, here's something really interesting. Did you know that the mass of the moon is 0.012 of the mass of the Earth? This part of the solar system is probably too simple to form a planet, but that just means there's more to discover. And then, when the enormous Jupiter was formed, it collected all the matter and all the planet Earth. And then, something truly amazing happened. The embryos of future planets, which happened to be relatively close to its orbit, began to form. This is where Phaeton would have appeared. Meanwhile, astronomers of past centuries had the incredible opportunity to study Phaeton. In a stunning turn of events, calculations were proven wrong. This mysterious object was larger than Mars but smaller than Jupiter, and it was located right on the border of our solar system's habitable zone. In that vast, mysterious place between cosmic life and death, as Houellebecq believed, new life could still arise. And it did. But farther from the sun, there was a vast, mysterious expanse of space, teeming with possibilities. Scientists were eager to uncover the truth behind this mysterious event, trying to understand what kind of catastrophe befell this ill-fated celestial body. So, American researcher Charles Koval made an incredible suggestion. That 175 million years ago, Phaeton collided with an asteroid and crumbled into 1 billion pieces. In a truly spectacular display, these celestial bodies, like bombs, fell on neighboring celestial bodies for a long time. Incredible as it may seem, Mars has a crater 600 kilometers in diameter and 25 kilometers deep. Let's look behind this phenomenon and see if we can spot the shattered remains of Phaeton. In addition, many of its pieces fell into the gravitational field of Mars, Jupiter, Saturn, and Neptune, where they became their clones or added to the planetary ring. This fascinating hypothesis suggests that the two largest debris pieces, 1,000 years later, had an especially intriguing fate. These magnificent fireballs danced around the Sun. One of these comets later allegedly became the ninth planet, Pluto, a truly astonishing turn of events. The other, as postulated by the brilliant American researcher Immanuel Velikovsky, became our beautiful morning star, Venus. At one time, the orbit of this comet crossed with the orbit of the Earth more than once, putting people in awe and terror. The danger was indeed real, Velikovsky wrote, and it was thrilling to see that none of the serious scientists believed it. In a truly astonishing turn of events, the Earth was occasionally knocked out of its orbit. This led to some truly incredible apocalyptic events, including earthquakes, volcanic eruptions, floods, and fires. In addition, there were more than one incredible climatic catastrophe, and the alternation of seasons was broken. In an incredible turn of events, the space bombardment stopped around 800 BC. The last remaining shells saved our Earth. The forces of gravity finally settled down. Since then, the planet Venus has been peacefully circling in its orbit, sporting a magnificent fiery tail. However, the legend eventually dissipated, but not before it captured the imagination of many. The hypothesis was put to the test and proved to be incorrect. Later calculations showed that the planet Phaeton was never between Mars and Jupiter. A fascinating discovery. In a truly astonishing turn of events, it was revealed that only tiny planets were actually circumnavigating. Since 1983, an asteroid has been named Phaeton, but here's the really cool part. He's not part of the asteroid belt. He's located much closer to Earth. In a truly astonishing turn of events, Venus is being abandoned by its satellites. The cloud veil has long presented an intriguing challenge to those studying the surface of Venus with telescopes. But the most exciting discovery was that there were no noticeable landmarks of red spots of dark seas. Scientists have yet to accurately determine the period of rotation of this planet, which leaves plenty of room for discovery. At one time, they had a fascinating theory that Venus is always turned to the Sun the same side. In 1968, scientists made a thrilling discovery. Venus still rotates. However, it's a slow spin. Oh, you can't look here. A day on Venus flies by without you noticing. A day on Venus is an incredible 243 times longer than a day on Earth. If people could live here, any newspaper would be full of reviews of all the amazing things that happen during the year. It's even shorter than a day on Venus. It lasts 225 Earth days. In a breathtaking display of energy, this magnificent body then proceeds to move with astonishing speed, faster than the Sun itself, to complete one full rotation around its axis. It's all mixed up, and it's fascinating. Just stop and think for a moment. Why is Venus spinning so slowly? Maybe there was once a huge satellite near it. That's what slowed it down. The powerful tidal forces it generated were so intense that they heated up the planet. In a flash, it all happened. In just a few 100,000 years, this satellite grew to the size of Mercury and left Venus behind. But since then, our celestial neighbors have remained a red-hot, clumsy planet, and it's been a wild ride. This is just a hypothesis, but it's a fascinating one, but it has yet to be disproved. In 2006, an incredible new hypothesis was released by Alex Alplamai and David Stevenson from the California Institute of Technology. In a bold new theory, she suggests that Venus collided with another celestial body in its distant past. In an incredible turn of events, The debris disintegrated to form a satellite of Venus. The theory of the origin of the Earth's moon looks similar and is just as fascinating. But wait, there's more. After another collision with a large celestial body, Venus began to rotate in the opposite direction. Then, its satellite began to move back towards the planet, just like the moon does with Earth. And it kept going until it collapsed on Venus. However, confirming this hypothesis would be incredible. In an incredible turn of events, rapid volcanic activity transformed the surface of Venus and erased all traces of ancient catastrophes. The good news is that the satellite of Venus has already been discovered. In 1672, the Italian astronomer Giovanni Domenico Cassini made an incredible discovery. A lifespan of 16,200,007,129 years. By then, he had already achieved the incredible feat of becoming the first director of the Paris Observatory. Cassini was so excited about his discovery that he simply couldn't wait to share it with the world. But 14 years later, he made another incredible discovery. And then he made the brilliant decision to leave a note about it in the Journal of Observations. Cassini was thrilled to discover that the satellite was quite large. It was a whopping 4 times the mass of Venus. And guess what? The same satellite was seen by other scientists later on. In 1740, it was seen by the English astronomer and optician James Short, who was thrilled to catch a glimpse of it. In 1759, the German astronomer Andreas Mayer made an incredible discovery. Joseph Louis Lagrange followed up in 1761 with another remarkable observation. In a particularly exciting development, the latter reported that the orbital plane of the satellite of Venus is perpendicular to the ecliptic. In 1761, something truly extraordinary occurred. For a brief moment, the Sun, Venus, and Earth found themselves in perfect alignment. And here's the really cool part. If you look at the Sun through binoculars or a telescope, you can see the black spot of Venus moving across its disk. This incredible phenomenon is known as the passage of Venus across the Sun's disk. It's a truly special event to catch a glimpse of. Once in more than 100 years, then repeated in 8 years, and then it has to wait for a whole 100 years, but it'll be worth it. During this incredible event, all astronomers were glued to Venus for 2.5 centuries. But fate has not yet rewarded them with discoveries. On May 26, New Style June 6, 1761, Russian scientist Mikhail Vasilyevich Lomonosov made a groundbreaking discovery. He observed the atmosphere of Venus. In that same year, 5 astronomers observed the satellite of Venus a whopping 18 times. The most fascinating report came from the German astronomer Abram Scheitan. On June 6, he had the incredible opportunity to witness Venus passing across the disk of the Sun, accompanied by a small dark spot. However, on the same day, British astronomer Samuel Dunn had the opportunity to observe something else near Venus. In 1764, 2 observers had the incredible opportunity to spot the satellite 8 times. Others tried to do so, but unfortunately were unsuccessful. The debate was really heating up. Some observers were unlucky, failing to see the satellite each time it appeared. Others were more fortunate, catching sight of it on numerous occasions. In 1766, Pater Maximilian Hill, director of the Vienna Observatory, made an intriguing suggestion that all cases of observation of this free satellite can be explained by optical deception. The image of Venus looks so bright that it reappears through the telescope's lenses. He believed, thanks to the amazing phenomenon of the eye's fundus being poisoned. That's why so many enthusiastic observers see a speck near Venus. While some were delighted by this fascinating new discovery, not having guessed for so many years, others wasted no time in sharing the news. In 1770, the German astronomer Johann Heinrich Lambert, one of the founders of this science, introduced the basic concepts of light intensity, brightness, illuminance, and albedo. He also established a number of metric laws that changed the way we view the world around us. He published the most detailed information about the satellite of Venus in the Berlin Astronomical Yearbook. In an amazing twist, it is set back from the planet at 66.5 of the radius of Venus, which is the same distance from it as the Moon is from the Earth. However, this figure doesn't quite align with the period of revolution of the satellite, which presents an exciting opportunity for further investigation. In a stunning display of precision, Lambert's calculations revealed a remarkable 11 days, 3 hours, and 03 minutes. The thrilling, uncertain situation with the Venus satellite continued until the end of the 19th century. In 1884, the Belgian astronomer Jean-Charles Mazot made an unexpected but brilliant suggestion that helped solve this mystery. He made an incredible discovery: a pattern in previous observational results. Incredible as it may seem, the average interval between the discovery of a satellite was 1,080 days, or 2.96 million years. Who knows? Maybe we're not dealing with a satellite or an independent planet orbiting the Sun. Comes close to Venus every 3 years. This amazing phenomenon is called a conjunction. Nitrogen gave this planet a name. He named it Neith, after the Egyptian goddess of hunting and war, which no mortal is allowed to see. But 3 years later, the Belgian Academy of Sciences published an in-depth report investigating sightings of Neith, which was very exciting. In a stunning revelation, it was discovered that these were all stars that had been fortuitously observed in the vicinity of Venus. For example, the incredible James Short actually saw a star whose stellar magnitude was less than 1/8. The observations of Urban and Jacques Montaigne were similarly explained in an equally fascinating way. Christian, an astronomer from Copenhagen, may have seen the star Theta from the constellation Libra in 1768. The Danish astronomer Rare was particularly distinguished. He made an incredible discovery. He mistook 2 stars from Orion, one from Taurus, and one from Gemini for a companion of Venus. Unfortunately, Lambert's orbital calculations were not as accurate as he hoped. After this incredible document was made public, only one other case of observation of the satellite of Venus has been known to date, and it was on August 13, 1892. In the year 1857, the incredible American astronomer Edward Emerson Barnard made his mark on history. The third, who had previously discovered the Horsehead Nebula, made an incredible discovery: an object of stellar magnitude equal to 1/7 near Venus. In this location, no star should have appeared. Barnard had excellent eyesight, and everyone knew it. The truth is still out there. It could have been an asteroid flying past Venus, or even a supernova star that briefly flashed behind Venus. In that case, this flash was strangely overlooked by none of the other astronomers, and no one else saw it, making it one of the most intriguing mysteries in astronomy. He knows. But now, astronomers have discovered something truly fascinating. Venus has a pseudo-satellite. It's the asteroid 2002 and 68. It orbits the Sun and sometimes crosses the orbits of Mercury and Earth. In an amazing coincidence, its movements perfectly mirror those of Venus, due to an incredible 1:1 orbital resonance. In the 19th and 20th centuries, we had the incredible phenomenon of a second moon. In a series of exciting discoveries, astronomers have identified a new satellite of our planet, the second moon. However, each time the discoveries were not confirmed. In 1746, the observatory in Toulouse made an incredible announcement. Frédéric Petit, the observatory's director, revealed that his team had discovered another tiny satellite orbiting our planet. This discovery was made on the evening of March 21, 1846. After checking their observations, G5 made an incredible discovery. The second moon orbits in an elliptical orbit, making one revolution in just 2 hours 44 minutes and 59 seconds. It moves away from Earth at a distance of 3,570 kilometers, appearing almost in front of it, only 11.4 kilometers from the surface. Subsequently, he was so intrigued by the idea of the second moon that he even proposed a fascinating theory: that some features of the movement of the Earth's main satellite could be explained by the influence of this tiny planet. However, his fellow astronomers ignored the incredible discovery he made. Fortunately, the story was brought back to life by the incredible Jules Verne in the mid-19th century. He happened to read about the incredible discovery of the second moon, and this inspired him to weave its magic into the fate of his characters. In the fantastic novel Around the Moon, published in 1869, a spaceship or shell was launched to the moon and became its satellite. The situation seemed hopeless for our heroes, but they were lucky enough to meet on their way a small celestial body, the very second moon. Is it really possible? I'm so excited to tell you all about this, Michelle Gordon exclaimed. Guess what? The Earth has 2 satellites, and yes, it has 2 satellites, although it is commonly believed that it has only one. And there's more. This second satellite is so small and its speed is so high that the inhabitants of Earth cannot notice it, only observing the interference produced by it. The French astronomer N5 made an incredible discovery. He was able to detect the existence of this satellite and calculate its orbit. I'd love to know if all astronomers recognize the existence of this satellite, Nicholas asked, his eyes alight with curiosity. No, Orbith replied with a grin, but if they, like us, had encountered it up here, they would know for sure. In a breathtaking turn of events, the encounter nearly resulted in a collision with the second moon. Amazingly, the projectile changed direction and eventually returned to Earth. Can you believe it? 1 million people read the popular science fiction novel and filled in this important scene as well. And get this, a discovery supposedly made by a French astronomer. Amazingly, there were still people out there who were carrying on his work. In 1800, George Walter of Hamburg made an incredible discovery. He had found a whole system of tiny satellites orbiting our planet. He even provided the exact parameters of one of them. The second moon was an astonishing 700 kilometers wide. It was located at a distance of 1 million kilometers from the Earth, making one revolution around it for 119 days. A truly remarkable distance. In a fascinating twist, Walter Mata reveals that this satellite is sometimes mistaken for the Sun. He also mentioned the incredible American polar explorer Adolf Eric Greely, who in October 1881, while in Greenland, spent 10 days observing the solar disk. Once the polar night had fallen, Walter also made the thrilling prediction that on February 4, 1800, the second moon would pass through the Sun's disk. People were really excited about his prediction for February 4th. In a truly remarkable turn of events, the post office in Greifswald, Germany, became an observatory. A good dozen eager spectators huddled against the office windows, their eyes fixed on the sun. It was a truly magnificent sight, blindingly glittering above them. Mr. Zeigel, the postmaster, his household, and colleagues were all eager to help the astronomers in any way they could. The sunlight was streaming into their eyes, making them sparkle. But they were seeing things. In a truly remarkable sight, they observed a dark spot emerge and gradually make its way across the solar disk, which was an astonishing 5 times wider than it. The discovery was confirmed. In a thrilling turn of events, it was revealed that 2 seasoned astronomers, Winkler from Jena and Baron von Banco from Austria-Hungary, had also been observing the sun at that very moment. While they didn't witness anything extraordinary, they did observe the fascinating phenomenon of ordinary sunspots. So, the discovery turned into a mistake. But what a mistake it was. Walter, however, was not one to rest. He was absolutely certain that he could see a second moon, but it again eluded observation. In 1903, the American astronomer William Henry Pickering inadvertently spearheaded the search for this planet, publishing an article in the magazine about the search for a satellite of the moon. After all, everything that was said about this hypothetical object could be applied to observations of the second moon, and it was a truly exciting prospect. The article revealed the thrilling news that the satellite, with a diameter of 30 centimeters and located 320 kilometers from Earth's surface, can be seen in a 3-inch telescope. Amazingly, a satellite as big as 3 meters would be visible even with the naked eye. If you can't see it, it means it's less than 3 meters across. I'd like to return to the fascinating idea of G5, who believed that the second moon influences the motion of our main satellite. This could only be the case if the second moon reached a cross-section of several kilometers, which would certainly have been noticed even by the Babylonians. In 1922, the same journal published an article by Pickering that was specifically about the second moon and this meteoritic satellite. This was big news for enthusiasts everywhere. The article revealed that 3 5-inch telescopes with a low battery are the perfect setup for spotting the satellite. This is what amateur astronomers do. Just a few short years later, the German astronomical journal Stern reported the thrilling news that the German amateur astronomer Peale had discovered such a satellite on May 24, 1926, as it passed across the moon's disk. But this discovery, too, like others like it, was sadly overlooked. The search for a second moon brought astronomy back into the spotlight, sparking a new debate about its similarities to astrology. In 1918, the English astrologer real Walter Richard Holt gave this celestial body the name Lilith. Holt was convinced that it was black in color, which meant that it couldn't be observed with astronomical instruments. How intriguing! And then, in the most incredible moments, this mysterious black moon passes across the disk of the sun. And the best part is, it can be observed as authoritatively. The astrologer used to say that Lilith is as massive as the moon, and it's true. And they didn't even think about how such an enormous body could affect the motion of the Earth. Forget about astrologers for a moment and consider the possibility that Petty, Spire, Ewald, Matt, and their colleagues were absolutely right. It's just that every so often, they made an incredible discovery. Earth's satellites weren't as long-lived as they thought. Sometimes, our planet is captured by small bodies flying past it. Meteorites, amazingly, they don't last long. They orbit around the Earth for 115 hours, entering the upper atmosphere and gradually losing speed. They make a couple of revolutions and sometimes even surprise amateur astronomers. In an incredible turn of events, these meteors usually disintegrate, leaving researchers who mistook them for a real Earth satellite with a world of speculation to explore. Some scientists also believe that the moon sometimes grabs a small, approaching clump, which is really fascinating. In a few short years, the satellite will fall on the surface of the moon. It's only a matter of time. Maybe we'll have another chance to wow all you stargazers out there. The search for the second moon is still going strong today. In 1997, another triumph came their way when Canadian astronomer Paul Gerd highlighted a peculiar asteroid, 3753, which was moving in an unusual orbit. It was a satellite of Earth. However, observations showed that it was not quite as true to our satellite as we first thought.